The Mathematical Principles of Natural Philosophy. By Isaac Newton. Dedication. To the teachers of the Normal School of the State of New York. Gentlemen. A stirring freshness in the air, and ruddy streaks upon the horizon of the moral world betoken the grateful dawning of a new era. The days of a driveling instruction are departing. With us is the opening promise of a better time, wherein genuine manhood doing its noblest work shall have adequate reward. Teacher is the highest and most responsible office man can fill. Its dignity is, and will yet be held commensurate with its duty, a duty boundless as man's intellectual capacity, and great as his moral need, a duty from the performance of which shall emanate an influence not limited to the now and the here, but which surely will, as time flows into eternity and space into infinity, roll up, a measureless curse or a measureless blessing, in inconceivable swellings along the infinite curve. It is an office that should be esteemed of even sacred import in this country. Ere long 100 millions, extending from the Atlantic to the Pacific, from Baffin's Bay to that of Panama, shall call themselves American citizens. What a field for those two master passions of the human soul, the love of rule, and the love of gain! How shall our liberties continue to be preserved from the graspings of ambition and the corruptions of gold? Not by bills of rights constitutions, and statute books, but alone by the rightly cultivated hearts and heads of the people. They must themselves guard the Arkansas. It is yours to fit them for the consecrated charge. Look well to it, for you appear clothed in the majesty of great power. It is yours to fashion, and to inform, to save, and to perpetuate. You are the educators of the people, you are the prime conservators of the public weal. Betray your trust, and the sacred fires would go out, and the altars crumble into dust, knowledge become lost in tradition, and Christian nobleness a fable. As you, therefore, are multiplied in number, elevated in consideration, increased in means, and fulfill, well and faithfully, all the requirements of true teachers, so shall our favored land lift up her head among the nations of the earth, and call herself blessed. In conclusion, gentlemen, to you, as the conspicuous leaders in the vast and honorable labor of educational reform and popular teaching, the first American edition of the Principia of Newton, the greatest work of the greatest teacher, is most respectfully dedicated. N. W. Chittenden. Editor. How do you find this book? Any thoughts about the book or the author? Any suggestion for improvement? Please take a moment to share your thoughts in a comment. If you like it, share it with your friends who might enjoy it as well. Subscribe to keep in touch. Visit CompleteAudiobooks.com for more quality content. Introduction to the American edition. That the Principia of Newton should have remained so generally unknown in this country to the present day is a somewhat remarkable fact. Because the name of the author, learned with the very elements of science, is revered at every hearthstone where knowledge and virtue are of chief esteem, while, abroad, in all the high places of the land, the character which that name recalls is held up as the noblest illustration of what man may be, and may do, in the possession and manifestation of preeminent intellectual and moral worth. Because the work is celebrated, not only in the history of one career and one mind, but in the history of all achievement and human reason itself. Because of the spirit of inquiry, which has been aroused, and which, in pursuing its searchings, is not always satisfied with stopping short of the fountainhead of any given truth. And, finally, because of the earnest endeavor that has been and is constantly going on, in many sections of the Republic, to elevate the popular standard of education and give to scientific and other efforts a higher and a better aim. True, the Principia has been hitherto inaccessible to popular use. A few copies in Latin, and occasionally one in English may be found in some of our larger libraries, or in the possession of some ardent disciple of the great master. But a dead language in the one case, and an enormous price in both, particularly in that of the English edition, have thus far opposed very sufficient obstacles to the wide circulation of the work. It is now, however, placed within the reach of all. And in performing this labor, the utmost care has been taken, by collation, revision, and otherwise, to render the first American edition the most accurate and beautiful in our language. Le plus beau monument que l'on puisse lever à la gloire de Newton, c'est une bonne edition de ses ouvrages, and a monument like unto that we would here set up. The Principia, above all, glows with the immortality of a transcendent mind. Marble and brass dissolve and pass away. But the true creations of genius endure, in time and beyond time, forever. High upon the adamant of the indestructible, they send forth afar and near, over the troublous waters of life, a pure, unwavering, quenchless light whereby the myriads of barks, richly laden with reason, intelligence and various faculty, are guided through the night and the storm, by the beetling shore and the hidden rock, the breaker and the shoal, safely into havens calm and secure. To the teacher and the taught, the scholar and the student, the devotee of science and the worshipper of truth, the Principia must ever continue to be of inestimable value. If to educate means, not so much to store the memory with symbols and facts, as to bring forth the faculties of the soul and develop them to the full by healthy nurture and a hardy discipline, then what so effective to the accomplishment of that end as the study of geometrical synthesis? The calculus, in some shape or other, is, indeed, necessary to the successful prosecution of researches in the higher branches of philosophy. But has not the analytical encroached upon the synthetical, and algorithmic formulae been employed when not requisite either for the evolution of truth, or even its apter illustration? To each method belongs, undoubtedly, an appropriate use. Newton, himself the inventor of flux ions, censured the handling of geometrical subjects by algebraical calculations, and the maturest opinions which he expressed were additionally in favor of the geometrical method. His preference, so strongly marked, is not to be reckoned a mere matter of taste. And his authority should bear with preponderating weight upon the decision of every instructor in adopting what may be deemed the best plan to ensure the completest mental development. Geometry, the vigorous product of remote time, blended with the earliest aspirations of science and the earliest applications of art, as well in the measures of music as in the movement of spheres, as wholly in the structure of the atom as in that of the world. Directing motion and shaping appearance, in a word, at the molding of the created all, is, in comprehensive view, the outward form of that inner harmony of which and in which all things are. Plainly, therefore, this noble study has other and infinitely higher uses than to increase the power of abstraction. A more general and thorough cultivation of it should be strenuously insisted on. Passing from the pages of Euclid or Legendre, might not the student be led, at the suitable time, to those of the Principia wherein geometry may be found in varied use from the familiar to the sublime? The profoundest and the happiest results, it is believed, would attend upon this enlargement of our educational system. Let the Principia, then, be gladly welcomed into every hall where a true teacher presides. And they who are guided to the diligent study of this incomparable work, who become strengthened by its reason, assured by its evidence, and enlightened by its truths, and who rise into loving communion with the great and pure spirit of its author, will go forth from the scenes of their pupillage, and take their places in the world as strong-minded, right-hearted men, such men as the theory of our government contemplates and its practical operation absolutely demands. Life of Sir Isaac Newton. From the thick darkness of the Middle Ages man's struggling spirit emerged as in new birth, breaking out of the iron control of that period. Growing strong and confident in the tug and din of succeeding conflict and revolution, it bounded forwards and upwards with resistless vigor to the investigation of physical and moral truth, ascending height after height, sweeping afar over the earth, penetrating afar up into the heavens, increasing in endeavor, enlarging in endowment. Everywhere boldly, earnestly outstretching, till, in the author of the Principia, one arose, who, grasping the master key of the universe and treading its celestial paths, opened up to the human intellect the stupendous realities of the material world, and, in the unrolling of its harmonies, gave to the human heart a new song to the goodness, wisdom, and majesty of the all-creating, all-sustaining, all-perfect God. Sir Isaac Newton, in whom the rising intellect seemed to attain, as it were, to its culminating point, was born on the 25th of December, O.S. 1642, Christmas Day, at Woolsthorpe, in the parish of Colsterworth, in Lincolnshire. His father, John Newton, died at the age of 36, and only a few months after his marriage to Harriet Ayscough, daughter of James Ayscough, of Rutlandshire. Mrs. Newton, probably wrought upon by the early loss of her husband, gave premature birth to her only and posthumous child, of which, too, from its extreme diminutiveness, she appeared likely to be soon bereft. Happily, it was otherwise decreed. The tiny infant, on whose little lips the breath of life so doubtingly hovered, lived to a vigorous maturity, to a hale old age, lived to become the boast of his country, the wonder of his time, and the ornament of his species. Beyond the grandfather, Robert Newton, the descent of Sir Isaac cannot with certainty be traced. Two traditions were held in the family, one, that they were of Scotch extraction. The other, that they came originally from Newton, in Lancashire, dwelling, for a time, however, at Westby, county of Lincoln, before the removal to and purchase of Woolsthorpe, about 100 years before this memorable birth. The widow Newton was left with the simple means of a comfortable subsistence. The Woolsainthorpe estate together with small one which she possessed at Sowstern, in Leicestershire, yielded her an income of some £80. And upon this limited sum, she had to rely chiefly for the support of herself, and the education of her child. She continued his nurture for 3 years, when, marrying again, she confided the tender charge to the care of her own mother. Great genius is seldom marked by precocious development, and young Isaac, sent, at the usual age, to 2-day schools at Skillington and Stoke, exhibited no unusual traits of character. In his 12th year, he was placed at the public school at Grantham, and boarded at the house of Mr. Clark, an apothecary. But even in this excellent seminary, his mental acquisitions continued for a while unpromising enough. Study apparently had no charms for him, he was very inattentive, and ranked low in the school. One day, however, the boy immediately above our seemingly dull student gave him a severe kick in the stomach. Isaac, deeply affected, but with no outburst of passion, betook himself, with quiet, incessant toil, to his books. He quickly passed above the offending classmate, yet there he stopped not. The strong spirit was, for once and forever, awakened, and, yielding to its noble impulse, he speedily took up his position at the head of all. His peculiar character began now rapidly to unfold itself. Close application grew to be habitual. Observation alternated with reflection. A sober, silent, thinking lad, yet, the wisest and the kindliest, the indisputable leader of his fellows. Generosity, modesty, and a love of truth distinguished him then as ever afterwards. He did not often join his classmates in play, but he would contrive for them various amusements of a scientific kind. Paper kites he introduced, carefully determining their best form and proportions, and the position and number of points whereby to attach the string. He also invented paper lanterns. These served ordinarily to guide the way to school in winter mornings, but occasionally for quite another purpose. They were attached to the tails of kites in a dark night, to the dismay of the country people dreading portentous comets, and to the immeasurable delight of his companions. To him, however, young as he was, life seemed to have become an earnest thing. When not occupied with his studies, his mind would be engrossed with mechanical contrivances, now imitating, now inventing. He became singularly skillful in the use of his little saws, hatchets, hammers, and other tools. A windmill was erected near Grantham. During the operations of the workmen, he was frequently present. In a short time, he had completed a perfect working model of it, which elicited general admiration. Not content, however, with this exact imitation, he conceived the idea of employing, in the place of sails, animal power, and, adapting the construction of his mill accordingly, he enclosed in it a mouse, called the miller, and which by acting on a sort of tread-wheel, gave motion to the machine. He invented, too, a mechanical carriage, having 4 wheels, and put in motion with a handle worked by the person sitting inside. The measurement of time early drew his attention. He first constructed a water clock, in proportions somewhat like an old-fashioned house clock. The index of the dial plate was turned by a piece of wood acted upon by dropping water. This instrument, though long used by himself, and by Mr. Clark's family, did not satisfy his inquiring mind. His thoughts rose to the sun, and, by careful and oft-repeated observations of the solar movements, he subsequently formed many dials. One of these, named Isaac's dial, was the accurate result of years' labor, and was frequently referred to for the hour of the day by the country people. May we not discern in these continual efforts, the diligent research, the patient meditation, the aspiring glance, and the energy of discovery, the stirring elements of that wondrous spirit, which, clear, calm, and great, moved, in after years, through deep of nature's mysteries, unlocking her strongholds, dispelling darkness, educing order, everywhere silently conquering. Newton had an early and decided taste for drawing. Pictures, taken sometimes from copies, but often from life, and drawn, colored and framed by himself, ornamented his apartment. He was skilled also, in poetical composition, excelled in making verses. Some of these were borne in remembrance and repeated, 70 years afterward, by Mrs. Vincent, for whom, in early youth, as Miss Story, he formed an ardent attachment. She was the sister of a physician resident near Woolsthorpe, but Newton's intimate acquaintance with her began at Grantham, where they were both numbered among the inmates of the same house. 2 or 3 years younger than himself, of great personal beauty, and unusual talent, her society afforded him the greatest pleasure, and their youthful friendship, it is believed, gradually rose to a higher passion. But inadequacy of fortune prevented their union. Miss Story was afterwards twice married, Newton, never. His esteem for her continued unabated during life, accompanied by numerous acts of attention and kindness. In 1656, Newton's mother was again left a widow, and took up her abode once more at Woolsthorpe. He was now 15 years of age, and had made great progress in his studies. But she, desirous of his help, and from motives of economy, recalled him from school. Business occupations, however, and the management of the farm, proved utterly distasteful to him. When sent to Grantham Market on Saturdays, he would betake himself to his former lodgings in the apothecary's garret, where some of Mr. Clark's old books employed his thoughts till the aged and trustworthy servant had executed the family commissions and announced the necessity of return, or, at other times, our young philosopher would seat himself under a hedge, by the wayside, and continue his studies till the same faithful personage, proceeding alone to the town and completing the day's business, stopped as he returned. The more immediate affairs of the farm received no better attention. In fact, his passion for study grew daily more absorbing, and his dislike for every other occupation more intense. His mother, therefore, wisely resolved to give him all the advantages which an education could confer. He was sent back to Grantham School, where he remained for some months in busy preparation for his academical studies. At the recommendation of one of his uncles, who had himself studied at Trinity College, Cambridge, Newton proceeded thither, and was duly admitted, on the 5th day of June 1660, in the 18th year of his age. The eager student had now entered upon a new and wider field, and we find him devoting himself to the pursuit of knowledge with amazing ardor and perseverance. Among other subjects, his attention was soon drawn to that of judicial astrology. He exposed the folly of this pseudoscience by erecting a figure with the aid of 1 or 2 of the problems of Euclid, and thus began his study of the mathematics. His researches into this science were prosecuted with unparalleled vigor and success. Regarding the propositions contained in Euclid as self-evident truths, he passed rapidly over this ancient system, a step which he afterward much regretted, and mastered, without further preparatory study, the analytical geometry of Descartes. Wallace's arithmetic of infinites, Saunderson's logic, and the optics of Kepler, he also studied with great care, writing upon them many comments, and, in these notes on Wallace's work was undoubtedly the germ of his fluxionary calculus. His progress was so great that he found himself more profoundly versed than his tutor in many branches of learning. Yet his acquisitions were not gotten with the rapidity of intuition, but they were thoroughly made and firmly secured. Quickness of apprehension, or intellectual nimbleness did not belong to him. He saw too far, his insight was too deep. He dwelt fully, cautiously upon the least subject. While to the consideration of the greatest, he brought a massive strength joined with a matchless clearness, that, regardless of the merely trivial or unimportant, bore with unerring sagacity upon the prominences of the subject, and, grappling with its difficulties, rarely failed to surmount them. His early and last friend, Dr. Barrow, in compass of invention only inferior to Newton, who had been elected professor of Greek in the university, in 1660, was made Lucasian professor of mathematics in 1663. And soon afterward delivered his optical lectures. The manuscripts of these were revised by Newton, and several oversights corrected, and many important suggestions made by him. But they were not published till 1669. In the year 1665, he received the degree of Bachelor of Arts. And, in 1666, he entered upon those brilliant and imposing discoveries which have conferred inappreciable benefits upon science, and immortality upon his own name. Newton, himself, states that he was in possession of his method of flux ions, in the year 1666, or before. Infinite quantities had long been a subject of profound investigation, among the ancients by Archimedes, and Pappus of Alexandria. Among the moderns by Kepler, Cavalieri, Roberval, Fermat and Wallis. With consummate ability Dr. Wallis had improved upon the labors of his predecessors. With a higher power, Newton moved forwards from where Wallis stopped. Our author first invented his celebrated binomial theorem. And then, applying this theorem to the rectification of curves, and to the determination of the surfaces and contents of solids, and the position of their centers of gravity, he discovered the general principle of deducing the areas of curves from the ordinate, by considering the area as a nascent quantity, increasing by continual flux ion in the proportion of the length of the ordinate, and supposing the abscissa to increase uniformly in proportion to the time. Regarding lines as generated by the motion of points, surfaces by the motion of lines, and solids by the motion of surfaces, and considering that the ordinates, abscissae, and of curves thus formed, vary according to a regular law depending on the equation of the curve, he deduced from this equation the velocities with which these quantities are generated, and obtained by the rules of infinite series the ultimate value required. To the velocities with which every line or quantity is generated, he gave the name of flux ions, and to the lines or quantities themselves, that of fluents. A discovery that successively baffled the acutest and strongest intellects, that, variously modified, has proved of incalculable service in aiding to develop the most abstruse and the highest truths in mathematics and astronomy, and that was of itself enough to render any name illustrious in the crowded annals of science. At this period, the most distinguished philosophers were directing all their energies to the subject of light and the improvement of the refracting telescope. Newton, having applied himself to the grinding of optic glasses of other figures than spherical, experienced the impracticability of executing such lenses, and conjectured that their defects, and consequently those of refracting telescopes, might arise from some other cause than the imperfect convergency of rays to a single point. He accordingly procured a triangular glass prism to try therewith the celebrated phenomena of colors. His experiments, entered upon with zeal, and conducted with that industry, accuracy, and patient thought, for which he was so remarkable, resulted in the grand conclusion, that light was not homogeneous, but consisted of rays, some of which were more refrangible than others. This profound and beautiful discovery opened up a new era in the history of optics. As bearing, however, directly upon the construction of telescopes, he saw that a lens refracting exactly like a prism would necessarily bring the different rays to different foci, at different distances from the glass, confusing and rendering the vision indistinct. Taking for granted that all bodies produce spectra of equal length, he dismissed all further consideration of the refracting instrument, and took up the principle of reflection. Rays of all colors, he found, were reflected regularly, so that the angle of reflection was equal to the angle of incidence, and hence he concluded that optical instruments might be brought to any degree of perfection imaginable, provided reflecting specula of the requisite figure and finish could be obtained. At this stage of his optical researches, he was forced to leave Cambridge on account of the plague which was then desolating England. He retired to Woolsthorpe. The old manor house, in which he was born, was situated in a beautiful little valley, on the west side of the River Witham. And here in the quiet home of his boyhood, he passed his days in serene contemplation, while the stalking pestilence was hurrying its tens of thousands into undistinguishable graves. Towards the close of a pleasant day in the early autumn of 1666, he was seated alone beneath a tree, in his garden, absorbed in meditation. He was a slight young man, in the 24th year of his age, his countenance mild and full of thought. For a century previous, the science of astronomy had advanced with rapid strides. The human mind had risen from the gloom and bondage of the Middle Ages, in unparalleled vigor, to unfold the system, to investigate the phenomena, and to establish the laws of the heavenly bodies. Copernicus, Tycho Brahe, Kepler, Galileo, and others had prepared and lighted the way for him who was to give to their labor its just value, and to their genius its true luster. At his bidding isolated facts were to take order as parts of one harmonious whole, and sagacious conjectures grow luminous in the certain splendor of demonstrated truth. And this ablest man had come, was here. His mind, familiar with the knowledge of past effort, and its unequaled faculties developed in transcendent strength, was now moving on to the very threshold of its grandest achievement. Step by step the untrodden path was measured, till, at length, the entrance seemed disclosed, and the tireless explorer to stand amid the first opening wonders of the universe. The nature of gravity, that mysterious power which causes all bodies to descend towards the center of the earth, had, indeed, dawned upon him. And reason busily united link to link of that chain which was yet to be traced, joining the least to the vastest, the most remote to the nearest, in one harmonious bond. From the bottoms of the deepest caverns to the summits of the highest mountains, this power suffers no sensible change. May not its action, then, extend to the moon? Undoubtedly, and further reflection convinced him that such a power might be sufficient for retaining that luminary in her orbit round the earth. But, though this power suffers no sensible variation, in the little change of distance from the earth's center, at which we may place ourselves, yet, at the distance of the moon, may not its force undergo more or less diminution? The conjecture appeared most probable, and, in order to estimate what the degree of diminution might be, he considered that if the moon be retained in her orbit by the force of gravity, the primary planets must also be carried round the sun by the like power. And, by comparing the periods of the several planets with their distances from the sun, he found that, if they were held in their courses by any power like gravity, its strength must decrease in the duplicate proportion of the increase of distance. In forming this conclusion, he supposed the planets to move in perfect circles, concentric to the sun. Now was this the law of the moon's motion? Was such a force, emanating from the earth and directed to the moon, sufficient, when diminished as the square of the distance, to retain her in her orbit? To ascertain this master fact, he compared the space through which heavy bodies fall, in a second of time, at a given distance from the center of the earth, namely, at its surface, with the space through which the moon falls, as it were, to the earth, in the same time, while revolving in a circular orbit. He was absent from books, and, therefore, adopted, in computing the earth's diameter, the common estimate of 60 miles to a degree of latitude as then in use among geographers and navigators. The result of his calculations did not, of course, answer his expectations. Hence, he concluded that some other cause, beyond the reach of observation, analogous, perhaps, to the vortices of Descartes, joined its action to that of the power of gravity upon the moon. Though by no means satisfied, he yet abandoned a while further inquiry, and remained totally silent upon the subject. These rapid marches in the career of discovery, combined with the youth of Newton, seemed to evince a penetration the most lively, and an invention the most exuberant. But in him there was a conjunction of influences as extraordinary as fortunate. Study, unbroken, persevering and profound, carried on its informing and disciplining work upon a genius, natively the greatest, and rendered freest in its movements, and clearest in its vision, through the untrammelling and enlightening power of religion. And, in this happy concurrence, are to be sought the elements of those amazing abilities, which, grasping, with equal facility, the minute and the stupendous, brought these successively to light, and caused science to make them her own. In 1667, Newton was made a junior fellow, and, in the year following, he took his degree of Master of Arts, and was appointed to a senior fellowship. On his return to Cambridge, in 1668, he resumed his optical labors. Having thought of a delicate method of polishing metal, he proceeded to the construction of his newly projected reflecting telescope, a small specimen of which he actually made with his own hands. It was 6 inches long, and magnified about 40 times, a power greater than a refracting instrument of 6 feet tube could exert with distinctness. Jupiter, with his 4 satellites, and the horns, or moon-like phases of Venus were plainly visible through it. This was the first reflecting telescope ever executed and directed to the heavens. He gave an account of it, in a letter to a friend, dated February 23 d. 1668-9, a letter which is also remarkable for containing the first allusion to his discoveries, concerning the nature of light. Encouraged by the success of his first experiment, he again executed with his own hands, not long afterward, a second and superior instrument of the same kind. The existence of this having come to the knowledge of the Royal Society of London, in 1671, they requested it of Newton for examination. He accordingly sent it to them. It excited great admiration, it was shown to the king. A drawing and description of it was sent to Paris, and the telescope itself was carefully preserved in the library of the Society. Newton lived to see his invention in public use, and of eminent service in the cause of science. In the spring of 1669, he wrote to his friend Francis Aston, Esq. Then about setting out on his travels, a letter of advice and directions. It was dated May 18, and is interesting as exhibiting some of the prominent features in Newton's character. Thus: since in your letter you give me so much liberty of spending my judgment about what may be to your advantage in traveling, I shall do it more freely than perhaps otherwise would have been decent. First, then, I will lay down some general rules, most of which, I believe, you have considered already, but if any of them be new to you, they may excuse the rest. If none at all, yet is my punishment more in writing than yours in reading. When you come into any fresh company, 1. Observe their humors. 2. Suit your own carriage thereto, by which insinuation you will make their converse more free and open. 3. Let your discourse be more inquiries and doubtings than peremptory assertions or disputings, it being the design of travellers to learn, not to teach. Besides, it will persuade your acquaintance that you have the greater esteem of them, and so make them more ready to communicate what they know to you, whereas nothing sooner occasions disrespect and quarrels than peremptoriness. You will find little or no advantage in seeming wiser or much more ignorant than your company. 4. Seldom discommend anything though never so bad, or do it but moderately, lest you be unexpectedly forced to an unhandsome retraction. It is safer to commend anything more than it deserves, than to discommend a thing so much as it deserves. For commendations meet not so often with oppositions, or, at least, are not usually so ill resented by men that think otherwise, as discommendations. And you will insinuate into men's favor by nothing sooner than seeming to approve and commend what they like, but beware of doing it by comparison. 5. If you be affronted, it is better, in a foreign country, to pass it by in silence, and with a jest, though with some dishonor, than to endeavor revenge. For, in the first case, your credit's ne'er the worse when you return into England, or come into other company that have not heard of the quarrel. But, in the second case, you may bear the marks of the quarrel while you live, if you outlive it at all. But, if you find yourself unavoidably engaged, 'tis best, I think, if you can command your passion and language, to keep them pretty evenly at some certain moderate pitch, not much heightening them to exasperate your adversary, or provoke his friends, nor letting them grow overmuch dejected to make him insult. In a word, if you can keep reason above passion, that and watchfulness will be your best defendants. To which purpose you may consider, that, though such excuses as this, he provoked me so much I could not forbear, may pass among friends, yet amongst strangers they are insignificant, and only argue a traveller's weakness. To these I may add some general heads for inquiries or observations, such as at present I can think on. As, 1. To observe the policies, wealth, and state affairs of nations, so far as a solitary traveller may conveniently do. 2. Their impositions upon all sorts of people, trades, or commodities, that are remarkable. 3. Their laws and customs, how far they differ from ours. 4. Their trades and arts wherein they excel or come short of us in England. 5. Such fortifications as you shall meet with, their fashion, strength, and advantages for defense, and other such military affairs as are considerable. 6. The power and respect belonging to their degrees of nobility or magistracy. 7. It will not be time misspent to make a catalogue of the names and excellencies of those men that are most wise, learned, or esteemed in any nation. 8. Observe the mechanism and manner of guiding ships. 9. Observe the products of nature in several places, especially in mines, with the circumstances of mining and of extracting metals or minerals out of their ore, and of refining them. And if you meet with any transmutations out of their own species into another, as out of iron into copper, out of any metal into quicksilver, out of one salt into another, or into an insipid body, and those, above all, will be worth your noting, being the most luciferous, and many times luciferous experiments. 2. In philosophy. 10. The prices of diet and other things. 11. And the staple commodities of places. These generals, such as at present I could think of, if they will serve for nothing else, yet they may assist you in drawing up a model to regulate your travels by. As for particulars, these that follow are all that I can now think of, viz. Whether at Scamnitium, in Hungary, where there are mines of gold, copper, iron, vitriol, antimony, and they change iron into copper by dissolving it in a vitriolate water, which they find in cavities of rocks in the mines, and then melting the slimy solution in a strong fire, which in the cooling proves copper. The like is said to be done in other places, which I cannot now remember, perhaps, too. It may be done in Italy. For about 20 or 30 years agone there was a certain vitriol came from thence, called Roman vitriol, but of a nobler virtue than that which is now called by that name, which vitriol is not now to be gotten, because perhaps they make a greater gain by some such trick as turning iron into copper with it than by selling it. 2. Whether, in Hungary, Sclavonia, Bohemia, near the town Isla, or at the mountains of Bohemia near Silesia, there be rivers whose waters are impregnated with gold, perhaps, the gold being dissolved by some corrosive water like aqua regis, and the solution carried along with the stream that runs through the mines. And whether the practice of laying mercury in the rivers, till it be tinged with gold, and then straining the mercury through leather, that the gold may stay behind, be a secret yet, or openly practiced. 3. There is newly contrived, in Holland, a mill to grind glasses plain withal, and I think polishing them too, perhaps it will be worth the while to see it. 4. There is in Holland one, Borri, who some years since was imprisoned by the Pope, to have extorted from him secrets, as I am told, of great worth, both as to medicine and profit, but he escaped into Holland, where they have granted him a guard. I think he usually goes clothed in green. Pray inquire what you can of him, and whether his ingenuity be any profit to the Dutch. You may inform yourself whether the Dutch have any tricks to keep their ships from being all worm-eaten in their voyages to the Indies. Whether pendulum clocks do any service in finding out the longitude. And I am very weary, and shall not stay to part with a long compliment, only I wish you a good journey, and God be with you. It was not till the month of June, 1669, that our author made known his method of fluxions. He then communicated the work which he had composed upon the subject, and entitled, Analysis per Equations Numero Terminorum Infinitas, to his friend Dr. Barrow. The latter, in a letter dated 20th of the same month, mentioned it to Mr. Collins, and transmitted it to him, on the 31st of July thereafter. Mr. Collins greatly approved of the work, took a copy of it, and sent the original back to Dr. Barrow. During the same and the 2 following years, Mr. Collins, by his extensive correspondence, spread the knowledge of this discovery among the mathematicians in England, Scotland, France, Holland and Italy. Dr. Barrow, having resolved to devote himself to theology, resigned the Lucasian professorship of mathematics, in 1669, in favour of Newton, who accordingly received the appointment to the vacant chair. During the years 1669, 1670, and 1671, our author, as such professor, delivered a course of optical lectures. Though these contained his principal discoveries relative to the different refrangibility of light, yet the discoveries themselves did not become publicly known, it seems, till he communicated them to the Royal Society. A few weeks after being elected a member thereof, in the spring of 1671-2. He now rose rapidly in reputation, and was soon regarded as foremost among the philosophers of the age. His paper on light excited the deepest interest in the Royal Society, who manifested an anxious solicitude to secure the author from the arrogations of others, and proposed to publish his discourse in the monthly numbers in which the transactions were given to the world. Newton, gratefully sensible of these expressions of esteem, willingly accepted of the proposal for publication. He gave them also, at this time, the results of some further experiments in the decomposition and recomposition of light, that the same degree of refrangibility always belonged to the same color, and the same color to the same degree of refrangibility, that the 7 different colors of the spectrum were original, or simple, and that whiteness, or white light was a compound of all these 7 colors. The publication of his new doctrines on light soon called forth violent opposition as to their soundness. Hooke and Huygens, men eminent for ability arid learning, were the most conspicuous of the assailants. And though Newton effectually silenced all his adversaries, yet he felt the triumph of little gain in comparison with the loss his tranquillity had sustained. He subsequently remarked in allusion to this controversy, and to one with whom he was destined to have a longer and a bitterer conflict, I was so persecuted with discussions arising from the publication of my theory of light, that I blamed my own imprudence for parting with so substantial a blessing as my quiet to run after a shadow. In a communication to Mr. Oldenburg, Secretary of the Royal Society, in 1672, our author stated many valuable suggestions relative to the construction of reflecting microscopes which he considered even more capable of improvement than telescopes. He also contemplated, about the same time, an edition of Kinckweisen's Algebra, with notes and additions, partially arranging, as an introduction to the work, a treatise, entitled, A Method of Flux Ions, but he finally abandoned the design. This treatise, however, he resolved, or rather consented, at a late period of his life, to put forth separately, and the plan would probably have been carried into execution had not his death intervened. It was translated into English and published in 1736 by John Coulson, Professor of Mathematics in Cambridge. Newton, it is thought, made his discoveries concerning the inflection and diffraction of light before 1674. The phenomena of the inflection of light had been first discovered more than 10 years before by Grimaldi. And Newton began by repeating one of the experiments of the learned Jesuit, admitting a beam of the sun's light through a small pinhole into a dark chamber, the light diverged from the aperture in the form of cone. And the shadows of all bodies placed in this light were larger than might have been expected, and surrounded with 3 colored fringes, the nearest being widest, and the most remote the narrowest. Newton, advancing upon this experiment, took exact measures of the diameter of the shadow of a human hair, and of the breadth of the fringes, at different distances behind it, and discovered that these diameters and breadths were not proportional to the distances at which they were measured. He hence supposed that the rays which passed by the edge of the hair were deflected or turned aside from it, as if by a repulsive force, the nearest rays suffering the greatest, the more remote a less degree of deflection. In explanation of the colored fringes, he queried, whether the rays which differ in refrangibility do not differ also in flexibility, and whether they are not, by these different inflections, separated from one another, so as after separation to make the colors in the 3 fringes above described. Also, Whether the rays, in passing by the edges and sides of bodies, are not bent several times backwards and forwards with an eel-like motion, the three fringes arising from three such bendings. His inquiries on this subject were here interrupted and never renewed. His theory of the colors of natural bodies was communicated to the Royal Society, in February, 1675. This is justly regarded as one of the profoundest of his speculations. The fundamental principles of the theory in brief, are, that bodies possessing the greatest refractive powers reflect the greatest quantity of light, and that, at the confines of equally refracting media, there is no reflection. That the minutest particles of almost all natural bodies are in some degree transparent. That between the particles of bodies there are pores, or spaces, either empty or filled with media of a less density than the particles themselves. That these particles, and pores or spaces, have some definite size. Hence he deduced the transparency, opacity, and colors of natural bodies. Transparency arises from the particles and their pores being too small to cause reflection at their common surfaces, the light all passing through. Opacity from the opposite cause of the particles and their pores being sufficiently large to reflect the light which is stopped or stifled by the multitude of reflections. And colors from the particles, according to their several sizes, reflecting rays of one color and transmitting those of another, or in other words, the color that meets the eye is the color reflected, while all the other rays are transmitted or absorbed. Analogous in origin to the colors of natural bodies, he considered the colors of thin plates. This subject was interesting and important, and had attracted considerable investigation. He, however, was the first to determine the law of the production of these colors, and, during the same year made known the results of his researches herein to the Royal Society. His mode of procedure in these experiments was simple and curious. He placed a double convex lens of a large known radius of curvature, upon the flat surface of a plano-convex object glass. Thus, from their point of contact at the center, to the circumference of the lens, he obtained plates of air, or spaces varying from the extremest possible thinness, by slow degrees, to a considerable thickness. Letting the light fall, every different thickness of this plate of air gave different colors, the point of contact of the lens and glass forming the center of numerous concentric colored rings. Now the radius of curvature of the lens being known, the thickness of the plate of air, at any given point, or where any particular color appeared, could be exactly determined. Carefully noting, therefore, the order in which the different colors appeared, he measured, with the nicest accuracy, the different thicknesses at which the most luminous parts of the rings were produced, whether the medium were air, water, or mica, all these substances giving the same colors at different thicknesses. The ratio of which he also ascertained. From the phenomena observed in these experiments, Newton deduced his theory of fits of easy reflection and transmission of light. It consists in supposing that every particle of light, from its first discharge from a luminous body, possesses, at equally distant intervals, dispositions to be reflected from, or transmitted through the surfaces of bodies upon which it may fall. For instance, if the rays are in a fit of easy reflection, they are on reaching the surface, repelled, thrown off, or reflected from it; if, in a fit of easy transmission, they are attracted, drawn in, or transmitted through it. By this theory of fits, our author likewise explained the colors of thick plates. He regarded light as consisting of small material particles emitted from shining substances. He thought that these particles could be recombined into solid matter, so that, gross bodies and light were convertible into one another, that the particles of light and the particles of solid bodies acted mutually upon each other. Those of light agitating and heating those of solid bodies, and the latter attracting and repelling the former. Newton was the first to suggest the idea of the polarization of light. In the paper entitled An Hypothesis Explaining Properties of Light, December, 1675. Our author first introduced his opinions respecting ether, opinions which he afterward abandoned and again permanently resumed, a most subtle spirit which pervades all bodies, and is expanded through all the heavens. It is electric, and almost, if not quite immeasurably elastic and rare. By the force and action of which spirit the particles of bodies mutually attract one another, at near distances, and cohere, if contiguous. And electric bodies operate at greater distances, as well repelling as attracting the neighboring corpuscles, and light is emitted, reflected, refracted, inflected, and heats bodies. And all sensation is excited, and the members of animal bodies move at the command of the will, namely, by the vibrations of this spirit, mutually propagated along the solid filaments of the nerves, from the outward organs of sense to the brain. And from the brain into the muscles. This spirit was no anima mundi, nothing further from the thought of Newton. But was it not, on his part, a partial recognition of, or attempt to reach an ultimate material force, or primary element, by means of which, in the roaring loom of time, this material universe, God's visible garment, may be woven for us? The Royal Society were greatly interested in the results of some experiments, which our author had, at the same time, communicated to them relative to the excitation of electricity in glass. And they, after several attempts and further direction from him, succeeded in reproducing the same phenomena. One of the most curious of Newton's minor inquiries related to the connection between the refractive powers and chemical composition of bodies. He found on comparing the refractive powers and the densities of many different substances, that the former were very nearly proportional to the latter, in the same bodies. Unctuous and sulphureous bodies were noticed as remarkable exceptions, as well as the diamond, their refractive powers being 2 or 3 times greater in respect of their densities than in the case of other substances, while, as among themselves, the one was generally proportional to the other. He hence inferred as to the diamond a great degree of combustibility, a conjecture which the experiments of modern chemistry have shown to be true. The chemical researches of our author were probably pursued with more or less diligence from the time of his witnessing some of the practical operations in that science at the apothecaries at Grantham. De Natura Acidorum is a short chemical paper, on various topics, and published in Dr. Horsley's edition of his works. Tabula Quantitatum et Graduum Caloris was inserted in the Philosophical Transactions. It contains a comparative scale of temperature from that of melting ice to that of a small kitchen coal fire. He regarded fire as a body heated so hot as to emit light copiously, and flame as a vapor, fume, or exhalation heated so hot as to shine. To elective attraction, by the operation of which the small particles of bodies, as he conceived, act upon one another, at distances so minute as to escape observation, he ascribed all the various chemical phenomena of precipitation, combination, solution, and crystallization, and the mechanical phenomena of cohesion and capillary attraction. Newton's chemical views were illustrated and confirmed, in part, at least, in his own lifetime. As to the structure of bodies, he was of opinion, that the smallest particles of matter may cohere by the strongest attractions, and compose bigger particles of weaker virtue. And many of these may cohere and compose bigger particles whose virtue is still weaker. And so on for divers successions, until the progression end in the biggest particles, on which the operations in chemistry and the colors of natural bodies depend, and which by adhering, compose bodies of sensible magnitude. There is good reason to suppose that our author was a diligent student of the writings of Jacob Behmen, and that in conjunction with a relative, Dr. Newton, he was busily engaged, for several months in the earlier part of life, in quest of the philosopher's tincture. Great alchemist, however, very imperfectly describes the character of Behmen, whose researches into things material and things spiritual, things human and things divine, afford the strongest evidence of a great and original mind. More appropriately here, perhaps, than elsewhere, may be given Newton's account of some curious experiments, made in his own person, on the action of light upon the retina. Locke, who was an intimate friend of our author, wrote to him for his opinion on a certain fact stated in Boyle's Book of Colors. Newton, in his reply, dated June 30, 1691, narrates the following circumstances, which probably took place in the course of his optical researches. Thus: the observation you mention in Mr. Boyle's Book of Colors I once tried upon myself with the hazard of my eyes. The manner was this. I looked a very little while upon the sun in the looking-glass with my right eye, and then turned my eyes into a dark corner of my chamber, and winked, to observe the impression made, and the circles of colors which encompassed it. And how they decayed by degrees, and at last vanished. This I repeated a second and a third time. At the third time, when the phantasm of light and colors about it were almost vanished, intending my fancy upon them to see their last appearance, I found, to my amazement, that they began to return. And by little and little to become as lively and vivid as when I had newly looked upon the sun. But when I ceased to intend my fancy upon them, they vanished again. After this, I found, that as often as I went into the dark, and intended my mind upon them, as when a man looks earnestly to see anything which is difficult to be seen, I could make the phantasm return without looking any more upon the sun, and the oftener I made it return, the more easily I could make it return again. And, at length, by repeating this, without looking any more upon the sun, I made such an impression on my eye, that, if I looked upon the clouds, or a book, or any bright object, I saw upon it a round bright spot of light like the sun, and, which is still stranger, though I looked upon the sun with my right eye only, and not with my left, yet my fancy began to make an impression upon my left eye, as well as upon my right. For if I shut my right eye, or looked upon a book, or the clouds, with my left eye, I could see the spectrum of the sun almost as plain as with my right eye, if I did but intend my fancy a little while upon it. For at first, if I shut my right eye, and looked with my left, the spectrum of the sun did not appear till I intended my fancy upon it, but by repeating, this appeared every time more easily. And now, in a few hours' time, I had brought my eyes to such a pass, that I could look upon no blight object with either eye, but I saw the sun before me, so that I durst neither write nor read. But to recover the use of my eyes, shut myself up in my chamber made dark, for 3 days together, and used all means to divert my imagination from the sun. For if I thought upon him, I presently saw his picture, though I was in the dark. But by keeping in the dark, and employing my mind about other things, I began in 3 or 4 days to have some use of my eyes again. And by forbearing to look upon bright objects, recovered them pretty well, though not so well but that, for some months after, the spectrum of the sun began to return as often as I began to meditate upon the phenomena. Even though I lay in bed at midnight with my curtains drawn. But now I have been very well for many years, though I am apt to think, if I durst venture my eyes, I could still make the phantasm return by the power of my fancy. This story I tell you, to let you understand, that in the observation related by Mr. Boyle, the man's fancy probably concurred with the impression made by the sun's light to produce that phantasm of the sun which he constantly saw in bright objects. And so your question about the cause of phantasm involves another about the power of fancy, which I must confess is too hard a knot for me to untie. To place this effect in a constant motion is hard, because the sun ought then to appear perpetually. It seems rather to consist in a disposition of the sensorium to move the imagination strongly, and to be easily moved, both by the imagination and by the light, as often as bright objects are looked upon. Though Newton had continued silent, yet his thoughts were by no means inactive upon the vast subject of the planetary motions. The idea of universal gravitation, first caught sight of, so to speak, in the garden at Woolsthorpe, years ago, had gradually expanded upon him. We find him, in a letter to Dr. Hooke, Secretary of the Royal Society, dated in November, 1679, proposing to verify the motion of the earth by direct experiment, namely, by the observation of the path pursued by a body falling from a considerable height. He had concluded that the path would be spiral, but Dr. Hooke maintained that it would be an eccentric ellipse in vacuo, and an elliptic spiral in a resisting medium. Our author, aided by this correction of his error, and by the discovery that a projectile would move in an elliptical orbit when under the influence of a force varying inversely as the square of the distance, was led to discover the theorem by which he afterwards examined the ellipsis, and to demonstrate the celebrated proposition that a planet acted upon by an attractive force varying inversely as the squares of the distances will describe an elliptical orbit, in one of whose foci the attractive force resides. When he was attending a meeting of the Royal Society, in June 1682, the conversation fell upon the subject of the measurement of a degree of the meridian, executed by M. Picard, a French astronomer, in 1679. Newton took a memorandum of the result. And afterward, at the earliest opportunity, computed from it the diameter of the earth, furnished with these new data, he resumed his calculation of 1666. As he proceeded therein, he saw that his early expectations were now likely to be realized, the thick rushing, stupendous results overpowered him. He became unable to carry on the process of calculation, and entrusted its completion to one of his friends. The discoverer had, indeed, grasped the master fact: the law of falling bodies at the earth's surface was at length identified with that which guided the moon in her orbit. And so his great thought, that had for 16 years loomed up in dim, gigantic outline, amid the first dawn of a plausible hypothesis, now stood forth, radiant and not less grand, in the midday light of demonstrated truth. It were difficult, nay impossible to imagine, even, the influence of a result like this upon a mind like Newton's. It was as if the keystone had been fitted to the glorious arch by which his spirit should ascend to the outskirts of infinite space, spanning the immeasurable, weighing the imponderable, computing the incalculable, mapping out the marchings of the planets and the far wanderings of the corners, and catching, bring back to earth some clearer notes of that higher melody which, as a sounding voice, bears perpetual witness to the design and omnipotence of a creating deity. Newton, extending the law thus obtained, composed a series of about 12 propositions on the motion of the primary planets about the Sun. These were sent to London, and communicated to the Royal Society about the end of 1683. At or near this period, other philosophers, as Sir Christopher Wren, Dr. Halley, and Dr. Hooke, were engaged in investigating the same subject, but with no definite or satisfactory results. Dr. Halley, having seen, it is presumed, our author's propositions, went in August, 1684, to Cambridge to consult with him upon the subject. Newton assured him that he had brought the demonstration to perfection. In November, Dr. Halley received a copy of the work, and, in the following month, announced it to the Royal Society, with the author's promise to have it entered upon their register. Newton, subsequently reminded by the Society of his promise, proceeded in the diligent preparation of the work, and, though suffering an interruption of 6 weeks, transmitted the manuscript of the first book to London before the end of April. The work was entitled Philosophiae Naturalis Principia Mathematica, dedicated to the Royal Society, and presented thereto on the 28th of April, 1685-6. The highest encomiums were passed upon it. And the Council resolved, on the 19th of May, to print it at the expense of the Society, and under the direction of Dr. Halley. The latter, a few days afterward, communicated these steps to Newton, who, in a reply, dated the 20th of June, holds the following language: "The proof you sent me I like very well. I designed the whole to consist of 3 books. The second was finished last summer, being short, and only wants transcribing, and drawing the cuts fairly. Some new propositions I have since thought on, which I can as well let alone. The third wants the theory of comets. In autumn last, I spent 2 months in calculation to no purpose for want of a good method, which made me afterward return to the first book, and enlarge it with diverse propositions, some relating to comets. Others to other things found out last winter. The third I now design to suppress. Philosophy is such an impertinently litigious lady, that a man had as good be engaged in lawsuits as have to do with her. I found it so formerly, and now I can no sooner come near her again, but she gives me warning. The first 2 books without the third will not so well bear the title of Philosophiae Naturalis Principia Mathematica, and thereupon I had altered it to this, De Motu Corporum Libri Duo. But after second thought I retain the former title. It will help the sale of the book, which I ought not to diminish now 'tis yours." This warning arose from some pretensions put forth by Dr. Hooke. And though Newton gave a minute and positive refutations of such claims, yet, to reconcile all differences, he generously added to Prop. 4, Course 6, Book I. A scholium, in which Wren, Hooke and Halley are acknowledged to have independently deduced the law of gravity from the second law of Kepler. The suppression of the third book Dr. Halley could not endure to see. I must again beg you, says he, not to let your resentments run so high as to deprive us of your third book, wherein your applications of your mathematical doctrine to the theory of comets, and several curious experiments, which, as I guess by what you write ought to compose it, will undoubtedly render it acceptable to those who will call themselves philosophers without mathematics, which are much the greater number. To these solicitations Newton yielded. There were no resentments, however, as we conceive, in his design to suppress. He sought peace, for he loved and valued it above all applause. But, in spite of his efforts for tranquility's sake, his course of discovery was all along molested by ignorance or presumptuous rivalry. The publication of the great work now went rapidly forwards. The second book was sent to the Society, and presented on the 2d March, the third, on the April 6th, and the whole was completed and published in the month of May, 1686-7. In the second lemma of the second book, the fundamental principle of his fluxionary calculus was, for the first time, given to the world, but its algorithm or notation did not appear till published in the second volume of Dr. Wallace's works, in 1693. And thus was ushered into existence the Principia, a work to which preeminence above all the productions of the human intellect has been awarded, a work that must be esteemed of priceless worth so long as science has a votary, or a single worshipper be left to kneel at the altar of truth. The entire work bears the general title of the Mathematical Principles of Natural Philosophy. It consists of 3 books. The first 2, entitled, Of the Motion of Bodies, are occupied with the laws and conditions of motions and forces, and are illustrated with many scholia treating of some of the most general and best established points in philosophy, such as the density and resistance of bodies, spaces void of matter, and the motion of sound and light. From these principles, there is deduced, in the third book, drawn up in as popular a style as possible and entitled, Of the System of the World, the Constitution of the System of the World. In regard to this book, the author says, I had, indeed, composed the third book in a popular method, that it might be read by many. But afterwards, considering that such as had not sufficiently entered into the principles could not easily discover the strength of the consequences, nor lay aside the prejudices to which they had been many years accustomed, therefore, to prevent disputes which might be raised upon such accounts, I chose to reduce the substance of this book into the form of propositions, in the mathematical way, which should be read by those only who had first made themselves masters of the principles established in the preceding books, not that I would advise any one to the previous study of every proposition of those books. It is enough if one carefully reads the definitions, the laws of motion, and the 3 first sections of the first book. He may then pass on to this book, and consult such of the remaining propositions of the first 2 books, as the references in this, and his occasions shall require. So that, the system of the world is composed both, in a popular method, and in the form of mathematical propositions. The principle of universal gravitation, namely, that every particle of matter is attracted by, or gravitates to, every other particle of matter, with a force inversely proportional to the squares of their distances, is the discovery which characterizes the Principia. This principle the author deduced from the motion of the moon, and the 3 laws of Kepler, laws, which Newton, in turn, by his greater law, demonstrated to be true. From the first law of Kepler, namely, the proportionality of the areas to the times of their description, our author inferred that the force which retained the planet in its orbit was always directed to the sun. And from the second, namely, that every planet moves in an ellipse with the sun in one of its foci, he drew the more general inference that the force by which the planet moves round that focus varies inversely as the square of its distance therefrom, and he demonstrated that a planet acted upon by such a force could not move in any other curve than a conic section, showing when the moving body would describe a circular, an elliptical, a parabolic, or hyperbolic orbit. He demonstrated, too, that this force, or attracting, gravitating power resided in every, the least particle, but that, in spherical masses, it operated as if confined to their centers. So that, one sphere or body will act upon another sphere or body, with a force directly proportional to the quantity of matter, and inversely as the square of the distance between their centers. And that their velocities of mutual approach will be in the inverse ratio of their quantities of matter. Thus he grandly outlined the universal law. Verifying its truth by the motions of terrestrial bodies, then by those of the moon and other secondary orbs, he finally embraced, in one mighty generalization, the entire solar system, all the movements of all its bodies, planets, satellites and comets, explaining and harmonizing the many diverse and theretofore inexplicable phenomena. Guided by the genius of Newton, we see sphere bound to sphere, body to body, particle to particle, atom to mass, the minutest part to the stupendous whole, each to all, and all to each, in the mysterious bonds of a ceaseless, reciprocal influence. An influence whose workings are shown to be alike present in the globular dewdrop, or oblate spheroidal earth, in the falling shower, or vast heaving ocean tides, in the flying thistledown, or fixed, ponderous rock. In the swinging pendulum, or time-measuring sun, in the varying and unequal moon, or earth's slowly retrograding poles, in the uncertain meteor, or blazing comet wheeling swiftly away on its remote, yet determined round. An influence, in fine, that may link system to system through all the star-glowing firmament. Then firmament to firmament, again and again, till, converging home, it may be, to some ineffable centre, where more presently dwells he who inhabiteth immensity. And where infinitudes meet and eternities have their conflux, and where around move, in softest, swiftest measure, all the countless hosts that crowd heaven's fathomless deeps. And yet Newton, amid the loveliness and magnitude of omnipotence, lost not sight of the Almighty One. A secondary, however universal, was not taken for the first cause. An impressed force, however diffused and powerful, assumed not the functions of the creating, giving energy. Material beauties, splendors, and sublimities, however rich in glory, and endless in extent, concealed not the attributes of an intelligent supreme. From the depths of his own soul, through reason and the word, he had risen, a priori, to God, from the heights of omnipotence, through the design and law of the builded universe, he proved a posteriori, a deity. I had, says he, an eye upon such principles as might work, with considering men, for the belief of a deity, in writing the Principia. At the conclusion whereof, he teaches that, this most beautiful system of the sun, planets and comets, could only proceed from the counsel and dominion of an intelligent and powerful being. And if the fixed stars are the centers of other like systems, these, being formed by the likewise counsels, must be all subject to the dominion of one. Especially since the light of the fixed stars is of the same nature with the light of the sun, and from every system light passes into all other systems, and lest the systems of the fixed stars should, by their gravity, fall on each other mutually. He hath placed those systems at immense distances one from another. This being governs all things, not as the soul of the world, but as Lord over all, and on account of his dominion he is wont, to be called Lord God Pi Alpha Nu Tau Omicron Kappa Rho Alpha Tau Omega Rho, or universal ruler, for God is a relative word, and has a respect to servants. And deity is the dominion of God, not over his own body, as those imagine who fancy God to be the soul of the world, but over servants. The supreme God is a being eternal, infinite, absolutely perfect. But a being, however perfect, without dominion, cannot be said to be Lord God, for we say, my God, your God, the God of Israel, the God of gods, and Lord of lords. But we do not say, my eternal, your eternal, the eternal of Israel, the eternal of gods, we do not say my infinite, or my perfect, these are titles which have no respect to servants. The word God usually signifies Lord, but every Lord is not God. It is the dominion of a spiritual being which constitutes a God, a true, supreme, or imaginary dominion makes a true, supreme, or imaginary God. And from his true dominion it follows that the true God is a living, intelligent and powerful being. And from his other perfections, that he is supreme or most perfect. He is eternal and infinite, omnipotent and omniscient, that is, his duration reaches from eternity to eternity, his presence from infinity to infinity. He governs all things and knows all things, that are or can be done. He is not eternity or infinity, but eternal and infinite. He is not duration and space, but he endures and is present. He endures forever and is everywhere present. And by existing always and everywhere, he constitutes duration and space. Since every particle of space is always, and every indivisible moment of duration is everywhere, certainly the Maker and Lord of things cannot be never and nowhere. Every soul that has perception is, though in different times and different organs of sense and motion, still the same indivisible person. There are given successive parts in duration, coexistent parts in space, but neither the one nor the other in the person of a man, or his thinking principle, and much less can they be found in the thinking substance of God. Every man, so far as he is a thing that has perception, is one and the same man during his whole life, in all and each of his organs of sense. God is one and the same God, always and everywhere. He is omnipresent, not virtually only, but also substantially, for virtue cannot subsist without substance. In him are all things contained and moved, yet neither affects the other. God suffers nothing from the motion of bodies. Bodies find no resistance from the omnipresence of God. It is allowed by all that the Supreme God exists necessarily, and by the same necessity he exists always and everywhere. Whence also he is all similar, all eye, all ear, all brain, all arm, all power to perceive, to understand, and to act, but in a manner not at all human, in a manner not at all corporeal, in a manner utterly unknown to us. As a blind man has no idea of colors, so have we no idea of the manner by which the all-wise God perceives and understands all things. He is utterly void of all body, and bodily figure, and can therefore neither be seen, nor heard, nor touched. Nor ought he to be worshipped under the representation of any corporeal thing. We have ideas of his attributes, but what the real substance of anything is we know not. In bodies we see only their figures and colors, we hear only the sounds, we touch only their outward surfaces, we smell only the smells, and taste only the savors. But their inward substances are not to be known either by our senses, or by any reflex act of our minds, much less, then, have we any idea of the substance of God. We know him only by his most wise and excellent contrivances of things, and final causes. We admire him for his perfections, but we reverence and adore him on account of his dominion, for we adore him as his servants. And a God without dominion, providence, and final causes, is nothing else but fate and nature. Blind metaphysical necessity, which is certainly the same always and everywhere, could produce no variety of things. All that diversity of natural things which we find suited to different times and places could arise from nothing but the ideas and will of a being necessarily existing. Thus, the diligent student of science, the earnest seeker of truth, led, as through the courts of a sacred temple, wherein, at each step, new wonders meet the eye, till, as a crowning grace, they stand before a holy of holies. And learn that all science and all truth are one which hath its beginning and its end in the knowledge of him whose glory the heavens declare, and whose handiwork the firmament showeth forth. The introduction of the pure and lofty doctrines of the Principia was perseveringly resisted. Descartes, with his system of vortices, had sown plausibly to the imagination, and error had struck down deeply, and shot up luxuriantly, not only in the popular, but in the scientific mind. Besides the idea, in itself so simple and so grand, that the great masses of the planets were suspended in empty space, and retained in their orbits by an invisible influence residing in the sun, was to the ignorant a thing inconceivable. And to the learned a revival of the occult qualities of the ancient physics. This remark applies particularly to the continent. Leibniz misapprehended, Huygens in part rejected, John Bernoulli opposed, and Fontenelle never received the doctrines of the Principia. So that, the saying of Voltaire is probably true, that though Newton survived the publication of his great work more than 40 years, yet, at the time of his death, he had not above 20 followers out of England. But in England, the reception of our author's philosophy was rapid and triumphant. His own labors, while Lucasian professor, those of his successors in that chair, Whiston and Saunderson, those of Dr. Samuel Clarke, Dr. Lawton, Roger Coates, and Dr. Bentley, the experimental lectures of Dr. Keel and Desaguliers, The early and powerful exertions of David Gregory at Edinburgh, and of his brother James Gregory at St. Andrews, tended to diffuse widely in England and Scotland a knowledge of, and taste for the truths of the Principia. Indeed, its mathematical doctrines constituted, from the first, a regular part of academical instruction. While its physical truths, given to the public in popular lectures, illustrated by experiments, had, before the lapse of 20 years, become familiar to, and adopted by the general mind. Pemberton's popular View of Sir Isaac Newton's Philosophy was published, in 1728, and the year afterward, an English translation of the Principia, and System of the World, by Andrew Mott. And since that period, the labors of Le Sueur and Jacquier, of Thorpe, of Jebb, of Wright and others have greatly contributed to display the most hidden treasures of the Principia. About the time of the publication of the Principia, James II, bent on re-establishing the Romish faith, had, among other illegal acts, ordered by Mandamus, the University of Cambridge to confer the degree of Master of Arts upon an ignorant monk. Obedience to this mandate was resolutely refused. Newton was one of the 9 delegates chosen to defend the independence of the university. They appeared before the High Court, and successfully, the king abandoned his design. The prominent part which our author took in these proceedings, and his eminence in the scientific world, induced his proposal as one of the parliamentary representatives of the university. He was elected, in 1688, and sat in the Convention Parliament till its dissolution. After the first year, however, he seems to have given little or no attention to his parliamentary duties, being seldom absent from the university till his appointment in the Mint, in 1695. Newton began his theological researches sometime previous to 1691, in the prime of his years, and in the matured vigor of his intellectual powers. From his youth, as we have seen, he had devoted himself with an activity the most unceasing, and an energy almost superhuman to the discovery of physical truth, giving to philosophy a new foundation, and to science a new temple. To pass on, then, from the consideration of the material, more directly to that of the spiritual, was a natural, nay, with so large and devout a soul, a necessary advance. The Bible was to him of inestimable worth. In the elastic freedom, which a pure and unswerving faith in him of Nazareth gives, his mighty faculties enjoyed the only completest scope for development. His original endowment, however great, combined with a studious application, however profound, would never, without this liberation from the dominion of passion and sense, have enabled him to attain to that wondrous concentration and grasp of intellect, for which fame has as yet assigned him no equal. Gratefully he owned, therefore, the same author in the book of nature and the book of Revelation. These were to him as drops of the same unfathomable ocean, as outrayings of the same inner splendor, as tones of the same ineffable voice, as segments of the same infinite curve. With great joy he had found himself enabled to proclaim, as an interpreter, from the hieroglyphs of creation, the existence of a God, and now, with greater joy, and in the fullness of his knowledge, and in the fullness of his strength, he labored to make clear, from the utterances of the inspired word, the far mightier confirmations of a supreme good, in all its glorious amplitude of being and of attribute, and to bring the infallible workings thereof plainly home to the understandings and the affections of his fellow men. And finally to add the weight of his own testimony in favor of that religion, whose truth is now, indeed, girded with the iron and the rock of a ponderous and colossal demonstration. His work, entitled, Observations upon the Prophecies of Holy Writ, particularly the prophecies of Daniel and the Apocalypse of St. John, first published in London, in 1733–42. Consists of 2 parts, the one devoted to the prophecies of Daniel, and the other to the Apocalypse of St. John. In the first part, he treats concerning the compilers of the books of the Old Testament, of the prophetic language, of the vision of the 4 beasts, of the kingdoms represented by the feet of the image composed of iron and clay, of the 10 kingdoms represented by the 10 horns of the beast, of the 11th horn of Daniel's 4th beast, of the power which should change times and laws, of the kingdoms represented in Daniel by the ram and he-goat, of the prophecy of the 70 weeks, of the times of the birth and passion of Christ, of the prophecy of the scripture of truth. Of the king who doeth according to his will, and magnified himself above every god, and honored Mahusims, and regarded not the desire of women, of the Mahusim, honored by the king who doeth according to his will. In the second part, he treats of the time when the Apocalypse was written, of the scene of the vision, and the relation which the Apocalypse has to the book of the law of Moses, and to the worship of God in the temple. Of the relation which the Apocalypse has to the prophecies of Daniel, and of the subject of the prophecy itself. Newton regards the prophecies as given, not for the gratification of man's curiosity, by enabling him to foreknow, but toward his conviction that the world is governed by providence, by witnessing their fulfillment. Enough of prophecy, he thinks, has already been fulfilled to afford the diligent seeker abundant evidence of God's providence. The whole work is marked by profound erudition, sagacity and argument. And not less learning, penetration and masterly reasoning are conspicuous in his historical account of two notable corruptions of scriptures in a letter to a friend. This treatise, first accurately published in Dr. Horsley's edition of his works, relates to two texts, the one, Epistle of St. John v. 7, the other, Epistle of St. Paul to Timothy 3. 16. As this work had the effect to deprive the advocates of the doctrine of the Trinity of two leading texts, Newton has been looked upon as an Arian, but there is absolutely nothing in his writings to warrant such a conclusion. His remaining theological works consist of the Lexicon Propheticum, which was left incomplete. A Latin dissertation on the sacred cubit of the Jews, which was translated into English, and published, in 1737, among the miscellaneous works of John Greaves, and 4 letters addressed to Dr. Bentley, containing some arguments in proof of a deity. These letters were dated respectively, December 10, 1692, January 17, 1693, February 25, 1693, and 11 Lth February, 1693, the fourth bearing an earlier date than the third. The best faculties and the profoundest acquirements of our author are convincingly manifest in these lucid and powerful compositions. They were published in 1756, and reviewed by Dr. Samuel Johnson. Newton's religious writings are distinguished by their absolute freedom from prejudice. Everywhere, throughout them, there glows the genuine nobleness of soul. To his whole life, indeed, we may here fitly extend the same observation. He was most richly imbued with the very spirit of the Scriptures which he so delighted to study and to meditate upon. His was a piety, so fervent, so sincere and practical, that it rose up like a holy incense from every thought and act. His a benevolence that not only willed, but endeavored the best for all. His a philanthropy that held in the embracings of its love every brother man. His a toleration of the largest and the truest. Condemning persecution in every, even its mildest form. And kindly encouraging each striving after excellence, a toleration that came not of indifference for the immoral and the impious met with their quick rebuke, but a toleration that came of the wise humbleness and the Christian charity, which see in the nothingness of self and the almightiness of truth, no praise for the ablest, and no blame for the feeblest in their strugglings upward to light and life. In the winter of 1691-2, on returning from chapel, one morning, Newton found that a favorite little dog, called Diamond, had overturned a lighted taper on his desk, and that several papers containing the results of certain optical experiments were nearly consumed. His only exclamation, on perceiving his loss, was, "O Diamond, Diamond, little knowest thou the mischief thou hast done." Dr. Brewster, in his Life of our author, gives the following extract from the manuscript diary of Mr. Abraham de la Prime, a student in the university at the time of this occurrence. 1692, February, 3. What I heard today I must relate. There is one Mr. Newton, whom I have very oft seen, fellow of Trinity College, that is mighty famous for his learning, being a most excellent mathematician, philosopher, divine, and he has been fellow of the Royal Society these many years. And among other very learned books and tracts, he's written one upon the mathematical principles of philosophy, which has given him a mighty name, he having received, especially from Scotland, abundance of congratulatory letters for the same. But of all the books he ever wrote, there was one of Colours and Light, established upon thousands of experiments which he had been 20 years of making, and which had cost him many hundreds of pounds. This book which he valued so much, and which was so much talked of, had the ill luck to perish, and be utterly lost just when the learned author was almost at pitting a conclusion at the same, after this manner, in a winter's morning. Leaving it among his other papers on his study table while he went to chapel, the candle, which he had unfortunately left burning there, too, catched hold by some means of other papers, and they fired the aforesaid book, and utterly consumed it and several other valuable writings. And which is most wonderful, did no further mischief. But when Mr. Newton came from chapel, and had seen what was done, every one thought he would have run mad. He was so troubled thereat that he was not himself for a month after. A long account of this his system of colours you may find in the Transactions of the Royal Society, which he had sent up to them long before this sad mischance happened unto him. It will be borne in mind that all of Newton's theological writings, with the exception of the letters to Dr. Bentley, were composed before this event which, we must conclude, from Prime's words, produced a serious impression upon our author for about a month. But M. Byett, in his Life of Newton, relying on a memorandum contained in a small manuscript journal of Huygens, declares this occurrence to have caused a derangement of Newton's intellect. M. Byett's opinions and deductions, however, as well as those of Laplace, upon this subject, were based upon erroneous data, and have been overthrown by the clearest proof. There is not, in fact, the least evidence that Newton's reason was, for a single moment, dethroned. On the contrary, the testimony is conclusive that he was, at all times, perfectly capable of carrying on his mathematical, metaphysical, and astronomical inquiries. Loss of sleep, loss of appetite, and irritated nerves will disturb somewhat the equanimity of the most serene. And an act done, or language employed, under such temporary discomposure, is not a just criterion of the general tone and strength of a man's mind. As to the accident itself, we may suppose, whatever might have been its precise nature, that it greatly distressed him, and, still further, that its shock may have originated the train of nervous derangements, which afflicted him, more or less, for 2 years afterward. Yet, during this very period of ill health, we find him putting forth his highest powers. In 1692, he prepared for, and transmitted to Dr. Wallace the first proposition of the treatise on quadratures, with examples of it in first, second and third fluxions. He investigated, in the same year, the subject of halos, making and recording numerous and important observations relative thereto. Those profound and beautiful letters to Dr. Bentley were written at the close of this and the beginning of the next year. In October, 1693, Locke, who was then about publishing a second edition of his work on the human understanding, requested Newton to reconsider his opinions on innate ideas. And in 1694, he was zealously occupied in perfecting his lunar theory, visiting Flamstead, at the Royal Observatory of Greenwich, in September, and obtaining a series of lunar observations. And commencing, in October, a correspondence with that distinguished practical astronomer, which continued till 1698. We now arrive at the period when Newton permanently withdrew from the seclusion of a collegiate, and entered upon a more active and public life. He was appointed Warden of the Mint, in 1695, through the influence of Charles Montague, Chancellor of the Exchequer, and afterward Earl of Halifax. The current coin of the nation had been adulterated and debased, and Montague undertook a recoinage. Our author's mathematical and chemical knowledge proved eminently useful in accomplishing this difficult and most salutary reform. In 1699, he was promoted to the Mastership of the Mint, an office worth £1200 or £1500 per annum, and which he held during the remainder of his life. He wrote, in this capacity, an official report on the coinage, which has been published. He also prepared a table of assays of foreign coins, which was printed at the end of Dr. Arbuthnot's tables of ancient coins, weights, and measures, in 1727. Newton retained his professorship at Cambridge till 1703. But he had, on receiving the appointment of Master of the Mint, in 1699, made Mr. Whiston his deputy, with all the emoluments of the office. and, on finally resigning, procured his nomination to the vacant chair. In January 1697, John Bernoulli proposed to the most distinguished mathematicians of Europe 2 problems for solution. Leibniz, admiring the beauty of one of them, requested the time for solving it to be extended to 12 months, twice the period originally named. The delay was readily granted. Newton, however, sent in, the day after he received the problems, a solution of them to the President of the Royal Society. Bernoulli obtained solutions from Newton, Leibniz, and the Marquis de l'Hôpital. But Newton's, though anonymous, he immediately recognized tanquam ungulationem as the lion is known by his claw. We may mention here the famous problem of the trajectories proposed by Leibniz, in 1716, for the purpose of feeling the pulse of the English analysts. Newton received the problem about 5 o'clock in the afternoon, as he was returning from the Mint, and though it was extremely difficult and he himself much fatigued, yet he completed its solution, the same evening before he went to bed. The history of these problems affords, by direct comparison, a striking illustration of Newton's vast superiority of mind. That amazing concentration and grasp of intellect, of which we have spoken, enabled him to master speedily, and, as it were, by a single effort, those things, for the achievement of which, the many would essay utterly in vain, and the very few attain only after long and renewed striving. And yet, with a modesty as unparalleled as his power, he attributed his successes, not to any extraordinary sagacity, but solely to industry and patient thought. He kept the subject of consideration constantly before him, and waited till the first dawning opened gradually into a full and clear light, never quitting, if possible, the mental process till the object of it were wholly gained. He never allowed this habit of meditation to appear in his intercourse with society, but in the privacy of his own chamber, or in the midst of his own family, he gave himself up to the deepest abstraction. Occupied with some interesting investigation, he would often sit down on his bedside, after he rose, and remain there, for hours, partially dressed. Mealtime would frequently come and pass unheeded. So that, unless urgently reminded, he would neglect to take the requisite quantity of nourishment. But notwithstanding his anxiety to be left undisturbed, he would, when occasion required, turn aside his thoughts, though bent upon the most intricate research, and then, when leisure served, again direct them to the very point where they ceased to act, and this he seemed to accomplish not so much by the force of his memory, as by the force of his inventive faculty, before the vigorous intensity of which, no subject, however abstruse, remained long unexplored. He was elected a member of the Royal Academy of Sciences at Paris, in 1699, when that distinguished body were empowered, by a new charter, to admit a small number of foreign associates. In 1700, he communicated to Dr. Halley a description of his reflecting instrument for observing the moon's distance from the fixed stars. This description was published in the Philosophical Transactions, in 1742. The instrument was the same as that produced by Mr. Hadley, in 1731, and which, under the name of Hadley's quadrant, has been of so great use in navigation. On the assembling of the new Parliament, in 1701, Newton was re-elected one of the members for the University of Cambridge. In 1703, he was chosen President of the Royal Society of London, to which office he was annually re-elected till the period of his decease, about 25 years afterward. Our author unquestionably devoted more labor to, and, in many respects, took a greater pride in his optical, than his other discoveries. This science he had placed on a new and indestructible basis. And he wished not only to build, but to perfect the costly and glowing structure. He had communicated, before the publication of the Principia, his most important researches on light to the Royal Society, in detached papers which were inserted in successive numbers of the Transactions. But he did not publish a connected view of these labors till 1704, when they appeared under the title of Optics, or, a treatise on the reflections, refractions, inflections and colors of light. To this, but to no subsequent edition, were added 2 mathematical treatises, entitled Tractatus duo de Specibus et Magnitudine Figurarum Curvilinearum, the one bearing the title Tractatus de Quadratura Curvarum, and the other, that of Enumeratio Linearum Tertii Ordinis. The publication of these mathematical treatises was made necessary in consequence of plagiarisms from the manuscripts of them loaned by the author to his friends. Dr. Samuel Clarke published a Latin translation of the Optics, in 1706, whereupon he was presented by Newton, as a mark of his grateful approbation, with £500, or £100 for each of his children. The work was afterward translated into French. It had a remarkably wide circulation, and appeared, in several successive editions, both in England and on the Continent. There is displayed, particularly on this optical treatise, the author's talent for simplifying and communicating the profoundest speculations. It is a faculty rarely united to that of the highest invention. Newton possessed both. And thus that mental perfectness which enabled him to create, to combine, and to teach, and so render himself, not the ornament only, but inconceivably more, the preeminent benefactor of his species. The honor of knighthood was conferred on our author in 1705. Soon afterward, he was a candidate again for the representation of the university, but was defeated by a large majority. It is thought that a more pliant man was preferred by both ministers and electors. Newton was always remarkable for simplicity of dress, and his only known departure from it was on this occasion, when he is said to have appeared in a suit of laced clothes. The algebraical lectures which he had, during 9 years, delivered at Cambridge, were published by Whiston, in 1707, under the title of Arithmetica Universalis, signed the composition et resolutions Arithmetica Liber. This publication is said to have been a breach of confidence on Whiston's part. Mr. Ralph Sun, not long afterward, translated the work into English, and a second edition of it, with improvements by the author, was issued at London, 1712, by Dr. Machin. Subsequent editions, both in English and Latin, with commentaries, have been published. In June, 1709, Newton entrusted the superintendence of a second edition of the Principia to Roger Coates, Plumian Professor of Astronomy at Cambridge. The first edition had been sold off for some time. Copies of the work had become very rare, and could only be obtained at several times their original cost. A great number of letters passed between the author and Mr. Coates during the preparation of the edition, which finally appeared in May, 1713. It had many alterations and improvements, and was accompanied by an admirable preface from the pen of Coates. Our author's early treatise, entitled, Analysis per Equations Numero Terminorum Infinitas, as well as a small tract, bearing the title of Methodus Differentialis, was published, with his consent, in 1711. The former of these, and the treatise De Quadratura Curvarum, translated into English, with a large commentary, appeared in 1745. His work, entitled, Artis Analyticae Specimina, vel Geometria Analytica, was first given to the world in the edition of Dr. Horsley, 1779. It is a notable fact, in Newton's history, that he never voluntarily published any one of his purely mathematical writings. The cause of this unwillingness in some, and, in other instances, of his indifference, or, at least, want of solicitude to put forth his works may be confidently sought for in his repugnance to everything like contest or dispute. But, going deeper than this aversion, we find, underlying his whole character and running parallel with all his discoveries, that extraordinary humility which always preserved him in a position so relatively just to the behests of time and eternity. That the infinite value of truth, and the utter worthlessness of fame, were alike constantly present to him. Judging of his course, however, in its more temporary aspect, as bearing upon his immediate quiet, it seemed the most unfortunate. For an early publication, especially in the case of his method of flux ions, would have anticipated all rivalry, and secured him from the contentious claims of Leibniz. Still each one will solve the problem of his existence in his own way, and, with a man like Newton, his own, as we conceive, could be no other than the best way. The conduct of Leibniz in this affair is quite irreconcilable with the stature and strength of the man, giant-like, and doing nobly, in many ways, a giant's work, yet cringing himself into the dimensions and performances of a common calumniator. Opening in 1699, the discussion in question continued till the close of Leibniz's life, in 1716. We give the summary of the case as contained in the report of the Committee of the Royal Society, the deliberately weighed opinion of which has been adopted as an authoritative decision in all countries. We have consulted the letters and letter books in the custody of the Royal Society, and those found among the papers of Mr. John Collins, dated between the years 1669 and 1677, inclusive, and showed them to such as knew and avouched the hands of Mr. Barrow, Mr. Collins, Mr. Oldenburg, and Mr. Leibniz, and compared those of Mr. Gregory with one another, and with copies of some of them taken in the hand of Mr. Collins. And have extracted from them what relates to the matter referred to us, all which extracts, herewith delivered to you, we believe to be genuine and authentic. And by these letters and papers we find Mr. Leibniz was in London in the beginning of the year 1673, and went thence in or about March, to Paris, where he kept a correspondence with Mr. Collins, by means of Mr. Oldenburg, till about September, 1676, and then returned, by London and Amsterdam, to Hanover, and that Mr. Collins was very free in communicating to able mathematicians what he had received from Mr. Newton and Mr. Gregory. 2. That when Mr. Leibniz was the first time in London, he contended for the invention of another differential method, properly so called, and, notwithstanding he was shown by Dr. Pell that it was Newton's method, persisted in maintaining it to be his own invention, by reason that he had found it by himself without knowing what Newton had done before, and had much improved it. And we find no mention of his having any other differential method than Newton's before his letter of the 21st of June, 1677, which was a year after a copy of Mr. Newton's letter of the 10th of December, 1672, had been sent to Paris to be communicated to him, and above 4 years after Mr. Collins began to communicate that letter to his correspondents. In which letter the method of flux ions was sufficiently described to any intelligent person. 3. That by Mr. Newton's letter, of the 13th of June, 1676 it appears that he had the method of flux ions above 5 years before the writing of that letter. And by his analysis per A equations numero terminorum infinitas, communicated by Dr. Barrow to Mr. Collins, in July, 1669, we find that he had invented the method before that time. 4. That the differential method is one and the same with the method of flux ions, excepting the name and mode of notation, Mr. Leibniz calling those quantities differences which Mr. Newton calls moments, or flux ions, and marking them with a letter D, a mark not used by Mr. Newton. And, therefore, we take the proper question to be, not who invented this or that method, but, who was the first inventor of the method. And we believe that those who have reputed Mr. Leibniz the first inventor knew little or nothing of his correspondence with Mr. Collins and Mr. Oldenburg long before, nor of Mr. Newton's having that method above 15 years before Mr. Leibniz began to publish it in the Acta Eruditorum of Leipzig. For which reason we reckon Mr. Newton the first inventor, and are of opinion that Mr. Keel, in asserting the same, has been no ways injurious to Mr. Leibniz. And we submit to the judgment of the Society, whether the extract and papers, now presented to you, together with what is extant, to the same purpose, in Dr. Wallace's 3rd volume, may not deserve to be made public. This report, with the collection of letters and manuscripts, under the title of Commercium Epistolicum D. Johannes Collins Idealiorum de Analysi pro moda Jussu Societatis Regii Editum, appeared accordingly in the early part of 1713. Its publication seemed to infuse additional bitterness into the feelings of Leibniz, who descended to unfounded charges and empty threats. He had been privy councillor to the Elector of Hanover, before that prince was elevated to the British throne, and in his correspondence, in 1715 and 1716, with the Abbé Conti, then at the court of George I. And with Caroline, Princess of Wales, he attacked the doctrines of the Principia, and indirectly its author, in a manner very discreditable to himself, both as a learned and as an honourable man. His assaults, however, were triumphantly met. And, to the complete overthrow of his rival pretensions, Newton was induced to give the finishing blow. The verdict is universal and irreversible that the English preceded the German philosopher, by at least 10 years, in the invention of flux ions. Newton could not have borrowed from Leibniz, but Leibniz might have borrowed from Newton. A new edition of the Commercium Epistolicum was published in 1722-5. But neither in this, nor in the former edition, did our author take any part. The disciples, enthusiastic, capable and ready, effectually shielded, with the buckler of truth, the character of the master, whose own conduct throughout was replete with delicacy, dignity, and justice. He kept aloof from the controversy, in which Dr. Keel stood forth as the chief representative of the Newtonian side, till the very last, when, for the satisfaction of the king, George I, rather than for his own, he consented to put forth his hand and firmly secure his rights upon a certain and impregnable basis. A petition to have inventions for promoting the discovery of the longitude at sea, suitably rewarded, was presented to the House of Commons, in 1714. A committee, having been appointed to investigate the subject, called upon Newton and others for their opinions. That of our author was given in writing. A report, favorable to the desired measure, was then taken up, and a bill for its adoption subsequently passed. On the accession of George I, in 1714, Newton became an object of profound interest at court. His position under government, his surpassing fame, his spotless character, and, above all, his deep and consistent piety, attracted the reverent regard of the Princess of Wales, afterward Queen Consort to George II. She was a woman of a highly cultivated mind, and derived the greatest pleasure from conversing with Newton and corresponding with Leibniz. One day, in conversation with her, our author mentioned and explained a new system of chronology, which he had composed at Cambridge, where he had been in the habit of refreshing himself with history and chronology, when he was weary with other studies. Subsequently, in the year 1718, she requested a copy of this interesting and ingenious work. Newton, accordingly, drew up an abstract of the system from the separate papers in which it existed, and gave it to her on condition that it should not be communicated to any other person. Some time afterward she requested that the Abbé Conti might be allowed to have a copy of it. The author consented, and the Abbé received a copy of the manuscript, under the like injunction and promise of secrecy. This manuscript bore the title of A Short Chronicle, from the First Memory of Things in Europe, to the Conquest of Persia, by Alexander the Great. After Newton took up his residence in London, he lived in a style suited to his elevated position and rank. He kept his carriage, with an establishment of 3 male and 3 female servants. But to everything like vain show and luxury he was utterly averse. His household affairs, for the last 20 years of his life, were under the charge of his niece, Mrs. Catherine Barton, wife and widow of Colonel Barton, a woman of great beauty and accomplishment, and subsequently married to John Conduit, Esq. At home Newton was distinguished by that dignified and gentle hospitality which springs alone from true nobleness. On all proper occasions, he gave splendid entertainments, though without ostentation. In society, whether of the palace or the cottage, his manner was self-possessed and urbane, his look benign and affable, his speech candid and modest, his whole air undisturbedly serene. He had none of what are usually called the singularities of genius, suiting himself easily to every company, except that of the vicious and wicked, and speaking of himself and others, naturally, so as never even to be suspected of vanity. There was in him, if we may be allowed the expression, a wholeness of nature, which did not admit of such imperfections and weakness. The circle was too perfect, the law too constant, and the disturbing forces too slight to suffer scarcely any of those eccentricities which so interrupt and mar the movements of many bright spirits, rendering their course through the world more like that of the blazing meteor than that of the light and life-imparting sun. In brief, the words greatness and goodness could not, humanly speaking, be more fitly employed than when applied as the preeminent characteristics of this pure, meek and venerable sage. In the 80th year of his age, Newton was seized with symptoms of stone in the bladder. His disease was pronounced incurable. He succeeded, however, by means of a strict regimen, and other precautions, in alleviating his complaint, and procuring long intervals of ease. His diet, always frugal, was now extremely temperate, consisting chiefly of broth, vegetables, and fruit, with, now and then, a little butcher meat. He gave up the use of his carriage, and employed, in its stead, when he went out, a chair. All invitations to dinner were declined, and only small parties were received, occasionally, at his own house. In 1724 he wrote to the Lord Provost of Edinburgh, offering to contribute £20 yearly toward the salary of Mr. Maclaurin, provided he accepted the assistant professorship of mathematics in the university of that place. Not only in the cause of ingenuity and learning, but in that of religion, in relieving the poor and assisting his relations, Newton annually expended large sums. He was generous and charitable almost to a fault. Those, he would often remark, who gave away nothing till they died, never gave at all. His wealth had become considerable by a prudent economy. But he regarded money in no other light than as one of the means wherewith he had been entrusted to do good, and he faithfully employed it accordingly. He experienced, in spite of all his precautionary measures, a return of his complaint in the month of August, of the same year, 1724, when he passed a stone the size of pea. It came from him in 2 pieces, the one at the distance of 2 days from the other. Tolerable good health then followed for some months. In January, 1725, however, he was taken with a violent cough and inflammation of the lungs. In consequence of this attack, he was prevailed upon to remove to Kensington, where his health greatly improved. In February following, he was attacked in both feet with the gout, of the approach of which he had received, a few years before, a slight warning, and the presence of which now produced a very beneficial change in his general health. Mr. Conduit, his nephew, has recorded a curious conversation which took place, at or near this time, between himself and Sir Isaac. I was, on Sunday night, the 7th March, 1724-5, at Kensington, with Sir Isaac Newton, in his lodgings, just after he was out of a fit of the gout, which he had had in both of his feet, for the first time, in the 83rd year of his age. He was better after it, and his head clearer and memory stronger than I had known them for some time. He then repeated to me, by way of discourse, very distinctly, though rather in answer to my queries, than in one continued narration, what he had often hinted to me before, viz. That it was his conjecture, he would affirm nothing, that there was a sort of revolution in the heavenly bodies. That the vapors and light, emitted by the sun, which had their sediment, as water and other matter, had gathered themselves, by degrees, into a body, and attracted more matter from the planets, and at last made a secondary planet, viz. one of those that go round another planet, and then, by gathering to them, and attracting more matter, became a primary planet. And then, by increasing still, became a comet, which, after certain revolutions, by coming nearer and nearer to the sun, had all its volatile parts condensed. And became a matter fit to recruit and replenish the sun, which must waste by the constant heat and light it emitted, as a faggot would this fire if put into it, we were sitting by it would fire. And that would probably be the effect of the comet of 1680, sooner or later. For, by the observations made upon it, it appeared, before it came near the sun, with a tail only 2 or 3 degrees long. But, by the heat it contracted, in going so near the sun, it seemed to have a tail of 30 or 40 degrees when it went from it, that he could not say when this comet would drop into the sun. It might perhaps have 5 or 6 revolutions more first, but whenever it did it would so much increase the heat of the sun that this earth would be burned, and no animals in it could live. That he took the 3 phenomena, seen by Hipparchus, Tycho Brahe, and Kepler's disciples, to have been of this kind, for he could not otherwise account for an extraordinary light, as those were, appearing, all at once. Among the fixed stars, all which he took to be suns, enlightening other planets, as our sun does ours, as big as Mercury or Venus seems to us, and gradually diminishing, for 16 months, and then sinking into nothing. He seemed to doubt whether there were not intelligent beings, superior to us, who superintended these revolutions of the heavenly bodies, by the direction of the Supreme Being. He appeared also to be very clearly of opinion that the inhabitants of this world were of short date, and all-edged, as one reason for that opinion, that all arts, as letters, ships, printing, needle, and were discovered within the memory of history, which could not have happened if the world had been eternal, and that there were visible marks of ruin upon it which could not be affected by flood only. When I asked him how this earth could have been repeopled if ever it had undergone the same fate it was threatened with hereafter, by the comet of 1680, he answered, that required the power of a creator. He said he took all the planets to be composed of the same matter with this earth, viz., earth, water, stones, and but variously concocted. I asked him why he would not publish his conjectures, as conjectures, and instanced that Kepler had communicated his. And though he had not gone near so far as Kepler, yet Kepler's guesses were so just and happy that they had been proved and demonstrated by him. His answer was, I do not deal in conjectures. But, on my talking to him about the 4 observations that had been made of the comet of 1680, at 574 years distance, and asking him the particular times, he opened his Principia, which laid on the table, and showed me the particular periods, viz. First, the Julium Sidus, in the time of Justinian, in 1106, in 1680. And I, observing that he said there of that comet, incidet in corpus solis, and in the next paragraph adds, stelli fixi refici passant, told him I thought he owned there what we had been talking about, viz. that the comet would drop into the sun, and that fixed stars were recruited and replenished by comets when they dropped into them, and, consequently, that the sun would be recruited too. And asked him why he would not own as fully what he thought of the sun as well as what he thought of the fixed stars. He said, that concerned us more, and, laughing, added, that he had said enough for people to know his meaning. In the summer of 1725, a French translation of the Chronological MS, of which the Abbé Conti had been permitted, some time previous, to have a copy, was published at Paris, in violation of all good faith. The Punic Abbé had continued true to his promise of secrecy while he remained in England, but no sooner did he reach Paris than he placed the manuscript into the hands of M. Freret, a learned antiquarian, who translated the work, and accompanied it with an attempted refutation of the leading points of the system. In November, of the same year, Newton received a presentation copy of this publication, which bore the title of Abrège de chronologie de M. Le Chevalier Newton, fait par lui-même, et traduit sur le manuscrit anglais. Soon afterward a paper entitled Remarks on the Observations Made on a Chronological Index of Sir Isaac Newton, translated into French by the Observator, and published at Paris, was drawn up by our author, and printed in the Philosophical Transactions for 1725. It contained a history of the whole matter, and a triumphant reply to the objections of M. Freret. This answer called into the field a fresh antagonist, Father Suyat, whose 5 dissertations on this subject were chiefly remarkable for the want of knowledge and want of decorum, which they displayed. In consequence of these discussions, Newton was induced to prepare his larger work for the press, and had nearly completed it at the time of his death. It was published in 1728, under the title of the Chronology of the Ancient Kingdoms Amended, to which is prefixed a short chronicle from the first memory of things in Europe to the conquest of Persia by Alexander the Great. It consists of 6 chapters. 1. On the chronology of the Greeks. According to Whiston, our author wrote out 18 copies of this chapter with his own hand, differing little from one another. 2. Of the Empire of Egypt. 3. Of the Assyrian Empire. 4. Of the 2 contemporary empires of the Babylonians and Medes. 5. A description of the Temple of Solomon. 6. Of the Empire of the Persians. This chapter was not found copied with the other 5, but as it was discovered among his papers, and appeared to be a continuation of the same work, the editor thought proper to add it thereto. Newton's letter to a person of distinction who had desired his opinion of the learned Bishop Lloyd's hypothesis concerning the form of the most ancient year, closes this enumeration of his chronological writings. A 3rd edition of the Principia appeared in 1726, with many changes and additions. About 4 years were consumed in its preparation and publication, which were under the superintendence of Dr. Henry Pemberton, an accomplished mathematician, and the author of A View of Sir Isaac Newton's Philosophy. 1728, this gentleman enjoyed numerous opportunities of conversing with the aged and illustrious author. I found, says Pemberton, he had read fewer of the modern mathematicians than one could have expected, but his own prodigious invention readily supplied him with what he might have an occasion for in the pursuit of any subject he undertook. I have often heard him censure the handling geometrical subjects by algebraic calculations. And his book of algebra he called by the name of Universal Arithmetic, in opposition to the injudicious title of geometry, which Descartes had given to the treatise. Wherein he shows how the geometer may assist his invention by such kind of computations. He thought Huygens the most elegant of any mathematical writer of modern times, and the most just imitator of the ancients. Of their taste and form of demonstration, Sir Isaac always professed himself a great admirer. I have heard him even censure himself for not following them yet more closely than he did. And speak with regret of his mistake at the beginning of his mathematical studies, in applying himself to the works of Descartes and other algebraic writers. Before he had considered the elements of Euclid with that attention which so excellent a writer deserves. Though his memory was much decayed, continues Dr. Pemberton, he perfectly understood his own writings. And even this failure of memory, we would suggest, might have been more apparent than real, or, in medical terms, more the result of functional weakness than organic decay. Newton seems never to have confided largely to his memory, and as this faculty manifests the most susceptibility to cultivation, so, in the neglect of due exercise, it more readily and plainly shows a diminution of its powers. Equanimity and temperance had, indeed, preserved Newton singularly free from all mental and bodily ailment. His hair was, to the last, quite thick, though as white as silver. He never made use of spectacles, and lost but one tooth to the day of his death. He was of middle stature, well knit, and, in the latter part of his life, somewhat inclined to be corpulent. Mr. Conduit says, he had a very lively and piercing eye, a comely and gracious aspect, with a fine head of hair, white as silver, without any baldness, and when his peruke was off was a venerable sight. According to Bishop Atterbury, in the whole air of his face and make there was nothing of that penetrating sagacity which appears in his compositions. He had something rather languid in his look and manner which did not raise any great expectation in those who did not know him. Hearn remarks, Sir Isaac was a man of no very promising aspect. He was a short, well-set man. He was full of thought, and spoke very little in company, so that his conversation was not agreeable. When he rode in his coach, one arm would be out of his coach on one side and the other on the other. These different accounts we deem easily reconcilable. In the rooms of the Royal Society, in the street, or in mixed assemblages, Newton's demeanour, always courteous, unassuming and kindly, still had in it the overawings of a profound repose and reticency, out of which the communicative spirit and the lively and piercing eye would only gleam in the quiet and unrestrained freedom of his own fireside. But this I immediately discovered in him, adds Pemberton, still further, which at once both surprised and charmed me. Neither his extreme great age, nor his universal reputation had rendered him stiff in opinion, or in any degree elated. Of this I had occasion to have almost daily experience. The remarks I continually sent him by letters on his Principia, were received with the utmost goodness. These were so far from being any ways displeasing to him, that, on the contrary, it occasioned him to speak many kind things of me to my friends, and to honor me with a public testimony of his good opinion. A modesty, openness, and generosity, peculiar to the noble and comprehensive spirit of Newton. Full of wisdom and perfect in beauty, yet not lifted up by pride nor corrupted by ambition. None, however, knew so well as himself the stupendousness of his discoveries in comparison with all that had been previously achieved. And none realized so thoroughly as himself the littleness thereof in comparison with the vast region still unexplored. A short time before his death he uttered this memorable sentiment, I do not know what I may appear to the world. But to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before me. How few ever reached the shore even, much less find a smoother pebble or a prettier shell. Newton had now resided about 2 years at Kensington, and the air which he enjoyed there, and the state of absolute rest, proved of great benefit to him. Nevertheless he would occasionally go to town. And on Tuesday, the 28th of February, 1727, he proceeded to London, for the purpose of presiding at a meeting of the Royal Society. At this time his health was considered, by Mr. Conduit, better than it had been for many years. But the unusual fatigue he was obliged to suffer, in attending the meeting, and in paying and receiving visits, speedily produced a violent return of the affection in the bladder. He returned to Kensington on Saturday, the 4th of March. Dr. Mead and Dr. Cheselden attended him. They pronounced his disease to be the stone, and held out no hopes of recovery. On Wednesday, the 15th of March, he seemed a little better. And slight, though groundless, encouragement was felt that he might survive the attack. From the very first of it, his sufferings had been intense. Paroxysm followed paroxysm, in quick succession, large drops of sweat rolled down his face. But not a groan, not a complaint, not the least mark of peevishness or impatience escaped him, and during the short intervals of relief, he even smiled and conversed with his usual composure and cheerfulness. The flesh quivered, but the heart quaked not. The impenetrable gloom was settling down, the destroyer near. The portals of the tomb opening, still, amid this utter wreck and dissolution of the mortal, the immortal remained serene, unconquerable, the radiant light broke through the gathering darkness. And death yielded up its sting, and the grave its victory. On Saturday morning, 18th, he read the newspapers, and carried on a pretty long conversation with Dr. Mead. His senses and faculties were then strong and vigorous. But at 6 o'clock, the same evening, he became insensible, and in this state he continued during the whole of Sunday, and till Monday, the 20th, when he expired, between 1 and 2 o'clock in the morning, in the 85th year of his age. And these were the last days of Isaac Newton. Thus closed the career of one of Earth's greatest and best men. His mission was fulfilled. Unto the giver, in manifold addition, the talents were returned. While it was yet day he had worked. And for the night that quickly cometh he was not unprepared. Full of years, and full of honors, the heaven-sent was recalled, and, in the confidence of a certain hope, peacefully he passed away into the silent depths of eternity. His body was placed in Westminster Abbey, with the state and ceremonial that usually attended the interment of the most distinguished. In 1731, his relatives, the inheritors of his personal estate, erected a monument to his memory in the most conspicuous part of the abbey, which had often been refused by the dean and chapter to the greatest of England's nobility. During the same year a medal was struck at the Tower in his honor, and, in 1755, a full-length statue of him, in white marble, admirably executed, by Roubiliac, at the expense of Dr. Robert Smith, was erected in the antechamber of Trinity College, Cambridge. There is a painting executed in the glass of one of the windows of the same college, made pursuant to the will of Dr. Smith, who left £500 for that purpose. Newton left a personal estate of about £32,000. It was divided among his 4 nephews and 4 nieces of the half-blood, the grandchildren of his mother, by the Reverend Mr. Smith. The family estates of Woolsthorpe and Susterne fell to John Newton, the heir-at-law, whose great-grandfather was Sir Isaac's uncle. Before his death he made an equitable distribution of his 2 other estates, the one in Berkshire to the sons and daughter of a brother of Mrs. Conduit, and the other, at Kensington, to Catherine, the only daughter of Mr. Conduit, and who afterward became Viscountess Lymington. Mr. Conduit succeeded to the offices of the Mint, the duties of which he had discharged during the last 2 years of Sir Isaac's life. Our author's works are found in the collection of Castilian, Berlin, 1744, 4-2. 8 tom, in Bishop Horsley's edition, London, 1779, 4-2. 5 volume, in the Biographia Britannica, and Newton also published Byrne. Varinii Geographia, and 1681, 8vo. There are, however, numerous manuscripts, letters, and other papers, which have never been given to the world. These are preserved, in various collections, namely, in the Library of Trinity College, Cambridge. In the Library of Corpus Christi College, Oxford, in the Library of Lord Macclesfield, and, lastly and chiefly, in the possession of the family of the Earl of Portsmouth, through the Viscountess Lymington. Everything appertaining to Newton has been kept and cherished with peculiar veneration. Different memorials of him are preserved in Trinity College, Cambridge. In the rooms of the Royal Society, of London, and in the Museum of the Royal Society of Edinburgh. The Manor House, at Woolsthorpe, was visited by Dr. Stukeley, in October, 1721, who, in a letter to Dr. Mead, written in 1727, gave the following description of it: "'Tis built of stone, as is the way of the country hereabouts, and a reasonably good one. They led me upstairs and showed me Sir Isaac's study, where I supposed he studied, when in the country, in his younger days, or perhaps when he visited his mother from the university. I observed the shelves were of his own making, being pieces of deal boxes, which probably he sent his books and clothes down in on those occasions. There were, some years ago, 200 or 300 books in it of his father-in-law, Mr. Smith, which Sir Isaac gave to Dr. Newton, of our town. The celebrated apple tree, the fall of one of the apples of which is said to have turned the attention of Newton to the subject of gravity, was destroyed by the wind about 20 years ago. But it has been preserved in the form of a chair. The house itself has been protected with religious care. It was repaired in 1798, and a tablet of white marble put up in the room where our author was born, with the following inscription: Sir Isaac Newton, son of John Newton, Lord of the Manor of Woolsthorpe, was born in this room. On the 25th of December, 1642. Nature and nature's laws were hid in night. God said, Let Newton be, and all was light. The author's preface. Since the ancients, as we are told by Pappus, made great account of the science of mechanics in the investigation of natural things, and the moderns, laying aside substantial forms and occult qualities, have endeavored to subject the phenomena of nature to the laws of mathematics, I have in this treatise cultivated mathematics so far as it regards philosophy. The ancients considered mechanics in a twofold respect, as rational, which proceeds accurately by demonstration, and practical. To practical mechanics all the manual arts belong, from which mechanics took its name. But as artificers do not work with perfect accuracy, it comes to pass that mechanics is so distinguished from geometry, that what is perfectly accurate is called geometrical, what is less so, is called mechanical. But the errors are not in the art, but in the artificers. He that works with less accuracy is an imperfect mechanic, and if any could work with perfect accuracy, he would be the most perfect mechanic of all. For the description if right lines and circles, upon which geometry is founded, belongs to mechanics. Geometry does not teach us to draw these lines, but requires them to be drawn. For it requires that the learner should first be taught to describe these accurately, before he enters upon geometry, then it shows how by these operations problems may be solved. To describe right lines and circles are problems, but not geometrical problems. The solution of these problems is required from mechanics, and by geometry the use of them, when so solved, is shown. And it is the glory of geometry that from those few principles, brought from without, it is able to produce so many things. Therefore geometry is founded in mechanical practice, and is nothing but that part of universal mechanics which accurately proposes and demonstrates the art of measuring. But since the manual arts are chiefly conversant in the moving of bodies, it comes to pass that geometry is commonly referred to their magnitudes, and mechanics to their motion. In this sense rational mechanics will be the science of motions resulting from any forces whatsoever, and of the forces required to produce any motions, accurately proposed and demonstrated. This part of mechanics was cultivated by the ancients in the 5 powers which relate to manual arts, who considered gravity, it not being a manual power, no otherwise than as it moved weights by those powers. Our design not respecting arts, but philosophy, and are subject not manual but natural powers, we consider chiefly those things which relate to gravity, levity, elastic force, the resistance of fluids, and the like forces, whether attractive or impulsive. And therefore we offer this work as the mathematical principles of philosophy. For all the difficulty of philosophy seems to consist in this, from the phenomena of motions to investigate the forces of nature, and then from these forces to demonstrate the other phenomena. And to this end the general propositions in the first and second book are directed. In the third book we give an example of this in the explication of the system of the world. For by the propositions mathematically demonstrated in the former books, we in the third derive from the celestial phenomena the forces of gravity with which bodies tend to the sun and the several planets. Then from these forces, by other propositions which are also mathematical, we deduce the motions of the planets, the comets, the moon, and the sea. I wish we could derive the rest of the phenomena of nature by the same kind of reasoning from mechanical principles. For I am induced by many reasons to suspect that they may all depend upon certain forces by which the particles of bodies, by some causes hitherto unknown, are either mutually impelled towards each other, and cohere in regular figures, or are repelled and recede from each other. Which forces being unknown, philosophers have hitherto attempted the search of nature in vain, but I hope the principles here laid down will afford some light either to this or some truer method of philosophy. In the publication of this work the most acute and universally learned Mr. Edmund Halley not only assisted me with his pains in correcting the press and taking care of the schemes, but it was to his solicitations that its becoming public is owing. For when he had obtained of me my demonstrations of the figure of the celestial orbits, he continually pressed me to communicate the same to the Royal Society, who afterwards, by their kind encouragement and entreaties, engaged me to think of publishing them. But after I had begun to consider the inequalities of the lunar motions, and had entered upon some other things relating to the laws and measures of gravity, and other forces, and the figures that would be described by bodies attracted according to given laws, and the motion of several bodies moving among themselves, the motion of bodies in resisting mediums, the forces, densities, and motions, of mediums, the orbits of the comets, and such like, deferred that publication till I had made a search into those matters, and could put forth the whole together. What relates to the lunar motions, being imperfect, I have put all together in the corollaries of Prop. 66, to avoid being obliged to propose and distinctly demonstrate the several things there contained in a method more prolix than the subject deserved, and interrupt the series of the several propositions. Some things, found out after the rest, I chose to insert in places less suitable, rather than change the number of the propositions and the citations. I heartily beg that what I have here done may be read with candor, and that the defects in a subject so difficult be not so much reprehended as kindly supplied, and investigated by new endeavours of my readers. Isaac Newton. Cambridge. Trinity College, May 8, 1686. In the second edition the second section of the first book was enlarged. In the seventh section of the second book the theory of the resistances of fluids was more accurately investigated, and confirmed by new experiments. In the third book the moon's theory and the precession of the equinoxes were more fully deduced from their principles, and the theory of the comets was confirmed by more examples of the calculation of their orbits, done also with greater accuracy. In this third edition the resistance of mediums is somewhat more largely handled than before, and new experiments of the resistance of heavy bodies falling in air are added. In the third book, the argument to prove that the moon is retained in its orbit by the force of gravity is enlarged on, and there are added new observations of Mr. Pounds of the proportion of the diameters of Jupiter to each other. There are, besides, added Mr. Kirk's observations of the comet in 1680, the orbit of that comet computed in an ellipsis by Dr. Halley, and the orbit of the comet in 1723, computed by Mr. Bradley. Book 1. Definitions. Definition I. The quantity of matter is the measure of the same, arising from its density and bulk conjunctly. Thus air of a double density, in a double space, is quadruple in quantity, in a triple space, sextuple in quantity. The same thing is to be understood of snow, and fine dust or powders, that are condensed by compression or liquefaction, and of all bodies that are by any causes whatever differently condensed. I have no regard in this place to a medium, if any such there is, that freely pervades the interstices between the parts of bodies. It is this quantity that I mean hereafter everywhere under the name of body or mass. And the same is known by the weight of each body, for it is proportional to the weight, as I have found by experiments on pendulums, very accurately made, which shall be shown hereafter. Definition 2. The quantity of motion is the measure of the same, arising from the velocity and quantity of matter conjunctly. The motion of the whole is the sum of the motions of all the parts. And therefore in a body double in quantity, with equal velocity, the motion is double, with twice the velocity, it is quadruple. Definition 3. The vis insita, or innate force of matter, is a power of resisting, by which every body, as much as in it lies, endeavors to persevere in its present state, whether it be of rest, or of moving uniformly forward in a right line. This force is ever proportional to the body whose force it is, and differs nothing from the inactivity of the mass, but in our manner of conceiving it. A body, from the inactivity of matter, is not without difficulty put out of its state of rest or motion. Upon which account, this vis insita, may, by a most significant name, be called vis inertia, or force of inactivity. But a body exerts this force only, when another force, impressed upon it, endeavors to change its condition, and the exercise of this force may be considered both as resistance and impulse. It is resistance, in so far as the body, for maintaining its present state, withstands the force impressed. It is impulse, in so far as the body, by not easily giving way to the impressed force of another, endeavors to change the state of that other. Resistance is usually ascribed to bodies at rest, and impulse to those in motion. But motion and rest, as commonly conceived, are only relatively distinguished, nor are those bodies always truly at rest, which commonly are taken to be so. Definition 4. An impressed force is an action exerted upon a body, in order to change its state either of rest, or of moving uniformly forward in a right line. This force consists in the action only, and remains no longer in the body, when the action is over. For a body maintains every new state it acquires, by its vis inertia only. Impressed forces are of different origins as from percussion, from pressure, from centripetal force. Definition V. A centripetal force is that by which bodies are drawn or impelled, or any way tend, towards a point as to a center. Of this sort is gravity, by which bodies tend to the center of the earth, magnetism, by which iron tends to the lodestone. And that force, whatever it is, by which the planets are perpetually drawn aside from the rectilinear motions, which otherwise they would pursue, and made to revolve in curvilinear orbits. A stone, whirled about in a sling, endeavors to recede from the hand that turns it. And by that endeavor, distends the sling, and that with so much the greater force, as it is revolved with the greater velocity, and as soon as ever it is let go, flies away. That force which opposes itself to this endeavor, and by which the sling perpetually draws back the stone towards the hand, and retains it in its orbit, because it is directed to the hand as the center of the orbit, I call the centripetal force. And the same thing is to be understood of all bodies, revolved in any orbits. They all endeavor to recede from the centers of their orbits. And were it not for the opposition of a contrary force which restrains them to, and detains them in their orbits, which I therefore call centripetal, would fly off in right lines, with an uniform motion. A projectile, if it was not for the force of gravity, would not deviate towards the earth, but would go off from it in a right line, and that with an uniform motion, if the resistance of the air was taken away. It is by its gravity that it is drawn aside perpetually from its rectilinear course, and made to deviate towards the earth, more or less, according to the force of its gravity, and the velocity of its motion. The less its gravity is, for the quantity of its matter, or the greater the velocity with which it is projected, the less will it deviate from a rectilinear course, and the farther it will go. If a leaden ball, projected from the top of a mountain by the force of gunpowder with a given velocity, and in a direction parallel to the horizon, is carried in a curved line to the distance of 2 miles before it falls to the ground. The same, if the resistance of the air were taken away, with a double or decuple velocity, would fly twice or 10 times as far. And by increasing the velocity, we may at pleasure increase the distance to which it might be projected, and diminish the curvature of the line, which it might describe, till at last it should fall at the distance of 10, 30, or 90 degrees. Or even might go quite round the whole earth before it falls. Or lastly, so that it might never fall to the earth, but go forward into the celestial spaces, and proceed in its motion in infinitum. And after the same manner that a projectile, by the force of gravity, may be made to revolve in an orbit, and go round the whole earth, the moon also, either by the force of gravity, if it is endued with gravity, or by any other force that impels it towards the earth, may be perpetually drawn aside towards the earth, out of the rectilinear way, which by its innate force it would pursue, and would be made to revolve in the orbit which it now describes, nor could the moon without some such force, be retained in its orbit. If this force was too small, it would not sufficiently turn the moon out of a rectilinear course; if it was too great, it would turn it too much, and draw down the moon from its orbit towards the earth. It is necessary, that the force be of a just quantity, and it belongs to the mathematicians to find the force, that may serve exactly to retain a body in a given orbit, with a given velocity. And vice versa, to determine the curvilinear way, into which a body projected from a given place, with a given velocity, may be made to deviate from its natural rectilinear way, by means of a given force. The quantity of any centripetal force may be considered as of 3 kinds, absolute, accelerative, and motive. Definition 6. The absolute quantity of a centripetal force is the measure of the same proportional to the efficacy of the cause that propagates it from the center, through the spaces round about. Thus the magnetic force is greater in one lodestone and less in another according to their sizes and strength of intensity. Definition 7. The accelerative quantity of a centripetal force is the measure of the same, proportional to the velocity which it generates in a given time. Thus the force of the same lodestone is greater at a less distance, and less at a greater; also the force of gravity is greater in valleys, less on tops of exceeding high mountains. And yet less, as shall hereafter be shown, at greater distances from the body of the earth, but at equal distances, it is the same everywhere. Because, taking away, or allowing for, the resistance of the air, it equally accelerates all falling bodies, whether heavy or light, great or small. Definition 8. The motive quantity of a centripetal force, is the measure of the same, proportional to the motion which it generates in a given time. Thus the weight is greater in a greater body, less in a less body. And, in the same body, it is greater near to the earth, and less at remoter distances. This sort of quantity is the centripetency, or propension of the whole body towards the center, or, as I may say, its weight. And it is always known by the quantity of an equal and contrary force just sufficient to hinder the descent of the body. These quantities of forces, we may, for brevity's sake, call by the names of motive, accelerative, and absolute forces. And, for distinction's sake, consider them, with respect to the bodies that tend to the center, to the places of those bodies, and to the center of force towards which they tend. That is to say, I refer the motive force to the body as an endeavor and propensity of the whole towards a center, arising from the propensities of the several parts taken together. The accelerative force to the place of the body, as a certain power or energy diffused from the center to all places around to move the bodies that are in them. And the absolute force to the center, as endued with some cause, without which those motive forces would not be propagated through the spaces round about. Whether that cause be some central body, such as is the lodestone, in the center of the magnetic force, or the earth in the center of the gravitating force, or anything else that does not yet appear. For I here design only to give a mathematical notion of those forces, without considering their physical causes and seats. Wherefore the accelerative force will stand in the same relation to the motive, as celerity does to motion. For the quantity of motion arises from the celerity drawn into the quantity of matter, and the motive force arises from the accelerative force drawn into the same quantity of matter. For the sum of the actions of the accelerative force, upon the several articles of the body, is the motive force of the whole. Hence it is, that near the surface of the earth, where the accelerative gravity, or force productive of gravity, in all bodies is the same, the motive gravity or the weight is as the body, but if we should ascend to higher regions, where the accelerative gravity is less, the weight would be equally diminished, and would always be as the product of the body, by the accelerative gravity. So in those regions, where the accelerative gravity is diminished into 1/2, the weight of a body 2 or 3 times less, will be 4 or 6 times less. I likewise call attractions and impulses, in the same sense, accelerative and motive. And use the words attraction, impulse or propensity of any sort towards a center, promiscuously, and indifferently, one for another. Considering those forces not physically, but mathematically, wherefore, the reader is not to imagine, that by those words, I anywhere take upon me to define the kind, or the manner of any action, the causes, or the physical reason thereof. Or that I attribute forces, in a true and physical sense, to certain centers, which are only mathematical points. When at any time I happen to speak of centers as attracting, or as endued with attractive powers. Scholium. Hitherto I have laid down the definitions of such words as are less known, and explained the sense in which I would have them to be understood in the following discourse. I do not define time, space, place and motion, as being well known to all. Only I must observe, that the vulgar conceive those quantities under no other notions but from the relation they bear to sensible objects. And thence arise certain prejudices, for the removing of which, it will be convenient to distinguish them into absolute and relative, true and apparent, mathematical and common. Absolute, true, and mathematical time, of itself, and from its own nature flows equably without regard to anything external, and by another name is called duration, relative, apparent, and common time. Is some sensible and external, whether accurate or unequable, measure of duration by the means of motion, which is commonly used instead of true time. Such as an hour, a day, a month, a year. 2. Absolute space, in its own nature, without regard to anything external, remains always similar and immovable. Relative space is some movable dimension or measure of the absolute spaces, which our senses determine by its position to bodies, and which is vulgarly taken for immovable space, such as the dimension of a subterraneous, an aerial, or celestial space, determined by its position in respect of the earth. Absolute and relative space are the same in figure and magnitude, but they do not remain always numerically the same. For if the earth, for instance, moves, a space of our air, which relatively and in respect of the earth remains always the same, will at one time be one part of the absolute space into which the air passes. At another time it will be another part of the same, and so, absolutely understood, it will be perpetually mutable. 3. Place is a part of space which a body takes up, and is according to the space either absolute or relative. I say, a part of space, not the situation, nor the external surface of the body. For the places of equal solids are always equal, but their superficies, by reason of their dissimilar figures, are often unequal. Positions properly have no quantity, nor are they so much the places themselves, as the properties of places. The motion of the whole is the same thing with the sum of the motions of the parts. That is, the translation of the whole, out of its place, is the same thing with the sum of the translations of the parts out of their places. And therefore the place of the whole is the same thing with the sum of the places of the parts, and for that reason, it is internal, and in the whole body. For, absolute motion is the translation of a body from one absolute place into another. And relative motion, the translation from one relative place into another. Thus in a ship under sail, the relative place of a body is that part of the ship which the body possesses, or that part of its cavity which the body fills, and which therefore moves together with the ship, and relative rest is the continuance of the body in the same part of the ship, or of its cavity. But real, absolute rest, is the continuance of the body in the same part of that immovable space, in which the ship itself, its cavity, and all that it contains, is moved. Wherefore, if the earth is really at rest, the body, which relatively rests in the ship, will really and absolutely move with the same velocity which the ship has on the earth. But if the earth also moves, the true and absolute motion of the body will arise, partly from the true motion of the earth, in immovable space, partly from the relative motion of the ship on the earth. And if the body moves also relatively in the ship, its true motion will arise, partly from the true motion of the earth, in immovable space, and partly from the relative motions as well of the ship on the earth, as of the body in the ship. And from these relative motions will arise the relative motion of the body on the earth. As if that part of the earth, where the ship is, was truly moved toward the east, with a velocity of 10,010 parts. While the ship itself, with a fresh gale, and full sails, is carried towards the west, with a velocity expressed by 10 of those parts, but a sailor walks in the ship towards the east, with 1 part of the said velocity. Then the sailor will be moved truly in immovable space towards the east, with a velocity of 10,001 parts, and relatively on the earth towards the west, with a velocity of 9 of those parts. Absolute time, in astronomy, is distinguished from relative, by the equation or correction of the vulgar time. For the natural days are truly unequal, though they are commonly considered as equal, and used for a measure of time. Astronomers correct this inequality for their more accurate deducing of the celestial motions. It may be, that there is no such thing as an equable motion, whereby time may be accurately measured. All motions may be accelerated and retarded, but the true, or equable, progress of absolute time is liable to no change. The duration or perseverance of the existence of things remains the same, whether the motions are swift or slow, or none at all, and therefore it ought to be distinguished from what are only sensible measures thereof. And out of which we collect it, by means of the astronomical equation. The necessity of which equation, for determining the times of a phenomenon, is evinced as well from the experiments of the pendulum clock, as by eclipses of the satellites of Jupiter. As the order of the parts of time is immutable, so also is the order of the parts of space. Suppose those parts to be moved out of their places, and they will be moved, if the expression may be allowed, out of themselves. For times and spaces are, as it were, the places as well of themselves as of all other things. All things are placed in time as to order of succession, and in space as to order of situation. It is from their essence or nature that they are places. And that the primary places of things should be movable, is absurd. These are therefore the absolute places, and translations out of those places, are the only absolute motions. But because the parts of space cannot be seen, or distinguished from one another by our senses, therefore in their stead we use sensible measures of them. For from the positions and distances of things from any body considered as immovable, we define all places, and then with respect to such places, we estimate all motions, considering bodies as transferred from some of those places into others. And so, instead of absolute places and motions, we use relative ones, and that without any inconvenience in common affairs. But in philosophical disquisitions, we ought to abstract from our senses, and consider things themselves, distinct from what are only sensible measures of them. For it may be that there is no body really at rest, to which the places and motions of others may be referred. But we may distinguish rest and motion, absolute and relative, one from the other by their properties, causes and effects. It is a property of rest, that bodies really at rest do rest in respect to one another. And therefore as it is possible, that in the remote regions of the fixed stars, or perhaps far beyond them, there may be some body absolutely at rest. But impossible to know, from the position of bodies to one another in our regions whether any of these do keep the same position to that remote body, it follows that absolute rest cannot be determined from the position of bodies in our regions. It is a property of motion, that the parts, which retain given positions to their wholes, do partake of the motions of those wholes. For all the parts of revolving bodies endeavor to recede from the axis of motion. And the impetus of bodies moving forward, arises from the joint impetus of all the parts. Therefore, if surrounding bodies are moved, those that are relatively at rest within them, will partake of their motion. Upon which account, the true and absolute motion of a body cannot be determined by the translation of it from those which only seem to rest, for the external bodies ought not only to appear at rest, but to be really at rest. For otherwise, all included bodies, beside their translation from near the surrounding ones, partake likewise of their true motions, and though that translation were not made they would not be really at rest, but only seem to be so. For the surrounding bodies stand in the like relation to the surrounded as the exterior part of a whole does to the interior, or as the shell does to the kernel. But, if the shell moves, the kernel will also move, as being part of the whole, without any removal from near the shell. A property, near akin to the preceding, is this, that if a place is moved, whatever is placed therein moves along with it. And therefore a body, which is moved from a place in motion, partakes also of the motion of its place. Upon which account, all motions, from places in motion, are no other than parts of entire and absolute motions. And every entire motion is composed of the motion of the body out of its first place, and the motion of this place out of its place, and so on, until we come to some immovable place, as in the before-mentioned example of the sailor. Wherefore, entire and absolute motions can be no otherwise determined than by immovable places, and for that reason I did before refer those absolute motions to immovable places, but relative ones to movable places. Now no other places are immovable but those that, from infinity to infinity, do all retain the same given position one to another, and upon this account must ever remain unmoved, and do thereby constitute immovable space. The causes by which true and relative motions are distinguished, one from the other, are the forces impressed upon bodies to generate motion. True motion is neither generated nor altered, but by some force impressed upon the body moved. But relative motion may be generated or altered without any force impressed upon the body. For it is sufficient only to impress some force on other bodies with which the former is compared, that by their giving way, that relation may be changed, in which the relative rest or motion of this other body did consist. Again, true motion suffers always some change from any force impressed upon the moving body, but relative motion does not necessarily undergo any change by such forces. For if the same forces are likewise impressed on those other bodies, with which the comparison is made, that the relative position may be preserved, then that condition will be preserved in which the relative motion consists. And therefore any relative motion may be changed when the true motion remains unaltered, and the relative may be preserved when the true suffers some change. Upon which accounts, true motion does by no means consist in such relations. The effects which distinguish absolute from relative motion are, the forces of receding from the axis of circular motion. For there are no such forces in a circular motion purely relative, but in a true and absolute circular motion, they are greater or less, according to the quantity of the motion. If a vessel, hung by a long cord, is so often turned about that the cord is strongly twisted, then filled with water, and held at rest together with the water. After, by the sudden action of another force, it is whirled about the contrary way, and while the cord is untwisting itself, the vessel continues for some time in this motion. The surface of the water will at first be plain, as before the vessel began to move, but the vessel, by gradually communicating its motion to the water, will make it begin sensibly to revolve, and recede by little and little from the middle, and ascend to the sides of the vessel, forming itself into a concave figure, as I have experienced, and the swifter the motion becomes, the higher will the water rise, till at last, performing its revolutions in the same times with the vessel, it becomes relatively at rest in it. This ascent of the water shows its endeavor to recede from the axis of its motion, and the true and absolute circular motion of the water, which is here directly contrary to the relative, discovers itself, and may be measured by this endeavor. At first, when the relative motion of the water in the vessel was greatest, it produced no endeavor to recede from the axis. The water showed no tendency to the circumference, nor any ascent towards the sides of the vessel, but remained of a plane surface, and therefore its true circular motion had not yet begun. But afterwards, when the relative motion of the water had decreased, the ascent thereof towards the sides of the vessel proved its endeavor to recede from the axis. And this endeavor showed the real circular motion of the water perpetually increasing, till it had acquired its greatest quantity, when the water rested relatively in the vessel. And therefore this endeavor does not depend upon any translation of the water in respect of the ambient bodies, nor can true circular motion be defined by such translation. There is only one real circular motion of any one revolving body, corresponding to only one power of endeavoring to recede from its axis of motion, as its proper and adequate effect. But relative motions, in one and the same body, are innumerable, according to the various relations it bears to external bodies, and like other relations, are altogether destitute of any real effect. Any otherwise than they may perhaps partake of that one only true motion. And therefore in their system who suppose that our heavens, revolving below the sphere of the fixed stars, carry the planets along with them. The several parts of those heavens, and the planets, which are indeed relatively at rest in their heavens, do yet really move. For they change their position one to another, which never happens to bodies truly at rest, and being carried together with their heavens, partake of their motions, and as parts of revolving wholes, endeavor to recede from the axis of their motions. Wherefore relative quantities are not the quantities themselves, whose names they bear, but those sensible measures of them either accurate or inaccurate, which are commonly used instead of the measured quantities themselves. And if the meaning of words is to be determined by their use, then by the names time, space, place and motion, their measures are properly to be understood. And the expression will be unusual, and purely mathematical, if the measured quantities themselves are meant. Upon which account, they do strain the sacred writings, who there interpret those words for the measured quantities. Nor do those less defile the purity of mathematical and philosophical truths, who confound real quantities themselves with their relations and vulgar measures. It is indeed a matter of great difficulty to discover, and effectually to distinguish, the true motions of particular bodies from the apparent. Because the parts of that immovable space, in which those motions are performed, do by no means come under the observation of our senses. Yet the thing is not altogether desperate, for we have some arguments to guide us, partly from the apparent motions, which are the differences of the true motions, partly from the forces, which are the causes and effects of the true motions. For instance, if two globes, kept at a given distance one from the other by means of a cord that connects them, were revolved about their common center of gravity, we might, from the tension of the cord, discover the endeavor of the globes to recede from the axis of their motion, and from thence we might compute the quantity of their circular motions. And then if any equal forces should be impressed at once on the alternate faces of the globes to augment or diminish their circular motions, from the increase or decrease of the tension of the cord, we might infer the increment or decrement of their motions. And thence would be found on what faces those forces ought to be impressed, that the motions of the globes might be most augmented, that is, we might discover their hindermost faces, or those which, in the circular motion, do follow. But the faces which follow being known, and consequently the opposite ones that precede, we should likewise know the determination of their motions. And thus we might find both the quantity and the determination of this circular motion, even in an immense vacuum, where there was nothing external or sensible with which the globes could be compared. But now, if in that space some remote bodies were placed that kept always a given position one to another, as the fixed stars do in our regions, we could not indeed determine from the relative translation of the globes among those bodies, whether the motion did belong to the globes or to the bodies. But if we observed the cord, and found that its tension was that very tension which the motions of the globes required, we might conclude the motion to be in the globes, and the bodies to be at rest. And then, lastly, from the translation of the globes among the bodies, we should find the determination of their motions. But how we are to collect the true motions from their causes, effects, and apparent differences. And, vice versa, how from the motions, either true or apparent, we may come to the knowledge of their causes and effects, shall be explained more at large in the following tract. For to this end it was that I composed it. Axioms, or laws of motion. Law I. Every body perseveres in its state of rest, or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon. Projectiles persevere in their motions, so far as they are not retarded by the resistance of the air, or impelled downwards by the force of gravity. A top, whose parts by their cohesion are perpetually drawn aside from rectilinear motions, does not cease its rotation, otherwise than as it is retarded by the air. The greater bodies of the planets and comets, meeting with less resistance in more free spaces, preserve their motions both progressive and circular for a much longer time. Law 2. The alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. If any force generates a motion, a double force will generate double the motion, a triple force triple the motion, whether that force be impressed altogether and at once, or gradually and successively. And this motion, being always directed the same way with the generating force, if the body moved before, is added to or subducted from the former motion, according as they directly conspire with or are directly contrary to each other. Or obliquely joined, when they are oblique, so as to produce a new motion compounded from the determination of both. Law 3. To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal, and directed to contrary parts. Whatever draws or presses another is as much drawn or pressed by that other. If you press a stone with your finger, the finger is also pressed by the stone. If a horse draws a stone tied to a rope, the horse, if I may so say, will be equally drawn back towards the stone, for the distended rope, by the same endeavor to relax or unbend itself, will draw the horse as much towards the stone as it does the stone towards the horse, and will obstruct the progress of the one as much as it advances that of the other. If a body impinge upon another, and by its force change the motion of the other, that body also, because of the equality of the mutual pressure, will undergo an equal change, in its own motion, towards the contrary part. The changes made by these actions are equal, not in the velocities but in the motions of bodies, that is to say, if the bodies are not hindered by any other impediments. For, because the motions are equally changed, the changes of the velocities made towards contrary parts are reciprocally proportional to the bodies. This law takes place also in attractions, as will be proved in the next scholium. Corollary I. A body by two forces conjoined will describe the diagonal of a parallelogram, in the same time that it would describe the sides, by those forces apart. If a body in a given time, by the force m impressed apart in the place A, should with an uniform motion be carried from A to B, and by the force n impressed apart in the same place, should be carried from A to C. Complete the parallelogram ABCD, and, by both forces acting together, it will in the same time be carried in the diagonal from A to D. For since the force n acts in the direction of the line AC, parallel to BD, this force, by the second law, will not at all alter the velocity generated by the other force m, by which the body is carried towards the line BD. The body therefore will arrive at the line BD in the same time, whether the force n be impressed or not, and therefore at the end of that time it will be found somewhere in the line BD. By the same argument, at the end of the same time it will be found somewhere in the line CD. Therefore it will be found in the point D, where both lines meet. But it will move in a right line from A to D, by law I. Corollary 2. And hence is explained the composition of any one direct force AD, out of any two oblique forces AC and CD. And, on the contrary, the resolution of any one direct force AD into two oblique forces AC and CD, which composition and resolution are abundantly confirmed from mechanics. As if the unequal radii OM and non drawn from the center O of any wheel, should sustain the weights A and P by the chords MA and NP, and the forces of those weights to move the wheel were required. Through the center O draw the right line KOL, meeting the chords perpendicularly in K and L. And from the center O, with OL the greater of the distances OK and OL, describe a circle, meeting the chord MA in D, and drawing OD, make AC parallel and DC perpendicular thereto. Now, it being indifferent whether the points K, L, D, of the chords be fixed to the plane of the wheel or not, the weights will have the same effect whether they are suspended from the points K and L, or from D and L. Let the whole force of the weight A be represented by the line AD, and let it be resolved into the forces AC and CD. Of which the force AC, drawing the radius OD directly from the center, will have no effect to move the wheel, but the other force DC, drawing the radius DO perpendicularly, will have the same effect as if it drew perpendicularly the radius OL equal to OD. That is, it will have the same effect as the weight P, if that weight is to the weight A as the force DC is to the force dA, that is, because of the similar triangles ADC, DOK, as OK to OD or OL. Therefore the weights A and P, which are reciprocally as the radii OK and OL that lie in the same right line, will be equipollent, and so remain in equilibrio, which is the well-known property of the balance, the lever, and the wheel. If either weight is greater than in this ratio, its force to move the wheel will be so much greater. If the weight P, equal to the weight P, is partly suspended by the chord NP, partly sustained by the oblique plane PG. Draw PH, NH, the former perpendicular to the horizon, the latter to the plane PG, and if the force of the weight P tending downwards is represented by the line PH, it may be resolved into the forces Pn, Hn. If there was any plane PQ, perpendicular to the chord Pn, cutting the other plane PG in a line parallel to the horizon, and the weight P was supported only by those planes PQ, PG, it would press those planes perpendicularly with the forces Pn, Hn. To wit, the plane PQ with the force Pn, and the plane PG with the force Hn. And therefore if the plane PQ was taken away, so that the weight might stretch the chord, because the chord, now sustaining the weight, supplies the place of the plane that was removed, it will be strained by the same force Pn which pressed upon the plane before. Therefore, the tension of this oblique chord Pn will be to that of the other perpendicular chord Pn as Pn to Ph. And therefore if the weight P is to the weight A in a ratio compounded of the reciprocal ratio of the least distances of the chords Pn, Am, from the center of the wheel, and of the direct ratio of Ph to Pn, the weights will have the same effect towards moving the wheel, and will therefore sustain each other, as anyone may find by experiment. But the weight P pressing upon those two oblique planes, may be considered as a wedge between the two internal surfaces of a body split by it, and hence the forces of the wedge and the mallet may be determined. For because the force with which the weight presses the plane PQ is to the force with which the same, whether by its own gravity, or by the blow of a mallet, is impelled in the direction of the line PH towards both the planes, as Pn to Ph. And to the force with which it presses the other plane PG, as Pn to NH. And thus the force of the screw may be deduced from a like resolution of forces, it being no other than a wedge impelled with the force of a lever. Therefore the use of this corollary spreads far and wide, and by that diffusive extent the truth thereof is farther confirmed. For on what has been said depends the whole doctrine of mechanics variously demonstrated by different authors. For from hence are easily deduced the forces of machines, which are compounded of wheels, pulleys, levers, cords, and weights, ascending directly or obliquely, and other mechanical powers. As also the force of the tendons to move the bones of animals. Corollary 3. The quantity of motion, which is collected by taking the sum of the motions directed towards the same parts, and the difference of those that are directed to contrary parts, suffers no change from the action of bodies among themselves. For action and its opposite reaction are equal, by law 3, and therefore, by law 2, they produce in the motions equal changes towards opposite parts. Therefore if the motions are directed towards the same parts, whatever is added to the motion of the preceding body will be subducted from the motion of that which follows, so that the sum will be the same as before. If the bodies meet, with contrary motions, there will be an equal deduction from the motions of both, and therefore the difference of the motions directed towards opposite parts will remain the same. Thus if a spherical body A with 2 parts of velocity is triple of a spherical body B which follows in the same right line with 10 parts of velocity, the motion of A will be to that of B as 6 to 10. Suppose, then, their motions to be of 6 parts and of 10 parts, and the sum will be 16 parts. Therefore, upon the meeting of the bodies, if A acquire 3, 4, or 5 parts of motion, B will lose as many. And therefore after reflection A will proceed with 9, 10, or 11 parts, and B with 7, 6, or 5 parts, the sum remaining always of 16 parts as before. If the body A acquire 9, 10, 11, or 12 parts of motion, and therefore after meeting proceed with 15, 16, 17, or 18 parts, the body B, losing so many parts as A has got, will either proceed with 1 part, having lost 9, or stop and remain at rest, as having lost its whole progressive motion of 10 parts. Or it will go back with 1 part, having not only lost its whole motion, but, if I may so say, 1 part more, or it will go back with 2 parts, because a progressive motion of 12 parts is taken off. And so the sums of the conspiring motions 15 plus 1, or 16 plus 0, and the differences of the contrary motion 17 to 1 and 18 to 2, will always be equal to 16 parts, as they were before the meeting in reflection of the bodies. But, the motions being known with which the bodies proceed after reflection, the velocity of either will be also known, by taking the velocity after to the velocity before reflection, as the motion after is to the motion before. As in the last case, where the motion of the body A was of 6 parts before reflection and of 18 parts after, and the velocity was of 2 parts before reflection, the velocity thereof after reflection will be found to be of 6 parts. By saying, as the 6 parts of motion before to 18 parts after, so are 2 parts of velocity before reflection to 6 parts after. But if the bodies are either not spherical, or, moving in different right lines, impinge obliquely one upon the other, and their motions after reflection are required. In those cases we are first to determine the position of the plane that touches the concurring bodies in the point of concourse, then the motion of each body, by choral. 2, is to be resolved into 2, one perpendicular to that plane, and the other parallel to it. This done, because the bodies act upon each other in the direction of a line perpendicular to this plane, the parallel motions are to be retained the same after reflection as before. And to the perpendicular motions we are to assign equal changes towards the contrary parts, in such manner that the sum of the conspiring and the difference of the contrary motions may remain the same as before. From such kind of reflections also sometimes arise the circular motions of bodies about their own centers. But these are cases which I do not consider in what follows. And it would be too tedious to demonstrate every particular that relates to this subject. Corollary 4. The common center of gravity of 2 or more bodies does not alter its state of motion or rest by the actions of the bodies among themselves. And therefore the common center of gravity of all bodies acting upon each other, excluding outward actions and impediments, is either at rest, or moves uniformly in a right line. For if 2 points proceed with an uniform motion in right lines, and their distance be divided in a given ratio, the dividing point will be either at rest, or proceed uniformly in a right line. This is demonstrated hereafter in Lem. Xi and its choral, when the points are moved in the same plane, and by a like way of arguing, it may be demonstrated when the points are not moved in the same plane. Therefore if any number of bodies move uniformly in right lines, the common center of gravity of any 2 of them is either at rest, or proceeds uniformly in a right line. Because the line which connects the centers of those 2 bodies so moving is divided at that common center in a given ratio. In like manner the common center of those 2 and that of a third body will be either at rest or moving uniformly in a right line because at that center the distance between the common center of the 2 bodies, and the center of this last, is divided in a given ratio. In like manner the common center of these 3, and of a fourth body, is either at rest, or moves uniformly in a right line. Because the distance between the common center of the 3 bodies, and the center of the fourth is there also divided in a given ratio, and so on in infinitum. Therefore, in a system of bodies where there is neither any mutual action among themselves, nor any foreign force impressed upon them from without, and which consequently move uniformly in right lines, the common center of gravity of them all is either at rest or moves uniformly forward in a right line. Moreover, in a system of 2 bodies mutually acting upon each other, since the distances between their centers and the common center of gravity of both arc reciprocally as the bodies, the relative motions of those bodies whether of approaching to or of receding from that center, will be equal among themselves. Therefore, since the changes which happen to motions are equal and directed to contrary parts, the common center of those bodies, by their mutual action between themselves, is neither promoted nor retarded, nor suffers any change as to its state of motion or rest. But in a system of several bodies, because the common center of gravity of any two acting mutually upon each other suffers no change in its state by that action, and much less the common center of gravity of the others with which that action does not intervene. But the distance between those two centers is divided by the common center of gravity of all the bodies into parts reciprocally proportional to the total sums of those bodies whose centers they are, and therefore while those two centers retain their state of motion or rest, the common center of all does also retain its state. It is manifest that the common center of all never suffers any change in the state of its motion or rest from the actions of any two bodies between themselves. But in such a system all the actions of the bodies among themselves either happen between two bodies, or are composed of actions interchanged between some two bodies. And therefore they do never produce any alteration in the common center of all as to its state of motion or rest. Wherefore, since that center, when the bodies do not act mutually one upon another, either is at rest or moves uniformly forward in some right line, it will, notwithstanding the mutual actions of the bodies among themselves, always persevere in its state either of rest, or of proceeding uniformly in a right line, unless it is forced out of this state by the action of some power impressed from without upon the whole system. And therefore the same law takes place in a system consisting of many bodies as in one single body, with regard to their persevering in their state of motion or of rest. For the progressive motion, whether of one single body, or of a whole system of bodies, is always to be estimated from the motion of the center of gravity. Corollary v. The motions of bodies included in a given space are the same among themselves, whether that space is at rest, or moves uniformly forwards in a right line without any circular motion. For the differences of the motions tending towards the same parts, and the sums of those that tend towards contrary parts, are, at first, by supposition, in both cases the same. And it is from those sums and differences that the collisions and impulses do arise with which the bodies mutually impinge one upon another. Wherefore, by law too, the effects of those collisions will be equal in both cases. And therefore the mutual motions of the bodies among themselves in the one case will remain equal to the mutual motions of the bodies among themselves in the other. A clear proof of which we have from the experiment of a ship, where all motions happen after the same manner, whether the ship is at rest, or is carried uniformly forwards in a right line. Corollary 6. If bodies, anyhow moved among themselves, are urged in the direction of parallel lines by equal accelerative forces, they will all continue to move among themselves, after the same manner as if they had been urged by no such forces. For these forces acting equally, with respect to the quantities of the bodies to be moved, and in the direction of parallel lines, will, by law too, move all the bodies equally, as to velocity. And therefore will never produce any change in the positions or motions of the bodies among themselves. Scholium. Hitherto I have laid down such principles as have been received by mathematicians, and are confirmed by abundance of experiments. By the first two laws and the first two corollaries, Galileo discovered that the descent of bodies observed the duplicate ratio of the time, and that the motion of projectiles was in the curve of a parabola. Experience agreeing with both, unless so far as these motions are a little retarded by the resistance of the air. When a body is falling, the uniform force of its gravity acting equally, impresses, in equal particles of time, equal forces upon that body, and therefore generates equal velocities. And in the whole time impresses a whole force, and generates a whole velocity proportional to the time. And the spaces described in proportional times are as the velocities and the times conjunctly, that is, in a duplicate ratio of the times. And when a body is thrown upwards, its uniform gravity impresses forces and takes off velocities proportional to the times. And the times of ascending to the greatest heights are as the velocities to be taken off, and those heights are as the velocities and the times conjunctly, or in the duplicate ratio of the velocities. And if a body be projected in any direction, the motion arising from its projection is compounded with the motion arising from its gravity. As if the body A by its motion of projection alone could describe in a given time the right line AB, and with its motion of falling alone could describe in the same time the altitude AC. Complete the parallelogram ABDC, and the body by that compounded motion will at the end of the time be found in the place D, and the curved line AED, which that body describes, will be a parabola, to which the right line AB will be a tangent in A, and whose ordinate BD will be as the square of the line AB. On the same laws and corollaries depend those things which have been demonstrated concerning the times of the vibration of pendulums, and are confirmed by the daily experiments of pendulum clocks. By the same, together with the third law, Sir Christ Wren, Dr. Wallace, and Mr. Huygens, the greatest geometers of our times, did severally determine the rules of the congress and reflection of hard bodies, and much about the same time communicated their discoveries to the Royal Society, exactly agreeing among themselves as to those rules. Dr. Wallace, indeed, was something more early in the publication, then followed Sir Christopher Wren, and, lastly, Mr. Huygens. But Sir Christopher Wren confirmed the truth of the thing before the Royal Society by the experiment of pendulums, which Mr. Marriott soon after thought fit to explain in a treatise entirely upon that subject. But to bring this experiment to an accurate agreement with the theory, we are to have a due regard as well to the resistance of the air as to the elastic force of the concurring bodies. Let the spherical bodies A, B be suspended by the parallel and equal strings AC, BD, from the centers C, D. About these centers, with those intervals, describe the semicircles EAF, GBH, bisected by the radii CA, DB. Bring the body A to any point R of the arc EAF, and, withdrawing the body B, let it go from thence, and after one oscillation suppose it to return to the point V, then RV will be the retardation arising from the resistance of the air. Of this RV let ST be a fourth part, situated in the middle, to wit, so as RS and TV may be equal, and RS may be to ST as 3 to 2, then will ST represent very nearly the retardation during the descent from S to A. Restore the body B to its place, and, supposing the body A to be let fall from the point S, the velocity thereof in the place of reflection A, without sensible error, will be the same as if it had descended in vacuo from the point T. Upon which account this velocity may be represented by the chord of the arc TA. For it is a proposition well known to geometers, that the velocity of a pendulous body in the lowest point is as the chord of the arc which it has described in its descent. After reflection, suppose the body A comes to the place S, and the body B to the place K. Withdraw the body B, and find the place V, from which if the body A, being let go, should after one oscillation return to the place R, ST may be a fourth part of RV, so placed in the middle thereof as to leave RS equal to TV. And let the chord of the arc Ta represent the velocity which the body A had in the place A immediately after reflection. For T will be the true and correct place to which the body A should have ascended, if the resistance of the air had been taken off. In the same way we are to correct the place K to which the body B ascends, by finding the place L to which it should have ascended in vacuo. And thus everything may be subjected to experiment, in the same manner as if we were really placed in vacuo. These things being done, we are to take the product, if I may so say, of the body A, by the chord of the arc TA, which represents its velocity, that we may have its motion in the place A immediately before reflection. And then by the chord of the arc Ta, that we may have its motion in the place A immediately after reflection. And so we are to take the product of the body B by the chord of the arc BL, that we may have the motion of the same immediately after reflection. And in like manner, when two bodies are let go together from different places, we are to find the motion of each, as well before as after reflection, and then we may compare the motions between themselves, and collect the effects of the reflection. Thus trying the thing with pendulums of 10 feet, in unequal as well as equal bodies, and making the bodies to concur after a descent through large spaces, as of 8, 12, or 16 feet, I found always, without an error of 3 inches. That when the bodies concurred together directly, equal changes towards the contrary parts were produced in their motions, and, of consequence, that the action and reaction were always equal. As if the body A impinged upon the body B at rest with 9 parts of motion, and losing 7, proceeded after reflection with 2, the body B was carried backwards with those 7 parts. If the bodies concurred with contrary motions, A with 12 parts of motion, and B with 6, then if A receded with 2, B receded with 8, to wit, with a deduction of 14 parts of motion on each side. For from the motion of a subducting 12 parts, nothing will remain, but subducting 2 parts more, a motion will be generated of 2 parts towards the contrary way. And so, from the motion of the body B of 6 parts, subducting 14 parts, a motion is generated of 8 parts towards the contrary way. But if the bodies were made both to move towards the same way, A, the swifter, with 14 parts of motion, B, the slower, with 5, and after reflection A went on with 5, B likewise went on with 14 parts, 9 parts being transferred from A to B. And so in other cases. By the congress and collision of bodies, the quantity of motion, collected from the sum of the motions directed towards the same way, or from the difference of those that were directed towards contrary ways, was never changed. For the error of an inch or 2 in measures may be easily ascribed to the difficulty of executing everything with accuracy. It was not easy to let go the 2 pendulums so exactly together that the bodies should impinge one upon the other in the lowermost place AB, nor to mark the places S and K, to which the bodies ascended after congress. Nay, and some errors, too, might have happened from the unequal density of the parts of the pendulous bodies themselves, and from the irregularity of the texture proceeding from other causes. But to prevent an objection that may perhaps be all-edged against the rule, for the proof of which this experiment was made, as if this rule did suppose that the bodies were either absolutely hard, or at least perfectly elastic, whereas no such bodies are to be found in nature, I must add, that the experiments we have been describing, by no means depending upon that quality of hardness, do succeed as well in soft as in hard bodies. For if the rule is to be tried in bodies not perfectly hard, we are only to diminish the reflection in such a certain proportion as the quantity of the elastic force requires. By the theory of Wren and Huygens, bodies absolutely hard return one from another with the same velocity with which they meet. But this may be affirmed with more certainty of bodies perfectly elastic. In bodies imperfectly elastic the velocity of the return is to be diminished together with the elastic force. Because that force, except when the parts of bodies are bruised by their congress, or suffer some such extension as happens under the strokes of a hammer, is, as far as I can perceive, certain and determined. And makes the bodies to return one from the other with a relative velocity, which is in a given ratio to that relative velocity with which they met. This I tried in balls of wool, made up tightly, and strongly compressed. For, first, by letting go the pendulous bodies, and measuring their reflection, I determined the quantity of their elastic force. And then, according to this force, estimated the reflections that ought to happen in other cases of congress. And with this computation other experiments made afterwards did accordingly agree. The balls always receding one from the other with a relative velocity, which was to the relative velocity with which they met as about 5 to 9. Balls of steel returned with almost the same velocity, those of cork with a velocity something less. But in balls of glass the proportion was as about 15 to 16. And thus the third law, so far as it regards percussions and reflections, is proved by a theory exactly agreeing with experience. In attractions, I briefly demonstrate the thing after this manner. Suppose an obstacle is interposed to hinder the congress of any 2 bodies A, B, mutually attracting one the other, then if either body, as A, is more attracted towards the other body B, then that other body B is towards the first body A. The obstacle will be more strongly urged by the pressure of the body A than by the pressure of the body B, and therefore will not remain in equilibrio, but the stronger pressure will prevail, and will make the system of the 2 bodies, together with the obstacle, to move directly towards the parts on which B lies. And in free spaces, to go forward in infinitum with a motion perpetually accelerated, which is absurd and contrary to the first law. For, by the first law, the system ought to persevere in its state of rest, or of moving uniformly forward in a right line, and therefore the bodies must equally press the obstacle, and be equally attracted one by the other. I made the experiment on the lodestone and iron. If these, placed apart in proper vessels, are made to float by one another in standing water, neither of them will propel the other. But, by being equally attracted, they will sustain each other's pressure, and rest at last in an equilibrium. So the gravitation betwixt the earth and its parts is mutual. Let the earthify be cut by any plane e.g. into two parts e.g.f. and e.g.I., and their weights one towards the other will be mutually equal. For if by another plane hk, parallel to the former e.g., the greater part e.g.I. is cut into two parts e.g.kh and hki, whereof hki is equal to the part efg, first cut off, it is evident that the middle part e.g.kh will have no propension by its proper weight towards either side, but will hang as it were, and rest in an equilibrium betwixt both. But the one extreme part hki will with its whole weight bear upon and press the middle part towards the other extreme part egf. And therefore the force with which egi, the sum of the parts hki and egkh, tends towards the third part egf, is equal to the weight of the part hki, that is, to the weight of the third part egf. And therefore the weights of the two parts egi and egf, one towards the other, are equal, as I was to prove. And indeed if those weights were not equal, the whole earth floating in the non-resisting ether would give way to the greater weight, and, retiring from it, would be carried off in infinitum. And as those bodies are equipollent in the congress and reflection, whose velocities are reciprocally as their innate forces, so in the use of mechanic instruments those agents are equipollent, and mutually sustain each the contrary pressure of the other, whose velocities, estimated according to the determination of the forces, are reciprocally as the forces. So those weights are of equal force to move the arms of a balance, which during the play of the balance are reciprocally as their velocities upwards and downwards. That is, if the ascent or descent is direct, those weights are of equal force, which are reciprocally as the distances of the points at which they are suspended from the axis of the balance. But if they are turned aside by the interposition of oblique planes, or other obstacles, and made to ascend or descend obliquely, those bodies will be equipollent, which are reciprocally as the heights of their ascent and descent taken according to the perpendicular. And that on account of the determination of gravity downwards. And in like manner in the pulley, or in a combination of pulleys, the force of a hand drawing the rope directly, which is to the weight, whether ascending directly or obliquely. As the velocity of the perpendicular ascent of the weight to the velocity of the hand that draws the rope, will sustain the weight. In clocks and such like instruments, made up from a combination of wheels, the contrary forces that promote and impede the motion of the wheels, if they are reciprocally as the velocities of the parts of the wheel on which they are impressed, will mutually sustain the one the other. The force of the screw to press a body is to the force of the hand that turns the handles by which it is moved, as the circular velocity of the handle in that part where it is impelled by the hand is to the progressive velocity of the screw towards the pressed body. The forces by which the wedge presses or drives the two parts of the wood it cleaves are to the force of the mallet upon the wedge, as the progress of the wedge in the direction of the force impressed upon it by the mallet is to the velocity with which the parts of the wood yield to the wedge, in the direction of lines perpendicular to the sides of the wedge. And the like account is to be given of all machines. The power and use of machines consist only in this, that by diminishing the velocity we may augment the force, and the contrary, from whence in all sorts of proper machines, we have the solution of this problem. To move a given weight with a given power, or with a given force to overcome any other given resistance. For if machines are so contrived that the velocities of the agent and resistant are reciprocally as their forces, the agent will just sustain the resistant, but with a greater disparity of velocity will overcome it. So that if the disparity of velocities is so great as to overcome all that resistance which commonly arises either from the attrition of contiguous bodies as they slide by one another, or from the cohesion of continuous bodies that are to be separated, or from the weights of bodies to be raised, the excess of the force remaining, after all those resistances are overcome, will produce an acceleration of motion proportional thereto. as well in the parts of the machine as in the resisting body. But to treat of mechanics is not my present business. I was only willing to show by those examples the great extent and certainty of the third law of motion. For if we estimate the action of the agent from its force and velocity conjunctly, and likewise the reaction of the impediment conjunctly from the velocities of its several parts, and from the forces of resistance arising from the attrition, cohesion, weight, and acceleration of those parts, the action and reaction in the use of all sorts of machines will be found always equal to one another. And so far as the action is propagated by the intervening instruments, and at last impressed upon the resisting body, the ultimate determination of the action will be always contrary to the determination of the reaction. Of the motion of bodies. Section 1. Of the method of first and last ratios of quantities, by the help whereof we demonstrate the propositions that follow. Lemma I. Quantities, and the ratios of quantities, which in any finite time converge continually to equality, and before the end of that time approach nearer the one to the other than by any given difference, become ultimately equal. If you deny it, suppose them to be ultimately unequal, and let d be their ultimate difference. Therefore they cannot approach nearer to equality than by that given difference d, which is against the supposition. Lemma 2. If in any figure as, terminated by the right lines AA, AE, and the curve ACE, there be inscribed any number of parallelograms of B, CD, and C, comprehended under equal bases AB, BC, CD, and C, and the sides, BB, CC, DD, and C, parallel to one side AA of the figure, and the parallelograms AKBL, BLCM, CMDN, and C, are completed. Then if the breadth of those parallelograms be supposed to be diminished, and their number to be augmented in infinitum, I say, that the ultimate ratios which the inscribed figure AKBLCMDD, the circumscribed figure ALBCNDOE, and curvilinear figure ABCD, will have to one another, are ratios of equality. For the difference of the inscribed and circumscribed figures is the sum of the parallelograms KL, LM, MU, DU, that is, from the equality of all their bases, the rectangle under one of their bases KB in the sum of their altitudes AA, that is, the rectangle ABLA. But this rectangle, because its breadth AB is supposed diminished in infinitum, becomes less than any given space. And therefore, by lem 1, the figures inscribed and circumscribed become ultimately equal one to the other. And much more will the intermediate curvilinear figure be ultimately equal to either. QED. Lemma 3. The same ultimate ratios are also ratios of equality, when the breadths, AB, BC, DC, and C, of the parallelograms are unequal, and are all diminished in infinitum. For suppose AF equal to the greatest breadth, and complete the parallelogram FAAF. This parallelogram will be greater than the difference of the inscribed and circumscribed figures, but, because its breadth AF is diminished in infinitum, it will become less than any given rectangle. QED. Core 1. Hence the ultimate sum of those evanescent parallelograms will in all parts coincide with the curvilinear figure. Core 2. Much more will the rectilinear figure comprehended under the chords of the evanescent arcs of BC, CD, and C, ultimately coincide with the curvilinear figure. Core 3. And also the circumscribed rectilinear figure comprehended under the tangents of the same arcs. Sur. 4 and therefore these ultimate figures, as to their perimeters ACE, are not rectilinear, but curvilinear limits of rectilinear figures. Lemma 4. If in two figures AS, PPRT, you inscribe, as before, two ranks of parallelograms, an equal number in each rank, and, when their breadths are diminished in infinitum, the ultimate ratios of the parallelograms in one figure to those in the other, each to each respectively, are the same. I say, that those two figures AS, PPRT, are to one another in that same ratio. For as the parallelograms in the one are severally to the parallelograms in the other, so, by composition, is the sum of all in the one to the sum of all in the other, and so is the one figure to the other, because, by lem 3, the former figure to the former sum, and the latter figure to the latter sum, are both in the ratio of equality. QED. Sur. Hence if two quantities of any kind are anyhow divided into an equal number of parts, and those parts, when their number is augmented, and their magnitude diminished in infinitum, have a given ratio one to the other, the first to the first, the second to the second, and so on in order, the whole quantities will be one to the other in that same given ratio. For if, in the figures of this lemma, the parallelograms are taken one to the other in the ratio of the parts, the sum of the parts will always be as the sum of the parallelograms. And therefore supposing the number of the parallelograms in parts to be augmented, and their magnitudes diminished in infinitum, those sums will be in the ultimate ratio of the parallelogram in the one figure to the correspondent parallelogram in the other. That is, by the supposition, in the ultimate ratio of any part of the one quantity to the correspondent part of the other. Lemma v. In similar figures, all sorts of homologous sides, whether curvilinear or rectilinear, are proportional. And the areas are in the duplicate ratio of the homologous sides. Lemma 6. If any arc ACB, given in position is subtended by its chord AB, and in any point A, in the middle of the continued curvature, is touched by a right line AD, produced both ways. Then if the points A and B approach one another and meet, I say, the angle bad, contained between, the chord and the tangent, will be diminished in infinitum, and ultimately will vanish. For if that angle does not vanish, the arc ACB will contain with the tangent AD an angle equal to a rectilinear angle, and therefore the curvature at the point A will not be continued, which is against the supposition. Lemma 7. The same things being supposed, I say that the ultimate ratio of the arc, chord, and tangent, any one to any other, is the ratio of equality. For while the point B approaches towards the point A, consider always AB and AD as produced to the remote points B and D, and parallel to the secant BD draw BD, and let the arc ACB be always similar to the arc ACB. Then, supposing the points A and B to coincide, the angle DAB will vanish, by the preceding lemma, and therefore the right lines AB, AD, which are always finite, and the intermediate arc ACB, will coincide, and become equal among themselves. Wherefore, the right lines AB, AD, and the intermediate arc ACB, which are always proportional to the former, will vanish and ultimately acquire the ratio of equality. QED. Core 1. Whence if through B we draw BF parallel to the tangent, always cutting any right line AF passing through A in F, this line BF will be ultimately in the ratio of equality with the evanescent arc ACB. Because, completing the parallelogram AFBD, it is always in a ratio of equality with AD. Core 2. And if through B and more right lines are drawn, as B, BD, AF, AG, cutting the tangent AD and its parallel BF. The ultimate ratio of all the abscissas AD, AE, BF, BG, and of the chord and arc AB, any one to any other, will be the ratio of equality. Core 3. And therefore in all our reasoning about ultimate ratios, we may freely use any one of those lines for any other. Lemma 8. If the right lines AR, BR, with the arc ACB, the chord AB, and the tangent AD, constitute three triangles RAB, RACB, RAD, and the points A and B approach and meet, I say, that the ultimate form of these evanescent triangles is that of similitude. And their ultimate ratio that of equality. For while the point B approaches towards the point A, consider always AB, AD, AR, as produced to the remote points B, D, and R, and RBD as drawn parallel to RD, and let the arc ACB be always similar to the arc ACB. Then supposing the points A and B to coincide, the angle BAD will vanish, and therefore the three triangles RAB, RACB, RAD, which are always finite, will coincide, and on that account become both similar and equal. And therefore the triangles RAB, RACB, RAD, which are always similar and proportional to these, will ultimately become both similar and equal among themselves. QED. Sur. And hence in all reasonings about ultimate ratios, We may indifferently use any one of those triangles for any other. Lemma 9. If a right line AE, and a curved line ABC, both given by position, cut each other in a given angle, A. And to that right line, in another given angle, BD, CE are ordinately applied, meeting the curve in B, C. And the points B and C together approach towards and meet in the point A, I say, that the areas of the triangles ABD, ACE, will ultimately be one to the other in the duplicate ratio of the sides. For while the points B, C, approach towards the point A, suppose always AD to be produced to the remote points D and E, so as AD, AE may be proportional to AD, AE. And the ordinates DB, EC, to be drawn parallel to the ordinates DB and EC, and meeting AB and AC produced in B and C. Let the curve ABC be similar to the curve ABC, and draw the right line AG so as to touch both curves in A, and cut the ordinates DB, EC, DB, EC, in F, G, F, G. Then, supposing the length AE to remain the same, let the points B and C meet in the point A, and the angle CAG vanishing, the curvilinear areas ABD, ACE will coincide with the rectilinear areas AFD, H, and therefore, by lem. V, will be one to the other in the duplicate ratio of the sides AD, AE. But the areas ABD, ACE are always proportional to these areas, and so the sides AD, AE are to these sides. And therefore the areas ABD, ACE are ultimately one to the other in the duplicate ratio of the sides AD, AE. QED. Lemma X. The spaces which a body describes by any finite force urging it, whether that force is determined and immutable, or is continually augmented or continually diminished, are in the very beginning of the motion one to the other in the duplicate ratio of the times. Let the times be represented by the lines AD, AE, and the velocities generated in those times by the ordinates dB, EC. The spaces described with these velocities will be as the areas ABD, ACE, described by those ordinates, that is, at the very beginning of the motion, by lem. 9, in the duplicate ratio of the times AD, AE. QED. Core 1. And hence one may easily infer, that the errors of bodies describing similar parts of similar figures in proportional times, are nearly as the squares of the times in which they are generated. If so be these errors are generated by any equal forces similarly applied to the bodies, and measured by the distances of the bodies from those places of the similar figures, at which, without the action of those forces, the bodies would have arrived in those proportional times. Core 2. But the errors that are generated by proportional forces, similarly applied to the bodies at similar parts of the similar figures, are as the forces and the squares of the times conjunctly. Core 3. The same thing is to be understood of any spaces whatsoever described by bodies urged with different forces, all which, in the very beginning of the motion, are as the forces and the squares of the times conjunctly. Core 4. And therefore the forces are as the spaces described in the very beginning of the motion directly, and the squares of the times inversely. Core 5. And the squares of the times are as the spaces described directly, and the forces inversely. Scholium. If in comparing indeterminate quantities of different sorts one with another, any one is said to be as any other directly or inversely, the meaning is, that the former is augmented or diminished in the same ratio with the latter, or with its reciprocal. And if any one is said to be as any other two or more directly or inversely, the meaning is, that the first is augmented or diminished in the ratio compounded of the ratios in which the others, or the reciprocals of the others, are augmented or diminished. As if A is said to be as B directly, and C directly, and D inversely, the meaning is, that A is augmented or diminished in the same ratio with, that is to say, that A and are one to the other in a given ratio. Lemma 11. The evanescent subtense of the angle of contact, in all curves which at the point of contact have a finite curvature, is ultimately in the duplicate ratio of the subtense of the conterminate arc. Case 1. Let AB be that arc, AD its tangent, BD the subtents of the angle of contact perpendicular on the tangent, AB the subtents of the arc draw BG perpendicular to the subtents AB, and AG to the tangent AD, meeting in G. Then let the points D, B, and G approach to the points D, B, and G, and suppose J to be the ultimate intersection of the lines BG, AG, when the points D, B, have come to A. It is evident that the distance Gj may be less than any assignable. But, from the nature of the circles passing through the points A, B, G, A, B, G, and therefore the ratio of AB superscript 2 to AB superscript 2 is compounded of the ratios of AG to AG, and of BD to BD. But because Gj may be assumed of less length than any assignable, the ratio of AG to AG may be such as to differ from the ratio of equality by less than any assignable difference. And therefore the ratio of AB superscript 2 to AB superscript 2 may be such as to differ from the ratio of BD to BD by less than any assignable difference. Therefore, by lem I, the ultimate ratio of AB superscript 2 to AB superscript 2 is the same with the ultimate ratio of BD to BD. QED. Case 2. Now let BD be inclined to AD in any given angle, and the ultimate ratio of BD to BD will always be the same as before, and therefore the same with the ratio of AB superscript 2 to AB superscript 2. QED. Case 3. And if we suppose the angle D not to be given, but that the right line BD converges to a given point, or is determined by any other condition whatever. Nevertheless the angles D, being determined by the same law, will always draw nearer to equality, and approach nearer to each other than by any assigned difference, and therefore, by lem I, will at last be equal. And therefore the lines BD are in the same ratio to each other as before. QED. Core 1. Therefore since the tangents AD, the arcs AB, AB, and their sines, BC, become ultimately equal to the chords AB, AB, their squares will ultimately become as the subtenses BD. Core 2. Their squares are also ultimately as the versed sines of the arcs, bisecting the chords, and converging to a given point. For those versed sines are as the subtenses BD. Core 3. And therefore the versed sine is in the duplicate ratio of the time in which a body will describe the arc with a given velocity. Core 4. The rectilinear triangles ADB are ultimately in the triplicate ratio of the sides AD, and in a sesquiplicate ratio of the sides DB, as being in the ratio compounded of the sides AD to DB, and of AD to DB. So also the triangles ABC are ultimately in the triplicate ratio of the sides BC. What I call the sesquiplicate ratio is the subduplicate of the triplicate, as being compounded of the simple and subduplicate ratio. Core 5. And because DB are ultimately parallel and in the duplicate ratio of the lines AD, the ultimate curvilinear areas ADB will be, by the nature of the parabola, 2/3 of the rectilinear triangles ADB, and the segments AB. AB will be 1/3 of the same triangles. And thence those areas and those segments will be in the triplicate ratio as well of the tangents AD, as of the chords and arcs AB. Scholium. But we have all along supposed the angle of contact to be neither infinitely greater nor infinitely less than the angles of contact made by circles and their tangents. That is, that the curvature at the point A is neither infinitely small nor infinitely great, or that the interval AJ is of a finite magnitude. For DB may be taken as AD superscript 3, in which case no circle can be drawn through the point A, between the tangent AD and the curve AB, and therefore the angle of contact will be infinitely less than those of circles. And by a like reasoning, if DB be made successfully as AD4, AD5, AD6, AD7, and we shall have a series of angles of contact, proceeding in infinitum, wherein every succeeding term is infinitely less than the preceding. And if DB be made successively as AD superscript 2, AD3/2, AD4/3, AD5/4, AD6/5, AD7/6, and we shall have another infinite series of angles of contact, the first of which is of the same sort with those of circles, the second infinitely greater, and every succeeding one infinitely greater than the preceding. But between any two of these angles another series of intermediate angles of contact may be interposed, proceeding both ways in infinitum, wherein every succeeding angle shall be infinitely greater or infinitely less than the preceding. As if between the terms AD superscript 2 and AD superscript 2 there were interposed the series AD 13/6, AD 11/5, AD 9/4, AD 7/3, AD 5/2, AD 8/3, AD 11/4, AD 14/5, AD 17/6 and again, between any two angles of this series, a new series of intermediate angles may be interposed, differing from one another by infinite intervals. Nor is nature confined to any bounds. Those things which have been demonstrated of curved lines, and the superficies which they comprehend, may be easily applied to the curved superficies and contents of solids. These lemmas are premised to avoid the tediousness of deducing perplexed demonstrations ad absurdum, according to the method of the ancient geometers. For demonstrations are more contracted by the method of indivisibles, but because the hypothesis of indivisibles seems somewhat harsh, and therefore that method is reckoned less geometrical, I chose rather to reduce the demonstrations of the following propositions to the first and last sums and ratios of nascent and evanescent quantities, that is, to the limits of those sums and ratios. And so to premise, as short as I could, the demonstrations of those limits. For hereby the same thing is performed as by the method of indivisibles, and now those principles being demonstrated, we may use them with more safety. Therefore if hereafter I should happen to consider quantities as made up of particles, or should use little curved lines for right ones, I would not be understood to mean indivisibles, but evanescent divisible quantities, not the sums and ratios of determinate parts, but always the limits of sums and ratios. And that the force of such demonstrations always depends on the method laid down in the foregoing lemmas. Perhaps it may be objected, that there is no ultimate proportion of evanescent quantities. Because the proportion, before the quantities have vanished, is not the ultimate, and when they are vanished, is none. But by the same argument, it may be all-edged, that a body arriving at a certain place, and there stopping, has no ultimate velocity, because the velocity, before the body comes to the place, is not its ultimate velocity. When it has arrived, is none. But the answer is easy, for by the ultimate velocity is meant that with which the body is moved, neither before it arrives at its last place and the motion ceases, nor after, but at the very instant it arrives. That is, that velocity with which the body arrives at its last place, and with which the motion ceases. And in like manner, by the ultimate ratio of evanescent quantities is to be understood the ratio of the quantities not before they vanish, nor afterwards, but with which they vanish. In like manner the first ratio of nascent quantities is that with which they begin to be. And the first or last sum is that with which they begin and cease to be, or to be augmented or diminished. There is a limit which the velocity at the end of the motion may attain, but not exceed. This is the ultimate velocity. And there is the like limit in all quantities and proportions that begin and cease to be. And since such limits are certain and definite, to determine the same is a problem strictly geometrical. But whatever is geometrical we may be allowed to use in determining and demonstrating any other thing that is likewise geometrical. It may also be objected, that if the ultimate ratios of evanescent quantities are given, their ultimate magnitudes will be also given, and so all quantities will consist of indivisibles. Which is contrary to what Euclid has demonstrated concerning incommensurables, in the 10th book of his Elements. But this objection is founded on a false supposition. For those ultimate ratios with which quantities vanish are not truly the ratios of ultimate quantities, but limits towards which the ratios of quantities decreasing without limit do always converge. And to which they approach nearer than by any given difference, but never go beyond, nor in effect attain to, till the quantities are diminished in infinitum. This thing will appear more evident in quantities infinitely great. If two quantities, whose difference is given, be augmented in infinitum, the ultimate ratio of these quantities will be given, to wit, the ratio of equality. But it does not from thence follow, that the ultimate or greatest quantities themselves, whose ratio that is, will be given. Therefore if in what follows, for the sake of being more easily understood, I should happen to mention quantities as least, or evanescent, or ultimate, you are not to suppose that quantities of any determinate magnitude are meant, but such as are conceived to be always diminished without end. Section 2. Of the Invention of Centripetal Forces. Proposition I, Theorem I. The areas, which revolving bodies describe by radii drawn to an immovable center of force do lie in the same immovable planes, and are proportional to the times in which they are described. For suppose the time to be divided into equal parts, and in the first part of that time let the body by its innate force describe the right line AB in the second part of that time, the same would, by law I, if not hindered, proceed directly to C, along the line sequel to AB, so that by the radii AS, BS, CS, drawn to the center, the equal areas ASB, BSC, would be described. But when the body is arrived at B, suppose that a centripetal force acts at once with a great impulse, and, turning aside the body from the right line BC, compels it afterwards to continue its motion along the right line BC. Draw CC parallel to BS meeting BC in C, and at the end of the second part of the time, the body, by core I, of the laws, will be found in C, in the same plane with the triangle ASB. Join SC, and, because SB and CC are parallel, the triangle SBC will be equal to the triangle SBC, and therefore also to the triangle SAB. By the like argument, if the centripetal force acts successively in C, D, E and K, and makes the body, in each single particle of time, to describe the right line CD, DE, EF, and K, they will all lie in the same plane, and the triangle SCD will be equal to the triangle SBC, and SDE to SCD, and SEF to SDE. And therefore, in equal times, equal areas are described in one immovable plane, and, by composition, any sums SADS, SAFS, of those areas, are one to the other as the times in which they are described. Now let the number of those triangles be augmented, and their breadth diminished in infinitum, and, by core 4, lem. 3. Their ultimate perimeter ADF will be a curved line, and therefore the centripetal force, by which the body is perpetually drawn back from the tangent of this curve, will act continually. And any described areas SADS, SAFS, which are always proportional to the times of description, will, in this case also, be proportional to those times. QED. Core 1. The velocity of a body attracted towards an immovable center, in spaces void of resistance, is reciprocally as the perpendicular let fall from that center on the right line that touches the orbit. For the velocities in those places A, B, C, D, E, are as the bases AB, BC, CD, DE, EF, of equal triangles, and these bases are reciprocally as the perpendiculars let fall upon them. Core 2. If the chords AB, BC of two arcs, successively described in equal times by the same body, in spaces void of resistance, are completed into a parallelogram ABCV, and the diagonal BV of this parallelogram, in the position which it ultimately acquires when those arcs are diminished in infinitum, is produced both ways, it will pass through the center of force. Core 3. If the chords AB, BC, and DE, EF, of arcs described in equal times, in spaces void of resistance, are completed into the parallelograms ABCV, DFC. The forces in B and E are one to the other in the ultimate ratio of the diagonals BV, easy, when those arcs are diminished in infinitum. For the motions BC and EF of the body, by Cr. one of the laws, are compounded of the motions BC, BV, and EF, easy, but BV and easy, which are equal to CC and FF, in the demonstration of this proposition, were generated by the impulses of the centripetal force in B and E, and are therefore proportional to those impulses. Core 4. The forces by which bodies, in spaces void of resistance, are drawn back from rectilinear motions, and turned into curvilinear orbits, are one to another as the versed sines of arcs described in equal times. Which versed sines tend to the center of force, and bisect the chords when those arcs are diminished to infinity. For such versed sines are the halves of the diagonals mentioned in Core 3. Core 5. And therefore those forces are to the force of gravity as the said versed sines to the versed sines perpendicular to the horizon of those parabolic arcs which projectiles describe in the same time. Core 6. And the same things do all hold good, by Core 5 of the laws, when the planes in which the bodies are moved, together with the centers of force which are placed in those planes, are not at rest, but move uniformly forward in right lines. Proposition 2. Theorem 2. Every body that moves in any curved line described in a plane, and by a radius, drawn to a point either immovable, or moving forward with an uniform rectilinear motion, describes about that point areas proportional to the times, is urged by a centripetal force directed to that point. Case 1. For every body that moves in a curved line, is, by law 1, turned aside from its rectilinear course by the action of some force that impels it. And that force by which the body is turned off from its rectilinear course, and is made to describe, in equal times, the equal least triangles SAB, SBC, SCD, and about the immovable point S, by Prop. XL, Book 1, Elem. And Law 2, acts in the place B, according to the direction of a line parallel to CC, that is, in the direction of the line BS, and in the place C, according to the direction of a line parallel to DD, that is, in the direction of the line CS, and therefore acts always in the direction of lines tending to the immovable point S. QED. Case 2, and, by Cr. 5 of the laws, it is indifferent whether the superficies in which a body describes a curvilinear figure be quiescent, or moves together with the body, the figure described, and its point S, uniformly forward in right lines. Core 1. In non-resisting spaces or mediums, if the areas are not proportional to the times, the forces are not directed to the point in which the radii meet, but deviate therefrom in consequentia, or towards the parts to which the motion is directed, if the description of the areas is accelerated, but in antecedentia, if retarded. Core 2. And even in resisting mediums, if the description of the areas is accelerated, the directions of the forces deviate from the point in which the radii meet, towards the parts to which the motion tends. Scholium. A body may be urged by a centripetal force compounded of several forces, in which case the meaning of the proposition is, that the force which results out of all tends to the point S. But if any force acts perpetually in the direction of lines perpendicular to the described surface, this force will make the body to deviate from the plane of its motion, but will neither augment nor diminish the quantity of the described surface, and is therefore to be neglected in the composition of forces. Proposition 3. Theorem 3. Every body, that by a radius drawn to the center of another body, howsoever moved, describes areas about that center proportional to the times, is urged by a force compounded out of the centripetal force tending to that other body, and of all the accelerative force by which that other body is impelled. Let L represent the one, and T the other body, and, by Cr. 6 of the laws, if both bodies are urged in the direction of parallel lines, by a new force equal and contrary to that by which the second body T is urged, the first body L will go on to describe about the other body T the same areas as before, but the force by which that other body T was urged will be now destroyed by an equal and contrary force. And therefore, by law I, that other body T, now left to itself, will either rest, or move uniformly forward in a right line, and the first body L impelled by the difference of the forces, that is, by the force remaining, will go on to describe about the other body T areas proportional to the times. And therefore, by the 2, the difference of the forces is directed to the other body T as its center. QED. Core 1. Hence if the one body L, by a radius drawn to the other body t, describes areas proportional to the times. And from the whole force, by which the first body L is urged, whether that force is simple, or, according to core 2 of the laws, compounded out of several forces, we subduct, by the same core. That whole accelerative force by which the other body is urged, the whole remaining force by which the first body is urged will tend to the other body t, as its center. Core 2. And, if these areas are proportional to the times nearly, the remaining force will tend to the other body t nearly. Core 3. And vice versa, if the remaining force tends nearly to the other body t, those areas will be nearly proportional to the times. Core 4. If the body L, by a radius drawn to the other body t, describes areas, which, compared with the times, are very unequal, and that other body t be either at rest, or moves uniformly forward in a right line, the action of the centripetal force tending to that other body t is either none at all, or it is mixed and compounded with very powerful actions of other forces, and the whole force compounded of them all, if they are many, is directed to another, immovable or movable, center. The same thing obtains when the other body is moved by any motion whatsoever, provided that centripetal force is taken, which remains after subducting that whole force acting upon that other body t. Scholium. Because the equable description of areas indicates that a center is respected by that force with which the body is most affected, and by which it is drawn back from its rectilinear motion, and retained in its orbit. Why may we not be allowed, in the following discourse, to use the equable description of areas as an indication of a center, about which all circular motion is performed in free spaces? Proposition 4. Theorem 4. The centripetal forces of bodies, which by equable motions describe different circles, tend to the centers of the same circles, and are one to the other as the squares of the arcs described in equal times applied to the radii of the circles. These forces tend to the centers of the circles, by Prop. 2, and Core 2, Prop. I, and are one to another as the versed signs of the least arcs described in equal times, by Core 4, Prop. I. That is, as the squares of the same arcs applied to the diameters of the circles, by Lem. 7, and therefore since those arcs are as arcs described in any equal times, and the diameters are as the radii, the forces will be as the squares of any arcs described in the same time applied to the radii of the circles. QED. Core 1. Therefore, since those arcs are as the velocities of the bodies, the centripetal forces are in a ratio compounded of the duplicate ratio of the velocities directly, and of the simple ratio of the radii inversely. Core 2. And since the periodic times are in a ratio compounded of the ratio of the radii directly, and the ratio of the velocities inversely, the centripetal forces are in a ratio compounded of the ratio of the radii directly, and the duplicate ratio of the periodic times inversely. Core 3. Whence if the periodic times are equal, and the velocities therefore as the radii, the centripetal forces will be also as the radii, and the contrary. Core 4. If the periodic times and the velocities are both in the subduplicate ratio of the radii, the centripetal forces will be equal among themselves, and the contrary. Core 5. If the periodic times are as the radii, and therefore the velocities equal, the centripetal forces will be reciprocally as the radii, and the contrary. Core 6. If the periodic times are in the sesquiplicate ratio of the radii, and therefore the velocities reciprocally in the subduplicate ratio of the radii, the centripetal forces will be in the duplicate ratio of the radii inversely, and the contrary. Core 7. And universally, if the periodic time is as any power Rn of the radius r, and therefore the velocity reciprocally as the power Rn, 1 of the radius, the centripetal force will be reciprocally as the power R2n, 1 of the radius. And the contrary. Core 8. The same things all hold concerning the times, the velocities, and forces by which bodies describe the similar parts of any similar figures that have their centers in a similar position with those figures. As appears by applying the demonstration of the preceding cases to those. And the application is easy, by only substituting the equable description of areas in the place of equable motion, and using the distances of the bodies from the centers instead of the radii. Core 9. From the same demonstration it likewise follows, that the arc which a body, uniformly revolving in a circle by means of a given centripetal force, describes in any time, is a mean proportional between the diameter of the circle and the space which the same body falling by the same given force would descend through in the same given time. Scholium. The case of the sixth corollary obtains in the celestial bodies, as Sir Christopher Wren, Dr. Hooke, and Dr. Halley have severally observed. And therefore in what follows, I intend to treat more at large of those things which relate to centripetal force decreasing in a duplicate ratio of the distances from the centers. Moreover, by means of the preceding proposition and its corollaries, we may discover the proportion of a centripetal force to any other known force, such as that of gravity. For if a body by means of its gravity revolves in a circle concentric to the earth, this gravity is the centripetal force of that body. But from the descent of heavy bodies, the time of one entire revolution, as well as the arc described in any given time, is given, by core 9 of this prop. And by such propositions, Mr. Huygens, in his excellent book De Horologio Oscillatorio, has compared the force of gravity with the centrifugal forces of revolving bodies. The preceding proposition may be likewise demonstrated after this manner. In any circle suppose a polygon to be inscribed of any number of sides. And if a body, moved with a given velocity along the sides of the polygon, is reflected from the circle at the several angular points, the force, with which at every reflection it strikes the circle, will be as its velocity, and therefore the sum of the forces, in a given time, will be as that velocity in the number of reflections conjunctly, that is, if the species of the polygon be given, as the length described in that given time, and increased or diminished in the ratio of the same length to the radius of the circle. That is, as the square of that length applied to the radius, and therefore the polygon, by having its sides diminished in infinitum, coincides with the circle, as the square of the arc described in a given time applied to the radius. This is the centrifugal force, with which the body impels the circle, and to which the contrary force, wherewith the circle continually repels the body towards the center, is equal. Proposition V. Problem I. There being given, in any places, the velocity with which a body describes a given figure, by means of forces directed to some common center, to find that center. Let the three right lines PT, TQV, VR touch the figure described in as many points, P, Q, R, and meet in T and V. On the tangents erect the perpendiculars PA, QB, RC, reciprocally proportional to the velocities of the body in the points P, Q, R, from which the perpendiculars were raised. That is, so that PA may be to QB as the velocity in Q, to the velocity in P, and QB to RC as the velocity in R to the velocity in Q. Through the ends A, B, C, of the perpendiculars draw AD, DBE, EC, at right angles, meeting in D and E, and the right lines TD, VE produced, will meet in S, the center required. For the perpendiculars let fall from the center S on the tangents PT, QD, are reciprocally as the velocities of the bodies in the points P and Q, by core 1, prop I, and therefore, by construction, as the perpendiculars AP, BQ directly. That is, as the perpendiculars let fall from the point D on the tangents. Whence it is easy to infer that the points S, D, T, are in one right line. And by the like argument the points S, E, V are also in one right line. And therefore the center S is in the point where the right lines TD, VE meet. QED. Proposition 6. Theorem V. In a space void of resistance, if a body revolves in any orbit about an immovable center, and in the least time describes any arc just then nascent, and the versed sign of that arc is supposed to be drawn bisecting the chord, and produced passing through the center of force, the centripetal force in the middle of the arc will be as the versed sign directly and the square of the time inversely. For the versed sign in a given time is as the force, by core 4, prop 1. And augmenting the time in any ratio, because the arc will be augmented in the same ratio, the versed sign will be augmented in the duplicate of that ratio, by CR. 2 and 3, lem. 11, and therefore is as the force and the square of the time. Subduct on both sides the duplicate ratio of the time, and the force will be as the versed sign directly, and the square of the time inversely. QED. And the same thing may also be easily demonstrated by Coral, for, lem. X. Core 1. If a body P revolving about the center S describes a curved line APQ, which a right line ZPR touches in any point P. And from any other point Q of the curve, QR is drawn parallel to the distance SP, meeting the tangent in R, and QD is drawn perpendicular to the distance SP. The centripetal force will be reciprocally as the solid, if the solid be taken of that magnitude which it ultimately acquires when the points P and Q coincide. For QR is equal to the versed sign of double the arc QP, whose middle is P, and double the triangle SQP, or is proportional to the time in which that double arc is described, and therefore may be used for the exponent of the time. Core 2. By a like reasoning, the centripetal force is reciprocally as the solid, if SY is a perpendicular from the center of force on PR the tangent of the orbit. For the rectangles and are equal. Core 3. If the orbit is either a circle, or touches or cuts a circle concentrically, that is, contains with a circle the least angle of contact or section, having the same curvature and the same radius of curvature at the point P. And if PV be a chord of this circle, drawn from the body through the center of force, the centripetal force will be reciprocally as the solid. For PV is. Core 4. The same things being supposed, the centripetal force is as the square of the velocity directly, and that chord inversely. For the velocity is reciprocally as the perpendicular SY, by Core 1. Prop. I. Core 5. Hence if any curvilinear figure APQ is given, and therein a point S is also given, to which a centripetal force is perpetually directed, that law of centripetal force may be found. By which the body P will be continually drawn back from a rectilinear course, and being detained in the perimeter of that figure, will describe the same by a perpetual revolution. That is, we are to find, by computation, either the solid or the solid, reciprocally proportional to this force. Examples of this we shall give in the following problems. Proposition 7. Problem 2. If a body revolves in the circumference of a circle, it is proposed to find the law of centripetal force directed to any given point. Let VQPA be the circumference of the circle, S the given point to which as to a center the force tends. P the body moving in the circumference, Q the next place into which it is to move, and PRZ the tangent of the circle at the preceding place. Through the point S draw the chord PV, and the diameter VA of the circle, join AP, and draw QD perpendicular to SP, which produced, may meet the tangent PR in Z. And lastly, through the point Q, draw LR parallel to SP, meeting the circle in L, and the tangent PZ in R. And, because of the similar triangles ZQR, ZTP, VPA, we shall have RP superscript 2, that is, QRL to QD superscript 2 as AV superscript 2 to PV superscript 2. And therefore is equal to QD superscript 2. Multiply those equals by, and the points P and Q coinciding, for RL right PV, then we shall have. And therefore, by COR 1 and 5, Prop. 6, the centripetal force is reciprocally as. That is, because AV superscript 2 is given, reciprocally as the square of the distance or altitude SP, and the cube of the chord PV conjunctly. QEI. The same otherwise. On the tangent PR produced let fall the perpendicular SY. And, because of the similar triangles SYP, VPA, we shall have AV to PV as SP to SY, and therefore, and therefore, by Coral, 3 and 5, Prop. 6, the centripetal force is reciprocally as, that is, because AV is given, reciprocally as Q. EI. Core 1. Hence if the given point S, to which the centripetal force always tends, is placed in the circumference of the circle, as at V, the centripetal force will be reciprocally as the quadrato cube, or fifth power, of the altitude SP. Sur. 2. The force by which the body P in the circle APTV revolves about the center of force S is to the force by which the same body P may revolve in the same circle, and in the same periodic time, about any other center of force R. As to the cube of the right line SG, which, from the first center of force S is drawn parallel to the distance PR of the body from the second center of force R, meeting the tangent PG of the orbit in G. For by the construction of this proposition, the former force is to the latter as to, that is, as to, or, because of the similar triangles PSG, TPV, to SG superscript 3. Core 3. The force by which the body P in any orbit revolves about the center of force S, is to the force by which the same body may revolve in the same orbit, and the same periodic time, about any other center of force R, as the solid. Contained under the distance of the body from the first center of force S, and the square of its distance from the second center of force R, to the cube of the right line SG, drawn from the first center of the force S. Parallel to the distance Rp of the body from the second center of force R, meeting the tangent PG of the orbit in G. For the force in this orbit at any point P is the same as in a circle of the same curvature. Proposition 8. Problem 3. If a body moves in the semicircumference PQA, it is proposed to find the law of the centripetal force tending to a point S, so remote, that all the lines PS, RS drawn thereto, may be taken for parallels. From C, the center of the semicircle, let the semidiameter CA be drawn, cutting the parallels at right angles in M and N, and join CP. Because of the similar triangles CPM, PZT, and RZQ, we shall have CP superscript 2 to PM superscript 2 as PR superscript 2 to QD superscript 2. And, from the nature of the circle, PR superscript 2 is equal to the rectangle, or, the points P, Q, coinciding, to the rectangle. Therefore CP superscript 2 is to PM superscript 2 as to QD superscript 2, and therefore, by choral, 1 and 5, prop. 6. The centripetal force is reciprocally as, that is, neglecting the given ratio, reciprocally as PM superscript 3. QEI. And the same thing is likewise easily inferred from the preceding proposition. Scholium. And by a like reasoning, a body will be moved in an ellipsis, or even in an hyperbola, or parabola, by a centripetal force which is reciprocally AE the cube of the ordinate directed to an infinitely remote center of force. Proposition 9. Problem 4. If a body revolves in a spiral PQS, cutting all the radii SP, SQ, and, in a given angle, it is proposed to find the law of the centripetal force tending to the center of that spiral. Suppose the indefinitely small angle PSQ to be given, because, then, all the angles are given, the figure SPRQT will be given in specie. Therefore the ratio is also given, and is as QT, that is, because the figure is given in specie, as SP. But if the angle PSQ is any way changed, the right line QR, subtending the angle of contact QPR, by lemma 11, will be changed in the duplicate ratio of PR or QT. Therefore the ratio remains the same as before, that is, as SP. And is as SP superscript 3, and therefore, by choral, 1 and 5, prop. 6, the centripetal force is reciprocally as the cube of the distance SP. QEI. The same otherwise. The perpendicular SY let fall upon the tangent, and the chord PV of the circle concentrically cutting the spiral, are in given ratios to the height SP, and therefore SP superscript 3 is as SY superscript 2 PV, that is, by choral, 3 and 5, prop. 6 reciprocally as the centripetal force. Lemma 12. All parallelograms circumscribed about any conjugate diameters of a given ellipsis or hyperbola are equal among themselves. This is demonstrated by the writers on the conic sections. Proposition X, Problem V. If a body revolves in an ellipsis, it is proposed to find the law of the centripetal force tending to the center of the ellipsis. Suppose CA, CB to be semi-axes of the ellipsis, GP, DK, conjugate diameters. PF, QD perpendiculars to those diameters, QV an ordinate to the diameter GP, and if the parallelogram QVPR be completed, then, by the properties of the conic sections, the rectangle PVG will be to QV superscript 2 as PC superscript 2 to CD superscript 2. And, because of the similar triangles QVT, PCF, QV superscript 2 to QD superscript 2 as PC superscript 2 to PF superscript 2, and, by composition, the ratio of PVG to QD superscript 2 is compounded of the ratio of PC superscript 2 to CD superscript 2, and of the ratio of PC superscript 2 to PF superscript 2, that is, VG2 as PC superscript 2 to. Put QR for PV, and, by Lem. 12, BCCA for CDPF, also, the points P and Q coinciding, 2PC for VG, and multiplying the extremes and means together, we shall have equal to. Therefore, by Core 5, Prop. 6, the centripetal force is reciprocally as. That is, because is given, reciprocally as, that is, directly as the distance PC. QEI. The same otherwise. In the right line PG on the other side of the point T, take the point U so that 2 may be equal to TV. Then take UV, such as shall be to VG as DC superscript 2 to PC superscript 2. And because QV superscript 2 is to PVG as DC superscript 2 to PC superscript 2, by the conic sections, we shall have. Add the rectangle UPV to both sides, and the square of the chord of the arc PQ will be equal to the rectangle VPV. And therefore a circle which touches the conic section in P, and passes through the point Q, will pass also through the point V. Now let the points P and Q meet, and the ratio of UV to VG, which is the same with the ratio of DC superscript 2 to PC superscript 2, will become the ratio of PV to PG, or PV to 2PC, and therefore PV will be equal to. And therefore the force by which the body P revolves in the ellipsis will be reciprocally as, by Core 3, Prop 6, that is, because 2 DC superscript 2 PF superscript 2 is given, directly as PC. QEI. Core 1. And therefore the force is as the distance of the body from the center of the ellipsis. And, vice versa, if the force is as the distance, the body will move in an ellipsis whose center coincides with the center of force, or perhaps in a circle into which the ellipsis may degenerate. Core 2. And the periodic times of the revolutions made in all ellipses whatsoever about the same center will be equal. For those times in similar ellipses will be equal, by Choral 3 and 8, Prop. 4. But in ellipses that have their greater axis common, they are one to another as the whole areas of the ellipses directly, and the parts of the areas described in the same time inversely. That is, as the lesser axes directly, and the velocities of the bodies in their principal vertices inversely, that is, as those lesser axes directly, and the ordinates to the same point of the common axes inversely. And therefore, because of the equality of the direct and inverse ratios, in the ratio of equality. Scholium. If the ellipsis, by having its center removed to an infinite distance, degenerates into a parabola, the body will move in this parabola. And the force, now tending to a center infinitely remote, will become equable. Which is Galileo's theorem. And if the parabolic section of the cone, by changing the inclination of the cutting plane to the cone, degenerates into an hyperbola, the body will move in the perimeter of this hyperbola, having its centripetal force changed into a centrifugal force. And in like manner as in the circle, or in the ellipsis, if the forces are directed to the center of the figure placed in the abscissa, those forces by increasing or diminishing the ordinates in any given ratio, or even by changing the angle of the inclination of the ordinates to the abscissa, are always augmented or diminished in the ratio of the distances from the center, provided the periodic times remain equal. So also in all figures whatsoever, if the ordinates are augmented or diminished in any given ratio, or their inclination is any way changed, the periodic time remaining the same. The forces directed to any center placed in the abscissa are in the several ordinates augmented or diminished in the ratio of the distances from the center. Section 3. Of the motion of bodies in eccentric conic sections. Proposition 11. Problem 6. If a body revolves in an ellipsis, it is required to find the law of the centripetal force tending to the focus of the ellipsis. Let S be the focus of the ellipsis. Draw SP cutting the diameter dk of the ellipsis in E, and the ordinate QV in X, and complete the parallelogram QXPR. It is evident that EP is equal to the greater semi-axis AC, for drawing HI from the other focus H of the ellipsis parallel to EC, because CS, CH are equal, ES, EI will be also equal. So that EP is the half sum of PS, PI, that is, because of the parallels HI, PR, and the equal angles IPR, HPZ, of PS, PH, which taken together are equal to the whole axis 2AC. Draw QD perpendicular to SP, and putting L for the principal lattice rectum of the ellipsis, or 4, we shall have LQR to LPV as QR to PV, that is, as PE or AC to PC, and LPV to GVP as L to GV, and GVP to QV superscript 2 as PC superscript 2 to CD superscript 2, and by Coral. 2, Lem. 7, the points Q and P coinciding, QV superscript 2 is to QX superscript 2 in the ratio of equality, and QX superscript 2 or QV superscript 2 is to QD superscript 2 as EP superscript 2 to PF superscript 2, that is, as CA superscript 2 to PF superscript 2, or, by Lem. 12, as CD superscript 2 to CB superscript 2. And compounding all those ratios together, we shall have LQR to QD superscript 2 as AC LPC superscript 2 CD superscript 2, or 2 CB superscript 2 PC superscript 2 CD superscript 2 to PC GV CD superscript 2 CB superscript 2, or as 2 PC to GV. But the points Q and P coinciding, 2 PC and GV are equal. And therefore the quantities LQR and QD superscript 2, proportional to these, will be also equal. Let those equals be drawn into, and LSP superscript 2 will become equal to. And therefore, by Coral, 1 and 5, Prop. 6, the centripetal force is reciprocally as LSP superscript 2, that is, reciprocally in the duplicate ratio of the distance SP. QEI. The same otherwise. Since the force tending to the center of the ellipsis, by which the body P may revolve in that ellipsis, is, by Coral, 1, Prop. X, as the distance CP of the body from the center C of the ellipsis. Let CE be drawn parallel to the tangent PR of the ellipsis, and the force by which the same body P may revolve about any other points of the ellipsis, if CE and PS intersect in E, will be as, by Cor 3, Prop. 7. That is, if the point S is the focus of the ellipsis, and therefore PE be given as SP superscript 2 reciprocally. QEI. With the same brevity with which we reduced the fifth problem to the parabola, and hyperbola, we might do the like here, but because of the dignity of the problem and its use in what follows, I shall confirm the other cases by particular demonstrations. Proposition 12. Problem 7. Suppose a body to move in an hyperbola, it is required to find the law of the centripetal force tending to the focus of that figure. Let CA, CB be the semi-axis of the hyperbola, PG, KD other conjugate diameters, PF a perpendicular to the diameter KD, and QV an ordinate to the diameter GP. Draw SP cutting the diameter DK in E, and the ordinate QV in X, and complete the parallelogram QRPX. It is evident that EP is equal to the semi-transverse axis AC. For drawing HI, from the other focus H of the hyperbola, parallel to EC, because CS, CH are equal, ES, EI will be also equal, so that EP is the half difference of PS, PI. That is, because of the parallels IH, PR, and the equal angles IPR, HPZ, of PS, PH, the difference of which is equal to the whole axis 2AC. Draw QD perpendicular to SP. And putting L for the principal lattice rectum of the hyperbola, that is, for, we shall have LQR to LPV as QR to PV, or PX to PV, that is, because of the similar triangles PXV, PC, as PE to PC, or AC to PC. And LPV will be to GVPV as L to GV, and, by the properties of the conic sections, the rectangle GVP is to QV superscript 2 as PC superscript 2 to CD superscript 2, and by, Cor 2, Lem. 7, QV superscript 2 to QX superscript 2. The points Q and P coinciding, becomes a ratio of equality. And QX superscript 2 or QV superscript 2 is to QD superscript 2 as EP superscript 2 to PF superscript 2, that is, as CA superscript 2 to PF superscript 2, or, by Lem. 12, as CD superscript 2 to CB superscript 2, and, compounding all those ratios together, we shall have LQR to QD superscript 2 as AC LPC superscript 2 CD superscript 2, or 2 CB superscript 2 PC superscript 2 CD superscript 2 to PC GV CD superscript 2 CB superscript 2, or as 2 PC to GV. But the points P and Q coinciding, 2 PC and GV are equal. And therefore the quantities LQR and QD superscript 2, proportional to them, will be also equal. Let those equals be drawn into, and we shall have LSP superscript 2 equal to. And therefore, by Cor. I and 5, Prop. 6, the centripetal force is reciprocally as LSP superscript 2, that is, reciprocally in the duplicate ratio of the distance SP. QEI. The same otherwise. Find out the force tending from the center C of the hyperbola. This will be proportional to the distance CP. But from thence, by Cor 3, Prop. 7, the force tending to the focus S will be as, that is, because PE is given reciprocally as SP superscript 2. QEI. And the same way may it be demonstrated, that the body having its centripetal changed into a centrifugal force, will move in the conjugate hyperbola. Lemma 13. The lattice rectum of a parabola belonging to any vertex is quadruple the distance of that vertex from the focus of the figure. This is demonstrated by the writers on the conic sections. Lemma 14. The perpendicular, let fall from the focus of a parabola on its tangent, is a mean proportional between the distances of the focus from the point of contact, and from the principal vertex of the figure. For, let AP be the parabola, S its focus, A its principal vertex, P the point of contact, PO an ordinate to the principal diameter, PM the tangent meeting the principal diameter in M. And SN the perpendicular from the focus on the tangent, join N, and because of the equal lines MS and SP, MN and NP, MA and AO, the right lines N, OP, will be parallel. And thence the triangle SAN will be right-angled at A, and similar to the equal triangles SNM, SNP, therefore PS is to SN as SN to SA. QED. Cor 1. PS superscript 2 is to SN superscript 2 as PS to SA. Cor 2. And because SA is given, SN superscript 2 will be as PS. Cor 3. And the concourse of any tangent PM, with the right line SN, drawn from the focus perpendicular on the tangent, falls in the right line and that touches the parabola in the principal vertex. Proposition 13. Problem 8. If a body moves in the perimeter of a parabola, it is required to find the law of the centripetal force tending to the focus of that figure. Retaining the construction of the preceding lemma, let P be the body in the perimeter of the parabola. And from the place Q, into which it is next to succeed, draw QR parallel and QD perpendicular to SP, as also QV parallel to the tangent, and meeting the diameter PG in V, and the distance SP in X. Now, because of the similar triangles PXV, SPM, and of the equal sides SP, SM of the one, the sides px or qr and pv of the other will be also equal. But, by the conic sections, the square of the ordinate qv is equal to the rectangle under the latus rectum and the segment pv of the diameter, that is, by lem. 13, to the rectangle 4pspv, or 4psqr. And the points p and q coinciding, the ratio of qv to qx, by cor 2, lem. 7, becomes a ratio of equality. And therefore qx superscript 2, in this case, becomes equal to the rectangle 4psqr. But, because of the similar triangles qxt, spn, qx superscript 2 is to qd superscript 2 as ps superscript 2 to sn superscript 2, that is, by cor 1, lem. 14, as ps to sa, that is, as 4psqr to 4saqr, and therefore, by prop. 9, lib v, elementary. qd superscript 2 and 4saqr are equal. Multiply these equals by, and will become equal to sp superscript 2 4sa, and therefore, by cor 1 and 5, prop. 6, the centripetal force is reciprocally as sp superscript 2 4sa, that is, because 4sa is given, reciprocally in the duplicate ratio of the distance sp. q. ei. Cor 1. From the three last propositions it follows, that if any body p goes from the place p with any velocity in the direction of any right line pr, and at the same time is urged by the action of a centripetal force that is reciprocally proportional to the square of the distance of the places from the center, the body will move in one of the conic sections, having its focus in the center of force. And the contrary. For the focus, the point of contact, and the position of the tangent, being given, a conic section may be described, which at that point shall have a given curvature. But the curvature is given from the centripetal force and velocity of the body being given, and two orbits, mutually touching one the other, cannot be described by the same centripetal force and the same velocity. Cor 2. If the velocity with which the body goes from its place p is such, that in any infinitely small moment of time the linola pr may be thereby described, and the centripetal force such as in the same time to move the same body through the space qr, the body will move in one of the conic sections, whose principal latus rectum is the quantity in its ultimate state, when the lineally pr, qr are diminished in infinitum. In these corollaries I consider the circle as an ellipsis. And I accept the case where the body descends to the center in a right line. Proposition 14. Theorem 6. If several bodies revolve about one common center, and the centripetal force is reciprocally in the duplicate ratio of the distance of places from the center, I say, that the principal latera recta of their orbits are in the duplicate ratio of the areas, which the bodies by radii drawn to the center describe in the same time. 4. By cor 2, prop. 13, the latus rectum L is equal to the quantity in its ultimate state when the points P and Q coincide. But the linola QR in a given time is as the generating centripetal force, that is, by supposition, reciprocally as SP superscript 2. And therefore is as QD superscript 2 SP superscript 2, that is, the latus rectum L is in the duplicate ratio of the area QD SP. QED. Sur. Hence the whole area of the ellipsis, and the rectangle under the axis, which is proportional to it, is in the ratio compounded of the subduplicate ratio of the latus rectum, and the ratio of the periodic time. For the whole area is as the area QDSP, described in a given time, multiplied by the periodic time. Proposition 15. Theorem 7. The same things being supposed, I say, that the periodic times in ellipses are in the sesquiplicate ratio of their greater axes. For the lesser axis is a mean proportional between the greater axis and the latus rectum. And, therefore, the rectangle under the axis is in the ratio compounded of the subduplicate ratio of the latus rectum and the sesquiplicate ratio of the greater axis. But this rectangle, by cor 3. Prop. 14, is in a ratio compounded of the subduplicate ratio of the latus rectum, and the ratio of the periodic time. Subduct from both sides the subduplicate ratio of the latus rectum, and there will remain the sesquiplicate ratio of the greater axis, equal to the ratio of the periodic time. QED. Sur. Therefore the periodic times in ellipses are the same as in circles whose diameters are equal to the greater axis of the ellipses. Proposition 16. Theorem 8. The same things being supposed, and right lines being drawn to the bodies that shall touch the orbits, and perpendiculars being let fall on those tangents from the common focus. I say, that the velocities of the bodies are in a ratio compounded of the ratio of the perpendiculars inversely, and the subduplicate ratio of the principal latera recta directly. From the focus S draw SY perpendicular to the tangent PR, and the velocity of the body P will be reciprocally in the subduplicate ratio of the quantity. For that velocity is as the infinitely small arc PQ described in a given moment of time, that is, by Lem. 7, as the tangent PR, that is, because of the proportionals PR to QD, and SP to SY, as, or as SY reciprocally, and SP QD directly. But SP QD is as the area described in the given time, that is, by Prop. 14, in the subduplicate ratio of the latus rectum. QED. Core 1. The principal latera recta are in a ratio compounded of the duplicate ratio of the perpendiculars and the duplicate ratio of the velocities. Core 2. The velocities of bodies, in their greatest and least distances from the common focus, are in the ratio compounded of the ratio of the distances inversely, and the subduplicate ratio of the principal latera recta directly. For those perpendiculars are now the distances. Core 3. And therefore the velocity in a conic section, at its greatest or least distance from the focus, is to the velocity in a circle, at the same distance from the center. In the subduplicate ratio of the principal latus rectum to the double of that distance. Core 4. The velocities of the bodies revolving in ellipses, at their mean distances from the common focus, are the same as those of bodies revolving in circles, at the same distances, that is, by Core 6, Prop. 4, reciprocally in the subduplicate ratio of the distances. For the perpendiculars are now the lesser semi-axes, and these are as mean proportionals between the distances and the latera recta. Let this ratio inversely be compounded with the subduplicate ratio of the latera recta directly, and we shall have the subduplicate ratio of the distance inversely. Core 5. In the same figure, or even in different figures, whose principal latera recta are equal, the velocity of a body is reciprocally as the perpendicular let fall from the focus on the tangent. Core 6. In a parabola, the velocity is reciprocally in the subduplicate ratio of the distance of the body from the focus of the figure. It is more variable in the ellipsis, and less in the hyperbola, than according to this ratio. 4. By Core 2, Lem. 14, the perpendicular let fall from the focus on the tangent of a parabola is in the subduplicate ratio of the distance. In the hyperbola the perpendicular is less variable, in the ellipsis more. Core 7. In a parabola, the velocity of a body at any distance from the focus is to the velocity of a body revolving in a circle, at the same distance from the center, in the subduplicate ratio of the number 2 to 1. In the ellipsis it is less, and in the hyperbola greater, than according to this ratio. By Core 2 of this prop, the velocity at the vertex of a parabola is in this ratio, and, by Core 6 of this prop. And Prop. 4, the same proportion holds in all distances. And hence, also, in a parabola, the velocity is everywhere equal to the velocity of a body revolving in a circle at half the distance, in the ellipsis it is less, and in the hyperbola greater. Core 8. The velocity of a body revolving in any conic section is to the velocity of a body revolving in a circle, at the distance of half the principal latus rectum of the section. As that distance to the perpendicular let fall from the focus on the tangent of the section. This appears from Core 5. Core 9. Wherefore since, by Core 6, Prop. For, the velocity of a body revolving in this circle is to the velocity of another body revolving in any other circle reciprocally in the subduplicate ratio of the distances. Therefore, the velocity of a body revolving in a conic section will be to the velocity of a body revolving in a circle at the same distance as a mean proportional between that common distance. And half the principal lattice rectum of the section, to the perpendicular let fall from the common focus upon the tangent of the section. Proposition 17. Problem 9. Supposing the centripetal force to be reciprocally proportional to the squares of the distances of places from the center, and that the absolute quantity of that force is known. It is required to determine the line which a body will describe that is let go from a given place with a given velocity in the direction of a given right line. Let the centripetal force tending to the point S be such as will make the body P revolve in any given orbit PQ, and suppose the velocity of this body in the place P is known. Then from the place P suppose the body P to be let with a given velocity in the direction of the line PR, but by virtue of a centripetal force to be immediately turned aside from that right line into the conic section PQ. The right line PR will therefore touch in P. Suppose likewise that the right line PR touches the orbit PQ in P, and if from S you suppose perpendiculars let fall on those tangents, the principal lattice rectum of the conic section, by Cr. 1, Prop. 16, will be to the principal lattice rectum of that orbit in a ratio compounded of the duplicate ratio of the perpendiculars, and the duplicate ratio of the velocities, and is therefore given. Let this lattice rectum be L. The focus S of the conic section is also given. Let the angle RPH be the complement of the angle RPS to 2 right, and the line PH, in which the other focus H is placed, is given by position. Let fall SK perpendicular on PH, and erect the conjugate semi-axis BC. This done, we shall have SP superscript 2 kph plus ph superscript 2 equals sh superscript 2 equals 4 ch superscript 2 equals 4 bh superscript 2, for bc superscript 2 equals, L equals SP superscript 2 plus 2 sph plus ph superscript 2, L. Add on both sides 2 kph, SP superscript 2, ph superscript 2 plus L, and we shall have L equals 2 sph plus 2 kph, or sp plus ph to ph, as 2 sp plus 2 kp to L, whence ph is given both in length and position. That is, if the velocity of the body in P is such that the lattice rectum L is less than 2 sp plus 2 kp, ph will lie on the same side of the tangent PR with the line sp. And therefore the figure will be an ellipsis, which from the given foci S, H, and the principal axis SP plus PH, is given also. But if the velocity of the body is so great, that the lattice rectum L becomes equal to 2 SP plus 2 kp, the length PH will be infinite, and therefore, the figure will be a parabola, which has its axis SH parallel to the line PK, and is thence given. But if the body goes from its place P with a yet greater velocity, the length PH is to be taken on the other side the tangent. And so the tangent passing between the foci, the figure will be an hyperbola having its principal axis equal to the difference of the lines SP and PH, and thence is given. For if the body, in these cases, revolves in a conic section so found, it is demonstrated in Prop. 11, 12, and 13, that the centripetal force will be reciprocally as the square of the distance of the body from the center of force S. And therefore we have rightly determined the line PQ, which a body let go from a given place P with a given velocity, and in the direction of the right line PR given by position, would describe with such a force. QEF. Core 1. Hence in every conic section, from the principal vertex D, the lattice rectum L, and the focus S given, the other focus H is given, by taking DH to DS as the lattice rectum to the difference between the lattice rectum and 4DS. For the proportion, SP plus PH to PH as 2 SP plus 2 KP to L, becomes, in the case of this corollary, DS plus DH to DH as 4DS to L, and by division DS to DH as 4DS, L to L. Core 2. Whence if the velocity of a body in the principal vertex D is given, the orbit may be readily found. To wit, by taking its lattice rectum to twice the distance ds, in the duplicate ratio of this given velocity to the velocity of a body revolving in a circle at the distance ds, by Core 3, Prop. 16. And then taking dh to ds as the lattice rectum to the difference between the lattice rectum and 4 ds. Core 3. Hence also if a body move in any conic section, and is forced out of its orbit by any impulse, you may discover the orbit in which it will afterwards pursue its course. For by compounding the proper motion of the body with that motion, which the impulse alone would generate, you will have the motion with which the body will go off from a given place of impulse in the direction of a right line given in position. Core 4. And if that body is continually disturbed by the action of some foreign force, we may nearly know its course, by collecting the changes which that force introduces in some points, and estimating the continual changes it will undergo in the intermediate places, from the analogy that appears in the progress of the series. Scholium. If a body P, by means of a centripetal force tending to any given point R, move in the perimeter of any given conic section whose center is C, and the law of the centripetal force is required, draw CG parallel to the radius RP, and meeting the tangent PG of the orbit in G, and the force required, by Core 1, and Scholl. Prop. X, and Core 3, Prop. 7, will be as. Section 4. Of the finding of elliptic, parabolic, and hyperbolic orbits, from the focus given. Lemma 15. If from the two foci S, H, of any ellipsis or hyperbola, we draw to any third point V the right lines SV, HV, whereof one HV is equal to the principal axis of the figure, that is, to the axis in which the foci are situated, the other, SV, is bisected in T by the perpendicular TR let fall upon it. That perpendicular TR will somewhere touch the conic section, and, vice versa, if it does touch it, HV will be equal to the principal axis of the figure. 4. Let the perpendicular TR cut the right line HV, produced, if need be, in R, and join SR. Because TS, TV are equal, therefore the right lines SR, VR, as well as the angles TRS, TRV, will be also equal. Whence the point R will be in the conic section, and the perpendicular TR, will touch the same, and the contrary. QED. Proposition 18. Problem X. From a focus and the principal axis given, to describe elliptic and hyperbolic trajectories, which shall pass through given points, and touch right lines given by position. Let S be the common focus of the figures. A be the length of the principal axis of any trajectory, P a point through which the trajectory should pass, and TR a right line which it should touch. About the center P, with the interval AB, SP, if the orbit is an ellipsis, or AB plus SP, if the orbit is an hyperbola, describe the circle HG. On the tangent TR let fall the perpendicular ST, and produce the same to V, so that TV may be equal to ST. And about V as a center with the interval AB describe the circle FH. In this manner, whether two points P, P, are given, or two tangents TR, TR, or a point P and a tangent TR, we are to describe two circles. Let H be their common intersection, and from the foci S, H, with the given axis describe the trajectory, I say, the thing is done. 4. Because PH plus SP in the ellipsis, and PH, SP in the hyperbola, is equal to the axis, the described trajectory will pass through the point P, and, by the preceding lemma, will touch the right line TR. And by the same argument it will either pass through the 2 points P, P, or touch the 2 right lines TR, TR. QEF. Proposition 19. Problem 11. About a given focus, to describe a parabolic trajectory, which shall pass through given points, and touch right lines given by position. Let S be the focus, P a point, and TR a tangent of the trajectory to be described. About P as a center, with the interval PS, describe the circle FG. From the focus let fall ST perpendicular on the tangent, and produce the same to V, so as TV may be equal to ST. After the same manner another circle FG is to be described, if another point P is given, or another point V is to be found, if another tangent TR is given. Then draw the right line if, which shall touch the two circles FG, FG, if 2 points P, P are given. Or pass through the 2 points V, V, if two tangents TR, TR, are given, or touch the circle FG, and pass through the point V, if the point P and the tangent TR are given. On Phi let fall the perpendicular SI, and bisect the same in K. And with the axis SK and principal vertex K describe a parabola, I say the thing is done. For this parabola, because SK is equal to IK, and SP to FP, will pass through the point P, and, by core 3, lem. 14, because ST is equal to TV, and STR a right angle, it will touch the right line TR. QEF. Proposition XX. Problem 12. About a given focus to describe any trajectory given in specie which shall pass through given points, and touch right lines given by position. Case 1. About the focus S it is required to describe a trajectory ABC, passing through 2 points B, C. Because the trajectory is given in specie, the ratio of the principal axis to the distance of the foci will be given. In that ratio take KB to BS, and LC to CS. About the centers B, C, with the intervals BK, CL, describe two circles, and on the right line KL, that touches the same in K and L, let fall the perpendicular SG. Which cut in A and A, so that GA may be to AS, and GA to as KB to BS, and with the axis AA, and vertices A, describe a trajectory, I say the thing is done. For let H be the other focus of the described figure, and seeing GA is to AS as GA to as, then by division we shall have GA, or AA to as, AS, or SH in the same ratio. And therefore in the ratio which the principal axis of the figure to be described has to the distance of its foci. And therefore the described figure is of the same species with the figure which was to be described. And since KB to BS, and LC to CS, are in the same ratio, this figure will pass through the points B, C, as is manifest from the conic sections. Case 2. About the focus S it is required to describe a trajectory which shall somewhere touch two right lines TR. From the focus on those tangents let fall the perpendiculars ST, which produce to V, so that TV may be equal to TS. Bisect VV in O, and erect the indefinite perpendicular OH, and cut the right line VS infinitely produced in K and K, so that VK be to KS, and VK to KS, as the principal axis of the trajectory to be described is to the distance of its foci. On the diameter KK describe a circle cutting OH and H, and with the foci S, H, and principal axis equal to VH, describe a trajectory, I say, the thing is done. For bisecting KK in X, and joining HX, HS, HV, because VK is to KS as VK to KS. And by composition, as VK plus VK to KS plus KS, and by division, as VK to KS, that is, as 2VX to 2KX, and 2KX to 2SX, and therefore as VX to HX and HX to SX, the triangles VXH, HXS will be similar, therefore VH will be to SH as VX to XH. And therefore as VK to KS. Wherefore VH, the principal axis of the described trajectory, has the same ratio to SH, the distance of the foci, as the principal axis of the trajectory which was to be described has to the distance of its foci. And is therefore of the same species. And seeing VH are equal to the principal axis, and VS, versus are perpendicularly bisected by the right lines TR, it is evident, by lem. 15, that those right lines touch the described trajectory. QEF. Case 3. About the focus S it is required to describe a trajectory, which shall touch a right line TR in a given point R. On the right line TR let fall the perpendicular ST, which produced to V, so that TV may be equal to ST. Join VR, and cut the right line VS indefinitely produced in K and K, so that VK may be to SK, and VK to SK, as the principal axis of the ellipsis to be described to the distance of its foci. And on the diameter KK describing a circle, cut the right line VR produced in H, then with the foci S, H, and principal axis equal to VH, describe a trajectory. I say, the thing is done. For VH is to SH as VK to SK, and therefore as the principal axis of the trajectory which was to be described to the distance of its foci, as appears from what we have demonstrated in case 2. And therefore the described trajectory is of the same species with that which was to be described. But that the right line TR, by which the angle VRS is bisected, touches the trajectory in the point R, is certain from the properties of the conic sections. QEF. Case 4. About the focus S it is required to describe a trajectory APB that shall touch a right line TR, and pass through any given point P without the tangent, and shall be similar to the figure APB, described with the principal axis of, and foci S, H. On the tangent TR let fall the perpendicular ST, which produced to V, so that TV may be equal to ST. And making the angles HSQ, SHQ, equal to the angles VSP, SVP, about Q as a center, and with an interval which shall be 2 of as SP to VS, describe a circle cutting the figure APB in P, join SP, and draw SH such that it may be to SH as SP is to SP. And may make the angle PSH equal to the angle PSH, and the angle VSH equal to the angle PSQ. Then with the foci S, H, and principal axis AB, equal to the distance VH, describe a conic section. I say, the thing is done. For if SV is drawn so that it shall be to SP as SH is to SQ, and shall make the angle VSP equal to the angle HSQ, and the angle VSH equal to the angle PSQ, the triangles SVH, SPQ, will be similar, and therefore VH will be to PQ as SH is to SQ. That is, because of the similar triangles VSP, HSQ, as VS is to SP, or as up to PQ. Wherefore VH and UB are equal. But, because of the similar triangles VSH, VSH, VH is to SH as VH to SH. That is, the axis of the conic section now described is to the distance of its foci as the axis UB to the distance of the foci SH, and therefore the figure now described is similar to the figure AF. But, because the triangle PSH is similar to the triangle PSH, this figure passes through the point P, and because VH is equal to its axis, and VS is perpendicularly bisected by the right line TR, the said figure touches the right line TR. QE. F. Lemma 16. From 3 given points to draw to a fourth point that is not given 3 right lines whose differences shall be either given, or none at all. Case 1. Let the given points be A, B, C, and Z the fourth point which we are to find. Because of the given difference of the lines AZ, BZ, the locus of the point Z will be an hyperbola whose foci are A and B, and whose principal axis is the given difference. Let that axis be MN. Taking PM to MA as MN is to AB, erect PR perpendicular to AB, and let fall ZR perpendicular to PR, then from the nature of the hyperbola, ZR will be to AZ as MN is to AB. And by the like argument, the locus of the point Z will be another hyperbola, whose foci are A, C, and whose principal axis is the difference between AZ and CZ. And QS a perpendicular on AC may be drawn, to which, QS, if from any point Z of this hyperbola a perpendicular ZS is let fall, this ZS, shall be to AZ as the difference between AZ and CZ is to AC. Wherefore the ratios of ZR and ZS to AZ are given, and consequently the ratio of ZR to ZS one to the other. And therefore if the right lines RP, SQ, meet in T, and TZ and TA are drawn, the figure TRZS will be given in specie, and the right line TZ, in which the point Z is somewhere placed, will be given in position. There will be given also the right line TA, and the angle ATZ, and because the ratios of AZ and TZ to ZS are given, their ratio to each other is given also, and thence will be given likewise the triangle ATZ, whose vertex is the point Z. QEI. Case 2. If two of the three lines, for example AZ and BZ, are equal, draw the right line TZ so as to bisect the right line AB, then find the triangle ATZ as above. QEI. Case 3. If all the three are equal, the point Z will be placed in the center of a circle that passes through the points A, B, C. QEI. This problematic lemma is likewise solved in Apollonius's Book of Tactions restored by Vieta. Proposition 21. Problem 13. About a given focus to describe a trajectory that shall pass through given points and touch right lines given by position. Let the focus S, the point P, and the tangent TR be given, and suppose that the other focus H is to be found. On the tangent let fall the perpendicular ST, which produce to Y, so that TY may be equal to ST, and YH will be equal to the principal axis. Join SP, HP, and SP will be the difference between HP and the principal axis. After this manner, if more tangents TR are given, or more points P, we shall always determine as many lines YH, or PH, drawn from the said points Y or P, to the focus H, which either shall be equal to the axis, or differ from the axis by given lengths SP. And therefore which shall either be equal among themselves, or shall have given differences, from whence, by the preceding lemma, that other focus H is given. But having the foci in the length of the axis, which is either YH, or, if the trajectory be an ellipsis, PH plus SP, or PH, SP, if it be an hyperbola, the trajectory is given. QEI. Scholium. When the trajectory is an hyperbola, I do not comprehend its conjugate hyperbola under the name of this trajectory. For a body going on with a continued motion can never pass out of one hyperbola into its conjugate hyperbola. The case when 3 points are given is more readily solved thus. Let B, C, D, be the given points. Join BC, CD, and produce them to E, F, so as EB may be to EC as SB to SC, and FC to FD as SC to SD. On EF drawn and produced let fall the perpendiculars SG, BH, and in GS produced indefinitely take GA to AS, and GA to as HB is to BS, then A will be the vertex, and AA the principal axis of the trajectory. Which, according as GA is greater than, equal to, or less than as, will be either an ellipsis, a parabola, or an hyperbola, the point A in the first case falling on the same side of the line GF as the point A. In the second, going off to an infinite distance, in the third, falling on the other side of the line GF. For if on GF the perpendiculars CI, DK are let fall, IC will be to HB as EC to EB, that is, as SC to SB. And by permutation, IC to SC as HB to SB, or as GA to SA. And, by the like argument, we may prove that KD is to SD in the same ratio. Wherefore the points B, C, D lie in a conic section described about the focus S, in such manner that all the right lines drawn from the focus S to the several points of the section, and the perpendiculars let fall from the same points on the right line GF, are in that given ratio. That excellent geometer M. de la Hire has solved this problem much after the same way, in his Conics, Prop. XXV, Lib 8. Section 5. How the orbits are to be found when neither focus is given. Lemma 17. If from any point P of a given conic section, to the four produced sides AB, CD, AC, DB, of any trapezium ABDC inscribed in that section, as many right lines PQ, PR, PS, PT are drawn in given angles, each line to each side. The rectangle PQ-PR of those on the opposite sides AB, CD, will be to the rectangle PS-PT of those on the other two opposite sides AC, BD, in a given ratio. Case 1. Let us suppose, first, that the lines drawn to one pair of opposite sides are parallel to either of the other sides, as PQ and PR to the side AC, and PS and PT to the side AB. And farther, that one pair of the opposite sides, as AC and BD, are parallel betwixt themselves, then the right line which bisects those parallel sides will be one of the diameters of the conic section, and will likewise bisect RQ. Let O be the point in which RQ is bisected, and PO will be an ordinate to that diameter. Produce PO to K, so that OK may be equal to PO, and OK will be an ordinate on the other side of that diameter. Since, therefore, the points A, B, P and K are placed in the conic section, and PK cuts AB in a given angle, the rectangle PQK, by Prop. 17, 19, 21. And Xi, Book 3, of Apollonius's Conics, will be to the rectangle AQB in a given ratio. But QK and PR are equal, as being the differences of the equal lines OK, OP, and OQ, or, whence the rectangles PQK and PQPR are equal, and therefore the rectangle PQPR is to the rectangle AB, that is, to the rectangle PSPT in a given ratio. QED. Case 2. Let us next suppose that the opposite sides AC and BD of the trapezium are not parallel. Draw BD parallel to AC, and meeting as well the right line ST in T, as the conic section in D. Join CD cutting PQ in R, and draw DM parallel to PQ, cutting CD in M, and AB in N. Then, because of the similar triangles BTT, DBN, BT or PQ is to TT as DN to NB. And so RR is to AQ or PS as DM to N. Wherefore, by multiplying the antecedents by the antecedents, and the consequence by the consequence, as the rectangle PQRR is to the rectangle PSTT, so will the rectangle NDM be to the rectangle ANB. And, by case 1, so is the rectangle PQPR to the rectangle PS point, and by division, so is the rectangle PQPR to the rectangle PSPT. QED. Case 3. Let us suppose, lastly, the four lines PQ, PR, PS, PT, not to be parallel to the sides AC, AB, but any way inclined to them. In their place draw PQ, PR, parallel to AC, and PS, point parallel to AB. And because the angles of the triangles PQQ, PRR, PS's, PTT are given, the ratios of PQ to PQ, PR to PR, PS to PS, PT to point will be also given, and therefore the compounded ratios PQ-PR to PQ-PR, and PS-PT to PS point are given. But from what we have demonstrated before, the ratio of PQ-PR to PS point is given, and therefore also the ratio of PQ-PR to PS-PT. QED. Lemma 18. The same thing supposed, if the rectangle PQ-PR of the lines drawn to the two opposite sides of the trapezium is to the rectangle PSPT of those drawn to the other two sides in a given ratio, the point P, from whence those lines are drawn, will be placed in a conic section described about the trapezium. Conceive a conic section to be described passing through the points A, B, C, D, and any one of the infinite number of points P, as for example P. I say, the point P will be always placed in this section. If you deny the thing, join AP cutting this conic section somewhere else, if possible, than in P, as in B. Therefore if from those points P and B, in the given angles to the sides of the trapezium, we draw the right lines PQ, PR, PS, point, and BK, BN, BF, BD, we shall have, as BK BN to BF BD, so, by Lem. 17, PQ-PR to PS point. And so, by supposition, PQ-PR to PS-PT. And because of the similar trapezia BKAF, PQAS, as BK to BF, so PQ to PS, wherefore by dividing the terms of the preceding proportion by the correspondent terms of this, we shall have BN to BD as PR to PT. And therefore the equiangular trapezia DNBD, DRPT, are similar, and consequently their diagonals DB, DP do coincide. Wherefore B falls in the intersection of the right lines AP, DP, and consequently coincides with the point P. And therefore the point P, wherever it is taken, falls to be in the assigned conic section. QED. Sur. Hence if three right lines PQ, PR, PS, are drawn from a common point P, to as many other right lines given in position, AB, CD, AC, each to each, in as many angles respectively given. And the rectangle PQ-PR under any two of the lines drawn be to the square of the third PS in a given ratio. The point P, from which the right lines are drawn, will be placed in a conic section that touches the lines AB, CD in A and C, and the contrary. For the position of the three right lines AB, CD, AC remaining the same, let the line BD approach to and coincide with the line AC, then let the line PT come likewise to coincide with the line PS. And the rectangle PSPT will become PS superscript 2, and the right lines AB, CD, which before did cut the curve in the points A and B, C, and D, can no longer cut, but only touch, the curve in those coinciding points. Scholium. In this lemma, the name of conic section is to be understood in a large sense, comprehending as well the rectilinear section through the vertex of the cone, as the circular one parallel to the base. For if the point P happens to be in a right line, by which the points A and D, or C and B are joined, the conic section will be changed into two right lines, one of which is that right line upon which the point P falls. And the other is a right line that joins the other two of the 4 points. If the two opposite angles of the trapezium taken together are equal to two right angles, and if the 4 lines PQ, PR, PS, PT, are drawn to the sides thereof at right angles, or any other equal angles. And the rectangle PQ-PR under two of the lines drawn PQ and PR, is equal to the rectangle PSPT under the other two PS and PT, the conic section will become a circle. And the same thing will happen if the 4 lines are drawn in any angles, and the rectangle PQ-PR, under one pair of the lines drawn, is to the rectangle PSPT under the other pair as the rectangle under the signs of the angles S, T, in which the two last lines PS, PT are drawn to the rectangle under the signs of the angles Q, R, in which the first two PQ, PR are drawn. In all other cases the locus of the point P will be one of the 3 figures which pass commonly by the name of the conic sections. But in room of the trapezium ABCD, we may substitute a quadrilateral figure whose two opposite sides cross one another like diagonals. And one or two of the 4 points A, B, C, D may be supposed to be removed to an infinite distance, by which means the sides of the figure which converge to those points, will become parallel. And in this case the conic section will pass through the other points, and will go the same way as the parallels in infinitum. Lemma 19. To find a point P from which if 4 right lines PQ, PR, PS, PT are drawn to as many other right lines AB, CD, AC, BD, given by position, each to each, at given angles, the rectangle PQ-PR, under any two of the lines drawn, shall be to the rectangle PSPT, under the other two, in a given ratio. Suppose the lines AB, CD, to which the two right lines PQ, PR, containing one of the rectangles, are drawn to meet two other lines, given by position, in the points A, B, C, D. From one of those, as A, draw any right line AH, in which you would find the point P. Let this cut the opposite lines BD, CD, in H and I. And, because all the angles of the figure are given, the ratio of PQ to PA, and PA to PS, and therefore of PQ to PS, will be also given. Subducting this ratio from the given ratio of PQ-PR to PSPT, the ratio of PR to PT will be given. And adding the given ratios of PI to PR, and PT to PH, the ratio of PI to PH, and therefore the point P will be given. QEI. Core 1. Hence also a tangent may be drawn to any point D of the locus of all the points P. For the chord PD, where the points P and D meet, that is, where AH is drawn through the point D, becomes a tangent. In which case the ultimate ratio of the evanescent lines IP and PH will be found as above. Therefore draw CF parallel to AD, meeting BD in F, and cut it in E in the same ultimate ratio, then DE will be the tangent, because CF and the evanescent IH are parallel, and similarly cut in E and P. Core 2. Hence also the locus of all the points P may be determined. Through any of the points A, B, C, D, as A, draw AE touching the locus, and through any other point B parallel to the tangent, draw BF meeting the locus in F. And find the point F by this lemma. Bisect BF in G, and, drawing the indefinite line AG, this will be the position of the diameter to which BG and FG are ordinates. Let this AG meet the locus in H, and AH will be its diameter or lattice transversum, to which the lattice rectum will be as BG superscript 2 to AGGH. If AG nowhere meets the locus, the line AH being infinite, the locus will be a parabola. And its lattice rectum corresponding to the diameter AG will be. But if it does meet it anywhere, the locus will be an hyperbola, when the points A and H are placed on the same side the point G. And an ellipsis, if the point G falls between the points A and H, unless, perhaps, the angle AGB is a right angle, and at the same time BG superscript 2 equal to the rectangle AGH, in which case the locus will be a circle. And so we have given in this corollary a solution of that famous problem of the ancients concerning four lines, begun by Euclid, and carried on by Apollonius. And this not an analytical calculus, but a geometrical composition, such as the ancients required. Lemma XX. If the two opposite angular points A and P of any parallelogram ASPQ touch any conic section in the points A and P, and the sides AQ, AS of one of those angles, indefinitely produced, meet the same conic section in B and C. And from the points of concourse B and C to any fifth point D of the conic section, two right lines BD, CD are drawn meeting the two other sides PS, PQ of the parallelogram, indefinitely produced in T and R. The parts PR and PT, cut off from the sides, will always be one to the other in a given ratio. And vice versa, if those parts cut off are one to the other in a given ratio, the locus of the point D will be a conic section passing through the 4 points A, B, C, P. Case 1. Join BP, CP, and from the point D draw the two right lines DG, DE, of which the first DG shall be parallel to AB, and meet PB, PQ, CA in H, I, G, and the other DE shall be parallel to AC, and meet PC, PS, AB, in F, K, E, and, by lem. 17. The rectangle DEDF will be to the rectangle DGDH in a given ratio. But PQ is to DE, or IQ, as PB to HB, and consequently as PT to DH, and by permutation PQ is to PT as DE to DH. Likewise PR is to DF as RC to DC, and therefore as IG or PS to DG, and by permutation PR is to PS as DF to DG. And, by compounding those ratios, the rectangle PQPR will be to the rectangle PSPT as the rectangle DEDF is to the rectangle DGDH, and consequently in a given ratio. But PQ and PS are given, and therefore the ratio of PR to PT is given. Q. ED. Case 2. But if PR and PT are supposed to be in a given ratio one to the other, then by going back again, by a like reasoning, it will follow that the rectangle DEDF is to the rectangle DGDH in a given ratio, and so the point D, by lem. 18, will lie in a conic section passing through the points A, B, C, P, as its locus. QED. Core 1. Hence if we draw BC cutting PQ in R and in PT take point to PR in the same ratio which PT has to PR, then BT will touch the conic section in the point B. For suppose the point D to coalesce with the point B, so that the chord BD vanishing, BT shall become a tangent, and CD and BT will coincide with CB and BT. Core 2. And, vice versa, if BT is a tangent, and the lines BD, CD meet in any point D of a conic section, PR will be to PT as PR to PT. And, on the contrary, if PR is to PT as PR to point, then BD and CD will meet in some point D of a conic section. Core 3. One conic section cannot cut another conic section in more than 4 points. 4. If it is possible, let two conic sections pass through the 5 points A, B, C, P, O. And let the right line BD cut them in the points D, D, and the right line CD cut the right line PQ in Q. Therefore PR is to PT as PQ to PT, whence PR and PQ are equal one to the other, against the supposition. Lemma 21. If two movable and indefinite right lines BM, CM drawn through given points B, C, as poles, do by their point of concourse M describe a third right line MN given by position. And other two indefinite right lines BD, CD are drawn, making with the former two at those given points B, C, given angles, MBD, MCD, I say, that those two right lines BD, CD will by their point of concourse D describe a conic section passing through the points B, C. And, vice versa, if the right lines BD, CD do by their point of concourse D describe a conic section passing through the given points B, C, A, and the angle DBM is always equal to the given angle ABC. As well as the angle DCM always equal to the given angle ACB, the point M will lie in a right line given by position, as its locus. For in the right line MN let a point N be given, and when the movable point M falls on the immovable point N, let the movable point D fall on an immovable point P. Join CN, BN, CP, BP, and from the point P draw the right lines PT, PR meeting BD, CD in T and R, and making the angle BPT equal to the given angle BNM, and the angle CPR equal to the given angle CNM. Wherefore since, by supposition, the angles MBD, NBP are equal, as also the angles MCD, NCP, take away the angles NBD and NCD that are common, and there will remain the angles NBM and PBT, NCM and PCR equal. And therefore the triangles NBM, PBT are similar, as also the triangles NCM, PCR. Wherefore PT is to NM as PB to NB, and PR to NM as PC to NC. But the points, B, C, N, P are immovable, wherefore PT and PR have a given ratio to NM, and consequently a given ratio between themselves. And therefore, by lemma XX, the point D wherein the movable right lines BT and CR perpetually concur, will be placed in a conic section passing through the points B, C, P, QED. And, vice versa, if the movable point D lies in a conic section passing through the given points B, C, A. And the angle DBM is always equal to the given angle ABC, and the angle DCM always equal to the given angle ACB, and when the point D falls successively on any two immovable points P, P, of the conic section, the movable point M falls successively on two immovable points N, N. Through these points N, N, draw the right line NN, this line NN will be the perpetual locus of that movable point M. 4. If possible, let the point M be placed in any curved line. Therefore the point D will be placed in a conic section passing through the 5 points B, C, A, P, P, when the point M is perpetually placed in a curved line. But from what was demonstrated before, the point D will be also placed in a conic section passing through the same 5 points B, C, A, P, when the point M is perpetually placed in a right line. Wherefore the two conic sections will both pass through the same 5 points, against Coral, 3, Lem. XX, it is therefore absurd to suppose that the point M is placed in a curved line. QED. Proposition 22. Problem 14. To describe a trajectory that shall pass through 5 given points. Let the 5 given points be A, B, C, P, D. From any one of them, as A, to any other two as B, C, which may be called the poles, draw the right lines AB, AC, and parallel to those the lines TPS, PRQ, through the fourth point P. Then from the two poles B, C, draw through the fifth point D two indefinite lines BDT, CRD, meeting with the last drawn lines TPS, PRQ, the former with the former, and the latter with the latter, in T and R. Then drawing the right line TR parallel to TR, cutting off from the right lines PT, PR, any segments point, PR, proportional to PT, PR. And if through their extremities, T, R, and the poles B, C, the right lines BT, CRER drawn, meeting in D, that point D will be placed in the trajectory required. 4. By lem. XX, that point D is placed in a conic section passing through the 4 points A, B, C, P, and the lines RR, TT vanishing, the point D comes to coincide with the point D, wherefore the conic section passes through the 5 points A, B, C, P, D. Q. ED. The same otherwise. Of the given points join any three, as A, B, C. And about two of them B, C, as poles, making the angles ABC, ACB of a given magnitude to revolve, apply the legs BA, CA, first to the point D, then to the point P, and mark the points M, N, in which the other legs BL, CL intersect each other in both cases. Draw the indefinite right line MN, and let those movable angles revolve about their poles B, C, in such manner that the intersection, which is now supposed to be D, of the legs BL, CL, or BM, CM, may always fall in that indefinite right line MN. And the intersection, which is now supposed to be M, of the legs BA, CA, or BD, CD, will describe the trajectory required, PADDB. 4. By lem. XXI, the point D will be placed in a conic section passing through the points B, C. And when the point M comes to coincide with the points L, M, N, the point D will, by construction, come to coincide with the points A, D, P, wherefore a conic section will be described that shall pass through the 5 points A, B, C, P, D. QEF. Core 1. Hence a right line may be readily drawn which shall be a tangent to the trajectory in any given point B. Let the point D come to coincide with the point B, and the right line BD will become the tangent required. Core 2. Hence also may be found the centers, diameters, and latera recta of the trajectories, as in Core 2, lem. 19. Scolium. The former of these constructions will become something more simple by joining BP, and in that line, produced, if need be, taking BP to BP as PR is to PT. And through P draw the indefinite right line PE parallel to SPT, and in that line PE taking always PE equal to PR, and draw the right lines B, CR to meet in D. For since PR to point, PR to PT, PB to PB, PE to point, are all in the same ratio, PE and PR will be always equal. After this manner the points of the trajectory are most readily found, unless you would rather describe the curve mechanically, as in the second construction. Proposition 23. Problem 15. To describe a trajectory that shall pass through 4 given points, and touch a right line given by position. Case 1. Suppose that HB is the given tangent, B the point of contact, and C, D, P, the 3 other given points. Join BC, and draw PS parallel to BH, and PQ parallel to BC, complete the parallelogram BSPQ. Draw BD cutting SP in T, and CD cutting PQ in R. Lastly, draw any line TR parallel to TR, cutting off from PQ, PS, the segments PR, point proportional to PR, PT respectively, and draw CR, BT their point of concourse D will, by lem. XX, always fall on the trajectory to be described. The same otherwise. Let the angle CBH of a given magnitude revolve about the pole B, as also the rectilinear radius BC, both ways produced, about the pole C. Mark the points M, N, on which the leg BC of the angle cuts that radius when BH, the other leg thereof, meets the same radius in the points P and D. Then drawing the indefinite line MN, let that radius CP or CD and the leg BC of the angle perpetually meet in this line. And the point of concourse of the other leg BH with the radius will delineate the trajectory required. For if in the constructions of the preceding problem the point A comes to a coincidence with the point B, the line CA and CB will coincide, and the line AB, in its last situation, will become the tangent BH. And therefore the constructions there set down will become the same with the constructions here described. Wherefore the concourse of the leg BH with the radius will describe a conic section passing through the point C, D, P, and touching the line BH in the point B. QEF. Case 2. Suppose the 4 points B, C, D, P, given, being situated without the tangent HI. Join each two by the lines BD, CP meeting in G, and cutting the tangent in H and I. Cut the tangent in A in such manner that HA may be to IA as the rectangle under a mean proportional between CG and GP, and a mean proportional between BH and HD is to a rectangle under a mean proportional between GD and GB. And a mean proportional between PI and IC, and A will be the point of contact. For if HX, a parallel to the right line PI, cuts the trajectory in any points X and Y, the point A, by the properties of the conic sections, will come to be so placed that HA superscript 2 will become to AI superscript 2 in a ratio that is compounded out of the ratio of the rectangle XHY to the rectangle BHD, or of the rectangle CGP to the rectangle DGB. And the ratio of the rectangle BHD to the rectangle PIC. But after the point of contact A is found, the trajectory will be described as in the first case. QEF. But the point A may be taken either between or without the points H and I, upon which account a twofold trajectory may be described. Proposition 24. Problem 16. To describe a trajectory that shall pass through 3 given points, and touch 2 right lines given by position. Suppose HI, KL to be the given tangents and B, C, D, the given points. Through any two of those points, as B, D, draw the indefinite right line BD meeting the tangents in the points H, K. Then likewise through any other two of these points, as C, D, draw the indefinite right line CD meeting the tangents in the points I, L. Cut the lines drawn in R and S, so that HR may be to KR as the mean proportional between BH and HD is to the mean proportional between BK and KD, and IS to LS as the mean proportional between CI and ID is to the mean proportional between CL and LD. But you may cut, at pleasure, either within or between the points K and H, I and L, or without them, then draw RS cutting the tangents in A and P will be the points of contact. For if A and P are supposed to be the points of contact, situated anywhere else in the tangents, and through any of the points H, I, K, L, as I, situated in either tangent HI, a right line IY is drawn parallel to the other tangent KL. And meeting the curve in X and Y, and in that right line there be taken IZ equal to a mean proportional between 9 and IY, the rectangle XIY or IZ superscript 2, will, by the properties of the conic sections, be to LP superscript 2 as the rectangle CID is to the rectangle CLD, that is, by the construction, as SI is to SL superscript 2, and therefore IZ is to LP as SI to SL. Wherefore the points S, P, Z, are in one right line. Moreover, since the tangents meet in G, the rectangle XIY or IZ superscript 2 will, by the properties of the conic sections, be to IA superscript 2 as GP superscript 2 is to GA superscript 2, and consequently IZ will be to IA as GP to GA. Wherefore the points P, Z, A, lie in one right line, and therefore the points S, P, and A are in one right line. And the same argument will prove that the points R, P, and A are in one right line. Wherefore the points of contact A and P lie in the right line RS. But after these points are found, the trajectory may be described, as in the first case of the preceding problem. QEF. In this proposition, and case 2 of the foregoing, the constructions are the same, whether the right line xy cut the trajectory in x and y, or not, neither do they depend upon that section. But the constructions being demonstrated where that right line does cut the trajectory, the constructions where it does not are also known, and therefore, for brevity's sake, I omit any farther demonstration of them. Lemma 22. To transform figures into other figures of the same kind. Suppose that any figure HGI is to be transformed. Draw, at pleasure, two parallel lines AO, BL, cutting any third line AB, given by position, in A and B, and from any point G of the figure, draw out any right line GD, parallel to OA, till it meet the right line AB. Then from any given point O in the line OA, draw to the point D the right line OD, meeting BL in D. And from the point of concourse raise the right line DG containing any given angle with the right line BL, and having such ratio to OD as DG has to OD, and G will be the point in the new figure Gi, corresponding to the point G. And in like manner the several points of the first figure will give as many correspondent points of the new figure. If we therefore conceive the point G to be carried along by a continual motion through all the points of the first figure, the point G will be likewise carried along by a continual motion through all the points of the new figure. And describe the same. For distraction's sake, let us call DG the first ordinate, DG the new ordinate, AD the first abscissa, add the new abscissa. O the pole, OD the abscending radius, OA the first ordinate radius, and OA, by which the parallelogram OA ba is completed, the new ordinate radius. I say, then, that if the point G is placed in a right line given by position, the point G will be also placed in a right line given by position. If the point G is placed in a conic section, the point G will be likewise placed in a conic section. And here I understand the circle as one of the conic sections. But farther, if the point G is placed in a line of the third analytical order, the point G will also be placed in a line of the third order, and so on in curved lines of higher orders. The two lines in which the points G, G, are placed, will be always of the same analytical order. For as AD is to OA, so are OD to OD, DG to DG, and AB to AD, and therefore AD is equal to, and DG equal to. Now if the point G is placed in a right line, and therefore, in any equation by which the relation between the abscissa AD and the ordinate GD is expressed, those indeterminate lines AD and DG rise no higher than to one dimension. By writing this equation in place of AD, and in place of DG, a new equation will be produced, in which the new abscissa AD and new ordinate DG rise only to one dimension. And which therefore must denote a right line. But if AD and DG, or either of them, had risen to two dimensions in the first equation, AD and DG would likewise have risen to two dimensions in the second equation. And so on in three or more dimensions. The indeterminate lines, AD, DG in the second equation, and AD, DG, in the first, will always rise to the same number of dimensions. And therefore the lines in which the points G, G, are placed are of the same analytical order. I say farther, that if any right line touches the curved line in the first figure, the same right line transferred the same way with the curve into the new figure will touch that curved line in the new figure, and vice versa. For if any two points of the curve in the first figure are supposed to approach one the other till they come to coincide, the same points transferred will approach one the other till they come to coincide in the new figure. And therefore the right lines with which those points are joined will become together tangents of the curves in both figures. I might have given demonstrations of these assertions in a more geometrical form, but I study to be brief. Wherefore if one rectilinear figure is to be transformed into another, we need only transfer the intersections of the right lines of which the first figure consists, and through the transferred intersections to draw right lines in the new figure. But if a curvilinear figure is to be transformed, we must transfer the points, the tangents, and other right lines, by means of which the curved line is defined. This lemma is of use in the solution of the more difficult problems. For thereby we may transform the proposed figures, if they are intricate, into others that are more simple. Thus any right lines converging to a point are transformed into parallels, by taking for the first ordinate radius any right line that passes through the point of concourse of the converging lines. And that because their point of concourse is by this means made to go off in infinitum. And parallel lines are such as tend to a point infinitely remote. And after the problem is solved in the new figure, if by the inverse operations we transform the new into the first figure, we shall have the solution required. This lemma is also of use in the solution of solid problems. For as often as two conic sections occur, by the intersection of which a problem may be solved, any one of them may be transformed, if it is an hyperbola or a parabola, into an ellipsis, and then this ellipsis may be easily changed into a circle. So also a right line and a conic section, in the construction of plane problems, may be transformed into a right line and a circle. Proposition 25. Problem 17. To describe a trajectory that shall pass through two given points, and touch three right lines given by position. Through the concourse of any two of the tangents one with the other, and the concourse of the third tangent with the right line which passes through the two given points, draw an indefinite right line. And, taking this line for the first ordinate radius, transform the figure by the preceding lemma into a new figure. In this figure those two tangents will become parallel to each other, and the third tangent will be parallel to the right line that passes through the two given points. Supposite, KL to be those two parallel tangents, IC the third tangent, and HL a right line parallel thereto, passing through those points A, B, through which the conic section ought to pass in this new figure. And completing the parallelogram HICL, let the right lines high, IC, KL be so cut in C, D, E, that HC may be to the square root of the rectangle OB, IC, to ID, and CO to KD, as the sum of the right lines high in KL is to the sum of the three lines. The first whereof is the right line IC, and the other two are the square roots of the rectangles OB and ALB. And C, D, E, will be the points of contact. For by the properties of the conic sections, HC superscript 2 to the rectangle OB, and IC superscript 2 to ID superscript 2, and K superscript 2 to KD superscript 2, and L superscript 2 to the rectangle ALB, are all in the same ratio. And therefore HC to the square root of OB, IC to ID, K to KD, and L to the square root of ALB, are in the subduplicate of that ratio. And by composition, in the given ratio of the sum of all the antecedents high plus KL, to the sum of all the consequents. Wherefore from that given ratio we have the points of contact C, D, E, in the new figure. By the inverted operations of the last lemma, let those points be transferred into the first figure, and the trajectory will be there described by Prob. 14. QEF. But according as the points A, B, fall between the points H, L, or without them, the points C, D, E, must be taken either between the points H, I, K, L, or without them. If one of the points A, B, falls between the points H, I, and the other without the points H, L, the problem is impossible. Proposition 26. Problem 18. To describe a trajectory that shall pass through a given point, and touch four right lines given by position. From the common intersections, of any two of the tangents to the common intersection of the other two, draw an indefinite right line. And taking this line for the first ordinate radius, transform the figure, by lem. XX, into a new figure, and the two pairs of tangents, each of which before concurred in the first ordinate radius, will now become parallel. Let high and KL, IC and HL, be those pairs of parallels completing the parallelogram HICL. And let P be the point in this new figure corresponding to the given point in the first figure. Through O the center of the figure draw PQ, and OQ being equal to OP, Q will be the other point through which the conic section must pass in this new figure. Let this point be transferred, by the inverse operation of lem. XXII into the first figure, and there we shall have the 2 points through which the trajectory is to be described. But through those points that trajectory may be described by Prop. 17. Lemma 23. If two right lines, as AC, BD given by position, and terminating in given points A, B, are in a given ratio one to the other, and the right line CD, by which the indeterminate points C, D are joined is cut in K in a given ratio. I say, that the point K will be placed in a right line given by position. For let the right lines AC, BD meet in E, and in B take BG to AE as BD is to AC, and let FD be always equal to the given line EG. And, by construction, EC will be to GD, that is, to EF, as AC to BD, and therefore in a given ratio, and therefore the triangle EFC will be given in kind. Let CF be cut in L so as CL may be to CF in the ratio of CK to CD. And because that is a given ratio, the triangle EFL will be given in kind, and therefore the point L will be placed in the right line EL given by position. Join LK, and the triangles CLK, CFD will be similar. And because FD is a given line, and LK is to FD in a given ratio, LK will be also given. To this let EH be taken equal, and ELKH will be always a parallelogram. And therefore the point K is always placed in the side HK, given by position, of that parallelogram. QED. Sure. Because the figure EFLC is given in kind, the three right lines EF, EL, and EC, that is, GD, HK, and EC, will have given ratios to each other. Lemma 24. If three right lines, two whereof are parallel, and given by position, touch any conic section, I say, that the semi-diameter of the section which is parallel to those two is a mean proportional between the segments of those two that are intercepted between the points of contact and the third tangent. Let AF, GB be the two parallels touching the conic section ADB in A and B. EF the third right line touching the conic section in I, and meeting the two former tangents in F and G, and let CD be the semi-diameter of the figure parallel to those tangents. I say, that AF, CD, BG are continually proportional. For if the conjugate diameters AB, DM meet the tangent FG in E and H, and cut one the other in C, and the parallelogram IKCL be completed, from the nature of the conic sections, EC will be to CA as CA to CL. And so by division, EC, CA to CA, CL, or EA to AL, and by composition, EA to EA plus AL or EL, as EC to EC plus CA or EB, and therefore, because of the similitude of the triangles EAF, ELI, ECH, EBG, AF is to LI as CH to BG. Likewise, from the nature of the conic sections, LI, or CK, is to CD as CD to CH, and therefore, X equal perturbate, AF is to CD as CD to BG. QED. Core 1. Hence if two tangents FG, PQ, meet two parallel tangents AF, BG in F and G, P and Q, and cut one the other in O, AF, X equal perturbate, will be to BQ as AP to BG, and by division, as FP to GQ, and therefore as FO to OG. Core 2. Whence also the two right lines PG, FQ drawn through the points P and G, F and Q, will meet in the right line ACB passing through the center of the figure and the points of contact A, B. Lemma 25. If four sides of a parallelogram indefinitely produced touch any conic section, and are cut by a fifth tangent, I say, that, taking those segments of any two conterminous sides that terminate in opposite angles of the parallelogram, either segment is to the side from which it is cut off as that part of the other conterminous side which is intercepted between the point of contact and the third side is to the other segment. Let the four sides ML, IK, KL, MI, of the parallelogram MLIK touch the F conic section in A, B, C, D, and let the fifth tangent FQ cut those sides in F, Q, H, and E. And taking the segments MI, KQ of the sides MI, KI, or the segments KH, MF of the sides KL, ML, I say, that MI is to MI as BK to KQ, and kh to kl as am to mf. 4. By core 1 of the preceding lemma, me is to ei as am or bk to bq. And, by composition, me is to mi as bk to kq. Qed. Also kh is to hl as bk or am to af, and by division, kh to kl as am to mf. Qed. Core 1. Hence if a parallelogram IKLM described about a given conic section is given, the rectangle KQME, as also the rectangle KHMF equal thereto, will be given. 4. By reason of the similar triangles KQH, MFE, those rectangles are equal. Core 2. And if a sixth tangent EQ is drawn meeting the tangents KI, MI in Q and E, the rectangle KQME will be equal to the rectangle KQME, and KQ will be to me as KQ to me, and by division as QQ to EE. Core 3. Hence, also, if EQ, EQ, are joined and bisected, and a right line is drawn through the points of bisection, this right line will pass through the center of the conic section. For since QQ is to EE as KQ to me, the same right line will pass through the middle of all the lines EQ, EQ, MK, by lem. XEI, and the middle point of the right line MK is the center of the section. Proposition 27. Problem 19. To describe a trajectory that may touch 5 right lines given by position. Supposing ABG, BCF, GCD, FDE, EA to be the tangents given by position. Bisect in M and N, AF, B, the diagonals of the quadrilateral figure ABFE contained under any 4 of them, and, by core 3, lem. XXV, the right line MN drawn through the points of bisection will pass through the center of the trajectory. Again, bisect in P and Q, the diagonals, if I may so call them, BD, GF of the quadrilateral figure BGDF contained under any other 4 tangents, and the right line PQ. Drawn through the points of bisection will pass through the center of the trajectory. And therefore the center will be given in the concourse of the bisecting lines. Suppose it to be O, parallel to any tangent BC. Draw KL at such distance that the center O may be placed in the middle between the parallels. This KL will touch the trajectory to be described. Let this cut any other 2 tangents GCD, FDE, in L and K. Through the points C and K, F and L, where the tangents not parallel, GL, FK meet the parallel tangents of, KL, draw OK, FL meeting in R. And the right line are drawn and produced, will cut the parallel tangent CF, KL, in the points of contact. This appears from core 2, lem. 24. And by the same method the other points of contact may be found, and then the trajectory may be described by Prop. 14. QEF. Scholium. Under the preceding propositions are comprehended those problems wherein either the centers or asymptotes of the trajectories are given. For when points and tangents in the center are given, as many other points and as many other tangents are given at an equal distance on the other side of the center. And an asymptote is to be considered as a tangent, and its infinitely remote extremity, if we may say so, is a point of contact. Conceive the point of contact of any tangent removed in infinitum, and the tangent will degenerate into an asymptote. And the constructions of the preceding problems will be changed into the constructions of those problems wherein the asymptote is given. After the trajectory is described, we may find its axes and foci in this manner. In the construction and figure of lem. XXI, let those legs BP, CP, of the movable angles PBN, PCN, by the concourse of which the trajectory was described, be made parallel one to the other, and retaining that position, let them revolve about their poles B, C, in that figure. In the meanwhile let the other legs CN, BN, of those angles, by their concourse K or K, describe the circle BKGC. Let O be the center of this circle. And from this center upon the ruler MN, wherein those legs CN, BN did concur while the trajectory was described, let fall the perpendicular OH meeting the circle in K and L. And when those other legs CK, BK meet in the point K that is nearest to the ruler, the first legs CP, BP will be parallel to the greater axis, and perpendicular on the lesser, and the contrary will happen if those legs meet in the remotest point L. Whence if the center of the trajectory is given, the axes will be given, and those being given, the foci will be readily found. But the squares of the axes are one to the other as kh to lh, and thence it is easy to describe a trajectory given in kind through 4 given points. For if 2 of the given points are made the poles C, B, the third will give the movable angles PCK, PBK, but those being given, the circle BGKC may be described. Then, because the trajectory is given in kind, the ratio of OH to OK, and therefore OH itself, will be given. About the center O, with the interval OH, describe another circle, and the right line that touches this circle, and passes through the concourse of the legs CK, BK, when the first legs CK, BP meet in the fourth given point, will be the ruler MN. By means of which the trajectory may be described. Whence also on the other hand a trapezium given in kind, excepting a few cases that are impossible, may be inscribed in a given conic section. There are also other lemmas, by the help of which trajectories given in kind may be described through given points, and touching given lines. Of such a sort is this, that if a right line is drawn through any point given by position, that may cut a given conic section in 2 points, and the distance of the intersections is bisected. The point of bisection will touch another conic section of the same kind with the former, and having its axis parallel to the axis of the former. But I hasten to things of greater use. Lemma 26. To place the 3 angles of a triangle, given both in kind and magnitude, in respect of as many rigid lines given by position, provided they are not all parallel among themselves, in such manner that the several angles may touch the several lines. 3 indefinite right lines AB, AC, BC, are given by position, and it is required so to place the triangle def that its angle D may touch the line AB, its angle E the line AC, and its angle F the line BC. Upon DE, DF, and EF, describe 3 segments of circles DRE, DGF, EMF, capable of angles equal to the angles BAC, ABC, ACB respectively. But those segments are to be described toward such sides of the lines DE, DF, EF, that the letters dread may turn round about in the same order with the letters BACB, the letters DGFD in the same order with the letters ABCA. And the letters EMFE in the same order with the letters ACBA, then, completing those segments into entire circles, let the 2 former circles cut one the other in G, and suppose P and Q, to be their centers. Then joining GP, PQ, take GA to AB as GP is to PQ, and about the center G, with the interval GA, describe a circle that may cut the first circle DGE in A, join add cutting the second circle DFG in B, as well as AE cutting the third circle EMF in C. Complete the figure ABCDEF similar and equal to the figure ABCDF, I say, the thing is done. For drawing FC meeting add in N, and joining AG, BG, QG, QD, PD, by construction the angle EAD is equal to the angle CAB, and the angle ACF equal to the angle ACB, and therefore the triangle ANC equiangular to the triangle ABC. Wherefore the angle ANC or FND is equal to the angle ABC, and consequently to the angle FBD, and therefore the point N falls on the point B. Moreover the angle GPQ, which is half the angle GPD at the center, is equal to the angle GAD at the circumference. And the angle GQP, which is half the angle GQD at the center, is equal to the complement to 2 right angles of the angle GBD at the circumference, and therefore equal to the angle GBA. Upon which account the triangles GPQ, GAB, are similar, and GA is to AB as GP to PQ, that is, by construction, as GA to AB. Wherefore AB and AB are equal. And consequently the triangles ABC, ABC, which we have now proved to be similar, are also equal. And therefore since the angles D, E, F, of the triangle DEF do respectively touch the sides of AC, BC of the triangle ABC, the figure ABCDEF may be completed similar and equal to the figure ABCDF, and by completing it the problem will be solved. QEF. Core. Hence a right line may be drawn whose parts given in length may be intercepted between three right lines given by position. Suppose the triangle DEF, by the access of its point D to the side EF, and by having the sides DE, DF placed in directum to be changed into a right line whose given part DE is to be interposed between the right lines AB, AC given by position. And its given part DF is to be interposed between the right lines AB, BC, given by position, then, by applying the preceding construction to this case, the problem will be solved. Proposition 28. Problem XX. To describe a trajectory given both in kind and magnitude, given parts of which shall be interposed between three right lines given by position. Suppose a trajectory is to be described that may be similar and equal to the curve line DEF, and may be cut by three right lines AB, AC, BC, given by position, into parts DE and EF, similar and equal to the given parts of this curve line. Draw the right lines DE, EP, DF, and place the angles D, E, F, of this triangle DEF, so as to touch those right lines given by position, by lem. XXVI, then about the triangle describe the trajectory, similar and equal to the curve DEF. QEF. Lemma 27. To describe a trapezium given in kind, the angles whereof may be so placed, in respect of four right lines given by position, that are neither all parallel among themselves, nor converge to one common point. That the several angles may touch the several lines. Let the four right lines ABC, AD, BD, CE, be given by position, the first cutting the second in A, the third in B, and the fourth in C. And suppose a trapezium FGHI is to be described that may be similar to the trapezium FGHI, and whose angle F, equal to the given angle F, may touch the right line ABC. And the other angles G, H, I, equal to the other given angles, G, H, I, may touch the other lines AD, BD, CE, respectively. Join FH, and upon FG, FH, FI describe as many segments of circles FSG, FTH, FVI, the first of which FSG may be capable of an angle equal to the angle BAD, the second FTH capable of an angle equal to the angle CBD. And the third FVI of an angle equal to the angle ACE. But the segments are to be described towards those sides of the lines FG, FH, FI, that the circular order of the letters FSGF may be the same as of the letters BADB. And that the letters FTHF may turn about in the same order as the letters CBDC and the letters FVIF in the game order as the letters ACA. Complete the segments into entire circles, and let P be the center of the first circle FSG, Q the center of the second FTH. Join and produce both ways the line PQ, and in it take QR in the same ratio to PQ as BC has to AB. But QR is to be taken towards that side of the point Q, that the order of the letters P, Q, R may be the same as of the letters A, B, C, and about the center R with the interval RF describe a fourth circle FNC cutting the third circle FVI in C. Join FC cutting the first circle in A, and the second in B, draw AG, BH, CI, and let the figure AB Kefki be made similar to the figure ABC FGHI, and the trapezium FGHI will be that which was required to be described. For let the two first circles FSG, FTH cut one the other in K, join PK, QK, RK, AK, BK, CK, and produce QP to L. The angles FAK, FBK, FCK at the circumferences are the halves of the angles FPK, FQK, FRK, at the centers, and therefore equal to LPK, LQK, LRK, the halves of those angles. Wherefore the figure PQRK is equiangular and similar to the figure ABCK, and consequently AB is to BC as PQ to QR, that is, as AB to BC. But by construction, the angles FAG, FBH, FCI, are equal to the angles FAG, FBH, FCI. And therefore the figure AB Kefki may be completed similar to the figure ABC FGHI. Which done a trapezium FGHI will be constructed similar to the trapezium FGHI, and which by its angles F, G, H, I will touch the right lines ABC, AD, BD, CE, QEF. Core. Hence a right line may be drawn whose parts intercepted in a given order, between four right lines given by position, shall have a given proportion among themselves. Let the angles FGH, GHI, be so far increased that the right lines FG, GH, HI, may lie in directum. And by constructing the problem in this case, a right line FGHI will be drawn, whose parts FG, GH, HI, intercepted between the four right lines given by position, AB in AD, AD in BD, BD in CE, will be one to another as the lines FG, GH, HI. And will observe the same order among themselves. But the same thing may be more readily done in this manner. Produce AB to K and BD to L, so as BK may be to AB as HI to GH, and DL to BD as GI to FG, and join KL meeting the right line CE in I, produce IL to M, so as LM may be to IL as GH to HI. Then draw MQ parallel to LB, and meeting the right line AD in G, and join GI cutting AB, BD in F, H, I say, the thing is done. For let MG cut the right line AB in Q, and AD the right line KL in S, and draw AP parallel to BD, and meeting IL in P, and GM to LH, GI to high, me to Li, GI to HI, AK to BK, and AP to BL, will be in the same ratio. Cut DL in R, so as DL to RL may be in that same ratio, and because GS to GM, AS to AP, and DS to DL are proportional, therefore, X equal, as GS to LH, so will as B to BL, and DS to RL, and mixedly, BL, RL to LH, BL, as, DS to GS, AS. That is, BR is to BH as AD is to AG, and therefore as BD to GQ. And alternately BR is to BD as BH to GQ, or as F to FG. But by construction the line BL was cut in D and R in the same ratio as the line FI in G and H. And therefore BR is to BD as FH to FG. Wherefore FH is to FG as FH to FG. Since, therefore, GI to high likewise is as me to Li, that is, as GI to HI, it is manifest that the lines FI, Phi, are similarly cut in G and H, G and H. QEF. In the construction of this corollary, after the line LK is drawn cutting CE in I, we may produce IE to V, so as EV may be to EI as FH to HI, and then draw VF parallel to BD. It will come to the same, if about the center I with an interval IH, we describe a circle cutting BD in X, and produce IX to Y so as IY may be equal to if, and then draw YF parallel to BD. Sir Christopher Wren and Dr. Wallace have long ago given other solutions of this problem. Proposition 29. Problem 21. To describe a trajectory given in kind, that may be cut by four right lines given by position, into parts given in order, kind, and proportion. Suppose a trajectory is to be described that may be similar to the curve line FGHI, and whose parts, similar and proportional to the parts FG, GH, HI of the other, may be intercepted between the right lines AB and AD, AD, and BD. BD and CE given by position, viz. The first between the first pair of those lines, the second between the second, and the third between the third. Draw the right lines FG, GH, HI, FI, and, by lem. XXV, describe a trapezium FGHI that may be similar to the trapezium FGHI, and whose angles F, G, H, I, may touch the right lines given by position AB, AD, BD, CE, severally according to their order. And then about this trapezium describe a trajectory, that trajectory will be similar to the curve line FGHI. Scholium. This problem may be likewise constructed in the following manner. Joining FG, GH, HI, FI, produce GF to V, and join FH, IG, and make the angles CAK, DL equal to the angles FGH, VFH. Let AK, AL meet the right line BD in K and L, and thence draw KM, LN, of which let KM make the angle AKM equal to the angle GHI, and be itself to AK as HI is to GH. And let LN make the angle ALN equal to the angle FHI, and be itself to AL as HI to FH. But AK, KM, AL, LN are to be drawn towards those sides of the lines AD, AK, AL, that the letters CAKMC, ALKA, DALND may be carried round in the same order as the letters FGHIF, and draw MN meeting the right line CE in I. Make the angle IEP equal to the angle IGF, and let PE be to EI as FG to GI, and through P draw PQF that may with the right line ADE contain an angle PQE equal to the angle FIG, and may meet the right line AB and F, and join Phi. But PE and PQ are to be drawn towards those sides of the line CE, PE, that the circular order of the letters PEIP and PEQP may be the same as of the letters FGHIF. And if upon the line Phi, in the same order of letters, and similar to the trapezium FGHI, a trapezium FGHI is constructed, and a trajectory given in kind is circumscribed about it, the problem will be solved. So far concerning the finding of the orbits. It remains that we determine the motions of bodies in the orbits so found. Section 6. How the motions are to be found in given orbits. Proposition XXX. Problem 22. To find at any assigned time the place of a body moving in a given parabolic trajectory. Let S be the focus, and A the principal vertex of the parabola. And suppose 4ASM equal to the parabolic area to be cut off APS, which either was described by the radius SP, since the body's departure from the vertex, or is to be described thereby before its arrival there. Now the quantity of that area to be cut off is known from the time which is proportional to it. Bisect AS in G, and erect the perpendicular GH equal to BM, and a circle described about the center H, with the interval HS, will cut the parabola in the place P required. For letting fall PO perpendicular on the axis, and drawing PH, there will be AG superscript 2 plus GH superscript 2, equals HP superscript 2 equals AO superscript 2 plus PO superscript 2, 2GAO plus 2GH plus PO plus AG superscript 2 plus GH superscript 2. Whence 2GHPO, equals AO superscript 2 plus PO superscript 2, 2GAO, equals AO superscript 2 plus 3/4 PO superscript 2. For AO superscript 2 write. Then dividing all the terms by 2PO, and multiplying them by 2AS, we shall have 4/3GHAS, equals 1/6AOPO plus 1/2 ASPO equals PO equals to the area APS. But GH was 3M, and therefore 4/3GHAS is 4ASM. Wherefore the area cut off APS is equal to the area that was to be cut off 4ASM. QED. Core 1. Hence GH is to AS as the time in which the body described the arc AP to the time in which the body described the arc between the vertex A and the perpendicular erected from the focus S upon the axis. Core 2. And supposing a circle ASP perpetually to pass through the moving body P, the velocity of the point H is to the velocity which the body had in the vertex A as 3/8. And therefore in the same ratio is the line GH to the right line which the body, in the time of its moving from A to P, would describe with that velocity which it had in the vertex A. Core 3. Hence, also, on the other hand, the time may be found in which the body has described any assigned arc AP join AP, and on its middle point erect a perpendicular meeting the right line GH in H. Lemma 28. There is no oval figure whose area, cut off by right lines at pleasure, can be universally found by means of equations of any number of finite terms and dimensions. Suppose that within the oval any point is given, about which as a pole a right line is perpetually revolving with an uniform motion. While in that right line a movable point going out from the pole moves always forward with a velocity proportional to the square of that right line within the oval. By this motion that point will describe a spiral with infinite circumgyrations. Now if a portion of the area of the oval cut off by that right line could be found by a finite equation, the distance of the point from the pole, which is proportional to this area, might be found by the same equation. And therefore all the points of the spiral might be found by a finite equation also. And therefore the intersection of a right line given in position with the spiral might also be found by a finite equation. But every right line infinitely produced cuts a spiral in an infinite number of points. And the equation by which any one intersection of two lines is found at the same time exhibits all their intersections by as many roots, and therefore rises to as many dimensions as there are intersections. Because two circles mutually cut one another in 2 points, one of those intersections is not to be found but by an equation of 2 dimensions, by which the other intersection may be also found. Because there may be 4 intersections of 2 conic sections, any one of them is not to be found universally, but by an equation of 4 dimensions, by which they may be all found together. For if those intersections are severally sought, because the law and condition of all is the same, the calculus will be the same in every case, and therefore the conclusion always the same. Which must therefore comprehend all those intersections at once within itself, and exhibit them all indifferently. Hence it is that the intersections of the conic scions with the curves of the third order, because they may amount to 6, come out together by equations of 6 dimensions. And the intersections of 2 curves of the third order, because they may amount to 9, come out together by equations of 9 dimensions. If this did not necessarily happen, we might reduce all solid to plane problems, and those higher than solid to solid problems. But here I speak of curves irreducible in power. For if the equation by which the curve is defined may be reduced to a lower power, the curve will not be one single curve, but composed of 2, or more, whose intersections may be severally found by different calculuses. After the same manner the 2 intersections of right lines with the conic sections come out always by equations of 2 dimensions. The 3 intersections of right lines with the irreducible curves of the third order by equations of 3 dimensions, the 4 intersections of right lines with the irreducible curves of the fourth order, by equations of 4 dimensions. And so on in infinitum. Wherefore the innumerable intersections of a right line with a spiral, since this is but one simple curve and not reducible to more curves, require equations infinite in number of dimensions and roots, by which they may be all exhibited together. For the law and calculus of all is the same. For if a perpendicular is let fall from the pole upon that intersecting right line, and that perpendicular together with the intersecting line revolves about the pole, the intersections of the spiral will mutually pass the one into the other. And that which was first or nearest, after 1 revolution, will be the second, after 2, the third. And so on, nor will the equation in the meantime be changed but as the magnitudes of those quantities are changed, by which the position of the intersecting line is determined. Wherefore since those quantities after every revolution return to their first magnitudes, the equation will return to its first form. And consequently one and the same equation will exhibit all the intersections, and will therefore have an infinite number of roots, by which they may be all exhibited. And therefore the intersection of a right line with a spiral cannot be universally found by any finite equation. And of consequence there is no oval figure whose area, cut off by right lines at pleasure, can be universally exhibited by any such equation. By the same argument, if the interval of the pole and point by which the spiral is described is taken proportional to that part of the perimeter of the oval which is cut off, it may be proved that the length of the perimeter cannot be universally exhibited by any finite equation. But here I speak of ovals that are not touched by conjugate figures running out in infinitum. Sure. Hence the area of an ellipsis, described by a radius drawn from the focus to the moving body, is not to be found from the time given by a finite equation, and therefore cannot be determined by the description of curves geometrically rational. Those curves I call geometrically rational, all the points whereof may be determined by lengths that are definable by equations, that is, by the complicated ratios of lengths. Other curves, such as spirals, quadratrixes, and cycloids, I call geometrically irrational. For the lengths which are or are not as number to number, according to the 10th book of Elements, are arithmetically rational or irrational. And therefore I cut off an area of an ellipsis proportional to the time in which it is described by a curve geometrically irrational, in the following manner. Proposition 31. Problem 23. To find the place of a body moving in a given elliptic trajectory at any assigned time. Suppose A to be the principal vertex, S the focus, and O the center of the ellipsis APB, and let P be the place of the body to be found. Produce OA to G so as OG may be to OA as OA to OS. Erect the perpendicular GH, and about the center O, with the interval OG, describe the circle GEF. And on the ruler GH, as a base, suppose the wheel GEF to move forwards, revolving about its axis, and in the meantime by its point A describing the cycloid ALI. Which done, take GK to the perimeter GFG of the wheel, in the ratio of the time in which the body proceeding from A described the arc AP, to the time of a whole revolution in the ellipsis. Erect the perpendicular KL meeting the cycloid in L. Then LP drawn parallel to KG will meet the ellipsis in P, the required place of the body. For about the center O with the interval OA describe the semicircle AQB, and let LP, produced, if need be, meet the arc AQ in Q, and join SQ, OQ. Let OQ meet the arc EFG in F, and upon OQ let fall the perpendicular SR. The area APS is as the area AQS, that is, as the difference between the sector OQA and the triangle OQS, or as the difference of the rectangles 1/2 OQAQ, and 1/2 OQSR, that is, because 1/2 OQ is given. As the difference between the arc AQ and the right line SR. And therefore, because of the equality of the given ratios SR to the sine of the arc AQ, OS to OA, OA to OG, AQ to GF, and by division AQ, SR to GF, sine of the arc AQ, as GK, the difference between the arc GF and the sine of the arc AQ. QED. Scholium. But since the description of this curve is difficult, a solution by approximation will be preferable. First, then, let there be found a certain angle B which may be to an angle of 57.29578 degrees, which an arc equal to the radius subtends, as SH, the distance of the foci, to AB, the diameter of the ellipsis. Secondly, a certain length L, which may be to the radius in the same ratio inversely. And these being found, the problem may be solved by the following analysis. By any construction, or even by conjecture, suppose we know P the place of the body near its true place P. Then letting fall on the axis of the ellipsis the ordinate PR from the proportion of the diameters of the ellipsis, the ordinate RQ of the circumscribed circle AQB will be given. Which ordinate is the sine of the angle AOQ, supposing AO to be the radius, and also cuts the ellipsis in P. It will be sufficient if that angle is found by a rude calculus in numbers near the truth. Suppose we also know the angle proportional to the time, that is, which is to 4 right angles as the time in which the body described the arc AP, to the time of 1 revolution in the ellipsis. Let this angle be n. Then take an angle D, which may be to the angle B as the sine of the angle AOQ to the radius. And an angle E which may be to the angle N, AOQ plus D as the length L to the same length L diminished by the cosine of the angle AOQ, when that angle is less than a right angle, or increased thereby when greater. In the next place, take an angle F that may be to the angle B as the sine of the angle AOQ plus E to the radius, and an angle G that may be to the angle N, AOQ, E plus F as the length L to the same length L diminished by the cosine of the angle AOQ plus E, when that angle is less than a right angle, or increased thereby when greater. For the third time take an angle H, that may be to the angle B as the sine of the angle AOQ plus E plus G to the radius. And an angle I to the angle N, AOQ, E, G plus H, as the length L is to the same length L diminished by the cosine of the angle AOQ plus E plus G, when that angle is less than a right angle, or increased thereby when greater. And so we may proceed in infinitum. Lastly, take the angle AOQ equal to the angle AOQ plus E plus G plus I plus, and from its cosine or and the ordinate PR, which is to its sine QR as the lesser axis of the ellipsis to the greater, we shall have P the correct place of the body. When the angle N, AOQ plus D happens to be negative, the sine plus of the angle E must be everywhere changed into dash, and the sine, into plus. And the same thing is to be understood of the sines of the angles G and I, when the angles N, AOQ, E plus F, and N, AOQ, E, G plus H come out negative. But the infinite series AOQ plus E plus G plus I plus, and converges so very fast, that it will be scarcely ever needful to proceed beyond the second term E. And the calculus is founded upon this theorem, that the area APS is as the difference between the arc AQ and the right line let fall from the focus S perpendicularly upon the radius OQ. And by a calculus not unlike, the problem is solved in the hyperbola. Let its center be O, its vertex A, its focus S, and asymptote OK, and suppose the quantity of the area to be cut off is known, as being proportional to the time. Let that be A, and by conjecture suppose we know the position of a right line SP, that cuts off an area APS near the truth. Join OP, and from A and P to the asymptote draw AI, PK parallel to the other asymptote. And by the table of logarithms the area AIKP will be given, and equal thereto the area OPA, which subducted from the triangle OPS, will leave the area cut off APS. And by applying 2 APS, SA, or 2A, SAPS, the double difference of the area A that was to be cut off, and the area APS that is cut off, to the line SN that is let fall from the focus S, perpendicular upon the tangent TP. We shall have the length of the chord PQ. Which chord PQ is to be inscribed between A and P, if the area APS that is cut off be greater than the area A that was to be cut off, but towards the contrary side of the point P. If otherwise, and the point Q will be the place of the body more accurately. And by repeating the computation the place may be found perpetually to greater and greater accuracy. And by such computations we have a general analytical resolution of the problem. But the particular calculus that follows is better fitted for astronomical purposes. Supposing AO, OB, OD to be the semi-axis of the ellipsis, and L its lattice rectum, and D the difference betwixt the lesser semi-axis OD, and 1/2 L the half of the lattice rectum, let an angle Y be found, whose sine may be to the radius as the rectangle under that difference D, and AO plus OD the half sum of the axes to the square of the greater axis AB. Find also an angle Z, whose sine may be to the radius as the double rectangle under the distance of the foci SH and that difference D to triple the square of half the greater semi-axis AO. Those angles being once found, the place of the body may be thus determined. Take the angle T proportional to the time in which the arc BP was described, or equal to what is called the mean motion. And an angle V the first equation of the mean motion to the angle Y, the greatest first equation, as the sine of double the angle T is to the radius. And an angle X, the second equation, to the angle Z, the second greatest equation, as the cube of the sine of the angle T is to the cube of the radius. Then take the angle BHP the mean motion equated equal to T plus X plus V, the sum of the angles T, V, X, if the angle T is less than a right angle. Or equal to T plus X, V, the difference of the same, if that angle T is greater than 1 and less than 2 right angles, and if HP meets the ellipsis in P, draw SP, and it will cut off the area BSP nearly proportional to the time. This practice seems to be expeditious enough, because the angles V and X, taken in second minutes, if you please, being very small, it will be sufficient to find 2 or 3 of their first figures. But it is likewise sufficiently accurate to answer to the theory of the planet's motions. For even in the orbit of Mars, where the greatest equation of the center amounts to 10 degrees, the error will scarcely exceed 1 second. But when the angle of the mean motion equated BHP is found, the angle of the true motion BSP, and the distance SP, are readily had by the known methods. And so far concerning the motion of bodies in curved lines. But it may also come to pass that a moving body shall ascend or descend in a right line, and I shall now go on to explain what belongs to such kind of motions. Section 7. Concerning the rectilinear ascent and descent of bodies. Proposition 32. Problem 24. Supposing that the centripetal force is reciprocally proportional to the square of the distance of the places from the center. It is required to define the spaces which a body, falling directly, describes in given times. Case 1. If the body does not fall perpendicularly, it will, by Core 1 Prop. 13, describe some conic section whose focus is A placed in the center of force. Suppose that conic section to be ARPB and its focus S. And, first, if the figure be an ellipsis, upon the greater axis thereof AB describe the semicircle ADB, and let the right line DPC pass through the falling body, making right angles with the axis. And drawing DS, PS, the area ASD will be proportional to the area ASP, and therefore also to the time. The axis AB still remaining the same, let the breadth of the ellipsis be perpetually diminished, and the area ASD will always remain proportional to the time. Suppose that breadth to be diminished in infinitum. And the orbit APB in that case coinciding with the axis AB, and the focus S with the extreme point of the axis B, the body will descend in the right line AC, and the area ABD will become proportional to the time. Wherefore the space AC will be given which the body describes in a given time by its perpendicular fall from the place A, if the area ABD is taken proportional to the time. And from the point D the right line DC is let fall perpendicularly on the right line AB. QEI. Case 2. If the figure RPB is an hyperbola, on the same principal diameter AB describe the rectangular hyperbola bed. And because the areas CSP, CBFP, SPFB, are severally to the several areas CSD, CBED, SDB, in the given ratio of the height CP, CD, and the area SPFB is proportional to the time in which the body P will move through the arc PFB. The area SDB will be also proportional to that time. Let the latus rectum of the hyperbola RPB be diminished in infinitum, the latus transversum remaining the same. And the arc PB will come to coincide with the right line CB, and the focus S, with the vertex B, and the right line SD with the right line BD. And therefore the area BDEB will be proportional to the time in which the body C, by its perpendicular descent, describes the line CB. QEI. Case 3. And by the like argument, if the figure RPB is a parabola, and to the same principal vertex be another parabola bed is described, that may always remain given while the former parabola in whose perimeter the body P moves, by having its latus rectum diminished and reduced to nothing, comes to coincide with the line CB, the parabolic segment BDEB will be proportional to the time in which that body P or C will descend to the center S or B. QEI. Proposition 33. Theorem 9. The things above found being supposed. I say, that the velocity of a falling body in any place C is to the velocity of a body, describing a circle about the center B at the distance BC, in the subduplicate ratio of AC. The distance of the body from the remoter vertex A of the circle or rectangular hyperbola, to 1/2 AB, the principal semi-diameter of the figure. Let AB, the common diameter of both figures RPB, DB, be bisected in O, and draw the right line PT that may touch the figure RPB in P, and likewise cut that common diameter AB, produced, if need be, in T. And let SY be perpendicular to this line, and BQ to this diameter, and suppose the latus rectum of the figure RPB to be L. From Core 9, Prop. 16, it is manifest that the velocity of a body, moving in the line RPB about the center S, in any place P, is to the velocity of a body describing a circle about the same center, at the distance SP. In the subduplicate ratio of the rectangle 1/2 LSP to SY superscript 2. For by the properties of the conic sections ACB is to CP superscript 2 as 2AO to L, and therefore is equal to L. Therefore those velocities are to each other in the subduplicate ratio of to SY superscript 2. Moreover, by the properties of the conic sections, CO is to BO as BO to 2, and, by composition or division, as CB to BT, whence, by division or composition, BO, or plus CO will be to BO as CT to BT, that is, AC will be to AO as CP to BQ. And therefore is equal to. Now suppose Cp, the breadth of the figure RPB, to be diminished in infinitum, so as the point P may come to coincide with the point C, and the point S with the point B, and the line SP with the line BC, and the line SY with the line BQ. And the velocity of the body now descending perpendicularly in the line CB will be to the velocity of a body describing a circle about the center B, at the distance BC. In the subduplicate ratio of to SY superscript 2, that is, neglecting the ratios of equality of SP to BC, and BQ superscript 2 to SY superscript 2, in the subduplicate ratio of AC to AO, or 1/2 AB. QED. Core 1. When the points B and S come to coincide, TC will become to TS as AC to AO. Core 2. A body revolving in any circle at a given distance from the center, by its motion converted upwards, will ascend to double its distance from the center. Proposition 34. Theorem X. If the figure bed is a parabola, I say, that the velocity of a falling body in any place C is equal to the velocity by which a body may uniformly describe a circle about the center B at half the interval BC. 4. By Core 7, Prop. 16, the velocity of a body describing a parabola RPB about the center S, in any place P, is equal to the velocity of a body uniformly describing a circle about the same center S at half the interval SP. Let the breadth CP of the parabola be diminished in infinitum, so as the parabolic arc PFB may come to coincide with the right line CB, the center S with the vertex B, and the interval SP with the interval BC, and the proposition will be manifest. QED. Proposition 35. Theorem 11. The same thing supposed, I say, that the area of the figure DES, described by the indefinite radius SD, is equal to the area which a body with a radius equal to half the lattice rectum of the figure DES, by uniformly revolving about the center S, may describe in the same time. For suppose a body C in the smallest moment of time describes in falling the infinitely little line CC, while another body K, uniformly revolving about the center S in the circle OK, describes the arc KK. Erect the perpendicular CD, meeting the figure DES in D, join SD, SK, and draw DD meeting the axis AS in T, and thereon let fall the perpendicular SY. Case 1. If the figure DES is a circle, or a rectangular hyperbola, bisect its transverse diameter AS in O, and so will be half the lattice rectum. And because TC is to TD as CC to DD, and TD to TS as CD to SY, X equal TC will be to TS as CD CC to SY DD. But, by Core 1, Prop. 33, TC is to TS as AC to AO, to wit, if in the coalescence of the points D, the ultimate ratios of the lines are taken. Wherefore AC is to AO or SK as CD CC to SY DD. Farther, the velocity of the descending body in C is to the velocity of a body describing a circle about the center S, at the interval SC, in the subduplicate ratio of AC to AO or SK, by Prop. 33. And this velocity is to the velocity of a body describing the circle OK in the subduplicate ratio of SK to SC, by Core 6, Prop 4. And, X equal, the first velocity to the last, that is, the little line CC to the arc KK, in the subduplicate ratio of AC to SC, that is, in the ratio of AC to CD. Wherefore CD CC is equal to AC KK, and consequently AC to SK as AC KK to SY DD, and thence SK KK equal to SY DD, and 1/2 SKKK equal to 1/2 SYDD, that is, the area K equal to the area SDD. Therefore in every moment of time two equal particles, KSK and SDD, of areas are generated, which, if their magnitude is diminished, and their number increased in infinitum, obtain the ratio of equality, and consequently, by Corlem. For, the whole areas together generated are always equal. QED. Case 2. But if the figure DES is a parabola, we shall find, as above, CDCC to SYDD as TC to TS, that is, as 2 to 1, and that therefore 1/4 CDCC is equal to 1/2 SYDD. But the velocity of the falling body in C is equal to the velocity with which a circle may be uniformly described at the interval 1/2 SC, by Prop. 34. And this velocity to the velocity with which a circle may be described with the radius SK, that is, the little line CC to the arc KK, is, by Cor 6, Prop. 4, in the subduplicate ratio of SK to 1/2 SC, that is, in the ratio of SK to 1/2 CD. Wherefore 1/2 SKKK is equal to 1/4 CDCC, and therefore equal to 1/2 SYDD, that is, the area KSK is equal to the area SDD, as above. QED. Proposition 36. Problem 25. To determine the times of the descent of a body falling from place A. Upon the diameter AS, the distance of the body from the center at the beginning, describe the semicircle ADS, as likewise the semicircle OKH equal thereto, about the center S. From any place C of the body erect the ordinate CD. Join SD, and make the sector OSK equal to the area ASD. It is evident, by Prop. XXXV, that the body in falling will describe the space AC in the same time in which another body, uniformly revolving about the center S, may describe the arc OK. QE. F. Proposition 37. Problem 26. To define the times of the ascent or descent of a body projected upwards or downwards from a given place. Suppose the body to go off from the given place G, in the direction of the line GS, with any velocity. In the duplicate ratio of this velocity to the uniform velocity in a circle, with which the body may revolve about the center S at the given interval SG, take GA to 1/2 AS. If that ratio is the same as of the number 2 to 1, the point A is infinitely remote, in which case a parabola is to be described with any latus rectum to the vertex S, and axis SG, as appears by Prop. 34. But if that ratio is less or greater than the ratio of 2 to 1, in the former case a circle, in the latter a rectangular hyperbola, is to be described on the diameter SA, as appears by Prop. 33. Then about the center S, with an interval equal to half the latus rectum, describe the circle HKK. And at the place G of the ascending or descending body, and at any other place C, erect the perpendiculars GI, CD, meeting the conic section or circle in I and D. Then joining SI, SD, let the sectors HSK, HSK be made equal to the segment Cs, SEDS. And, by Prop. XXXV, the body G will describe the space GC in the same time in which the body K may describe the arc KK. QEF. Proposition 38. Theorem 12. Supposing that the centripetal force is proportional to the altitude or distance of places from the center. I say, that the times and velocities of falling bodies, and the spaces which they describe, are respectively proportional to the arcs, and the right and versed signs of the arcs. Suppose the body to fall from any place A in the right line AS. And about the center of force S, with the interval AS, describe the quadrant of a circle AE, and let CD be the right sign of any arc AD. And the body A will in the time AD in falling describe the space AC, and in the place C will acquire the velocity CD. This is demonstrated the same way from Prop. X, as Prop. XXXII was demonstrated from Prop. 11. Core 1. Hence the times are equal in which one body falling from the place A arrives at the center S, and another body revolving describes the quadrantal arc ADE. Core 2. Wherefore all the times are equal in which bodies falling from whatsoever places arrive at the center. For all the periodic times of revolving bodies are equal, by Core 3, Prop. 4. Proposition 39. Problem 27. Supposing a centripetal force of any kind, and granting the quadratures of curvilinear figures, it is required to find the velocity of a body, ascending or descending in a right line, in the several places through which it passes. As also the time in which it will arrive at any place, and vice versa. Suppose the body E to fall from any place A in the right line ADC. And from its place E imagine a perpendicular EG always erected proportional to the centripetal force in that place tending to the center C, and let BFG be a curved line, the locus of the point G. And in the beginning of the motion suppose EG to coincide with the perpendicular AB, and the velocity of the body in any place E will be as a right line whose square is equal to the curvilinear area ABGE. QEI. In EG take EM reciprocally proportional to a right line whose square is equal to the area ABGE, and let VLM be a curved line wherein the point M is always placed, and to which the right line AB produced is an asymptote. And the time in which the body in falling describes the line AE, will be as the curvilinear area ABTVME. QEI. For in the right line AE let there be taken the very small line DE of a given length, and let DLF be the place of the line EMG, when the body was in D. And if the centripetal force be such, that a right line, whose square is equal to the area ABGE, is as the velocity of the descending body, the area itself will be as the square of that velocity. That is, if for the velocities in D and E we write V in V plus I, the area ABFD will be as VV, and the area ABGE as VV plus 2 6 plus 2, and by division, the area DFGE as 2 6 plus 2, and therefore will be as. That is, if we take the first ratios of those quantities when just nascent, the length dF is as the quantity, and therefore also as half that quantity. But the time in which the body in falling describes the verve small line dE, is as that line directly and the velocity v inversely, and the force will be as the increment I of the velocity directly and the time inversely. And therefore if we take the first ratios when those quantities are just nascent, as, that is, as the length dF. Therefore a force proportional to dF or Eg will cause the body to descend with a velocity that is as the right line whose square is equal to the area ABGE. QED. Moreover, since the time in which a very small line dE of a given length may be described is as the velocity inversely, and therefore also inversely as a right line whose square is equal to the area ABFD. And since the line DL, and by consequence the nascent area DLME, will be as the same right line inversely, the time will be as the area DLME, and the sum of all the times will be as the sum of all the areas, that is, by Core Lem. For, the whole time in which the line AE is described will be as the whole area ATVME. QED. Core 1. Let P be the place from whence a body ought to fall, so as that, when urged by any known uniform centripetal force, such as gravity is vulgarly supposed to be, it may acquire in the place D a velocity equal to the velocity which another body, falling by any force whatever, hath acquired in that place D. In the perpendicular DF let there be taken dr, which may be to DF as that uniform force to the other force in the place D. Complete the rectangle PDRQ, and cut off the area ABFD equal to that rectangle. Then A will be the place from whence the other body fell. For completing the rectangle DRSE, since the area ABFD is to the area DFGE as VV to 2 6, and therefore as 1/2 V to I, that is, as half the whole velocity to the increment of the velocity of the body falling by the unequable force. And in like manner the area PQRD to the area DRSE as half the whole velocity to the increment of the velocity of the body falling by the uniform force. And since those increments, by reason of the equality of the nascent times, are as the generating forces, that is, as the ordinates df, dr, and consequently as the nascent areas dfge, drc, therefore, x equal, the whole areas abfd. PQRD will be to one another as the halves of the whole velocities. And therefore, because the velocities are equal, they become equal also. Core 2. Whence if any body be projected either upwards or downwards with a given velocity from any place d, and there be given the law of centripetal force acting on it, its velocity will be found in any other place, as e, by erecting the ordinate eg. And taking that velocity to the velocity in the place d as a right line whose square is equal to the rectangle PQRD, either increased by the curvilinear area d phage, if the place east is below the place d, or diminished by the same area d phage. If it be higher, is to the right line whose square is equal to the rectangle PQRD alone. Core 3. The time is also known by erecting the ordinate m reciprocally proportional to the square root of PQRD plus or d phage. And taking the time in which the body has described the line d to the time in which another body has fallen with an uniform force from P, and in falling arrived at d in the proportion of the curvilinear area dlme to the rectangle 2pd/dl. For the time in which a body falling with an uniform force hath described the line PD, is to the time in which the same body has described the line PE in the subduplicate ratio of PD to PE. That is, the very small line DE being just nascent, in the ratio of PD to PD plus 1/2 DE, or 2PD to 2PD plus DE, and, by division, to the time in which the body hath described the small line DE, as 2PD to DE. And therefore as the rectangle 2PD/dl to the area dlme. And the time in which both the bodies describe the very small line dE is to the time in which the body moving unequably hath described the line d as the area dlme to the area dlme. And, x equal, the first mentioned of these times is to the last as the rectangle 2PD/dl to the area dlme. Section 8. Of the invention of orbits wherein bodies will revolve, being acted upon by any sort of centripetal force. Proposition XL. Theorem 13. If a body, acted upon by any centripetal force, is anyhow moved, and another body ascends or descends in a right line, and their velocities be equal in any one case of equal altitudes, their velocities will be also equal at all equal altitudes. Let a body descend from A through D and E, to the center C, and let another body move from V in the curved line VIKK. From the center C, with any distances, describe the concentric circles DI, EK, meeting the right line AC in D and E, and the curve VIK in I and K, draw IC meeting KE in N, and on IK let fall the perpendicular NT. And let the interval DE or IN between the circumferences of the circles be very small, and imagine the bodies in D and I to have equal velocities. Then because the distances CD and CI are equal, the centripetal forces in D and I will be also equal. Let those forces be expressed by the equal lineally DE and IN, and let the force IN, by core 2 of the laws of motion, be resolved into two others, NT and IT. Then the force NT acting in the direction of the line NT perpendicular to the path ITK of the body will not at all affect or change the velocity of the body in that path, but only draw it aside from a rectilinear course. And make it deflect perpetually from the tangent of the orbit, and proceed in the curvilinear path ITKK. That whole force, therefore, will be spent in producing this effect. But the other force IT, acting in the direction of the course of the body, will be all employed in accelerating it, and in the least given time will produce an acceleration proportional to itself. Therefore the accelerations of the bodies in D and I, produced in equal times, are as the lines DE, IT, if we take the first ratios of the nascent lines DE, IN, IK, IT, NT, and in unequal times as those lines and the times conjunctly. But the times in which DE and IK are described, are, by reason of the equal velocities, in D and I, as the spaces describe DE and IK, and therefore the accelerations in the course of the bodies through the lines DE and IK are as DE and IT. And DE and IK conjunctly. That is, as the square of dE to the rectangle IT into IK. But the rectangle IK is equal to the square of IN, that is, equal to the square of dE. And therefore the accelerations generated in the passage of the bodies from D and I to E and K are equal. Therefore the velocities of the bodies in E and K are also equal, and by the same reasoning they will always be found equal in any subsequent equal distances. QED. By the same reasoning, bodies of equal velocities and equal distances from the center will be equally retarded in their ascent to equal distances. QED. Core 1. Therefore if a body either oscillates by hanging to a string, or by any polished and perfectly smooth impediment is forced to move in a curved line, and another body ascends or descends in a right line, and their velocities be equal at any one equal altitude, their velocities will be also equal at all other equal altitudes. For by the string of the pendulous body, or by the impediment of a vessel perfectly smooth, the same thing will be effected as by the transverse force Nt. The body is neither accelerated nor retarded by it, but only is obliged to leave its rectilinear course. Core 2. Suppose the quantity p to be the greatest distance from the center to which a body can ascend, whether it be oscillating, or revolving in a trajectory. And so the same projected upwards from any point of a trajectory with the velocity it has in that point. Let the quantity a be the distance of the body from the center in any other point of the orbit, and let the centripetal force be always as the power n(1) of the quantity a, the index of which power n(1) is any number n diminished by unity. Then the velocity in every altitude a will be as and therefore will be given. For by prop. XXXAX, the velocity of a body ascending and descending in a right line is in that very ratio. Proposition XLI. Problem 28. Supposing a centripetal force of any kind, and granting the quadratures of curvilinear figures, it is required to find as well the trajectories in which bodies will move, as the times of their motions in the trajectories found. Let any centripetal force tend to the center C, and let it be required to find the trajectory VIKK. Let there be given the circle VR, described from the center C with any interval CV. And from the same center describe any other circles ID, KE cutting the trajectory in I and K, and the right line CV in D and E. Then draw the right line CNX cutting the circles KE, VR in N and X, and the right line CKY meeting the circle VR in Y. Let the points I and K be indefinitely near, and let the body go on from V through I and K to K. And let the point A be the place from whence another body is to fall, so as in the place D to acquire a velocity equal to the velocity of the first body in I. And things remaining as in prop. XXXAX, the line OLA IK, described in the least given time will be as the velocity, and therefore as the right line whose square is equal to the area ABFD, and the triangle ICK proportional to the time will be given. And therefore Kn will be reciprocally as the altitude IC. That is, if there be given any quantity q, and the altitude IC be called A, as this quantity call Z, and suppose the magnitude of q to be such that in some case may be to Z as IK to Kn, and then in all cases will be to Z as IK to Kn, and ABFD to ZZ as IK superscript 2 to Kn superscript 2, and by division ABFD, ZZ to ZZ as IN superscript 2 to Kn superscript 2. And therefore to Z. Or as IN to Kn, and therefore a Kn will be equal to. Therefore since YXXC is to a Kn as Cx superscript 2, to AA, the rectangle XYXC will be equal to. Therefore in the perpendicular DF let there be taken continually DB, DC equal to, respectively, and let the curved line SAB, AC, the foci of the points B and C, be described, and from the point V let the perpendicular VA be erected to the line AC. Cutting off the curvilinear areas VDBA, VDCA, and let the ordinates EZ, X, be erected also. Then because the rectangle DBIN or DBZE is equal to half the rectangle AKN, or to the triangle ICK, and the rectangle DCIN or DCXE is equal to half the rectangle YXXC, or to the triangle XCY. That is, because the nascent particles dBze, ick of the areas vdBa, vic are always equal, and the nascent particles dcxe, xcy of the areas vdca, vcx are always equal, therefore the generated area v-ball be equal to the generated area vic, and therefore proportional to the time. And the generated area vdca is equal to the generated sector vcx. If, therefore, any time be given during which the body has been moving from v, there will be also given the area proportional to it vdBa. And thence will be given the altitude of the body CD or CI, and the area VDCA, and the sector VCX equal thereto, together with its angle VCI. But the angle VCI, and the altitude CI being given, there is also given the place I, in which the body will be found at the end of that time. QEI. Core 1. Hence the greatest and least altitudes of the bodies, that is, the apsides of the trajectories, may be found very readily. For the apsides are those points in which a right line IC drawn through the center falls perpendicularly upon the trajectory VIK, which comes to pass when the right lines IK and NK become equal, that is, when the area ABFD is equal to ZZ. Core 2. So also the angle KIN, in which the trajectory at any place cuts the line IC, may be readily found by the given altitude IC of the body, to wit, by making the sign of that angle to radius as Kn to Ik, that is, as Z to the square root of the area ABFD. Core 3. If to the center C, and the principal vertex V, there be described a conic section VRS, and from any point thereof, as R, there be drawn the tangent RT meeting the axis CV indefinitely produced in the point T. And then joining CR there be drawn the right line CP, equal to the abscissa CT, making an angle VCP proportional to the sector VCR. And if a centripetal force, reciprocally proportional to the cubes of the distances of the places from the center, tends to the center C. And from the place V there sets out a body with a just velocity in the direction of a line perpendicular to the right line CV, that body will proceed in a trajectory VPQ, which the point P will always touch. And therefore if the conic section VRS be an hyperbola, the body will descend to the center, but if it be an ellipsis, it will ascend perpetually, and go farther and farther off in infinitum. And, on the contrary, if a body endued with any velocity goes off from the place V, and according as it begins either to descend obliquely to the center, or ascends obliquely from it, the figure VRS be either an hyperbola or an ellipsis. The trajectory may be found by increasing or diminishing the angle VCP in a given ratio. And the centripetal force becoming centrifugal, the body will ascend obliquely in the trajectory VPQ, which is found by taking the angle VCP proportional to the elliptic sector VRC, and the length CP equal to the length CT, as before. All these things follow from the foregoing proposition, by the quadrature of a certain curve, the invention of which, as being easy enough, for brevity's sake I omit. Proposition 42. Problem 29. The law of centripetal force being given, it is required to find the motion of a body setting out from a given place, with a given velocity, in the direction of a given right line. Suppose the same things as in the three preceding propositions. And let the body go off from the place I in the direction of the little line, Ik, with the same velocity as another body, by falling with an uniform centripetal force from the place P, may acquire in D. And let this uniform force be to the force with which the body is at first urged in I, as dr to df. Let the body go on towards K. And about the center C, with the interval Ck, describe the circle Q, meeting the right line PD and E, and let there be erected the lines EG, EV, EW, ordinately applied to the curves BFG, ABV, AC. From the given rectangle PDRQ and the given law of centripetal force, by which the first body is acted on, the curve line BFG is also given, by the construction of prop. XXV, and its core 1. Then from the given angle CIK is given the proportion of the nascent lines IK, KN, and thence, by the construction of prob Atenei, there is given the quantity Q, with the curve lines ABV, AC. And therefore, at the end of any time div, there is given both the altitude of the body SU or CK, and the area Q, with the sector equal to it XC, the angle IC, and the place K, in which the body will then be found. QEI. We suppose in these propositions the centripetal force to vary in its recess from the center according to some law, which any one may imagine at pleasure, but at equal distances from the center to be everywhere the same. I have hitherto considered the motions of bodies in immovable orbits. It remains now to add something concerning their motions in orbits which revolve round the centers of force. Section 9. Of the motion of bodies in movable orbits, and of the motion of the apsides. Proposition 43. Problem XXX. It is required to make a body move in a trajectory that revolves about the center of force in the same manner as another body in the same trajectory at rest. In the orbit VPK, given by position, let the body P revolve, proceeding from V towards K. From the center C let there be continually drawn CP, equal to CP, making the angle VCP proportional to the angle VCP. And the area which the line CP describes will be to the area VCP, which the line CP describes at the same time, as the velocity of the describing line CP to the velocity of the describing line CP. That is, as the angle VCP to the angle VCP, therefore in a given ratio, and therefore proportional to the time. Since, then, the area described by the line CP in an immovable plane is proportional to the time, it is manifest that a body, being acted upon by a just quantity of centripetal force may revolve with the point P in the curved line which the same point P, by the method just now explained, may be made to describe an immovable plane. Make the angle VCU equal to the angle PCP, and the line CU equal to CV, and the figure UCP equal to the figure VCP, and the body being always in the point P, will move in the perimeter of the revolving figure UCP. And will describe its, revolving, arc up in the same time that the other body P describes the similar and equal arc VP in the quiescent figure VPK. Find, then, by Core 5, Prop. 6, the centripetal force by which the body may be made to revolve in the curved line which the point P describes in an immovable plane, and the problem will be solved. QEF. Proposition 44. Theorem 14. The difference of the forces, by which two bodies may be made to move equally, one in a quiescent, the other in the same orbit revolving, is in a triplicate ratio of their common altitudes inversely. Let the parts of the quiescent orbit Vp, pk be similar and equal to the parts of the revolving orbit up, pk, and let the distance of the points p and k be supposed of the utmost smallness. Let fall a perpendicular kr from the point k to the right line pc, and produce it to m, so that Mr. may be to kr as the angle VCP to the angle VCP. Because the altitudes of the bodies PC and PC, KC and KC, are always equal, it is manifest that the increments or decrements of the lines PC and PC are always equal. And therefore if each of the several motions of the bodies in the places P and P be resolved into two, by Cr. Two of the laws of motion, one of which is directed towards the center, or according to the lines PC, PC, and the other, transverse to the former, hath a direction perpendicular to the lines PC and PC. The motions towards the center will be equal, and the transverse motion of the body P will be to the transverse motion of the body P as the angular motion of the line PC to the angular motion of the line PC. That is, as the angle VCP to the angle VCP. Therefore, at the same time that the body P, by both its motions, comes to the point K, the body P, having an equal motion towards the center, will be equally moved from P towards C. And therefore that time being expired, it will be found somewhere in the line MKR, which, passing through the point K, is perpendicular to the line PC. And by its transverse motion will acquire a distance from the line C, that will be to the distance which the other body P acquires from the line PC as the transverse motion of the body P to the transverse motion of the other body P. Therefore since Kr is equal to the distance which the body P acquires from the line PC, and Mr. is to Kr as the angle VCP to the angle VCP, that is, as the transverse motion of the body P to the transverse motion of the body P. It is manifest that the body, at the expiration of that time, will be found in the place M. These things will be so, if the bodies P and P are equally moved in the directions of the lines PC and PC, and are therefore urged with equal forces in those directions. But if we take an angle PCN that is to the angle PCK as the angle VCP to the angle VCP, and NCB equal to KC, in that case the body P at the expiration of the time will really be in N. And is therefore urged with a greater force than the body P, if the angle NCP is greater than the angle KCP, that is, if the orbit up move either in consequentia or in antecedentia. With a celerity greater than the double of that with which the line CP moves in consequentia. And with a less force if the orbit moves slower in antecedentia. And the difference of the forces will be as the interval Mn of the places through which the body would be carried by the action of that difference in that given space of time. About the center C with the interval Cn or Ck, suppose a circle described cutting the lines Mr. Mn produced in S and T, and the rectangle MNMT will be equal to the rectangle MKMS, and therefore Mn will be equal to. But since the triangles PCK, PCN, in a given time, are of a given magnitude, Kr and Mr., and their difference Mk, and their sum Ms, are reciprocally as the altitude PC. And therefore the rectangle MKMS is reciprocally as the square of the altitude PC. But, moreover, Mt is directly as half a metric ton, that is, as the altitude PC. These are the first ratios of the nascent lines, and hence, that is, the nascent linola Mn, and the difference of the forces proportional thereto, are reciprocally as the cube of the altitude PC. QED. Core 1. Hence the difference of the forces in the places P and P, or K and K, is to the force with which a body may revolve with a circular motion from arc to K, in the same time that the body P in an immovable orb describes the arc PK. As the nascent line Mn to the versed sine of the nascent arc Rk, that is, as to, or as MKMS to the square of Rk. That is, if we take given quantities f and g in the same ratio to one another as the angle VCP bears to the angle VCP, as GG, FF to FF. And, therefore, if from the center C, with any distance CP or CP, there be described a circular sector equal to the whole area VPC, which the body revolving in an immovable orbit has by a radius drawn to the center described in any certain time. The difference of the forces, with which the body P revolves in an immovable orbit, and the body P in a movable orbit, will be to the centripetal force. With which another body by a radius drawn to the center can uniformly describe that sector in the same time as the area VPC is described, as GG, FF to FF. For that sector and the area PCK are to one another as the times in which they are described. Core 2. If the orbit VPK be an ellipsis, having its focus C, and its highest apsis V, and we suppose that the ellipsis up similar and equal to it, so that PC may be always equal to PC, and the angle VCP be to the angle VCP in the given ratio of G to F. And for the altitude PC or PC we put A, and 2 R for the latus rectum of the ellipsis, the force with which a body may be made to revolve in a movable ellipsis will be as, and vice versa. Let the force with which a body may revolve in an immovable ellipsis be expressed by the quantity, and the force in V will be. But the force with which a body may revolve in a circle at the distance CV, with the same velocity as a body revolving in an ellipsis has in V, is to the force with which a body revolving in an ellipsis is acted upon in the apsis V. As half the latus rectum of the ellipsis to the semidiameter CV of the circle, and therefore is as. And the force which is to this, as GG, FF to FF, is as, and this force, by core 1 of this prop, is the difference of the forces in V, with which the body P revolves in the immovable ellipsis VPK, and the body P in the movable ellipsis up. Therefore since by this prop, that difference at any other altitude A is to itself at the altitude CV as to, the same difference in every altitude A will be as. Therefore to the force, by which the body may revolve in an immovable ellipsis VPK add the excess, and the sum will be the whole force by which a body may revolve in the same time in the movable ellipsis up. Core 3. In the same manner it will be found, that, if the immovable orbit VPK be an ellipsis having its center in the center of the forces C, and there be supposed a movable ellipsis up, similar, equal, and concentrical to it. And 2r be the principal lattice rectum of that ellipsis, and 2t the lattice transversum, or greater axis, and the angle VCP be continually to the angle VCP as G to F. The forces with which bodies may revolve in the immovable and movable ellipsis, in equal times, will be as and respectively. Core 4. And universally, if the greatest altitude CV of the body be called T, and the radius of the curvature which the orbit VPK has in V, that is, the radius of a circle equally curve, be called R. And the centripetal force with which a body may revolve in any immovable trajectory VPK at the place V be called, and in other places P be indefinitely styled X. And the altitude CP be called A, and G be taken to F in the given ratio of the angle VCP to the angle VCP. The centripetal force with which the same body will perform the same motions in the same time, in the same trajectory up revolving with a circular motion, will be as the sum of the forces. Core 5. Therefore the motion of a body in an immovable orbit being given, its angular motion round the center of the forces may be increased or diminished in a given ratio. And thence new immovable orbits may be found in which bodies may revolve with new centripetal forces. Core 6. Therefore if there be erected the line VP of an indeterminate length, perpendicular to the line CV given by position, and CP be drawn, and CP equal to it, making the angle VCP having a given ratio to the angle VCP. The force with which a body may revolve in the curved line VPK, which the point P is continually describing, will be reciprocally as the cube of the altitude CP. For the body P, by its vis inertia alone, no other force impelling it, will proceed uniformly in the right line VP. Add, then, a force tending to the center C reciprocally as the cube of the altitude CP or CP, and, by what was just demonstrated, the body will deflect from the rectilinear motion into the curved line VPK. But this curve VPK is the same with the curve VPQ found in Core 3, Prop XLI, in which, I said, bodies attracted with such forces would ascend obliquely. Proposition XLV. Problem 31. To find the motion of the apsides in orbits approaching very near to circles. This problem is solved arithmetically by reducing the orbit, which a body revolving in a movable ellipsis, as in Core 2 and 3 of the above prop, describes in an immovable plane, to the figure of the orbit whose apsides are required, and then seeking the apsides of the orbit which that body describes in an immovable plane. But orbits acquire the same figure if the centripetal forces with which they are described, compared between themselves, are made proportional at equal altitudes. Let the point V be the highest apsis, and write T for the greatest altitude CV, A for any other altitude CP or CP, and X for the difference of the altitude CV, CP. And the force with which a body moves in an ellipsis revolving about its focus C, as in Core 2, and which in Core 2 was as, that is as, by substituting T, X for A, will become as. In like manner any other centripetal force is to be reduced to a fraction whose denominator is a superscript 3, and the numerators are to be made analogous by collating together the homologous terms. This will be made plainer by examples. Example 1. Let us suppose the centripetal force to be uniform, and therefore as or, writing T, X for A in the numerator, as. Then collating together the correspondent terms of the numerators, that is, those that consist of given quantities, with those of given quantities, and those of quantities not given with those of quantities not given. It will become RGG, RFF plus TFF to T superscript 3 as, FFX to 3TTX plus 3TXX, X superscript 3, or as, FF to 3TT plus 3TX, XX. Now since the orbit is supposed extremely near to a circle, let it coincide with a circle. And because in that case R and T become equal, and X is infinitely diminished, the last ratios will be, as RGG to T superscript 2, so, FF to 3TT, or as gg to tt, so ff to 3tt, and again, as gg to ff, so tt to 3tt, that is, as 1 to 3. And therefore g is to f, that is, the angle VCP to the angle VCP, as 1 to. Therefore since the body, in an immovable ellipsis, in descending from the upper to the lower apsis, describes an angle, if I may so speak, of 180 degrees. The other body in a movable ellipsis, and therefore in the immovable orbit we are treating of, will in its descent from the upper to the lower apsis, describe an angle VCP of deg. And this comes to pass by reason of the likeness of this orbit which a body acted upon by an uniform centripetal force describes, and of that orbit which a body performing its circuits in a revolving ellipsis will describe in a quiescent plane. By this collation of the terms, these orbits are made similar, not universally, indeed, but then only when they approach very near to a circular figure. A body, therefore revolving with an uniform centripetal force in an orbit nearly circular, will always describe an angle of degree, or 103 degrees, 55 m, 23 seconds, at the center. Moving from the upper apsis to the lower apsis when it has once described that angle, and thence returning to the upper apsis when it has described that angle again, and so on in infinitum. Exam. 2. Suppose the centripetal force to be as any power of the altitude a, as, for example, an 3 or, where n, 3 and n signify any indices of powers whatever, whether integers or fractions, rational or surd, affirmative or negative. That numerator n or being reduced to an indeterminate series by my method of converging series, will become nc. And conferring these terms with the terms of the other numerator rgg, rff plus tff, ffx, it becomes as rgg, rff plus tff to tn, so, ff2, nc. And taking the last ratios where the orbits approach to circles, it becomes as rgg to tn, so, ff to ntn, 1, or as gg to tn, 1, so ff to ntn dash, and again, gg to ff, so tn, 1 to ntn, 1, that is, as 1 to n. And therefore g is to f, that is the angle VCP to the angle VCP, as 1 to. Therefore since the angle VCP, described in the descent of the body from the upper apsis to the lower apsis in an ellipsis, is of 180 degrees. The angle VCP, described in the descent of the body from the upper apsis to the lower apsis in an orbit nearly circular which a body describes with a centripetal force proportional to the power n, 3, will be equal to an angle of deg. And this angle being repeated, the body will return from the lower to the upper apsis, and so on in infinitum. As if the centripetal force be as the distance of the body from the center, that is, as a, or, n will be equal to 4, and equal to 2. And therefore the angle between the upper and the lower apsis will be equal to degree, or 90 degrees. Therefore the body having performed a fourth part of one revolution, will arrive at the lower apsis, and having performed another fourth part, will arrive at the upper apsis, and so on by turns in infinitum. This appears also from Prop. X. For a body acted on by this centripetal force will revolve in an immovable ellipsis, whose center is the center of force. If the centripetal force is reciprocally as the distance, that is, directly as or, n will be equal to 2. And therefore the angle between the upper and lower apsis will be degree, or 127 degrees, 16 minutes, 45 seconds. And therefore a body revolving with such a force, will by a perpetual repetition of this angle, move alternately from the upper to the lower and from the lower to the upper apsis forever. So, also, if the centripetal force be reciprocally as the biquadrate root of the 11th power of the altitude, that is, reciprocally as, and, therefore, directly as or as, n will be equal to 1/4, and degree will be equal to 360 degrees. And therefore the body parting from the upper apsis, and from thence perpetually descending, will arrive at the lower apsis when it has completed one entire revolution. And thence ascending perpetually, when it has completed another entire revolution, it will arrive again at the upper apsis, and so alternately forever. Exam. 3. Taking m and n for any indices of the powers of the altitude, and b and c for any given numbers, suppose the centripetal force to be as, that is, as or, by the method of converging series above mentioned, as and k. And comparing the terms of the numerators, there will arise RGG, RFF plus TFF to BTM plus CTN as, FF2, MBTM, 1, NCTN plus BXTM, 2 plus CXTN, 2, and k. And taking the last ratios that arise when the orbits come to a circular form, there will come forth GG TOB TM, 1 plus CTN, 1 as FF to MBTM, 1 plus NCTN, 1, and again, GG to FF as BTM, 1 plus CTN, 1 to MBTN, 1 plus NCTN, 1. This proportion, by expressing the greatest altitude CV or T arithmetically by unity, becomes GG to FF as B plus C to MB plus NC, and therefore as 1 to. Whence G becomes to F, that is, the angle VCP to the angle VCP, as 1 to. And therefore since the angle VCP between the upper and the lower apsis, in an immovable ellipsis, is of 180 degrees. The angle VCP between the same apsides in an orbit which a body describes with a centripetal force, that is, as, will be equal to an angle of deg. And by the same reasoning, if the centripetal force be as, the angle between the apsides will be found equal to. After the same manner the problem is solved in more difficult cases. The quantity to which the centripetal force is proportional must always be resolved into a converging series whose denominator is a superscript 3. Then the given part of the numerator arising from that operation is to be supposed in the same ratio to that part of it which is not given. As the given part of this numerator RGG, RFF plus TFF, FFX is to that part of the same numerator which is not given. And taking away the superfluous quantities, and writing unity for T, the proportion of G to F is obtained. Core 1. Hence if the centripetal force be as any power of the altitude, that power may be found from the motion of the apsides. And so contrariwise. That is, if the whole angular motion, with which the body returns to the same apsis, be to the angular motion of one revolution, or 360 degrees, as any number as m to another as n, and the altitude called a. The force will be as the power of the altitude a, the index of which power is. This appears by the second example. Hence it is plain that the force in its recess from the center cannot decrease in a greater than a triplicate ratio of the altitude. A body revolving with such a force and parting from the apsis, if it once begins to descend, can never arrive at the lower apsis or least altitude, but will descend to the center, describing the curved line treated of in Core 3, Prop. XLI. But if it should, at its parting from the lower apsis, begin to ascend never so little, it will ascend in infinitum, and never come to the upper apsis, but will describe the curved line spoken of in the same core, and Core 6, Prop. 44. So that where the force in its recess from the center decreases in a greater than a triplicate ratio of the altitude, the body at its parting from the apsis, will either descend to the center, or ascend in infinitum, according as it descends or ascends at the beginning of its motion. But if the force in its recess from the center either decreases in a less than a triplicate ratio of the altitude, or increases in any ratio of the altitude whatsoever, the body will never descend to the center, but will at some time arrive at the lower apsis. And, on the contrary, if the body alternately ascending and descending from one apsis to another never comes to the center, then either the force increases in the recess from the center, or it decreases in a less than a triplicate ratio of the altitude. And the sooner the body returns from one apsis to another, the farther is the ratio of the forces from the triplicate ratio. As if the body should return to and from the upper apsis by an alternate descent and ascent in 8 revolutions, or in 4, or 2, or 1/1/2, that is, if m should be to n as 8, or 4, or 2, or 1/2 to 1, and therefore, be 3, or 3, or 3, or 3. Then the force will be as, or, that is, it will be reciprocally as, or. If the body after each revolution returns to the same apsis, and the apsis remains unmoved, then m will be to n as 1 to 1, and therefore will be equal to a, 2, or. And therefore the decrease of the forces will be in a duplicate ratio of the altitude, as was demonstrated above. If the body in 3/4 parts, or 2/3, or 1/3, or 1/4 part of an entire revolution, return to the same apsis, m will be to n as 3/4 or 2/3 or 1/3 or 1/4 to 1, and therefore is equal to, or, and therefore the force is either reciprocally as or directly as a 6 or a 13. Lastly, if the body in its progress from the upper apsis to the same upper apsis again, goes over one entire revolution and 3 degrees more, and therefore that apsis in each revolution of the body moves 3 degrees in consequentia, then m will be to n as 363 degrees, to 360 degrees, or as 121 to 120, and therefore will be equal to, and therefore the centripetal force will be reciprocally as, or reciprocally as very nearly. Therefore the centripetal force decreases in a ratio something greater than the duplicate, but approaching 59 3/4 times nearer to the duplicate than the triplicate. Core 2. Hence also if a body, urged by a centripetal force which is reciprocally as the square of the altitude, revolves in an ellipsis whose focus is in the center of the forces, and a new and foreign force should be added to or subducted from this centripetal force, the motion of the apsides arising from that foreign force may, by the third example, be known, and so on the contrary. As if the force with which the body revolves in the ellipsis be as, and the foreign force subducted as Ca, and therefore the remaining force as, then, by the third example, B will be equal to 1. M equal to 1, and N equal to 4. And therefore the angle of revolution between the apsides is equal to 180 degrees, suppose that foreign force to be 357.45 parts less than the other force with which the body revolves in the ellipsis, that is, C to be, A or T being equal to 1. And then 180 will be 180 or 180.7623, that is, 180 degrees, 45 minutes, 44 seconds. Therefore the body, parting from the upper apsis, will arrive at the lower apsis with an angular motion of 180 degrees, 45 minutes, 44 seconds, and this angular motion being repeated, will return to the upper apsis, and therefore the upper apsis in each revolution will go forward 1 degree, 31 minutes, 28 seconds. The apsis of the moon is about twice as swift. So much for the motion of bodies in orbits whose planes pass through the center of force. It now remains to determine those motions in eccentrical planes. For those authors who treat of the motion of heavy bodies used to consider the ascent and descent of such bodies, not only in a perpendicular direction, but at all degrees of obliquity upon any given planes. And for the same reason we are to consider in this place the motions of bodies tending to centers by means of any forces whatsoever, when those bodies move in eccentrical planes. These planes are supposed to be perfectly smooth and polished, so as not to retard the motion of the bodies in the least. Moreover, in these demonstrations, instead of the planes upon which those bodies roll or slide, and which are therefore tangent planes to the bodies, I shall use planes parallel to them, in which the centers of the bodies move. And by that motion describe orbits. And by the same method I afterwards determine the motions of bodies performed in curved superficies. Section 10. Of the motion of bodies in given superficies, and of the reciprocal motion of funependulous bodies. Proposition 46. Problem 32. Any kind of centripetal force being supposed, and the center of force, and any plane whatsoever in which the body revolves, being given, and the quadratures of curvilinear figures being allowed. It is required to determine the motion of a body going off from a given place, with a given velocity, in the direction of a given right line in that plane. Let S be the center of force, SC the least distance of that center from the given plane, P a body issuing from the place P in the direction of the right line PZ, Q the same body revolving in its trajectory. And PQR the trajectory itself which is required to be found, described in that given plane. Join CQ, QS, and if in Qs we take SV proportional to the centripetal force with which the body is attracted towards the center S, and draw Vt parallel to CQ, and meeting SC in T, then will the force SV be resolved into 2, by Sr. 2, of the laws of motion, the force St, and the force Tv, of which St attracting the body in the direction of a line perpendicular to that plane, does not at all change its motion in that plane. But the action of the other force Tv, coinciding with the position of the plane itself, attracts the body directly towards the given point C in that plane. And therefore causes the body to move in this plane in the same manner as if the force St were taken away, and the body were to revolve in free space about the center C by means of the force Tv alone. But there being given the centripetal force Tv with which the body Q revolves in free space about the given center C, there is given, by prop. XLII, the trajectory PQR which the body describes. The place Q, in which the body will be found at any given time, and, lastly, the velocity of the body in that place Q. And so a contra. QEI. Proposition 47. Theorem 15. Supposing the centripetal force to be proportional to the distance of the body from the center, all bodies revolving in any planes whatsoever will describe ellipses, and complete their revolutions in equal times. And those which move in right lines, running backwards and forwards alternately, will complete their several periods of going and returning in the same times. For letting all things stand as in the foregoing proposition, the force SV, with which the body Q revolving in any plane PQR is attracted towards the center S, is as the distance SQ. And therefore because SV and SQ, TV and CQ are proportional, the force TV with which the body is attracted towards the given point C in the plane of the orbit is as the distance CQ. Therefore the forces with which bodies found in the plane PQR are attracted towards the point C, are in proportion to the distances equal to the forces with which the same bodies are attracted every way towards the center S. And therefore the bodies will move in the same times, and in the same figures, in any plane PQR about the point C, as they would do in free spaces about the center S, and therefore, by core 2, prop. X, and core 2, prop. 38. They will in equal times either describe ellipses in that plane about the center C, or move to and fro in right lines passing through the center C in that plane, completing the same periods of time in all cases. QED. Scholium. The ascent and descent of bodies in curved superficies has a near relation to these motions we have been speaking of. Imagine curved lines to be described on any plane, and to revolve about any given axis passing through the center of force, and by that revolution to describe curved superficies. And that the bodies move in such sort that their centers may be always found in those superficies. If those bodies reciprocate to and fro with an oblique ascent and descent, their motions will be performed in planes passing through the axis, and therefore in the curved lines, by whose revolution those curved superficies were generated. In those cases, therefore, it will be sufficient to consider the motion in those curved lines. Proposition 48. Theorem 16. If a wheel stands upon the outside of a globe at right angles thereto, and revolving about its own axis goes forward in a great circle, the length of the curvilinear path which any point, given in the perimeter of the wheel, hath described since the time that it touched the globe, which curvilinear path we may call the cycloid or epicycloid, will be to double the versed sine of half the arc which since that time has touched the globe in passing over it. As the sum of the diameters of the globe and the wheel to the semi-diameter of the globe. Proposition 49. Theorem 17. If a wheel stand upon the inside of a concave globe at right angles thereto, and revolving about its own axis go forward in one of the great circles of the globe, the length of the curvilinear path which any point, given in the perimeter of the wheel, hath described since it touched the globe, will be to the double of the versed sine of half the arc which in all that time has touched the globe in passing over it. As the difference of the diameters of the globe and the wheel to the semi-diameter of the globe. Let ABL be the globe, C its center, BPV the wheel insisting thereon, E the center of the wheel, B the point of contact, and P the given point in the perimeter of the wheel. Imagine this wheel to proceed in the great circle ABL from A through B towards L, and in its progress to revolve in such a manner that the arcs AB, PB may be always equal one to the other. And the given point P in the perimeter of the wheel may describe in the meantime the curvilinear path AP. Let AP be the whole curvilinear path described since the wheel touched the globe in A, and the length of this path AP will be to twice the versed sine of the arc 1/2 PB as 2 CE to CB. For let the right line CE, produced if need be, meet the wheel in V, and join CP, BP, EP, VP, produce CP, and let fall thereon the perpendicular VF. Let PH, VH, meeting in H, touch the circle in P and V, and let PH cut VF in G, and to VP let fall the perpendiculars GI, HK. From the center C with any interval let there be described the circle NOM, cutting the right line CP in N, the perimeter of the wheel BP in O, and the curvilinear path AP in M. And from the center V with the interval VO let there be described a circle cutting VP produced in Q. Because the wheel in its progress always revolves about the point of contact B, it is manifest that the right line BP is perpendicular to that curved line AP which the point P of the wheel describes. And therefore that the right line VP will touch this curve in the point P. Let the radius of the circle NOM be gradually increased or diminished so that at last it become equal to the distance CP. And by reason of the similitude of the evanescent figure NOM, and the figure PFGVI, the ultimate ratio of the evanescent linearly PM, Pn, P, PQ, that is, the ratio of the momentary mutations of the curve AP, the right line CP. The circular arc BP, and the right line VP, will be the same as of the lines PV, PF, PG, PI, respectively. But since VF is perpendicular to CF, and VH to CV, and therefore the angles HVG, VCF equal, and the angle VHG, because the angles of the quadrilateral figure HVEP are right in V and P, is equal to the angle CEP, the triangles VHG, CEP will be similar. And thence it will come to pass that as EP is to CE so is HG to HV or HP, and so KI to KP, and by composition or division as CB to CE so is PI to PK, and doubling the consequence as CB to 2CE so PI to PV, and so is PQ to PM. Therefore the decrement of the line VP, that is, the increment of the line BV, VP to the increment of the curved line AP is in a given ratio of CB to 2CE, and therefore, by Corlem. 4. The lengths BV, VP and AP, generated by those increments, are in the same ratio. But if BV be radius, VP is the cosine of the angle BVP or 1/2 BEP, and therefore BV, VP is the versed sine of the same angle, and therefore in this wheel, whose radius is 1/2 BV, BV, VP will be double the versed sine of the arc 1/2 BP. Therefore AP is to double the versed sine of the arc 1/2 BP as 2 CE to CB. QED. The line AP in the former of these propositions we shall name the cycloid without the globe, the other in the latter proposition the cycloid within the globe, for distinction's sake. Core 1. Hence if there be described the entire cycloid ASL, and the same be bisected in S, the length of the part PS will be to the length PV, which is the double of the sine of the angle VBP, when EB is radius, as 2 CE to CB, and therefore in a given ratio. Core 2. And the length of the semiperimeter of the cycloid AS will be equal to a right line which is to the diameter of the wheel BV as 2 CE to CB. Proposition L, Problem 33. To cause a pendulous body to oscillate in a given cycloid. Let there be given within the globe QVS described with the center C, the cycloid QRS, bisected in R, and meeting the superficies of the globe with its extreme points Q and S on either hand. Let there be drawn CR bisecting the arc QS in O, and let it be produced to A in such sort that CA may be to CO as CO to CR. About the center C, with the interval CA, let there be described an exterior globe DAF. And within this globe, by a wheel whose diameter is AO, let there be described two semicycloids AQ, AS, touching the interior globe in Q and S, and meeting the exterior globe in A. From that point A, with a thread APT in length equal to the line AR, let the body T depend, and oscillate in such manner between the two semicycloids AQ, AS, that, as often as the pendulum parts from the perpendicular AR, the upper part of the thread AP may be applied to that semicycloid APS towards which the motion tends, and fold itself round that curved line, as if it were some solid obstacle. The remaining part of the same thread PT which has not yet touched the semicycloid continuing straight. Then will the weight T oscillate in the given cycloid QRS. QEF. For let the thread PT meet the cycloid QRS in T, and the circle QOS in V, and let CV be drawn. And to the rectilinear part of the thread PT from the extreme points P and T let there be erected the perpendiculars BP, TW, meeting the right line CV in B and W. It is evident, from the construction and generation of the similar figures AS, SR, that those perpendiculars PB, TW, cut off from CV the lengths VB, VW equal the diameters of the wheels OA, or. Therefore TP is to VP, which is double the sine of the angle VBP when 1/2 BV is radius, as BW to BV, or AO plus or to AO, that is, since CA and CO, CO and CR, and by division AO and or are proportional, as CA plus CO to CA, or, if BV be bisected in E, as 2 CE to CB. Therefore, by Core 1, Prop. 49, the length of the rectilinear part of the thread PT is always equal to the arc of the cycloid PS, and the whole thread APT is always equal to the half of the cycloid APS, that is, by Core 2, Prop. 49, to the length AR. And therefore contrariwise, if the string remain always equal to the length AR, the point T will always move in the given cycloid QRS. QED. Sur. The string AR is equal to the semicycloid AS, and therefore has the same ratio to AC the semidiameter of the exterior globe as the like semicycloid SR has to CO the semidiameter of the interior globe. Proposition Lee, Theorem 18. If a centripetal force tending on all sides to the center C of a globe, be in all places as the distance of the place from the center, and by this force alone acting upon it, the body T oscillate, in the manner above described, in the perimeter of the cycloid QRS. I say, that all the oscillations, how unequal soever in themselves, will be performed in equal times. For upon the tangent TW infinitely produced let fall the perpendicular CX, and join CT. Because the centripetal force with which the body T is impelled toward C is as the distance CT, let this, by Cr. 2, of the laws, be resolved into the part CX, TX, of which CX impelling the body directly from P stretches the thread PT, and by the resistance the thread makes to it is totally employed, producing no other effect. But the other part TX, impelling the body transversely or towards X, directly accelerates the motion in the cycloid. Then it is plain that the acceleration of the body, proportional to this accelerating force, will be every moment as the length Tx, that is, because CV, WV, and Tx, Tw proportional to them are given, as the length Tw, that is, by Core 1, Prop. 49, as the length of the arc of the cycloid Tr. If therefore two pendulums APT, apt, be unequally drawn aside from the perpendicular AR, and let fall together, their accelerations will be always as the arcs to be described Tr, Tr. But the parts described at the beginning of the motion are as the accelerations, that is, as the wholes that are to be described at the beginning, and therefore the parts which remain to be described. And the subsequent accelerations proportional to those parts, are also as the wholes, and so on. Therefore the accelerations, and consequently the velocities generated, and the parts described with those velocities, and the parts to be described, are always as the wholes. And therefore the parts to be described preserving a given ratio to each other will vanish together, that is, the two bodies oscillating will arrive together at the perpendicular AR. And since on the other hand the ascent of the pendulums from the lowest place are through the same cycloidal arcs with a retrograde motion, is retarded in the several places they pass through by the same forces by which their descent was accelerated. It is plain that the velocities of their ascent and descent through the same arcs are equal, and consequently performed in equal times. And, therefore, since the two parts of the cycloid Rs and Rq lying on either side of the perpendicular are similar and equal, the two pendulums will perform as well the wholes as the halves of their oscillations in the same times. QED. Sur. The force with which the body T is accelerated or retarded in any place T of the cycloid, is to the whole weight of the same body in the highest place S or Q as the arc of the cycloid TR is to the arc SR or QR. Proposition Lie. Problem 34. To define the velocities of the pendulums in the several places, and the times in which both the entire oscillations, and the several parts of them are performed. About any center G, with the interval GH equal to the arc of the cycloid RS, describe a semicircle HKM bisected by the semidiameter GK. And if a centripetal force proportional to the distance of the places from the center tend to the center G, and it be in the perimeter HIK equal to the centripetal force in the perimeter of the globe QOS tending towards its center. And at the same time that the pendulum T is let fall from the highest place S, a body, as L, is let fall from H to G. Then because the forces which act upon the bodies are equal at the beginning, and always proportional to the spaces to be described TR, LG, and therefore if TR and LG are equal, are also equal in the places T and L. It is plain that those bodies describe at the beginning equal spaces ST, HL, and therefore are still acted upon equally, and continue to describe equal spaces. Therefore by Prop. XXXVI, the time in which the body describes the arc ST is to the time of one oscillation, as the arc HI the time in which the body H arrives at L, to the semi-periphery HKM, the time in which the body H will come to M. And the velocity of the pendulous body in the place T is to its velocity in the lowest place R, that is, the velocity of the body H in the place L to its velocity in the place G. Or the momentary increment of the line HL to the momentary increment of the line HG, the arcs HI, HK increasing with an equable flux, as the ordinate Li to the radius GK, or as to SR. Hence, since in unequal oscillations there are described in equal time arcs proportional to the entire arcs of the oscillations, there are obtained from the times given, both the velocities and the arcs described in all the oscillations universally. Which was first required. Let now any pendulous bodies oscillate in different cycloids described within different globes, whose absolute forces are also different. And if the absolute force of any globe QOS be called V, the accelerative force with which the pendulum is acted on in the circumference of this globe, when it begins to move directly towards its center, will be as the distance of the pendulous body from that center and the absolute force of the globe conjunctly, that is, as COV. Therefore the line OLA HY, which is as this accelerated force COV, will be described in a given time, and if there be erected the perpendicular YZ meeting the circumference in Z, the nascent arc HC will denote that given time. But that nascent arc HC is in the subduplicate ratio of the rectangle GHY, and therefore as. Whence the time of an entire oscillation in the cycloid QRS, it being as the semi-periphery HKM, which denotes that entire oscillation, directly. And as the arc HC which in like manner denotes a given time inversely, will be as GH directly and inversely, that is, because GH and SR are equal, as, or, by core prop. L, as. Therefore the oscillations in all globes and cycloids, performed with what absolute forces soever, are in a ratio compounded of the subduplicate ratio of the length of the string directly, and the subduplicate ratio of the distance between the point of suspension and the center of the globe inversely, and the subduplicate ratio of the absolute force of the globe inversely also. QEI. Core 1. Hence also the times of oscillating, falling, and revolving bodies may be compared among themselves. For if the diameter of the wheel with which the cycloid is described within the globe is supposed equal to the semi-diameter of the globe, the cycloid will become a right line passing through the center of the globe. And the oscillation will be changed into a descent and subsequent ascent in that right line. Whence there is given both the time of the descent from any place to the center, and the time equal to it in which the body revolving uniformly about the center of the globe at any distance describes an arc of a quadrant. For this time, by case 2, is to the time of half the oscillation in any cycloid QRS as 1 to Core 2. Hence also follow what Sir Christopher Wren and M. Huygens have discovered concerning the vulgar cycloid. For if the diameter of the globe be infinitely increased, its spherical superficies will be changed into a plane, and the centripetal force will act uniformly in the direction of lines perpendicular to that plane. And this cycloid of ours will become the same with the common cycloid. But in that case the length of the arc of the cycloid between that plane and the describing point will become equal to 4 times the versed sine of half the arc of the wheel between the same plane and the describing point. As was discovered by Sir Christopher Wren. And a pendulum between two such cycloids will oscillate in a similar and equal cycloid in equal times, as M. Huygens demonstrated. The descent of heavy bodies also in the time of one oscillation will be the same as M. Huygens exhibited. The propositions here demonstrated are adapted to the true constitution of the earth, in so far as wheels moving in any of its great circles will describe, by the motions of nails fixed in their perimeters, cycloids without the globe. And pendulums, in mines and deep caverns of the earth, must oscillate in cycloids within the globe, that those oscillations may be performed in equal times. For gravity, as will be shown in the third book, decreases in its progress from the superficies of the earth, upwards in a duplicate ratio of the distances from the center of the earth, downwards in a simple ratio of the same. Proposition 53. Problem 35. Granting the quadratures of curvilinear figures, it is required to find the forces with which bodies moving in given curved lines may always perform their oscillations in equal times. Let the body T oscillate in any curved line STRQ, whose axis is AR passing through the center of force C, draw TX touching that curve in any place of the body T, and in that tangent TX take TY equal to the arc TR. The length of that arc is known from the common methods used for the quadratures of figures. From the point Y draw the right line YZ perpendicular to the tangent. Draw CT meeting that perpendicular in Z, and the centripetal force will be proportional to the right line TZ. QEI. For if the force with which the body is attracted from T toward C be expressed by the right line TZ taken proportional to it, that force will be resolved into two forces Ty, Yz. Of which Yz drawing the body in the direction of the length of the thread PT, does not at all change its motion. Whereas the other force Ty directly accelerates or retards its motion in the curve STRQ. Wherefore since that force is as the space to be described TR, the accelerations or retardations of the body in describing two proportional parts, a greater and a less, of two oscillations, will be always as those parts. And therefore will cause those parts to be described together. But bodies which continually describe together parts proportional to the wholes, will describe the wholes together also. QED. Core 1. Hence if the body T, hanging by a rectilinear thread at from the center A, describe the circular arc STRQ, and in the meantime be acted on by any force tending downwards with parallel directions, which is to the uniform force of gravity as the arc TR to its sine Tn, the times of the several oscillations will be equal. For because TZ, AR are parallel, the triangles ATN, ZTY are similar, and therefore TZ will be to at as TY to Tn. That is, if the uniform force of gravity be expressed by the given length at, the force Tz, by which the oscillations become isochronous, will be to the force of gravity at, as the arc Tr equal to Ty is to Tn the sine of that arc. Core 2. And therefore in clocks, if forces were impressed by some machine upon the pendulum which preserves the motion, And so compounded with the force of gravity that the whole force tending downwards should be always as a line produced by applying the rectangle under the arc TR and the radius AR to the sine Tn, all the oscillations will become isochronous. Proposition live. Problem 36. Granting the quadratures of curvilinear figures, it is required to find the times in which bodies by means of any centripetal force will descend or ascend in any curved lines described in a plane passing through the center of force. Let the body descend from any place S, and move in any curve STTR given in a plane passing through the center of force C, join CS, and let it be divided into innumerable equal parts, and let DD be one of those parts. From the center C, with the intervals CD, CD, let the circles DT, DT be described, meeting the curved line STTR in T. And because the law of centripetal force is given, and also the altitude CS from which the body at first fell, there will be given the velocity of the body in any other altitude CT, by Prop. 39. But the time in which the body describes the linola TT is as the length of that linola, that is, as the secant of the angle TTC directly, and the velocity inversely. Let the ordinate dn, proportional to this time, be made perpendicular to the right line CS at the point D, and because DD is given, the rectangle DD-DN, that is, the area DNND, will be proportional to the same time. Therefore if PNN be a curved line in which the point N is perpetually found, and its asymptote be the right line SQ standing upon the line CS at right angles, the area SQPND will be proportional to the time in which the body in its descent hath described the line ST. And therefore that area being found, the time is also given. QEI. Proposition LV, Theorem 19. If a body move in any curved superficies, whose axis passes through the center of force, and from the body a perpendicular be let fall upon the axis, and a line parallel and equal thereto be drawn from any given point of the axis, I say, that this parallel line will describe an area proportional to the time. Let BKL be a curved superficies, T a body revolving in it, STR a trajectory which the body describes in the same, S the beginning of the trajectory, OMK the axis of the curved superficies. Tn a right line let fall perpendicularly from the body to the axis. OP a line parallel and equal thereto drawn from the given point O in the axis, AP the orthographic projection of the trajectory described by the point P in the plane AOP in which the revolving line OP is found. The beginning of that projection, answering to the point S, TC a right line drawn from the body to the center, TG a part thereof proportional to the centripetal force with which the body tends towards the center C. TM a right line perpendicular to the curved superficies, TI a part thereof proportional to the force of pressure with which the body urges the superficies, and therefore with which it is again repelled by the superficies towards M. PTF a right line parallel to the axis and passing through the body, and GF, IH right lines let fall perpendicularly from the points G and I upon that parallel PHTF. I say, now, that the area AOP, described by the radius OP from the beginning of the motion, is proportional to the time. For the force Tg, by core 2, of the laws of motion, is resolved into the forces Tf, Fg, and the force Ti into the forces Th, Chi. But the forces Tf, Th, acting in the direction of the line PF perpendicular to the plane AOP, introduce no change in the motion of the body but in a direction perpendicular to that plane. Therefore its motion, so far as it has the same direction with the position of the plane, that is, the motion of the point P, by which the projection AP of the trajectory is described in that plane, is the same as if the forces Tf, Th were taken away, and the body were acted on by the forces Fg, Hi alone. That is, the same as if the body were to describe in the plane AOP the curve AP by means of a centripetal force tending to the center O, and equal to the sum of the forces Fg and Hi. But with such a force as that, by Prop. 1, the area AOP will be described proportional to the time. QED. Sur. By the same reasoning, if a body, acted on by forces tending to two or more centers in any the same right line CO, should describe in a free space any curved line st, the area AOP would be always proportional to the time. Proposition LVI. Problem 37. Granting the quadratures of curvilinear figures, and supposing that there are given both the law of centripetal force tending to a given center, and the curved superficies whose axis passes through that center. It is required to find the trajectory which a body will describe in that superficies, when going off from a given place with a given velocity, and in a given direction in that superficies. The last construction remaining, let the body t go from the given place s, in the direction of a line given by position, and turn into the trajectory sought str, whose orthographic projection in the plane BDO is ap. And from the given velocity of the body in the altitude sc, its velocity in any other altitude tc will be also given. With that velocity, in a given moment of time, let the body describe the particle tt of its trajectory, and let pp be the projection of that particle described in the plane AOP. Join op, and a little circle being described upon the curved superficies about the center t with the interval tt, let the projection of that little circle in the plane AOP be the ellipsis PQ. And because the magnitude of that little circle tt, and tn or po its distance from the axis CO is also given, the ellipsis PQ will be given both in kind and magnitude, as also its position to the right line PO. And since the area pop is proportional to the time, and therefore given because the time is given, the angle pop will be given. And thence will be given p the common intersection of the ellipsis and the right line op, together with the angle op, in which the projection ap of the trajectory cuts the line OP. But from thence, by conferring prop. XLI, with its 2D core, the manner of determining the curve ap easily appears. Then from the several points p of that projection erecting to the plane AOP, the perpendiculars pt meeting the curved superficies in t, there will be given the several points t of the trajectory. QEI. Section 11. Of the motions of bodies tending to each other with centripetal forces. I have hitherto been treating of the attractions of bodies towards an immovable center, though very probably there is no such thing existent in nature. For attractions are made towards bodies, and the actions of the bodies attracted and attracting are always reciprocal and equal, by law 3. So that if there are two bodies, neither the attracted nor the attracting body is truly at rest, but both, by core 4, of the laws of motion, being as it were mutually attracted, revolve about a common center of gravity. And if there be more bodies, which are either attracted by one single one which is attracted by them again, or which all of them, attract each other mutually, these bodies will be so moved among themselves, as that their common center of gravity will either be at rest, or move uniformly forward in a right line. I shall therefore at present go on to treat of the motion of bodies mutually attracting each other, considering the centripetal forces as attractions, though perhaps in a physical strictness they may more truly be called impulses. But these propositions are to be considered as purely mathematical, and therefore, laying aside all physical considerations, I make use of a familiar way of speaking, to make myself the more easily understood by a mathematical reader. Proposition 57. Theorem XX. Two bodies attracting each other mutually describe similar figures about their common center of gravity, and about each other mutually. For the distances of the bodies from their common center of gravity are reciprocally as the bodies, and therefore in a given ratio to each other, and thence, by composition of ratios, in a given ratio to the whole distance between the bodies. Now these distances revolve about their common term with an equable angular motion, because lying in the same right line they never change their inclination to each other mutually. But right lines that are in a given ratio to each other, and revolve about their terms with an equal angular motion, describe upon planes, which either rest with those terms, or move with any motion not angular. Figures entirely similar round those terms. Therefore the figures described by the revolution of these distances are similar. QED. Proposition 58. Theorem 21. If two bodies attract each other mutually with forces of any kind, and in the meantime revolve about the common center of gravity, I say, that, by the same forces, there may be described round either body unmoved a figure similar and equal to the figures which the bodies so moving describe round each other mutually. Let the bodies S and P revolve about their common center of gravity C, proceeding from S to T, and from P to Q. From the given point S let there be continually drawn SP, SQ, equal and parallel to SP, TQ. And the curve PQV, which the point P describes in its revolution round the immovable point S, will be similar and equal to the curves which the bodies S and P describe about each other mutually, and therefore, by the XX, similar to the curves ST and PQV which the same bodies describe about their common center of gravity C, and that because the proportions of the lines SC, CP, and SP or SP, to each other, are given. Case 1. The common center of gravity C, by core 4, of the laws of motion, is either at rest, or moves uniformly in a right line. Let us first suppose it at rest, and in S and P let there be placed two bodies, one immovable in S, the other movable in P, similar and equal to the bodies S and P. Then let the right lines PR and PR touch the curves PQ and PQ in P and P, and produce CQ and SQ to R and R. And because the figures CPRQ, SPRQ are similar, RQ will be to RQ as CP to SP, and therefore in a given ratio. Hence if the force with which the body P is attracted towards the body S, and by consequence towards the intermediate point the center C, were to the force with which the body P is attracted towards the center S, in the same given ratio, these forces would in equal times attract the bodies from the tangents PR to the arcs PQ, PQ, through the intervals proportional to them RQ, RQ. And therefore this last force, tending to S, would make the body P revolve in the curve PQV, which would become similar to the curve PQV, in which the first force obliges the body P to revolve. And their revolutions would be completed in the same times. But because those forces are not to each other in the ratio of CP to SP, but, by reason of the similarity and equality of the bodies S and S, P and Pan the equality of the distances SP, SP, mutually equal, the bodies in equal times will be equally drawn from the tangents. And therefore that the body P may be attracted through the greater interval RQ, there is required a greater time, which will be in the subduplicate ratio of the intervals. Because, by lemma x, the spaces described at the very beginning of the motion are in a duplicate ratio of the times. Suppose, then the velocity of the body P to be to the velocity of the body P in a subduplicate ratio of the distance SP to the distance CP, so that the arcs PQ, PQ, which are in a simple proportion to each other, may be described in times that are in a subduplicate ratio of the distances. And the bodies P, P, always attracted by equal forces, will describe round the quiescent centers C and S similar figures PQV, PQV, the latter of which PQV is similar and equal to the figure which the body P describes round the movable body S. QE. D. Case 2. Suppose now that the common center of gravity, together with the space in which the bodies are moved among themselves, proceeds uniformly in a right line, and, by Cr. 6, of the laws of motion, all the motions in this space will be performed in the same manner as before. And therefore the bodies will describe mutually about each other the same figures as before, which will be therefore similar and equal to the figure PQV. QED. Core 1. Hence two bodies attracting each other with forces proportional to their distance, describe, by prop. X, both round their common center of gravity, and round each other mutually concentrical ellipses. And, vice versa, if such figures are described, the forces are proportional to the distances. Core 2. And two bodies, whose forces are reciprocally proportional to the square of their distance, describe, by prop. 11, 12, 13, both round their common center of gravity, and round each other mutually, conic sections having their focus in the center about which the figures are described. And, vice versa, if such figures are described, the centripetal forces are reciprocally proportional to the squares of the distance. Core 3. Any two bodies revolving round their common center of gravity describe areas proportional to the times, by radii drawn both to that center and to each other mutually. Proposition Lix. Theorem 22. The periodic time of two bodies S and P revolving round their common center of gravity C, is to the periodic time of one of the bodies P revolving round the other S remaining unmoved. And describing a figure similar and equal to those which the bodies describe about each other mutually, in a subduplicate ratio of the other body S to the sum of the bodies S plus P. For, by the demonstration of the last proposition, the times in which any similar arcs PQ and PQ are described are in a subduplicate ratio of the distances CP and SP, or SP, that is, in a subduplicate ratio of the body S to the sum of the bodies S plus P. And by composition of ratios, the sums of the times in which all the similar arcs PQ and PQ are described, that is, the whole times in which the whole similar figures are described are in the same subduplicate ratio. QED. Proposition LX. Theorem 23. If two bodies S and P, attracting each other with forces reciprocally proportional to the squares of their distance, revolve about their common center of gravity, I say, that the principal axis of the ellipsis which either of the bodies, as P, describes by this motion about the other S, will be to the principal axis of the ellipsis, which the same body P may describe in the same periodical time about the other body S quiescent, as the sum of the two bodies S plus P to the first of two mean proportionals between that sum and the other body S. For if the ellipses described were equal to each other, their periodic times by the last theorem would be in a subduplicate ratio of the body S to the sum of the bodies S plus P. Let the periodic time in the latter ellipsis be diminished in that ratio, and the periodic times will become equal, but, by Prop. 15, the principal axis of the ellipsis will be diminished in a ratio sesquiplicate to the former ratio. That is, in a ratio to which the ratio of S to S plus P is triplicate, and therefore that axis will be to the principal axis of the other ellipsis as the first of two mean proportionals between S plus P and S to S plus P. And inversely the principal axis of the ellipsis described about the movable body will be to the principal axis of that described round the immovable as S plus P to the first of two mean proportionals between S plus P and S. QED. Proposition LXI. Theorem 24. If two bodies attracting each other with any kind of forces, and not otherwise agitated or obstructed, are moved in any manner whatsoever, those motions will be the same as if they did not at all attract each other mutually, but were both attracted with the same forces by a third body placed in their common center of gravity. And the law of the attracting forces will be the same in respect of the distance of the bodies from the common center, as in respect of the distance between the two bodies. For those forces with which the bodies attract each other mutually, by tending to the bodies, tend also to the common center of gravity lying directly between them, and therefore are the same as if they proceeded from an intermediate body. QED. And because there is given the ratio of the distance of either body from that common center to the distance between the two bodies, there is given, of course, the ratio of any power of one distance to the same power of the other distance. And also the ratio of any quantity derived in any manner from one of the distances compounded anyhow with given quantities, to another quantity derived in like manner from the other distance. And as many given quantities having that given ratio of the distances to the first. Therefore if the force with which one body is attracted by another be directly or inversely as the distance of the bodies from each other, or as any power of that distance, or, lastly, as any quantity derived after any manner from that distance compounded with given quantities, then will the same force with which the same body is attracted to the common center of gravity be in like manner directly or inversely as the distance of the attracted body from the common center, or as any power of that distance, or, lastly, as a quantity derived in like sort from that distance compounded with analogous given quantities. That is, the law of attracting force will be the same with respect to both distances. QED. Proposition 62. Problem 38. To determine the motions of two bodies which attract each other with forces reciprocally proportional to the squares of the distance between them, and are let fall from given places. The bodies, by the last theorem, will be moved in the same manner as if they were attracted by a third placed in the common center of their gravity. And by the hypothesis that center will be quiescent at the beginning of their motion, and therefore, by core 4, of the laws of motion, will be always quiescent. The motions of the bodies are therefore to be determined, by prob. xxv, in the same manner as if they were impelled by forces tending to that center, and then we shall have the motions of the bodies attracting each other mutually. QEI. Proposition 63. Problem 39. To determine the motions of two bodies attracting each other with forces reciprocally proportional to the squares of their distance, and going off from given places in given directions with given velocities. The motions of the bodies at the beginning being given, there is given also the uniform motion of the common center of gravity, and the motion of the space which moves along with this center uniformly in a right line, and also the very first or beginning motions of the bodies in respect of this space. Then, by core 5 of the laws, and the last theorem, the subsequent motions will be performed in the same manner in that space, as if that space together with the common center of gravity were at rest, and as if the bodies did not attract each other, but were attracted by a third body placed in that center. The motion therefore in this movable space of each body going off from a given place, in a given direction, with a given velocity, and acted upon by a centripetal force tending to that center, is to be determined by prob. 9 and xxvi, and at the same time will be obtained the motion of the other round the same center. With this motion compound the uniform progressive motion of the entire system of the space and the bodies revolving in it, and there will be obtained the absolute motion of the bodies in a movable space. QEI. Proposition 64. Problem XL. Supposing forces with which bodies mutually attract each other to increase in a simple ratio of their distances from the centers, it is required to find the motions of several bodies among themselves. Suppose the first two bodies T and L to have their common center of gravity in D. These, by core 1, the XXI, will describe ellipses having their centers in D, the magnitudes of which ellipses are known by prob V. Let now a third body S attract the two former T and L with the accelerative forces St, Sl, and let it be attracted again by them. The force St, by core 2, of the laws of motion, is resolved into the forces Sd, dt. And the force Sl into the forces Sd and dl. Now the forces dt, dl, which are as their sum Tl, and therefore as the accelerative forces with which the bodies T and L attract each other mutually, added to the forces of the bodies T and L, the first to the first, and the last to the last, compose forces proportional to the distances dt and dl as before, but only greater than those former forces, and therefore, by Cr. 1, prop. X, and core 1, and 8, prop. 4, they will cause those bodies to describe ellipses as before, but with a swifter motion. The remaining accelerative forces Sd and dl, by the motive forces Sdt and Sdl, which are as the bodies attracting those bodies equally and in the direction of the lines Ti, Lk parallel to ds. Do not at all change their situations with respect to one another, but cause them equally to approach to the line Ik, which must be imagined drawn through the middle of the body S, and perpendicular to the line ds. But that approach to the line Ik will be hindered by causing the system of the bodies T and L on one side, and the body S on the other, with proper velocities, to revolve round the common center of gravity C. With such a motion the body S, because the sum of the motive forces Sdt and Sdl is proportional to the distance Cs, tends to the center C, will describe an ellipsis round the same center C. And the point D, because the lines Cs and Cd are proportional, will describe a like ellipsis over against it. But the bodies T and L, attracted by the motive forces Sdt and Sdl, the first by the first, and the last by the last, equally and in the direction of the parallel lines Ti and Lk, as was said before, will, by Cr. 5 and 6, of the laws of motion, continue to describe their ellipses round the movable center D, as before. QEI. Let there be added a fourth body V, and, by the like reasoning, it will be demonstrated that this body and the point C will describe ellipses about the common center of gravity B. The motions of the bodies T, L, and S round the centers D and C remaining the same as before, but accelerated. And by the same method one may add yet more bodies at pleasure. QE. I. This would be the case, though the bodies T and L attract each other mutually with accelerative forces either greater or less than those with which they attract the other bodies in proportion to their distance. Let all the mutual accelerative attractions be to each other as the distances multiplied into the attracting bodies. And from what has gone before it will easily be concluded that all the bodies will describe different ellipses with equal periodical times about their common center of gravity B, in an immovable plane. QEI. Proposition LXV. Theorem 25. Bodies, whose forces decrease in a duplicate ratio of their distances from their centers, may move among themselves in ellipses, and by radii drawn to the foci may describe areas proportional to the times very nearly. In the last proposition we demonstrated that case in which the motions will be performed exactly in ellipses. The more distant the law of the forces is from the law in that case, the more will the bodies disturb each other's motions. Neither is it possible that bodies attracting each other mutually according to the law supposed in this proposition should move exactly in ellipses, unless by keeping a certain proportion of distances from each other. However, in the following crises the orbits will not much differ from ellipses. Case I. Imagine several lesser bodies to revolve about some very great one at different distances from it, and suppose absolute forces tending to every one of the bodies proportional to each. And because, by Cr. For, of the laws, the common center of gravity of them all is either at rest, or moves uniformly forward in a right line, suppose the lesser bodies so small that the great body may be never at a sensible distance from that center. And then the great body will, without any sensible error, be either at rest, or move uniformly forward in a right line. And the lesser will revolve about that great one in ellipses, and by radii drawn thereto will describe areas proportional to the times. If we accept the errors that may be introduced by the receding of the great body from the common center of gravity, or by the mutual actions of the lesser bodies upon each other. But the lesser bodies may be so far diminished, as that this recess and the mutual actions of the bodies on each other may become less than any assignable. And therefore so as that the orbits may become ellipses, and the areas answer to the times, without any error that is not less than any assignable. QEO. Case 2. Let us imagine a system of lesser bodies revolving about a very great one in the manner just described, or any other system of two bodies revolving about each other to be moving uniformly forward in a right line. And in the meantime to be impelled sideways by the force of another vastly greater body situate at a great distance. And because the equal accelerative forces with which the bodies are impelled in parallel directions do not change the situation of the bodies with respect to each other, but only oblige the whole system to change its place while the parts still retain their motions among themselves, it is manifest that no change in those motions of the attracted bodies can arise from their attractions towards the greater, unless by the inequality of the accelerative attractions, or by the inclinations of the lines towards each other, in whose directions the attractions are made. Suppose, therefore, all the accelerative attractions made towards the great body to be among themselves as the squares of the distances reciprocally. And then, by increasing the distance of the great body till the differences of the right lines drawn from that to the others in respect of their length, and the inclinations of those lines to each other, be less than any given, the motions of the parts of the system will continue without errors that are not less than any given. And because, by the small distance of those parts from each other, the whole system is attracted as if it were but one body, it will therefore be moved by this attraction as if it were one body. That is, its center of gravity will describe about the great body one of the conic sections, that is, a parabola or hyperbola when the attraction is but languid and an ellipsis when it is more vigorous. And by radii drawn thereto, it will describe areas proportional to the times, without any errors but those which arise from the distances of the parts, which are by the supposition exceedingly small, and may be diminished at pleasure. Qeo. By a like reasoning one may proceed to more compounded cases in infinitum. Core 1. In the second case, the nearer the very great body approaches to the system of two or more revolving bodies, the greater will the perturbation be of the motions of the parts of the system among themselves. Because the inclinations of the lines drawn from that great body to those parts become greater, and the inequality of the proportion is also greater. Core 2. But the perturbation will be greatest of all, if we suppose the accelerative attractions of the parts of the system towards the greatest body of all are not to each other reciprocally as the squares of the distances from that great body. Especially if the inequality of this proportion be greater than the inequality of the proportion of the distances from the great body. For if the accelerative force, acting in parallel directions and equally, causes no perturbation in the motions of the parts of the system, it must of course, when it acts unequally, cause a perturbation somewhere, which will be greater or less as the inequality is greater or less. The excess of the greater impulses acting upon some bodies, and not acting upon others, must necessarily change their situation among themselves. And this perturbation, added to the perturbation arising from the inequality in inclination of the lines, makes the whole perturbation greater. Core 3. Hence if the parts of this system move in ellipses or circles without any remarkable perturbation, it is manifest that, if they are at all impelled by accelerative forces tending to any other bodies, the impulse is very weak. Or else is impressed very near equally and in parallel directions upon all of them. Proposition 66. Theorem 26. If three bodies whose forces decrease in a duplicate ratio of the distances attract each other mutually, and the accelerative attractions of any two towards the third be between themselves reciprocally as the squares of the distances, and the two least revolve about the greatest, I say, that the interior of the two revolving bodies will, by radii drawn to the innermost and greatest, describe round that body areas more proportional to the times, and a figure more approaching to that of an ellipsis having its focus in the point of concourse of the radii, if that great body be agitated by those attractions, than it would do if that great body were not attracted at all by the lesser, but remained at rest. Or than it would if that great body were very much more or very much less attracted, or very much more or very much less agitated, by the attractions. This appears plainly enough from the demonstration of the second corollary of the foregoing proposition, but it may be made out after this manner by a way of reasoning more distinct and more universally convincing. Case 1. Let the lesser bodies P and S revolve in the same plane about the greatest body T, the body P describing the interior orbit PAB, and S the exterior orbit ESE. Let SK be the mean distance of the bodies P and S. And let the accelerative attraction of the body P towards S, at that mean distance, be expressed by that line SK. Make SL to SK as the square of SK to the square of SP, and SL will be the accelerative attraction of the body P towards S at any distance SP join PT, and draw LM parallel to it meeting ST in M, and the attraction SL will be resolved, by Cr. 2, of the laws of motion, into the attractions SM, LM. And so the body P will be urged with a threefold accelerative force. One of these forces tends towards T, and arises from the mutual attraction of the bodies T and P. By this force alone the body P would describe round the body T, by the radius PT, areas proportional to the times, and an ellipsis whose focus is in the center of the body T. And this it would do whether the body T remained unmoved, or whether it were agitated by that attraction. This appears from Prop. 11, and Core 2 and 3 of the 21. The other force is that of the attraction LM, which, because it tends from P to T, will be superadded to and coincide with the former force, and cause the areas to be still proportional to the times, by Core 3, the 21. But because it is not reciprocally proportional to the square of the distance pt, it will compose, when added to the former, a force varying from that proportion. Which variation will be the greater by how much the proportion of this force to the former is greater, ceteris paribus. Therefore, since by Prop. 11, and by Core 2, the xxi, the force with which the ellipsis is described about the focus T ought to be directed to that focus, and to be reciprocally proportional to the square of the distance pt. That compounded force varying from that proportion will make the orbit PAB vary from the figure of an ellipsis that has its focus in the point T. And so much the more by how much the variation from that proportion is greater, and by consequence by how much the proportion of the second force Lm to the first force is greater, ceteris paribus. But now the third force Sm, attracting the body P in a direction parallel to St, composes with the other forces a new force which is no longer directed from P to T. And which varies so much more from this direction by how much the proportion of this third force to the other forces is greater, ceteris paribus. And therefore causes the body P to describe, by the radius Tp, areas no longer proportional to the times, and therefore makes the variation from that proportionality so much greater by how much the proportion of this force to the others is greater. But this third force will increase the variation of the orbit PAB from the elliptical figure before mentioned upon two accounts, first because that force is not directed from P to T. And, secondly, because it is not reciprocally proportional to the square of the distance pt. These things being premised, it is manifest that the areas are then most nearly proportional to the times, when that third force is the least possible, the rest preserving their former quantity. And that the orbit PAB does then approach nearest to the elliptical figure above mentioned, when both the second and third, but especially the third force, is the least possible, the first force remaining in its former quantity. Let the accelerative attraction of the body T towards S be expressed by the line Sn. Then if the accelerative attractions Sm and Sn were equal, these, attracting the bodies T and P equally and in parallel directions would not at all change their situation with respect to each other. The motions of the bodies between themselves would be the same in that case as if those attractions did not act at all, by course 6, of the laws of motion. And, by a like reasoning, if the attraction Sn is less than the attraction Sm, it will take away out of the attraction Sm the part Sn. So that there will remain only the part, of the attraction, Mn to disturb the proportionality of the areas and times, and the elliptical figure of the orbit. And in like manner if the attraction Sn be greater than the attraction Sm, the perturbation of the orbit and proportion will be produced by the difference Mn alone. After this manner the attraction Sn reduces always the attraction Sm to the attraction Mn, the first and second attractions remaining perfectly unchanged. And therefore the areas and times come then nearest to proportionality, and the orbit PAB to the above-mentioned elliptical figure, when the attraction Mn is either none, or the least that is possible. That is, when the accelerative attractions of the bodies P and T approach as near as possible to equality, that is, when the attraction Sn is neither none at all, nor less than the least of all the attractions Sm, but is, as it were, a mean between the greatest and least of all those attractions Sm, that is, not much greater nor much less than the attraction Sk. Qed. Case 2. Let now the lesser bodies P, S, revolve about a greater T in different planes. And the force Lm, acting in the direction of the line Pt situate in the plane of the orbit PAB, will have the same effect as before, neither will it draw the body P from the plane of its orbit. But the other force Nm acting in the direction of a line parallel to St, and which, therefore, when the body S is without the line of the nodes is inclined to the plane of the orbit PAB. Besides the perturbation of the motion just now spoken of as to longitude, introduces another perturbation also as to latitude, attracting the body P out of the plane of its orbit. And this perturbation, in any given situation of the bodies P and T to each other, will be as the generating force Mn. And therefore becomes least when the force Mn is least, that is, as was just now shown, where the attraction Sn is not much greater nor much less than the attraction Sk. Qed. Core 1. Hence it may be easily collected, that if several less bodies P, S, R, and K revolve about a very great body T, the motion of the innermost revolving body P will be least disturbed by the attractions of the others. When the great body is as well attracted and agitated by the rest, according to the ratio of the accelerative forces, as the rest are by each other mutually. Core 2. In a system of three bodies, T, P, S, if the accelerative attractions of any two of them towards a third be to each other reciprocally as the squares of the distances, the body P, by the radius pt, will describe its area about the body T swifter near the conjunction A and the opposition B than it will near the quadratures C and D. For every force with which the body P is acted on and the body T is not, and which does not act in the direction of the line pt, does either accelerate or retard the description of the area, according as it is directed, whether in consequentia or in antecedentia. Such is the force Nm. This force in the passage of the body P from C to A is directed in consequentia to its motion, and therefore accelerates it, then as far as D in antecedentia, and retards the motion, then in consequentia as far as B. And lastly in antecedentia as it moves from B to C. Core 3. And from the same reasoning it appears that the body P cateris paribus moves more swiftly in the conjunction and opposition than in the quadratures. Core 4. The orbit of the body P, cateris paribus, is more curve at the quadratures than at the conjunction and opposition. For the swifter bodies move, the less they deflect from a rectilinear path. And besides the force KL, or Nm, at the conjunction and opposition, is contrary to the force with which the body T attracts the body P, and therefore diminishes that force. But the body P will deflect the less from a rectilinear path the less it is impelled towards the body T. Core 5. Hence the body P, cateris paribus, goes farther from the body T at the quadratures than at the conjunction and opposition. This is said, however, supposing no regard had to the motion of eccentricity. For if the orbit of the body P be eccentrical, its eccentricity, as will be shown presently by Core 9, will be greatest when the apsides are in the syzygies. And thence it may sometimes come to pass that the body P, in its near approach to the farther apsis, may go farther from the body T at the syzygies than at the quadratures. Core 6. Because the centripetal force of the central body T, by which the body P is retained in its orbit, is increased at the quadratures by the addition caused by the force Lm, and diminished at the syzygies by the subduction caused by the force Kl, and because the force Kl is greater than Lm, it is more diminished than increased. And, moreover, since that centripetal force, by Core 2, Prop. 4, is in a ratio compounded of the simple ratio of the radius Tp directly, and the duplicate ratio of the periodical time inversely. It is plain that this compounded ratio is diminished by the action of the force Kl. And therefore that the periodical time, supposing the radius of the orbit pt to remain the same, will be increased, and that in the subduplicate of that ratio in which the centripetal force is diminished. And, therefore, supposing this radius increased or diminished, the periodical time will be increased more or diminished less than in the sesquiplicate ratio of this radius, by Core 6, Prop. 4. If that force of the central body should gradually decay, the body P being less and less attracted would go farther and farther from the center T, and, on the contrary, if it were increased, it would draw nearer to it. Therefore if the action of the distant body S, by which that force is diminished, were to increase and decrease by turns, the radius Tp will be also increased and diminished by turns. And the periodical time will be increased and diminished in a ratio compounded of the sesquiplicate ratio of the radius, and of the subduplicate of that ratio in which the centripetal force of the central body T is diminished or increased. By the increase or decrease of the action of the distant body S. Core 7. It also follows, from what was before laid down, that the axis of the ellipsis described by the body P, or the line of the apsides, does as to its angular motion go forwards and backwards by turns, but more forwards than backwards. And by the excess of its direct motion is in the whole carried forwards. For the force with which the body P is urged to the body T at the quadratures, where the force Mn vanishes, is compounded of the force Lm and the centripetal force with which the body T attracts the body P. The first force Lm, if the distance pt be increased, is increased in nearly the same proportion with that distance, and the other force decreases in the duplicate ratio of the distance. And therefore the sum of these two forces decreases in a less than the duplicate ratio of the distance pt, and therefore, by Core 1, Prop. XLV will make the line of the apsides, or, which is the same thing, the upper apsis, to go backward. But at the conjunction and opposition the force with which the body P is urged towards the body T is the difference of the force KL, and of the force with which the body T attracts the body P. And that difference, because the force KL is very nearly increased in the ratio of the distance pt, decreases in more than the duplicate ratio of the distance pt, and therefore, by Core 1, Prop. XLV, causes the line of the apsides to go forwards. In the places between the syzygies and the quadratures, the motion of the line of the apsides depends upon both of these causes conjunctly. So that it either goes forwards or backwards in proportion to the excess of one of these causes above the other. Therefore since the force KL in the syzygies is almost twice as great as the force Lm in the quadratures, the excess will be on the side of the force KL, and by consequence the line of the apsides will be carried forwards. The truth of this and the foregoing corollary will be more easily understood by conceiving the system of the two bodies T and P to be surrounded on every side by several bodies S, and disposed about the orbit ESE. For by the actions of these bodies the action of the body T will be diminished on every side, and decrease in more than a duplicate ratio of the distance. Core 8. But since the progress or regress of the apsides depends upon the decrease of the centripetal force, that is, upon its being in a greater or less ratio than the duplicate ratio of the distance Tp, in the passage of the body from the lower apsis to the upper, and upon a like increase in its return to the lower apsis again, and therefore becomes greatest where the proportion of the force at the upper apsis to the force at the lower apsis recedes farthest from the duplicate ratio of the distances inversely. It is plain, that, when the apsides are in the syzygies, they will, by reason of the subducting force KL or NM, LM, go forward more swiftly, and in the quadratures by the additional force LM go backward more slowly. Because the velocity of the progress or slowness of the regress is continued for a long time, this inequality becomes exceedingly great. Core 9. If a body is obliged, by a force reciprocally proportional to the square of its distance from any center, to revolve in an ellipsis round that center, and afterwards in its descent from the upper apsis to the lower apsis, that force by a perpetual accession of new force is increased in more than a duplicate ratio of the diminished distance. It is manifest that the body, being impelled always towards the center by the perpetual accession of this new force, will incline more towards that center than if it were urged by that force alone, which decreases in a duplicate ratio of the diminished distance, and therefore will describe an orbit interior to that elliptical orbit, and that the lower apsis approaching nearer to the center than before. Therefore the orbit by the accession of this new force will become more eccentrical. If now, while the body is returning from the lower to the upper apsis, it should decrease by the same degrees by which it increases before the body would return to its first distance. And therefore if the force decreases in a yet greater ratio, the body, being now less attracted than before, will ascend to a still greater distance, and so the eccentricity of the orbit will be increased still more. Therefore if the ratio of the increase and decrease of the centripetal force be augmented each revolution, the eccentricity will be augmented also, and, on the contrary, if that ratio decrease, it will be diminished. Now, therefore, in the system of the bodies T, P, S, when the apsides of the orbit PAB are in the quadratures, the ratio of that increase and decrease is least of all, and becomes greatest when the apsides are in the syzygies. If the apsides are placed in the quadratures, the ratio near the apsides is less, and near the syzygies greater, than the duplicate ratio of the distances. And from that greater ratio arises a direct motion of the line of the apsides, as was just now said. But if we consider the ratio of the whole increase or decrease in the progress between the apsides, this is less than the duplicate ratio of the distances. The force in the lower is to the force in the upper apsis in less than a duplicate ratio of the distance of the upper apsis from the focus of the ellipsis to the distance of the lower apsis from the same focus. And, contrariwise, when the apsides are placed in the syzygies, the force in the lower apsis is to the force in the upper apsis in a greater than a duplicate ratio of the distances. For the forces Lm in the quadratures added to the forces of the body T compose forces in a less ratio, and the forces Kl in the syzygies subducted from the forces of the body T, leave the forces in a greater ratio. Therefore the ratio of the whole increase and decrease in the passage between the apsides is least at the quadratures and greatest at the syzygies. And therefore in the passage of the apsides from the quadratures to the syzygies it is continually augmented, and increases the eccentricity of the ellipsis. And in the passage from the syzygies to the quadratures it is perpetually decreasing, and diminishes the eccentricity. Core 10. That we may give an account of the errors as to latitude, let us suppose the plane of the orbit est to remain immovable. And from the cause of the errors above explained, it is manifest, that, of the two forces Nm, Ml, which are the only and entire cause of them, the force Ml acting always in the plane of the orbit Kb never disturbs the motions as to latitude. And that the force Nm, when the nodes are in the syzygies, acting also in the same plane of the orbit, does not at that time affect those motions. But when the nodes are in the quadratures, it disturbs them very much, and, attracting the body P perpetually out of the plane of its orbit, it diminishes the inclination of the plane in the passage of the body from the quadratures to the syzygies. And again increases the same in the passage from the syzygies to the quadratures. Hence it comes to pass that when the body is in the syzygies, the inclination is then least of all, and returns to the first magnitude nearly, when the body arrives at the next node. But if the nodes are situate at the octants after the quadratures, that is, between C and A, D and B, it will appear, from what was just now shown, that in the passage of the body P from either node to the 90th degree from thence, the inclination of the plane is perpetually diminished. Then, in the passage through the next 45 degrees to the next quadrature, the inclination is increased, and afterwards, again, in its passage through another 45 degrees to the next node, it is diminished. Therefore the inclination is more diminished than increased, and is therefore always less in the subsequent node than in the preceding one. And, by a like reasoning, the inclination is more increased than diminished and the nodes are in the other octants between A and D, B and C. The inclination, therefore, is the greatest of all when the nodes are in the syzygies. In their passage from the syzygies to the quadratures the inclination is diminished at each appulse of the body to the nodes, and becomes least of all when the nodes are in the quadratures, and the body in the syzygies. Then it increases by the same degrees by which it decreased before, and, when the nodes come to the next syzygies, returns to its former magnitude. Core 11. Because when the nodes are in the quadratures the body P is perpetually attracted from the plane of its orbit, and because this attraction is made towards S in its passage from the node C through the conjunction A to the node D, and to the contrary part in its passage from the node D through the opposition B to the node C, it is manifest that, in its motion from the node C, the body recedes continually from the former plane CD of its orbit till it comes to the next node. And therefore at that node, being now at its greatest distance from the first plane CD, it will pass through the plane of the orbit est not in D, the other node of that plane, but in a point that lies nearer to the body S, which therefore becomes a new place of the node in antecedentia to its former place. And, by a like reasoning, the nodes will continue to recede in their passage from this node to the next. The nodes, therefore, when situate in the quadratures, recede perpetually. And at the syzygies, where no perturbation can be produced in the motion as to latitude, are quiescent, in the intermediate places they partake of both conditions, and recede more slowly. And, therefore, being always either retrograde or stationary, they will be carried backwards, or in antecedentia, each revolution. Core 12. All the errors described in these corollaries are a little greater at the conjunction of the bodies P, S, than at their opposition, because the generating forces Nm and Ml are greater. Core 13. And since the causes and proportions of the errors and variations mentioned in these corollaries do not depend upon the magnitude of the body S, it follows that all things before demonstrated will happen. If the magnitude of the body S be imagined so great as that the system of the two bodies P and T may revolve about it, and from this increase of the body S, and the consequent increase of its centripetal force, from which the errors of the body P arise, it will follow that all these errors, at equal distances, will be greater in this case than in the other where the body S revolves about the system of the bodies P and T. Core 14. But since the forces Nm, Ml, when the body S is exceedingly distant, are very nearly as the force Sk and the ratio Pt to St conjunctly, that is, if both the distance Pt, and the absolute force of the body S be given, as St superscript 3 reciprocally. And since those forces Nm, Ml are the causes of all the errors and effects treated of in the foregoing corollaries, it is manifest that all those effects, if the system of bodies T and P continue as before, and only the distance St and the absolute force of the body S be changed, will be very nearly in a ratio compounded of the direct ratio of the absolute force of the body S, and the triplicate inverse ratio of the distance St. Hence if the system of bodies T and P revolve about a distant body S, those forces Nm, Ml, and their effects, will be, by Core 2 and 6, Prop 4, reciprocally in a duplicate ratio of the periodical time. And thence, also, if the magnitude of the body S be proportional to its absolute force, those forces Nm, Ml, and their effects, will be directly as the cube of the apparent diameter of the distant body S viewed from T, and so vice versa. For these ratios are the same as the compounded ratio above mentioned. Core 15. And because if the orbits ESE and PAB, retaining their figure, proportions, and inclination to each other, should alter their magnitude, and the forces of the bodies S and T should either remain, or be changed in any given ratio, these forces, that is, the force of the body T, which obliges the body P to deflect from a rectilinear course into the orbit PAB, and the force of the body S, which causes the body P to deviate from that orbit, would act always in the same manner, and in the same proportion. It follows, that all the effects will be similar and proportional, and the times of those effects proportional also, that is, that all the linear errors will be as the diameters of the orbits, the angular errors the same as before, and the times of similar linear errors, or equal angular errors, as the periodical times of the orbits. Core 16. Therefore if the figures of the orbits and their inclination to each other be given, and the magnitudes, forces, and distances of the bodies be anyhow changed, we may, from the errors and times of those errors in one case, collect very nearly the errors and times of the errors in any other case. But this may be done more expeditiously by the following method. The forces Nm, Ml, other things remaining unaltered, are as the radius Tp, and their periodical effects, by Core 2, Lem. X, are as the forces and the square of the periodical time of the body P conjunctly. These are the linear errors of the body P. And hence the angular errors as they appear from the center T, that is, the motion of the apsides and of the nodes. And all the apparent errors as to longitude and latitude, are in each revolution of the body P as the square of the time of the revolution, very nearly. Let these ratios be compounded with the ratios in Cor. 14, and in any system of bodies T, P, S, where P revolves about T very near to it, and T revolves about S at a great distance, the angular errors of the body P, observed from the center T, will be in each revolution of the body P as the square of the periodical time of the body P directly, and the square of the periodical time of the body T inversely. And therefore the mean motion of the line of the apsides will be in a given ratio to the mean motion of the nodes. And both those motions will be as the periodical time of the body P directly, and the square of the periodical time of the body T inversely. The increase or diminution of the eccentricity and inclination of the orbit PAB makes no sensible variation in the motions of the apsides and nodes, unless that increase or diminution be very great indeed. Core 17. Since the line LM becomes sometimes greater and sometimes less than the radius PT, let the mean quantity of the force Lm be expressed by that radius PT. And then that mean force will be to the mean force Sk or Sn, which may be also expressed by St, as the length Pt to the length St. But the mean force Sn or St, by which the body T is retained in the orbit it describes about S, is to the force with which the body P is retained in its orbit about T in a ratio compounded of the ratio of the radius St to the radius Pt, and the duplicate ratio of the periodical time of the body P about T to the periodical time of the body T about S. And, x equal. The mean force Lm is to the force by which the body P is retained in its orbit about T, or by which the same body P might revolve at the distance Pt in the same periodical time about any immovable point T, in the same duplicate ratio of the periodical times. The periodical times therefore being given, together with the distance Pt, the mean force Lm is also given, and that force being given, there is given also the force Mn, very nearly, by the analogy of the lines Pt and Mn. Core 18. By the same laws by which the body P revolves about the body T, let us suppose many fluid bodies to move round T at equal distances from it, and to be so numerous, that they may all become contiguous to each other, so as to form a fluid annulus, or ring, of a round figure, and concentrical to the body T. And the several parts of this annulus, performing their motions by the same law as the body P, will draw nearer to the body T, and move swifter in the conjunction and opposition of themselves and the body S, than in the quadratures. And the nodes of this annulus, or its intersections with the plane of the orbit of the body S or T, will rest at the syzygies, but out of the syzygies they will be carried backward, or in antecedentia, with the greatest swiftness in the quadratures, and more slowly in other places. The inclination of this annulus also will vary, and its axis will oscillate each revolution, and when the revolution is completed will return to its former situation, except only that it will be carried round a little by the precession of the nodes. Core 19. Suppose now the spherical body T, consisting of some matter not fluid, to be enlarged, and to extend itself on every side as far as that annulus, and that a channel were cut all round its circumference containing water. And that this sphere revolves uniformly about its own axis in the same periodical time. This water being accelerated and retarded by turns, as in the last corollary, will be swifter at the syzygies, and slower at the quadratures, than the surface of the globe, and so will ebb and flow in its channel after the manner of the sea. If the attraction of the bodies were taken away, the water would acquire no motion of flux and reflux by revolving round the quiescent center of the globe. The case is the same of a globe moving uniformly forwards in a right line, and in the meantime revolving about its center, by core 5 of the laws of motion, and of a globe uniformly attracted from its rectilinear course, by core 6, of the same laws. But let the body S come to act upon it, and by its unequable attraction the water will receive this new motion. For there will be a stronger attraction upon that part of the water that is nearest to the body, and a weaker upon that part which is more remote. And the force Lm will attract the water downwards at the quadratures, and depress it as far as the syzygies, and the force Kl will attract it upwards in the syzygies, and withhold its descent, and make it rise as far as the quadratures. Except only in so far as the motion of flux and reflux may be directed by the channel of the water, and be a little retarded by friction. Core 20. If, now, the annulus becomes hard, and the globe is diminished, the motion of flux and reflux will cease, but the oscillating motion of the inclination and the precession of the nodes will remain. Let the globe have the same axis with the annulus, and perform its revolutions in the same times, and at its surface touch the annulus within, and adhere to it. Then the globe partaking of the motion of the annulus, this whole compages will oscillate, and the nodes will go backward, for the globe, as we shall shew presently, is perfectly indifferent to the receiving of all impressions. The greatest angle of the inclination of the annulus single is when the nodes are in the syzygies. Thence in the progress of the nodes to the quadratures, it endeavors to diminish its inclination, ere it by that endeavor impresses a motion upon the whole globe. The globe retains this motion impressed, till the annulus by a contrary endeavor destroys that motion, and impresses a new motion in a contrary direction. And by this means the greatest motion of the decreasing inclination happens when the nodes are in the quadratures, and the least angle of inclination in the octants. After the quadratures. And, again, the greatest motion of reclination happens when the nodes are in the syzygies, and the greatest angle of reclination in the octants following. And the case is the same of a globe without this annulus, if it be a little higher or a little denser in the equatorial than in the polar regions, for the excess of that matter in the regions near the equator supplies the place of the annulus. And though we should suppose the centripetal force of this globe to be anyhow increased, so that all its parts were to tend downwards, as the parts of our earth gravitate to the center, yet the phenomena of this and the preceding corollary would scarce be altered. Except that the places of the greatest and least height of the water will be different, for the water is now no longer sustained and kept in its orbit by its centrifugal force, but by the channel in which it flows. And, besides, the force Lm attracts the water downwards most in the quadratures, and the force Kl or Nm, Lm attracts it upwards most in the syzygies. And these forces conjoined cease to attract the water downwards, and begin to attract it upwards in the octants before the syzygies, and cease to attract the water upwards, and begin to attract the water downwards in the octants after the syzygies. And thence the greatest height of the water may happen about the octants after the syzygies, and the least height about the octants after the quadratures. Excepting only so far as the motion of ascent or descent impressed by these forces may by the vis insita of the water continue a little longer, or be stopped a little sooner by impediments in its channel. Core 21. For the same reason that redundant matter in the equatorial regions of a globe causes the nodes to go backwards, and therefore by the increase of that matter that retrogradation is increased, by the diminution is diminished. And by the removal quite ceases, it follows, that, if more than that redundant matter be taken away, that is, if the globe be either more depressed, or of a more rare consistence near the equator than near the poles, there will arise a motion of the nodes in consequentia. Core 22. And thence from the motion of the nodes is known the constitution of the globe. That is, if the globe retains unalterably the same poles, and the motion, of the nodes, be in antecedentia, there is a redundance of the matter near the equator, but if in consequentia, a deficiency. Suppose a uniform and exactly spherical globe to be first at rest in a free space, then by some impulse made obliquely upon its superficies to be driven from its place, and to receive a motion partly circular and partly right forward. Because this globe is perfectly indifferent to all the axes that pass through its center, nor has a greater propensity to one axis or to one situation of the axis than to any other, it is manifest that by its own force it will never change its axis, or the inclination of it. Let now this globe be impelled obliquely by a new impulse in the same part of its superficies as before, and since the effect of an impulse is not at all changed by its coming sooner or later, it is manifest that these two impulses, successively impressed, will produce the same motion as if they were impressed at the same time, that is, the same motion as if the globe had been impelled by a simple force compounded of them both, by Cr. 2, of the laws, that is, a simple motion about an axis of a given inclination. And the case is the same if the second impulse were made upon any other place of the equator of the first motion. And also if the first impulse were made upon any place in the equator of the motion which would be generated by the second impulse alone, and therefore, also, when both impulses are made in any places whatsoever. For these impulses will generate the same circular motion as if they were impressed together, and at once, in the place of the intersections of the equators of those motions, which would be generated by each of them separately. Therefore, a homogeneous and perfect globe will not retain several distinct motions, but will unite all those that are impressed on it, and reduce them into one. Revolving, as far as in it lies, always with a simple and uniform motion about one single given axis, with an inclination perpetually invariable. And the inclination of the axis, or the velocity of the rotation, will not be changed by centripetal force. For if the globe be supposed to be divided into two hemispheres, by any plane whatsoever passing through its own center, and the center to which the force is directed, that force will always urge each hemisphere equally. And therefore will not incline the globe any way as to its motion round its own axis. But let there be added anywhere between the pole and the equator a heap of new matter like a mountain, and this, by its perpetual endeavor to recede from the center of its motion, will disturb the motion of the globe, and cause its poles to wander about its superficies, describing circles about themselves and their opposite points. Neither can this enormous avogadure of the poles be corrected, unless by placing that mountain either in one of the poles, in which case, by Cor 21, the nodes of the equator will go forwards, or in the equatorial regions, in which case, by Cor 20, the nodes will go backwards, or, lastly, by adding on the other side of the axis a new quantity of matter, by which the mountain may be balanced in its motion. And then the nodes will either go forwards or backwards, as the mountain and this newly added matter happen to be nearer to the pole or to the equator. Proposition 67. Theorem 27. The same laws of attraction being supposed, I say, that the exterior body S does, by radii drawn to the point O, the common center of gravity of the interior bodies P and T, describe round that center areas more proportional to the times. And an orbit more approaching to the form of an ellipsis having its focus in that center, than it can describe round the innermost and greatest body T by radii drawn to that body. For the attractions of the body S towards T and P compose its absolute attraction, which is more directed towards O, the common center of gravity of the bodies T and P, than it is to the greatest body T. And which is more in a reciprocal proportion to the square of the distance so, than it is to the square of the distance st, as will easily appear by a little consideration. Proposition 68. Theorem 28. The same laws of attraction supposed, I say, that the exterior body S will, by radii drawn to O, the common center of gravity of the interior bodies P and T, describe round that center areas more proportional to the times. And an orbit more approaching to the form of an ellipsis having its focus in that center, if the innermost and greatest body be agitated by these attractions as well as the rest, than it would do if that body were either at rest as not attracted, or were much more or much less attracted, or much more or much less agitated. This may be demonstrated after the same manner as Prop. LXV, but by a more prolix reasoning, which I therefore pass over. It will be sufficient to consider it after this manner. From the demonstration of the last proposition it is plain, that the center, towards which the body S is urged by the two forces conjunctly, is very near to the common center of gravity of those two other bodies. If this center were to coincide with that common center, and moreover the common center of gravity of all the three bodies were at rest, the body S on one side, and the common center of gravity of the other two bodies on the other side, would describe true ellipses about that quiescent common center. This appears from Cor 2, Prop LVIA, compared with what was demonstrated in Prop LXIV and LXV. Now this accurate elliptical motion will be disturbed a little by the distance of the center of the two bodies from the center towards which the third body S is attracted. Let there be added, moreover, a motion to the common center of the three, and the perturbation will be increased yet more. Therefore the perturbation is least when the common center of the three bodies is at rest. That is, when the innermost and greatest body T is attracted according to the same law as the rest are. And is always greatest when the common center of the three, by the diminution of the motion of the body T, begins to be moved, and is more and more agitated. Sure. And hence if more lesser bodies revolve about the great one, it may easily be inferred that the orbits described will approach nearer to ellipses. And the descriptions of areas will be more nearly equable, if all the bodies mutually attract and agitate each other with accelerative forces that are as their absolute forces directly, and the squares of the distances inversely. And if the focus of each orbit be placed in the common center of gravity of all the interior bodies, that is, if the focus of the first and innermost orbit be placed in the center of gravity of the greatest and innermost body. The focus of the second orbit in the common center of gravity of the two innermost bodies, the focus of the third orbit in the common center of gravity of the three innermost. And so on, then if the innermost body were at rest, and was made the common focus of all the orbits. Proposition 69. Theorem 29. In a system of several bodies A, B, C, D, and C. If any one of those bodies, as A, attract all the rest, B, C, D, and C, with accelerative forces that are reciprocally as the squares of the distances from the attracting body, and another body, as B, attracts also the rest. A, C, D, and C. With forces that are reciprocally as the squares of the distances from the attracting body, the absolute forces of the attracting bodies A and B will be to each other as those very bodies A and B to which those forces belong. For the accelerative attractions of all the bodies B, C, D, towards A, are by the supposition equal to each other at equal distances. And in like manner the accelerative attractions of all the bodies towards B are also equal to each other at equal distances. But the absolute attractive force of the body A is to the absolute attractive force of the body B as the accelerative attraction of all the bodies towards A to the accelerative attraction of all the bodies towards B at equal distances. And so is also the accelerative attraction of the body B towards A to the accelerative attraction of the body A towards B. But the accelerative attraction of the body B towards A is to the accelerative attraction of the body A towards B as the mass of the body A to the mass of the body B. Because the motive forces which, by the 2d, 7th, and 8th definition, are as the accelerative forces and the bodies attracted conjunctly are here equal to one another by the third law. Therefore the absolute attractive force of the body A is to the absolute attractive force of the body B as the mass of the body A to the mass of the body B. QED. Core 1. Therefore if each of the bodies of the system A, B, C, D, and C does singly attract all the rest with accelerative forces that are reciprocally as the squares of the distances from the attracting body, the absolute forces of all those bodies will be to each other as the bodies themselves. Core 2. By a like reasoning, if each of the bodies of the system A, B, C, D, and C do singly attract all the rest with accelerative forces, which are either reciprocally or directly in the ratio of any power whatever of the distances from the attracting body, or which are defined by the distances from each of the attracting bodies according to any common law, it is plain that the absolute forces of those bodies are as the bodies themselves. Core 3. In a system of bodies whose forces decrease in the duplicate ratio of the distances, if the lesser revolve about one very great one in ellipses, having their common focus in the center of that great body, and of a figure exceedingly accurate, and moreover by radii drawn to that great body describe areas proportional to the times exactly, the absolute forces of those bodies to each other will be either accurately or very nearly in the ratio of the bodies. And so on the contrary. This appears from core of prop. XLVA, compared with the first corollary of this prop. Scholium. These propositions naturally lead us to the analogy there is between centripetal forces, and the central bodies to which those forces used to be directed. For it is reasonable to suppose that forces which are directed to bodies should depend upon the nature and quantity of those bodies, as we see they do in magnetical experiments. And when such cases occur, we are to compute the attractions of the bodies by assigning to each of their particles its proper force, and then collecting the sum of them all. I here use the word attraction in general for any endeavor, of what kind soever, made by bodies to approach to each other. Whether that endeavor arise from the action of the bodies themselves, as tending mutually to or agitating each other by spirits emitted, or whether it arises from the action of the ether or of the air, or of any medium whatsoever, whether corporeal or incorporeal, anyhow impelling bodies placed therein towards each other. In the same general sense I use the word impulse, not defining in this treatise the species or physical qualities of forces, but investigating the quantities and mathematical proportions of them, as I observed before in the definitions. In mathematics we are to investigate the quantities of forces with their proportions consequent upon any conditions supposed. Then, when we enter upon physics, we compare those proportions with the phenomena of nature, that we may know what conditions of those forces answer to the several kinds of attractive bodies. And this preparation being made, we argue more safely concerning the physical species, causes, and proportions of the forces. Let us see, then, with what forces spherical bodies consisting of particles endued with attractive powers in the manner above spoken of must act mutually upon one another, and what kind of motions will follow from thence. Section 12. Of the attractive forces of spherical bodies. Proposition 70. Theorem XXX. If to every point of a spherical surface there tend equal centripetal forces decreasing in the duplicate ratio of the distances from those points. I say, that a corpuscle placed within that superficies will not be attracted by those forces any way. Let HIKL be that spherical superficies, and P a corpuscle placed within. Through P let there be drawn to this superficies to two lines HK, Illinois, intercepting very small arcs HI, KL, and because, by core 3, lem. 7, the triangles HPI, LPK are alike, those arcs will be proportional to the distances HP, LP. And any particles at HI and KL of the spherical superficies, terminated by right lines passing through P, will be in the duplicate ratio of those distances. Therefore the forces of these particles exerted upon the body P are equal between themselves. For the forces are as the particles directly, and the squares of the distances inversely. And these two ratios compose the ratio of equality. The attractions therefore, being made equally towards contrary parts, destroy each other. And by a like reasoning all the attractions through the whole spherical superficies are destroyed by contrary attractions. Therefore the body P will not be any way impelled by those attractions. QED. Proposition 71. Theorem 31. The same thing supposed as above, I say, that a corpuscle placed without the spherical superficies is attracted towards the center of the sphere with a force reciprocally proportional to the square of its distance from that center. Let AHKB, OCP, be two equal spherical superficies described about the center S, their diameters AB, up, and let P and P be two corpuscles situate without the spheres in those diameters produced. Let there be drawn from the corpuscles the lines PHK, PIL, PHK, PIL, cutting off from the great circles AHB, OB, the equal arcs HK, HK, Illinois, IL, and to those lines let fall the perpendiculars SD, SD, SE, SE, IR, IR. Of which let SD, SD, cut PL, PL, in F and F. Let fall also to the diameters the perpendiculars IQ, IQ. Let now the angles DPE, DPE, vanish. And because DS and DS, ES and ES are equal, the lines PE, PF, and PE, PF, and the lineolo DF, DF may be taken for equal, because their last ratio, when the angles DPE, DPE vanish together, is the ratio of equality. These things then supposed, it will be, as PI to PF so is RI to DF, and as PF to pi so is DF or DF to Re, and, x equal, as PI PF to PF pi so is RI to Re, that is, by core 3, lem 7, so is the arc IH to the arc IH. Again, PI is to PS as IQ to SE, and PS to pi as SE or SE to IQ, and, x equal, PI PS to PS pi as IQ to IQ. And compounding the ratios Pi superscript 2 PF PS is to pi superscript 2 PF PS, as IHIQ to IHIQ. That is, as the circular superficies which is described by the arc IH, as the semicircle AKB revolves about the diameter AB, is to the circular superficies described by the arc IH as the semicircle AC revolves about the diameter AB. And the forces with which these superficies attract the corpuscles P and P in the direction of lines tending to those superficies are by the hypothesis as the superficies themselves directly. And the squares of the distances of the superficies from those corpuscles inversely. That is, as PF PS to PF PS. And these forces again are to the oblique parts of them which, by the resolution of forces as in Core 2, of the laws, tend to the centers in the directions of the lines PS, as pi to PQ, and pi to PQ. That is, because of the like triangles PIQ and PSF, PIC and PSF, as PS to PF and PS to PF thence X equal, the attraction of the corpuscle P towards S is to the attraction of the corpuscle P towards S as is to, that is, as PS superscript 2 to PS superscript 2. And, by a like reasoning, the forces with which the superficies described by the revolution of the arcs KL attract those corpuscles, will be as PS superscript 2 to PS superscript 2. And in the same ratio will be the forces of all the circular superficies into which each of the spherical superficies may be divided by taking SD always equal to SD, and SE equal to SE. And therefore, by composition, the forces of the entire spherical superficies exerted upon those corpuscles will be in the same ratio. QED. Proposition 72. Theorem 32. If to the several points of a sphere there tend equal centripetal forces decreasing in a duplicate ratio of the distances from those points, and there be given both the density of the sphere and the ratio of the diameter of the sphere to the distance of the corpuscle from its center, I say, that the force with which the corpuscle is attracted is proportional to the semi-diameter of the sphere. For conceive two corpuscles to be severally attracted by two spheres, one by one, the other by the other, and their distances from the centers of the spheres to be proportional to the diameters of the spheres respectively. And the spheres to be resolved into like particles, disposed in a like situation to the corpuscles. Then the attractions of one corpuscle towards the several particles of one sphere will be to the attractions of the other towards as many analogous particles of the other sphere in a ratio compounded of the ratio of the particles directly, and the duplicate ratio of the distances inversely. But the particles are as the spheres, that is, in a triplicate ratio of the diameters, and the distances are as the diameters, and the first ratio directly with the last ratio taken twice inversely, becomes the ratio of diameter to diameter. QE. D. Core 1. Hence if corpuscles revolve in circles about spheres composed of matter equally attracting, and the distances from the centers of the spheres be proportional to their diameters, the periodic times will be equal. Core 2. And, vice versa, if the periodic times are equal, the distances will be proportional to the diameters. These two corollaries appear from Core 3, Prop. 4. Core 3. If to the several points of any two solids whatever, of like figure and equal density, there tend equal centripetal forces decreasing in a duplicate ratio of the distances from those points, the forces with which corpuscles placed in a like situation to those two solids will be attracted by them, will be to each other as the diameters of the solids. Proposition 73. Theorem 33. If to the several points of a given sphere there tend equal centripetal forces decreasing in a duplicate ratio of the distances from the points, I say, that a corpuscle placed within the sphere is attracted by a force proportional to its distance from the center. In the sphere ABCD, described about the center S, let there be placed the corpuscle P. And about the same center S, with the interval SP, conceived described an interior sphere PEQF. It is plain, by Prop. LXX, that the concentric spherical superficies, of which the difference AEBF of the spheres is composed, have no effect at all upon the body P, their attractions being destroyed by contrary attractions. There remains, therefore, only the attraction of the interior sphere PQF. And, by Prop. LXXII, this is as the distance PS. QED. Scholium. By the superficies of which I here imagine the solids composed, I do not mean superficies purely mathematical, but orbs so extremely thin, that their thickness is as nothing. That is, the evanescent orbs of which the sphere will at last consist when the number of the orbs is increased, and their thickness diminished without end. In like manner, by the points of which lines, surfaces, and solids are said to be composed, are to be understood equal particles, whose magnitude is perfectly inconsiderable. Proposition 74. Theorem 34. The same thing supposed, I say, that a corpuscle situate without the sphere is attracted with a force reciprocally proportional to the square of its distance from the center. For suppose the sphere to be divided into innumerable concentric spherical superficies. And the attractions of the corpuscle arising from the several superficies will be reciprocally proportional to the square of the distance of the corpuscle from the center of the sphere, by prop. Lxxi, and, by composition, the sum of those attractions, that is, the attraction of the corpuscle towards the entire sphere, will be in the same ratio. QED. Core 1. Hence the attractions of homogeneous spheres at equal distances from the centers will be as the spheres themselves. 4. By prop. Lxxi, if the distances be proportional to the diameters of the spheres, the forces will be as the diameters. Let the greater distance be diminished in that ratio, and the distances now being equal, the attraction will be increased in the duplicate of that ratio, and therefore will be to the other attraction in the triplicate of that ratio. That is, in the ratio of the spheres. Core 2. At any distances whatever the attractions are as the spheres applied to the squares of the distances. Core 3. If a corpuscle placed without an homogeneous sphere is attracted by a force reciprocally proportional to the square of its distance from the center, and the sphere consists of attractive particles, the force of every particle will decrease in a duplicate ratio of the distance from each particle. Proposition 75. Theorem 35. If to the several points of a given sphere there tend equal centripetal forces decreasing in a duplicate ratio of the distances from the points, I say, that another similar sphere will be attracted by it with a force reciprocally proportional to the square of the distance of the centers. For the attraction of every particle is reciprocally as the square of its distance from the center of the attracting sphere, by prop. Lxxiv, and is therefore the same as if that whole attracting force issued from one single corpuscle placed in the center of this sphere. But this attraction is as great as on the other hand the attraction of the same corpuscle would be, if that were itself attracted by the several particles of the attracted sphere with the same force with which they are attracted by it. But that attraction of the corpuscle would be, by prop. Lxxiv, reciprocally proportional to the square of its distance from the center of the sphere, therefore the attraction of the sphere, equal thereto, is also in the same ratio. QED. Core 1. The attractions of spheres towards other homogeneous spheres are as the attracting spheres applied to the squares of the distances of their centers from the centers of those which they attract. Core 2. The case is the same when the attracted sphere does also attract. For the several points of the one attract the several points of the other with the same force with which they themselves are attracted by the others again. And therefore since in all attractions, by law 3, the attracted and attracting point are both equally acted on, the force will be doubled by their mutual attractions, the proportions remaining. Core 3. Those several truths demonstrated above concerning the motion of bodies about the focus of the conic sections will take place when an attracting sphere is placed in the focus, and the bodies move without the sphere. Core 4. Those things which were demonstrated before of the motion of bodies about the center of the conic sections take place when the motions are performed within the sphere. Proposition 76. Theorem 36. If spheres be however dissimilar, as to density of matter and attractive force, in the same ratio onward from the center to the circumference, but everywhere similar, at every given distance from the center, on all sides round about, and the attractive force of every point decreases in the duplicate ratio of the distance of the body attracted, I say, that the whole force with which one of these spheres attracts the other will be reciprocally proportional to the square of the distance of the centers. Imagine several concentric similar spheres, A, B, C, D, E, F, and C. The innermost of which added to the outermost may compose a matter more dense towards the center, or subducted from them may leave the same more lax and rare. Then, by prop. Lxxv, these spheres will attract other similar concentric spheres GH, IK, LM, and C, each the other, with forces reciprocally proportional to the square of the distance SP. And, by composition or division, the sum of all those forces, or the excess of any of them above the others, That is, the entire force with which the whole sphere AB, composed of any concentric spheres or of their differences, will attract the whole sphere GH, composed of any concentric spheres or their differences, in the same ratio. Let the number of the concentric spheres be increased in infinitum, so that the density of the matter together with the attractive force may, in the progress from the circumference to the center, increase or decrease according to any given law. And by the addition of matter not attractive, let the deficient density be supplied, that so the spheres may acquire any form desired. And the force with which one of these attracts the other will be still, by the former reasoning, in the same ratio of the square of the distance inversely. QED. Core 1. Hence if many spheres of this kind, similar in all respects, attract each other mutually, the accelerative attractions of each to each, at any equal distances of the centers, will be as the attracting spheres. Core 2. And at any unequal distances, as the attracting spheres apply to the squares of the distances between the centers. Core 3. The motive attractions, or the weights of the spheres towards one another, will be at equal distances of the centers as the attracting and attracted spheres conjunctly, that is, as the products arising from multiplying the spheres into each other. Core 4. And at unequal distances, as those products directly, and the squares of the distances between the centers inversely. Core 5. These proportions take place also when the attraction arises from the attractive virtue of both spheres mutually exerted upon each other. For the attraction is only doubled by the conjunction of the forces, the proportions remaining as before. Sur. 6. If spheres of this kind revolve about others at rest, each about each, and the distances between the centers of the quiescent and revolving bodies are proportional to the diameters of the quiescent bodies, the periodic times will be equal. Sur. 7. And, again, if the periodic times are equal, the distances will be proportional to the diameters. Core 8. All those truths above demonstrated, relating to the motions of bodies about the foci of conic sections, will take place when an attracting sphere, of any form and condition like that above described, is placed in the focus. Core 9. And also when the revolving bodies are also attracting spheres of any condition like that above described. Proposition 77. Theorem 37. If to the several points of spheres there tend centripetal forces proportional to the distances of the points from the attracted bodies. I say, that the compounded force with which two spheres attract each other mutually is as the distance between the centers of the spheres. Case 1. Let AEBF be a sphere, S its center, P a corpuscle attracted. PS be the axis of the sphere passing through the center of the corpuscle, EF two planes cutting the sphere, and perpendicular to the axis, and equidistant, one on one side, the other on the other, from the center of the sphere. G and G the intersections of the planes and the axis, and H any point in the plane EF. The centripetal force of the point H upon the corpuscle P, exerted in the direction of the line PH, is as the distance PH, and, by Cr. 2, of the laws, the same exerted in the direction of the line PG, or towards the center S, is as the length PG. Therefore the force of all the points in the plane EF, that is, of that whole plane, by which the corpuscle P is attracted towards the center S is as the distance PG multiplied by the number of those points, that is, as the solid contained under that plane EF and the distance PG. And in like manner the force of the plane EF, by which the corpuscle P is attracted towards the center S, is as that plane drawn into its distance PG, or as the equal plane EF drawn into that distance PG. And the sum of the forces of both planes as the plane EF drawn into the sum of the distances PG plus PG, that is, as that plane drawn into twice the distance PS of the center and the corpuscle. That is, as twice the plane EF drawn into the distance PS, or as the sum of the equal planes EF plus EF drawn into the same distance. And, by a like reasoning, the forces of all the planes in the whole sphere, equidistant on each side from the center of the sphere, are as the sum of those planes drawn into the distance PS, that is, as the whole sphere and the distance PS conjunctly. QED. Case 2. Let now the corpuscle P attract the sphere AEBF. And, by the same reasoning, it will appear that the force with which the sphere is attracted is as the distance PS. QED. Case 3. Imagine another sphere composed of innumerable corpuscles P. And because the force with which every corpuscle is attracted is as the distance of the corpuscle from the center of the first sphere, and as the same sphere conjunctly, and is therefore the same as if it all proceeded from a single corpuscle situate in the center of the sphere, the entire force with which all the corpuscles in the second sphere are attracted, that is, with which that whole sphere is attracted, will be the same as if that sphere were attracted by a force issuing from a single corpuscle in the center of the first sphere, and is therefore proportional to the distance between the centers of the spheres. QED. Case 4. Let the spheres attract each other mutually, and the force will be doubled, but the proportion will remain. QED. Case 5. Let the corpuscle P be placed within the sphere AEBF, and because the force of the plane EF upon the corpuscle is as the solid contained under that plane and the distance PG, and the contrary force of the plane EP as the solid contained under that plane and the distance PG, the force compounded of both will be as the difference of the solids, that is, as the sum of the equal planes drawn into half the difference of the distances. That is, as that sum drawn into PS, the distance of the corpuscle from the center of the sphere. And, by a like reasoning, the attraction of all the planes EF, throughout the whole sphere, that is, the attraction of the whole sphere, is conjunctly as the sum of all the planes, or as the whole sphere, and as PS. The distance of the corpuscle from the center of the sphere. QED. Case 6. And if there be composed a new sphere out of innumerable corpuscles such as P, situate within the first sphere AEBF, it may be proved, as before, that the attraction, whether single of one sphere towards the other, or mutual of both towards each other, will be as the distance PS of the centers. QED. Proposition 78. Theorem 38. If spheres is the progress from the center to the circumference be however dissimilar and unequable, but similar on every side round about at all given distances from the center, and the attractive force of every point be as the distance of the attracted body, I say, that the entire force with which two spheres of this kind attract each other mutually is proportional to the distance between the centers of the spheres. This is demonstrated from the foregoing proposition, in the same manner as proposition LXXVI was demonstrated from proposition LXXV. Core. Those things that were above demonstrated in Prop. X and LXIV, of the motion of bodies round the centers of conic sections, take place when all the attractions are made by the force of spherical bodies of the condition above described, and the attracted bodies are spheres of the same kind. Scholium. I have now explained the two principal cases of attractions. To wit, when the centripetal forces decrease in a duplicate ratio of the distances, or increase in a simple ratio of the distances, causing the bodies in both cases to revolve in conic sections, and composing spherical bodies whose centripetal forces observe the same law of increase or decrease in the recess from the center as the forces of the particles themselves do. Which is very remarkable. It would be tedious to run over the other cases, whose conclusions are less elegant and important, so particularly as I have done these. I choose rather to comprehend and determine them all by one general method as follows. Lemma 29. If about the center S there be described any circle as AEB, and about the center P there be also described two circles EF, cutting the first in E and E, and the line PS in F and F, and there be let fall to PS the perpendiculars ED, ed. I say, that if the distance of the arcs EF be supposed to be infinitely diminished, the last ratio of the evanescent line DD to the evanescent line FF is the same as that of the line PE to the line PS. For if the line PE cut the arc EF in Q, and the right line EE, which coincides with the evanescent arc EE, be produced, and meet the right line PS in T, and there be let fall from S to PE the perpendicular SG. Then, because of the like triangles DTE, des, it will be as dd to ee so dt to te, or de to es, and because the triangles, eq, esg, by lem 8, and core 3, lem 7, are similar, it will be as ee to eq or ff so es to sg. And x equal, as dd to ff so de to sg, that is, because of the similar triangles pde, pgs, so is pe to ps. QED. Proposition 79. Theorem 39. Suppose a superficies as EFFE to have its breadth infinitely diminished, and to be just vanishing, and that the same superficies by its revolution round the axis PS describes a spherical concavo-convex solid. To the several equal particles of which there tend equal centripetal forces. I say, that the force with which that solid attracts a corpuscle situate in P is in a ratio compounded of the ratio of the solid dE superscript 2ff and the ratio of the force with which the given particle in the place ff would attract the same corpuscle. For if we consider, first, the force of the spherical superficies Fe which is generated by the revolution of the arc Fe, and is cut anywhere, as in R, by the line de. The annular part of the superficies generated by the revolution of the arc Re will be as the line Ola dd, the radius of the sphere Pe remaining the same. As Archimedes has demonstrated in his book of the sphere and cylinder. And the force of this superficies exerted in the direction of the lines Pe or Pr situate all round in the conical superficies, will be as this annular superficies itself. That is as the line Ola dd, or, which is the same, as the rectangle under the given radius Pe of the sphere and the line Ola dd. But that force, exerted in the direction of the line Ps tending to the center S, will be less in the ratio Pd to Pe, and therefore will be as Pd dd. Suppose now the line df to be divided into innumerable little equal particles, each of which call dd, and then the superficies Fe will be divided into so many equal annuli, whose forces will be as the sum of all the rectangles Pd dd, that is, as 1/2 Pf superscript 2, 1/2 Pd superscript 2, and therefore as de superscript 2. Let now the superficies Fe be drawn into the altitude Ff, and the force of the solid EFFE exerted upon the corpuscle P will be as de superscript 2 Ff. That is, if the force be given which any given particle as Ff exerts upon the corpuscle P at the distance Pf. But if that force be not given, the force of the solid EFFE will be as the solid dE superscript 2 Ff and that force not given, conjunctly. QED. Proposition 80. Theorem XL. If to the several equal parts of a sphere ABE described about the center S there tend equal centripetal forces, and from the several points D in the axis of the sphere AB in which a corpuscle, as F, is placed, there be erected the perpendiculars DE meeting the sphere in E, and if in those perpendiculars the lengths dN be taken as the quantity, and as the force which a particle of the sphere situate in the axis exerts at the distance PE upon the corpuscle P conjunctly. I say, that the whole force with which the corpuscle P is attracted towards the sphere is as the area A and B, comprehended under the axis of the sphere AB, and the curve line A and B, the locus of the point N. For supposing the construction in the last lemma and theorem to stand, conceive the axis of the sphere AB to be divided into innumerable equal particles dd, and the whole sphere to be divided into so many spherical concavo-convex laminae EFFE. And erect the perpendicular dN. By the last theorem, the force with which the laminae EFFE attracts the corpuscle P is as dE superscript 2 ff and the force of one particle exerted at the distance PE or PF, conjunctly. But, by the last lemma, dd is to ff as PE to PS, and therefore ff is equal to, and dE superscript 2 ff is equal to dd, and therefore the force of the lamina EFFE is as dd and the force of a particle exerted at the distance PF conjunctly. That is, by the supposition, as dN/dd, or as the evanescent area dN/nd. Therefore the forces of all the laminae exerted upon the corpuscle P are as all the areas dN/nd, that is, the whole force of the sphere will be as the whole area A and B. QED. Core 1. Hence if the centripetal force tending to the several particles remain always the same at all distances, and dn be made as the whole force with which the corpuscle is attracted by the sphere is as the area ANB. Core 2. If the centripetal force of the particles be reciprocally as the distance of the corpuscle attracted by it, and dn be made as, the force with which the corpuscle P is attracted by the whole sphere will be as the area ANB. Core 3. If the centripetal force of the particles be reciprocally as the cube of the distance of the corpuscle attracted by it, and dn be made as, the force with which the corpuscle is attracted by the whole sphere will be as the area ANB. Core 4. And universally if the centripetal force tending to the several particles of the sphere be supposed to be reciprocally as the quantity v, and dn be made as, the force with which a corpuscle is attracted by the whole sphere will be as the area ANB. Proposition 81. Problem XLI. The things remaining as above, it is required to measure the area ANB. From the point P let there be drawn the right line PH touching the sphere in H. And to the axis PAB, letting fall the perpendicular HI, bisect PI in L, and, by Prop. 12, Book 2, Elementary. PE superscript 2 is equal to PS superscript 2 plus SE superscript 2 plus 2 PSD. But because the triangles SPH, SHI are alike, SE superscript 2 or SH superscript 2 is equal to the rectangle PSI. Therefore PE superscript 2 is equal to the rectangle contained under PS and PS plus SI plus 2SD, that is, under PS and 2LS plus 2SD, that is, under PS and 2LD. Moreover DE superscript 2 is equal to SE superscript 2, SD superscript 2, or SE superscript 2, LS superscript 2 plus 2SLD, LD superscript 2, that is, 2SLD, LD superscript 2, ALB. For LS superscript 2, SE superscript 2 or LS superscript 2, SA superscript 2, by Prop. 6, Book 2, Elementary, is equal to the rectangle ALB. Therefore if instead of DE superscript 2 we write 2SLD, LD superscript 2, ALB, the quantity, which, by core 4 of the foregoing prop, is as the length of the ordinate dn, will now resolve itself into three parts. Where if instead of V we write the inverse ratio of the centripetal force, and instead of PE the mean proportional between PS and 2LD, those three parts will become ordinates to so many curved lines, whose areas are discovered by the common methods. QED. Example 1. If the centripetal force tending to the several particles of the sphere be reciprocally as the distance, instead of V write PE the distance, then 2PSLD for PE superscript 2, and dn will become as SL, 1/2 LD. Suppose dn equal to its double 2SL, LD, and 2SL the given part of the ordinate drawn into the length AB will describe the rectangular area 2SLAB. And the indefinite part LD, drawn perpendicularly into the same length with a continued motion, in such sort as in its motion one way or another it may either by increasing or decreasing remain always equal to the length LD, will describe the area. That is, the area SLAB. Which taken from the former area 2SLAB, leaves the area SLAB. But the third part, drawn after the same manner with a continued motion perpendicularly into the same length, will describe the area of an hyperbola, which subducted from the area SLAB will leave ANB the area sought. Whence arises this construction of the problem? At the points, L, A, B, erect the perpendiculars LL, AA, BB, making AA equal to LB, and BB equal to LA, making LL and LB asymptotes, described through the points A, B, the hyperbolic curve of. And the chord BA being drawn, will enclose the area ABA equal to the area sought ANB. Example 2. If the centripetal force tending to the several particles of the sphere be reciprocally as the cube of the distance, or, which is the same thing, as that cube applied to any given plane, write for V, and 2PSLD for PE superscript 2. And dn will become as that is, because PS, AS, SI are continually proportional, as If we draw then these three parts into the length AB, the first will generate the area of an hyperbola, the second 1/2 SI the area 1/2 ABSI. The third the area, that is, 1/2 ABSI. From the first subduct the sum of the second and third, and there will remain A and B, the area sought. Whence arises this construction of the problem? At the points L, A, S, B, erect the perpendiculars LLAASS, BB, of which suppose SS equal to SI, and through the point S, to the asymptotes LL, LB, describe the hyperbola as meeting the perpendiculars AA, BB, in A and B. And the rectangle 2ASI, subducted from the hyperbolic area AS B, will leave A and B the area sought. Example 3. If the centripetal force tending to the several particles of the spheres decrease in a quadruplicate ratio of the distance from the particles, write for V, then for PE, and dN will become as. These three parts drawn into the length AB, produce so many areas, viz. into, and into. And these after due reduction come forth, SI superscript 2, and SI superscript 2 plus. And these by subducting the last from the first, become. Therefore the entire force with which the corpuscle P is attracted towards the center of the sphere is as, that is, reciprocally as PS superscript 3 Pi. QEI. By the same method one may determine the attraction of a corpuscle situate within the sphere, but more expeditiously by the following theorem. Proposition 82. Theorem XLI. In a sphere described about the center S with the interval SA, if there be taken SI, SA, SP continually proportional. I say, that the attraction of a corpuscle within the sphere in any place I is to its attraction without the sphere in the place P in a ratio compounded of the subduplicate ratio of IS, PS, the distances from the center. And the subduplicate ratio of the centripetal forces tending to the center in those places P and I. As if the centripetal forces of the particles of the sphere be reciprocally as the distances of the corpuscle attracted by them. The force with which the corpuscle situate in I is attracted by the entire sphere will be to the force with which it is attracted in P in a ratio compounded of the subduplicate ratio of the distance SI to the distance SP. And the subduplicate ratio of the centripetal force in the place I arising from any particle in the center to the centripetal force in the place P arising from the same particle in the center. That is, in the subduplicate ratio of the distances SI, SP to each other reciprocally. These two subduplicate ratios compose the ratio of equality, and therefore the attractions in I and P produced by the whole sphere are equal. By the like calculation, if the forces of the particles of the sphere are reciprocally in a duplicate ratio of the distances, it will be found that the attraction in I is to the attraction in P as the distance SP to the semidiameter SA of the sphere. If those forces are reciprocally in a triplicate ratio of the distances, the attractions in I and P will be to each other as SP superscript 2 to SA superscript 2, if in a quadruplicate ratio, as SP superscript 3 to SA superscript 3. Therefore since the attraction in P was found in this last case to be reciprocally as PS superscript 3 Pi, the attraction in I will be reciprocally as SA superscript 3 Pi, that is, because SA superscript 3 is given reciprocally as Pi. And the progression is the same in infinitum. The demonstration of this theorem is as follows. The things remaining as above constructed, and a corpuscle being in any place P, the ordinate dn was found to be as. Therefore if IE be drawn, that ordinate for any other place of the corpuscle, as I, will become, mutatis mutandis, as. Suppose the centripetal forces flowing from any point of the sphere, as E, to be to each other at the distances IE and PE as pen to IN, where the number n denotes the index of the powers of PE and IE. And those ordinates will become as and whose ratio to each other is as PSIEIN to ISPE pen. Because SI, SE, SP are in continued proportion, the triangles SPE, SEI are alike, and thence IE is to PE as IS to SE or SA. For the ratio of IE to PE write the ratio of IS to SA, and the ratio of the ordinates becomes that of PSIN to SA pen. But the ratio of PS to SA is subduplicate of that of the distances PS, SI, and the ratio of IN to pen, because IE is to PE as IS to SA, is subduplicate of that of the forces at the distances PS, IS. Therefore the ordinates, and consequently the areas which the ordinates describe, and the attractions proportional to them, are in a ratio compounded of those subduplicate ratios. QED. Proposition 83. Problem 42. To find the force with which a corpuscle placed in the center of a sphere is attracted towards any segment of that sphere whatsoever. Let P be a body in the center of that sphere and RBSD a segment thereof contained under the plane RDS, and the spherical superficies RBS. Let DB be cut in F by a spherical superficies EFG described from the center P, and let the segment be divided into the parts BREFGS, FEDG. Let us suppose that segment to be not a purely mathematical but a physical superficies, having some, but a perfectly inconsiderable thickness. Let that thickness be called O, and, by what Archimedes has demonstrated, that superficies will be as PFDFO. Let us suppose besides the attractive forces of the particles of the sphere to be reciprocally as that power of the distances, of which n is index, and the force with which the superficies EFG attracts the body P will be, by prop. LXXAX, as, that is, as. Let the perpendicular Fn drawn into O be proportional to this quantity. And the curvilinear area BDI, which the ordinate Fn, drawn through the length dB with a continued motion will describe, will be as the whole force with which the whole segment RBSD attracts the body P. QEI. Proposition 84. Problem 43. To find the force with which a corpuscle, placed without the center of a sphere in the axis of any segment, is attracted by that segment. Let the body P placed in the axis ADB of the segment EBK be attracted by that segment. About the center P, with the interval PE, let the spherical superficies EFK be described, and let it divide the segment into two parts EBKFE and EFKDE. Find the force of the first of those parts by prop. LXXXI, and the force of the latter part by prop. LXXXIA, and the sum of the forces will be the force of the whole segment EBKDE. QEI. Scholium. The attractions of spherical bodies being now explained, it comes next in order to treat of the laws of attraction in other bodies consisting in like manner of attractive particles, but to treat of them particularly is not necessary to my design. It will be sufficient to subjoin some general propositions relating to the forces of such bodies, and the motions thence arising, because the knowledge of these will be of some little use in philosophical inquiries. Section 13. Of the attractive forces of bodies which are not of a spherical figure. Proposition 85. Theorem 42. If a body be attracted by another, and its attraction be vastly stronger when it is contiguous to the attracting body than when they are separated from one another by a very small interval. The forces of the particles of the attracting body decrease, in the recess of the body attracted, in more than a duplicate ratio of the distance of the particles. For if the forces decrease in a duplicate ratio of the distances from the particles, the attraction towards a spherical body being, by prop. LXXIV, reciprocally as the square of the distance of the attracted body from the center of the sphere, will not be sensibly increased by the contact, and it will be still less increased by it, if the attraction, in the recess of the body attracted, decreases in a still less proportion. The proposition, therefore, is evident concerning attractive spheres. And the case is the same of concave spherical orbs attracting external bodies. And much more does it appear in orbs that attract bodies placed within them, because there the attractions diffused through the cavities of those orbs are, by prop. LXX, destroyed by contrary attractions, and therefore have no effect even in the place of contact. Now if from these spheres and spherical orbs we take away any parts remote from the place of contact, and add new parts anywhere at pleasure, we may change the figures of the attractive bodies at pleasure. But the parts added or taken away, being remote from the place of contact, will cause no remarkable excess of the attraction arising from the contact of the two bodies. Therefore the proposition holds good in bodies of all figures. QED. Proposition 86. Theorem 43. If the forces of the particles of which an attractive body is composed decrease, in the recess of the attractive body, in a triplicate or more than a triplicate ratio of the distance from the particles, the attraction will be vastly stronger in the point of contact than when the attracting and attracted bodies are separated from each other, though by never so small an interval. For that the attraction is infinitely increased when the attracted corpuscle comes to touch an attracting sphere of this kind, appears, by the solution of problem XLI, exhibited in the second and third examples. The same will also appear, by comparing those examples and theorem XLI together, of attractions of bodies made towards concavo-convex orbs, whether the attracted bodies be placed without the orbs, or in the cavities within them. And by adding to or taking from those spheres and orbs any attractive matter anywhere without the place of contact, so that the attractive bodies may receive any assigned figure, the proposition will hold good of all bodies universally. QED. Proposition 87. Theorem 44. If two bodies similar to each other, and consisting of matter equally attractive, attract separately two corpuscles proportional to those bodies, and in a like situation to them, the accelerative attractions of the corpuscles towards the entire bodies will be as the accelerative attractions of the corpuscles towards particles of the bodies proportional to the wholes, and alike situated in them. For if the bodies are divided into particles proportional to the wholes, and alike situated in them, it will be, as the attraction towards any particle of one of the bodies to the attraction towards the correspondent particle in the other body. So are the attractions towards the several particles of the first body, to the attractions towards the several correspondent particles of the other body. And, by composition, so is the attraction towards the first whole body to the attraction towards the second whole body. QED. Core 1. Therefore if, as the distances of the corpuscles attracted increase, the attractive forces of the particles decrease in the ratio of any power of the distances, the accelerative attractions towards the whole bodies will be as the bodies directly, and those powers of the distances inversely. As if the forces of the particles decrease in a duplicate ratio of the distances from the corpuscles attracted, and the bodies are as a superscript 3 and b superscript 3, and therefore both the cubic sides of the bodies, and the distance of the attracted corpuscles from the bodies, are as A and B. The accelerative attractions towards the bodies will be as and, that is, as A and B the cubic sides of those bodies. If the forces of the particles decrease in a triplicate ratio of the distances from the attracted corpuscles, the accelerative attractions towards the whole bodies will be as and, that is, equal. If the forces decrease in a quadruplicate ratio, the attractions towards the bodies will be as and, that is, reciprocally as the cubic sides A and B. And so in other cases. Core 2. Hence, on the other hand, from the forces with which like bodies attract corpuscles similarly situated, may be collected the ratio of the decrease of the attractive forces of the particles as the attracted corpuscle recedes from them. If so be that decrease is directly or inversely in any ratio of the distances. Proposition 88. Theorem XLV. If the attractive forces of the equal particles of any body be as the distance of the places from the particles, the force of the whole body will tend to its center of gravity, and will be the same with the force of a globe, consisting of similar and equal matter, and having its center in the center of gravity. Let the particles A, B, of the body RSTV attract any corpuscle Z with forces which, supposing the particles to be equal between themselves, are as the distances AZ, BZ. But, if they are supposed unequal, are as those particles and their distances AZ, BZ, conjunctly, or, if I may so speak, as those particles drawn into their distances AZ, BZ respectively. And let those forces be expressed by the contents under AAZ, and BBZ. Join AB, and let it be cut in G, so that AG may be to BG as the particle B to the particle A, and G will be the common center of gravity of the particles A and B. The force AAZ will, by core 2, of the laws, be resolved into the forces AGZ and AAG, and the force BBZ into the forces BGZ and BBG. Now the forces AAG and BBG, because A is proportional to B, and BG to AG, are equal, and therefore having contrary directions destroy one another. There remain then the forces AGZ and BGZ. These tend from Z towards the center G, and compose the force GZ, that is, the same force as if the attractive particles A and B were placed in their common center of gravity G, composing there a little globe. By the same reasoning, if there be added a third particle C, and the force of it be compounded with the force GZ tending to the center G, the force thence arising will tend to the common center of gravity of that globe in G and of the particle C. That is, to the common center of gravity of the three particles A, B, C, and will be the same as if that globe and the particle C were placed in that common center composing a greater globe there, and so we may go on in infinitum. Therefore the whole force of all the particles of any body whatever RSTV is the same as if that body, without removing its center of gravity, were to put on the form of a globe. QED. Sur. Hence the motion of the attracted body Z will be the same as if the attracting body RSTV were spherical. And therefore if that attracting body be either at rest, or proceed uniformly in a right line, the body attracted will move in an ellipsis having its center in the center of gravity of the attracting body. Proposition 89. Theorem 46. If there be several bodies consisting of equal particles whose forces are as the distances of the places from each, the force compounded of all the forces by which any corpuscle is attracted will tend to the common center of gravity of the attracting bodies, and will be the same as if those attracting bodies, preserving their common center of gravity, should unite there, and be formed into a globe. This is demonstrated after the same manner as the foregoing proposition. Sur. Therefore the motion of the attracted body will be the same as if the attracting bodies, preserving their common center of gravity, should unite there, and be formed into a globe. And, therefore, if the common center of gravity of the attracting bodies be either at rest, or proceed uniformly in a right line, the attracted body will move in an ellipsis having its center in the common center of gravity of the attracting bodies. Proposition XC. Problem 44. If to the several points of any circle there tend equal centripetal forces, increasing or decreasing in any ratio of the distances, it is required to find the force with which a corpuscle is attracted, that is, situate anywhere in a right line which stands at right angles to the plant of the circle at its center. Suppose a circle to be described about the center A with any interval AD in a plane to which the right line AP is perpendicular, and let it be required to find the force with which a corpuscle P is attracted towards the same. From any point E of the circle, to the attracted corpuscle P, let there be drawn the right line PE. In the right line PA take PF equal to PE, and make a perpendicular FK, erected at F, to be as the force with which the point E attracts the corpuscle P. And let the curve line IKL be the locus of the point K. Let that curve meet the plane of the circle in L. In PA take PH equal to PD, and erect the perpendicular HA meeting that curve in I, and the attraction of the corpuscle P towards the circle will be as the area AHIL drawn into the altitude AP. QE. I. For let there be taken in AE a very small line EE. Join PE, and in PE, PA take PC, PF equal to PE. And because the force, with which any point E of the annulus described about the center A with the interval AE in the aforesaid plane attracts to itself the body P, is supposed to be as Fk. And, therefore, the force with which that point attracts the body P towards A is as, and the force with which the whole annulus attracts the body P towards A is as the annulus and conjunctly. And that annulus also is as the rectangle under the radius AE and the breadth EE, and this rectangle, because PE and AE, EE and CE are proportional, is equal to the rectangle PECE or PEFF. The force with which that annulus attracts the body P towards A will be as PEFF and conjunctly, that is, as the content under FFFKAP, or as the area FKKF drawn into AP. And therefore the sum of the forces with which all the annuli, in the circle described about the center A with the interval AD, attract the body P towards A, is as the whole area vehicle drawn into AP. QED. Core 1. Hence if the forces of the points decrease in the duplicate ratio of the distances, that is, if Fk be as and therefore the area vehicle as, the attraction of the corpuscle P towards the circle will be as 1, that is, as. Core 2. And universally if the forces of the points at the distances d be reciprocally as any power dn of the distances, that is, if Fk be as and therefore the area vehicle as, the attraction of the corpuscle P towards the circle will be as. Core 3. And if the diameter of the circle be increased in infinitum, and the number n be greater than unity, the attraction of the corpuscle P towards the whole infinite plane will be reciprocally as pan, 2, because the other term vanishes. Proposition XCI. Problem XLV. To find the attraction of a corpuscle situate in the axis of a round solid, to whose several points there tend equal centripetal forces decreasing in any ratio of the distances whatsoever. Let the corpuscle P, situate in the axis AB of the solid DCG, be attracted towards that solid. Let the solid be cut by any circle as RFS, perpendicular to the axis, and in its semi-diameter Fs, in any plane pale KB passing through the axis, let there be taken, by prop. XC, the length Fk proportional to the force with which the corpuscle P is attracted towards that circle. Let the locus of the point K be the curved line LKI, meeting the planes of the outermost circles AL and BI in L and I. And the attraction of the corpuscle P towards the solid will be as the area labi. QEI. Core 1. Hence if the solid be a cylinder described by the parallelogram ADB revolved about the axis AB, and the centripetal forces tending to the several points be reciprocally as the squares of the distances from the points, the attraction of the corpuscle P towards this cylinder will be as AB, PE plus PD. For the ordinate Fk, by core 1, prop. XC, will be as 1. The part 1 of this quantity, drawn into the length AB, describes the area 1AB. And the other part, drawn into the length PB describes the area 1 into, as may be easily shown from the quadrature of the curve LKI. And, in like manner, the same part drawn into the length PA describes the area 1 into, and drawn into AB, the difference of PB and PA, describes 1 into, the difference of the areas. From the first content 1AB take away the last content 1 into, and there will remain the area labi equal to 1 into. Therefore the force, being proportional to this area, is as AB, PE plus PD. Core 2. Hence also is known the force by which a spheroid AGBC attracts any body P situate externally in its axis AB. Let NKRM be a conic section whose ordinate ER perpendicular to PE may be always equal to the length of the line PD, continually drawn to the point D in which that ordinate cuts the spheroid. From the vertices A, B, of the spheroid, let there be erected to its axis AB the perpendiculars AK, BM, respectively equal to AP, BP, and therefore meeting the conic section in K and M, and join KM cutting off from it the segment KMRK. Let S be the center of the spheroid, and SC its greatest semi-diameter, and the force with which the spheroid attracts the body P will be to the force with which a sphere described with the diameter AB attracts the same body as is to. And by a calculation founded on the same principles may be found the forces of the segments of the spheroid. Core 3. If the corpuscle be placed within the spheroid and in its axis, the attraction will be as its distance from the center. This may be easily collected from the following reasoning, whether the particle be in the axis or in any other given diameter. Let AGOF be an attracting spheroid, S its center, and P the body attracted. Through the body P let there be drawn the semi-diameter SPA, and two right lines DE, FG meeting the spheroid in D and E, F and G. And let PCM, HLN be the superficies of two interior spheroids similar and concentrical to the exterior, the first of which passes through the body P, and cuts the right lines DE, FG in B and C. And the latter cuts the same right lines in H and I, K and L.
Let the spheroids have all one common axis, and the parts of the right lines intercepted on both sides dP and B, FP and CG, DH and IE, FK and LG, will be mutually equal. Because the right lines DE, PB, and HI, are bisected in the same point, as are also the right lines FG, PC, and KL. Conceive now DPF, EPG to represent opposite cones described with the infinitely small vertical angles DPF, EPG, and the lines DH, EI to be infinitely small also. Then the particles of the cones DHKF, GLIE, cut off by the spheroidal superficies, by reason of the equality of the lines DH and EI, will be to one another as the squares of the distances from the body P. And will therefore attract that corpuscle equally. And by a like reasoning if the spaces DPF, EGCB be divided into particles by the superficies of innumerable similar spheroids concentric to the former and having one common axis, all these particles will equally attract on both sides the body P towards contrary parts. Therefore the forces of the cone DPF, and of the conic segment EGCB, are equal, and by their contrariety destroy each other. And the case is the same of the forces of all the matter that lies without the interior spheroid PCBM. Therefore the body P is attracted by the interior spheroid PCBM alone, and therefore, by core 3, prop. LXXA, its attraction is to the force with which the body A is attracted by the whole spheroid AGOD as the distance PS to the distance AS. QE. D. Proposition 92. Problem 46. An attracting body being given, it is required to find the ratio of the decrease of the centripetal forces tending to its several points. The body given must be formed into a sphere, a cylinder, or some regular figure, whose law of attraction answering to any ratio of decrease may be found by prop. LXXX, LXXXI, and XCI. Then, by experiments, the force of the attractions must be found at several distances, and the law of attraction towards the whole, made known by that means, will give the ratio of the decrease of the forces of the several parts. Which was to be found? Proposition 93. Theorem 47. If a solid be plane on one side, and infinitely extended on all other sides, and consist of equal particles equally attractive, whose forces decrease, in the recess from the solid, in the ratio of any power greater than the square of the distances, and a corpuscle placed towards either part of the plane is attracted by the force of the whole solid. I say that the attractive force of the whole solid, in the recess from its plane superficies, will decrease in the ratio of a power whose side is the distance of the corpuscle from the plane, and its index less by 3 than the index of the power of the distances. Case 1. Let LGL be the plane by which the solid is terminated. Let the solid lie on that hand of the plane that is towards I, and let it be resolved into innumerable planes MHM, NIN, OKO, and K, parallel to GL. And first let the attracted body C be placed without the solid. Let there be drawn CGHI perpendicular to those innumerable planes, and let the attractive forces of the points of the solid decrease in the ratio of a power of the distances whose index is the number n not less than 3. Therefore, by core 3, prop. XC, the force with which any plane MHM attracts the point C is reciprocally as CHN, 2. In the plane MHM take the length HM reciprocally proportional to CHN, 2, and that force will be as HM. In like manner in the several planes LGL, NIN, OKO, and K. Take the lengths GL, IN, KO, and K, reciprocally proportional to CGN, 2, CIN, 2, CKN, 2, and K. And the forces of those planes will be as the lengths so taken, and therefore the sum of the forces as the sum of the lengths, that is, the force of the whole solid as the area GLOK produced infinitely towards OK. But that area, by the known methods of quadratures, is reciprocally as CGN, 3, and therefore the force of the whole solid is reciprocally as CGN, 3. QED. Case 2. Let the corpuscle C be now placed on that hand of the plane LGL that is within the solid, and take the distance CK equal to the distance CG.
And the part of the solid LGLOKO terminated by the parallel planes LGL, OKO, will attract the corpuscle C, situate in the middle, neither one way nor another. The contrary actions of the opposite points destroying one another by reason of their equality. Therefore the corpuscle C is attracted by the force only of the solid situate beyond the plane OK. But this force, by case 1, is reciprocally as CKN, 3, that is, because CG, CK are equal, reciprocally as CGN, 3. QED. Core 1. Hence if the solid LGN be terminated on each side by two infinite parallel places LG, IN, its attractive force is known. Subducting from the attractive force of the whole infinite solid LGKO the attractive force of the more distant part NIKO infinitely produced towards KO. Core 2. If the more distant part of this solid be rejected, because its attraction compared with the attraction of the nearer part is inconsiderable, the attraction of that nearer part will, as the distance increases, decrease nearly in the ratio of the power CGN, 3. Core 3. And hence if any finite body, plane on one side, attract a corpuscle situate over against the middle of that plane, and the distance between the corpuscle and the plane compared with the dimensions of the attracting body be extremely small, and the attracting body consist of homogeneous particles, whose attractive forces decrease in the ratio of any power of the distances greater than the quadruplicate, the attractive force of the whole body will decrease very nearly in the ratio of a power whose side is that very small distance, and the index less by 3 than the index of the former power. This assertion does not hold good, however, of a body consisting of particles whose attractive forces decrease in the ratio of the triplicate power of the distances. Because, in that case, the attraction of the remoter part of the infinite body in the second corollary is always infinitely greater than the attraction of the nearer part. Scholium. If a body is attracted perpendicularly towards a given plane, and from the law of attraction given, the motion of the body be required, the problem will be solved by seeking, by prop. XXXAX, the motion of the body descending in a right line towards that plane, and, by core 2, of the laws, compounding that motion with an uniform motion performed in the direction of lines parallel to that plane. And, on the contrary, if there be required the law of the attraction tending towards the plane in perpendicular directions, by which the body may be caused to move in any given curve line, the problem will be solved by working after the manner of the third problem. But the operations may be contracted by resolving the ordinates into converging series. As if to a base A the length b be ordinately applied in any given angle, and that length b as any power of the base A. And there be sought the force with which a body, either attracted towards the base or driven from it in the direction of that ordinate, may be caused to move in the curved line which that ordinate always describes with its superior extremity. I suppose the base to be increased by a very small part O, and I resolve the ordinate into an infinite series nk, and I suppose the force proportional to the term of this series in which O is of 2 dimensions, that is, to the term. Therefore the force sought is as, or, which is the same thing, as if the ordinate describe a parabola, m being equals 2, and n equals 1, the force will be as the given quantity 2b degree, and therefore is given. Therefore with a given force the body will move in a parabola, as Galileo has demonstrated. If the ordinate describe an hyperbola, m being equals 0 to 1, and n equals 1, the force will be as 2a, 3 or 2b3. And therefore a force which is as the cube of the ordinate will cause the body to move in an hyperbola. But leaving this kind of propositions, I shall go on to some others relating to motion which I have not yet touched upon. Section 14. Of the motion of very small bodies when agitated by centripetal forces tending to the several parts of any very great body. Proposition 94. Theorem 48. If two similar mediums be separated from each other by a space terminated on both sides by parallel planes, and a body in its passage through that space be attracted or impelled perpendicularly towards either of those mediums, and not agitated or hindered by any other force, and the attraction be everywhere the same at equal distances from either plane, taken towards the same hand of the plane, I say, that the sign of incidence upon either plane will be to the sign of emergence of the other plane in a given ratio. Case 1. Let AA and BB be two parallel planes, and let the body light upon the first plane AA in the direction of the line GH, and in its whole passage through the intermediate space let it be attracted or impelled towards the medium of incidence. And by that action let it be made to describe a curved line HI, and let it emerge in the direction of the line IK. Let there be erected IM perpendicular to BB the plane of emergence, and meeting the line of incidence GH prolonged in M, and the plane of incidence AA in R, and let the line of emergence KI be produced and meet HM in L. About the center L, with the interval LA, let a circle be described cutting both HM in P and Q, and MI produced in N. And, first, if the attraction or impulse be supposed uniform, the curve HI, by what Galileo has demonstrated, be a parabola, whose property is that of a rectangle under its given latus rectum, and the line IM is equal to the square of HM. And moreover the line HM will be bisected in L, whence if to MI there be let fall the perpendicular LO, MO, or will be equal, and adding the equal lines on O, the holes MN, IR will be equal also. Therefore since IR is given, MN is also given, and the rectangle NMI is to the rectangle under the latus rectum and IM, that is, to HM superscript 2 in a given ratio. But the rectangle NMI is equal to the rectangle PMQ, that is, to the difference of the squares ML superscript 2, and PL superscript 2 or LI superscript 2, and HM superscript 2 hath a given ratio to its fourth part ML superscript 2. Therefore the ratio of ML superscript 2, Li superscript 2 to ML superscript 2 is given, and by conversion the ratio of Li superscript 2 to ML superscript 2, and its subduplicate, the ratio of Li to ML. But in every triangle, as LMI, the signs of the angles are proportional to the opposite sides. Therefore the ratio of the sine of the angle of incidence LMR to the sine of the angle of emergence LIR is given. QED. Case 2. Let now the body pass successively through several spaces terminated with parallel planes AB, EBCC, and C. And let it be acted on by a force which is uniform in each of them separately, but different in the different spaces. And by what was just demonstrated, the sine of the angle of incidence on the first plane AA is to the sine of emergence from the second plane BB in a given ratio. And this sine of incidence upon the second plane BB will be to the sine of emergence from the third plane CC in a given ratio, and this sine to the sine of emergence from the fourth plane DD in a given ratio, and so on in infinitum. And, by equality, the sine of incidence on the first plane to the sine of emergence from the last plane in a given ratio. Let now the intervals of the planes be diminished, and their number be infinitely increased, so that the action of attraction or impulse, exerted according to any assigned law, may become continual. And the ratio of the sine of incidence on the first plane to the sine of emergence from the last plane being all along given, will be given then also. QED. Proposition 95. Theorem 49. The same things being supposed, I say, that the velocity of the body before its incidence is to its velocity after emergence as the sine of emergence to the sine of incidence. Make AH and ID equal, and erect the perpendiculars AG, DK meeting the lines of incidence and emergence GH, IK, in G and K. In GH take TH equal to IK, and to the plane AA let fall a perpendicular TV. And, by SR. 2 of the laws of motion, let the motion of the body be resolved into 2, one perpendicular to the planes AA, BB, CC, and C, and another parallel to them. The force of attraction or impulse, acting in directions perpendicular to those planes, does not at all alter the motion in parallel directions. And therefore the body proceeding with this motion will in equal times go through those equal parallel intervals that lie between the line AG and the point H, and between the point I and the line DK. That is, they will describe the lines GH, IK in equal times. Therefore the velocity before incidence is to the velocity after emergence as GH to IK or TH, that is, as AH or ID to VH. That is, supposing th or ik radius, as the sign of emergence to the sign of incidence. QED. Proposition 96. Theorem L. The same things being supposed, and that the motion before incidence is swifter than afterwards. I say, that if the line of incidence be inclined continually, the body will be at last reflected, and the angle of reflection will be equal to the angle of incidence. For conceive the body passing between the parallel planes AA, BB, CC, and C. To describe parabolic arcs as above, and let those arcs be HP, PQ, QR, and C. And let the obliquity of the line of incidence GH to the first plane AA be such that the sign of incidence may be to the radius of the circle whose sign it is. In the same ratio which the same sign of incidence hath to the sign of emergence from the plane DD into the space DDEE. And because the sign of emergence is now become equal to radius, the angle of emergence will be a right one, and therefore the line of emergence will coincide with the plane DD. Let the body come to this plane in the point R. And because the line of emergence coincides with that plane, it is manifest that the body can proceed no farther towards the plane EE. But neither can it proceed in the line of emergence RD. Because it is perpetually attracted or impelled towards the medium of incidence. It will return, therefore, between the planes CC, DD, describing an arc of a parabola QRQ, whose principal vertex, by what Galileo has demonstrated, is in R, cutting the plane CC in the same angle at Q, that it did before at Q. Then going on in the parabolic arcs QP, PH, and C, similar and equal to the former arcs QP, PH, and C, it will cut the rest of the planes in the same angles at P, H, and C, as it did before in P, H, and C. And will emerge at last with the same obliquity at H with which it first impinged on that plane at H. Conceive now the intervals of the planes AA, BB, CC, DD, EE, and C. To be infinitely diminished, and the number infinitely increased, so that the action of attraction or impulse, exerted according to any assigned law, may become continual. And the angle of emergence remaining all along equal to the angle of incidence, will be equal to the same also at last. QED. Scholium. These attractions bear a great resemblance to the reflections and refractions of light made in a given ratio of the secants, as was discovered by Snellius, and consequently in a given ratio of the sines, as was exhibited by Descartes. For it is now certain from the phenomena of Jupiter's satellites, confirmed by the observations of different astronomers, that light is propagated in succession, and requires about 7 or 8 minutes to travel from the sun to the earth. Moreover, the rays of light that are in our air, as lately was discovered by Grimaldus, by the admission of light into a dark room through a small hole, which I have also tried, in their passage near the angles of bodies. Whether transparent or opaque, such as the circular and rectangular edges of gold, silver and brass coins, or of knives, or broken pieces of stone or glass, are bent or inflected round those bodies as if they were attracted to them. And those rays which in their passage come nearest to the bodies are the most inflected, as if they were most attracted, which tiling I myself have also carefully observed. And those which pass at greater distances are less inflected. And those at still greater distances are a little inflected the contrary way, and form 3 fringes of colors. In the figure S represents the edge of a knife, or any kind of wedge ASB. And Gauag, Fnunf, Empmi, DLSLD, are rays inflected towards the knife in the arcs OO, NVN, MTM, LSL, which inflection is greater or less according to their distance from the knife. Now since this inflection of the rays is performed in the air without the knife, it follows that the rays which fall upon the knife are first inflected in the air before they touch the knife. And the case is the same of the rays falling upon glass. The refraction, therefore, is made not in the point of incidence, but gradually, by a continual inflection of the rays, which is done partly in the air before they touch the glass, partly, if I mistake not, within the glass, after they have entered it. As is represented in the rays CKZC, Bibe, Oxa, falling upon R, Q, P, and inflected between K and Z, I and E, H and X. Therefore, because of the analogy there is between the propagation of the rays of light and the motion of bodies, I thought it not amiss to add the following propositions for optical uses, not at all considering the nature of the rays of light, or inquiring whether they are bodies or not, but only determining the trajectories of bodies which are extremely like the trajectories of the rays. Proposition 97. Problem 47. Supposing the sign of incidence upon any superficies to be in a given ratio to the sign of emergence, and that the inflection of the paths of those bodies near that superficies is performed in a very short space, which may be considered as a point. It is required to determine such a superficies as may cause all the corpuscles issuing from any one given place to converge to another given place. Let A be the place from whence the corpuscles diverge, be the place to which they should converge. CDE the curved line which by its revolution round the axis AB describes the superficies sought, D, E, any 2 points of that curve, and EF, e.g., perpendiculars let fall on the paths of the bodies AD, DB. Let the point D approach to and coalesce with the point E, and the ultimate ratio of the line DF by which AD is increased, to the line DG by which DB is diminished, will be the same as that of the sign of incidence to the sign of emergence. Therefore the ratio of the increment of the line AD to the decrement of the line DB is given. And therefore if in the axis AB there be taken any where the point C through which the curve CDE must pass, and CM the increment of AC be taken in that given ratio to CN the decrement of BC, and from the centers A, B, with the intervals AM, BN, there be described 2 circles cutting each other in D. That point D will touch the curve sought CDE, and, by touching it anywhere at pleasure, will determine that curve. QEI. Core 1. By causing the point A or B to go off sometimes in infinitum, and sometimes to move towards other parts of the point C, will be obtained all those figures which Cartesius has exhibited in his optics and geometry relating to refractions. The invention of which Cartesius having thought fit to conceal, is here laid open in this proposition. Core 2. If a body lighting on any superficies CD in the direction of a right line AD, drawn according to any law, should emerge in the direction of another right line DK, and from the point C there be drawn curved line CP, CQ, always perpendicular to AD, DK. The increments of the lines PD, QD, and therefore the lines themselves PD, QD, generated by those increments, will be as the signs of incidence and emergence to each other, and contra. Proposition 98. Problem 48. The same thing supposed, if round the axis AB any attractive superficies be described as CD, regular or irregular, through which the bodies issuing from the given place A must pass. It is required to find a second attractive superficies EF, which may make those bodies converge to a given place B. Let a line joining AB cut the first superficies in C and the second in E, the point D being taken anyhow at pleasure. And supposing the sign of incidence on the first superficies to the sign of emergence from the same, and the sign of emergence from the second superficies to the sign of incidence on the same, to be as any given quantity M to another given quantity N. Then produce AB to G, so that BG may be to CE as M, N to N, and AD to H, so that AH may be equal to AG, and DF to K, so that DK may be to DH as N to M. Join KB, and about the center D with the interval DH describe a circle meeting KB produced in L, and draw BF parallel to DL, and the point F will touch the line EF, which, being turned round the axis AB, will describe the superficies sought. QE. F. For conceive the line CP, CQ, to be everywhere perpendicular to AD, DF, and the lines ER, ES to FB, FD respectively, and therefore QS to be always equal to CE, and, by Core 2, Prop. XCV, PD will be to QD as M to N, and therefore as DL to DK, or FB to FK, and by division as DL, FB or PH, PD, FB to FD or FQ, QD. And by composition as PH, FB to FQ, that is, because PH and CG, QS and CE, are equal, as CE plus BG, FR to CE, FS. But, because BG is to CE as M, N to N, it comes to pass also that CE plus BG is to CE as M to N. And therefore, by division, FR is to FS as M to N, and therefore, by core 2, prop XCVII, the superficies EF compels a body, falling upon it in the direction DF, to go on in the line FR to the place B. QED. Scholium. In the same manner one may go on to 3 or more superficies. But of all figures the spherical is the most proper for optical uses. If the object glasses of telescopes were made of 2 glasses of a spherical figure, containing water between them, it is not unlikely that the errors of the refractions made in the extreme parts of the superficies of the glasses may be accurately enough corrected by the refractions of the water. Such object glasses are to be preferred before elliptic and hyperbolic glasses, not only because they may be formed with more ease and accuracy, but because the pencils of rays situate without the axis of the glass would be more accurately refracted by them. But the different refrangibility of different rays is the real obstacle that hinders optics from being made perfect by spherical or any other figures. Unless the errors thence arising can be corrected, all the labor spent in correcting the others is quite thrown away. Book 2. Of the motion of bodies. Section 1. Of the motion of bodies that are resisted in the ratio of the velocity. Proposition I, Theorem I. If a body is resisted in the ratio of its velocity, the motion lost by resistance is as the space gone over in its motion. For since the motion lost in each equal particle of time is as the velocity, that is, as the particle of space gone over, then, by composition, the motion lost in the whole time will be as the whole space gone over. QED. Sur. Therefore if the body, destitute of all gravity, move by its innate force only in free spaces, and there be given both its whole motion at the beginning, and also the motion remaining after some part of the way is gone over, there will be given also the whole space which the body can describe in an infinite time. For that space will be to the space now described as the whole motion at the beginning is to the part lost of that motion. Lemma I. Quantities proportional to their differences are continually proportional. Let A B to A, B as B to B, C and C to C, D, and, by conversion, will B to B as B to C and C to D, and QED. Proposition 2. Theorem 2. If a body is resisted in the ratio of its velocity, and moves, by its vis in theta only, through a similar medium, and the times be taken equal, the velocities in the beginning of each of the times are in a geometrical progression. And the spaces described in each of the times are as the velocities. Case 1. Let the time be divided into equal particles. And if at the very beginning of each particle we suppose the resistance to act with one single impulse which is as the velocity, the decrement of the velocity in each of the particles of time will be as the same velocity. Therefore the velocities are proportional to their differences, and therefore, by Lem. 1, Book 2, continually proportional. Therefore if out of an equal number of particles there be compounded any equal portions of time, the velocities at the beginning of those times will be as terms in a continued progression, which are taken by intervals, omitting everywhere an equal number of intermediate terms. But the ratios of these terms are compounded of the equal ratios of the intermediate terms equally repeated, and therefore are equal. Therefore the velocities, being proportional to those terms, are in geometrical progression. Let those equal particles of time be diminished, and their number increased in infinitum, so that the impulse of resistance may become continual. And the velocities at the beginnings of equal times, always continually proportional, will be also in this case continually proportional. QED. Case 2. And, by division, the differences of the velocities, that is, the parts of the velocities lost in each of the times, are as the wholes, but the spaces described in each of the times are as the lost parts of the velocities, by Prop. 1, Book I, and therefore are also as the wholes. QED. Choral. Hence if to the rectangular asymptotes AC, CH, the hyperbola BG is described, and AB, DG be drawn perpendicular to the asymptote AC, and both the velocity of the body, and the resistance of the medium, at the very beginning of the motion, be expressed by any given line AC, and, after some time is elapsed, by the indefinite line DC. The time may be expressed by the area ABGD, and the space described in that time by the line AD. For if that area, by the motion of the point D, be uniformly increased in the same manner as the time, the right line DC will decrease in a geometrical ratio in the same manner as the velocity. And the parts of the right line AC, described in equal times, will decrease in the same ratio. Proposition 3. Problem I. To define the motion of a body which, in a similar medium, ascends or descends in a right line, and is resisted in the ratio of its velocity, and acted upon by an uniform force of gravity. The body ascending, let the gravity be expounded by any given rectangle Bach, and the resistance of the medium, at the beginning of the ascent, by the rectangle Bade, taken on the contrary side of the right line AB. Through the point B, with the rectangular asymptotes AC, CH, describe an hyperbola, cutting the perpendiculars DE, in G, G, and the body ascending will in the time DGGD describe the space AG. In the time DGBA, the space of the whole ascent EGB, in the time ABKI, the space of descent BFK, and in the time AKI the space of descent KFFK. And the velocities of the bodies, proportional to the resistance of the medium, in these periods of time will be ABED, ABD, O, ABFI, ABFI respectively, and the greatest velocity which the body can acquire by descending will be Bach. For let the rectangle Bach be resolved into innumerable rectangles AK, KL, LM, MN, and which shall be as the increments of the velocities produced in so many equal times, then will O, AK, Al, AM, and be as the whole velocities. And therefore, by supposition, as the resistances of the medium in the beginning of each of the equal times. Make AC to AK, or ABHC to ABKK, as the force of gravity to the resistance in the beginning of the second time. Then from the force of gravity subduct the resistances, and ABHC, KKHC, LLHC, MMHC, and will be as the absolute forces with which the body is acted upon in the beginning of each of the times, and therefore, by law I, as the increments of the velocities, that is, as the rectangles AK, KL, LM, MN, and therefore, by Lem. 1, Book 2, in a geometrical progression. Therefore, if the right lines KK, LL, MM, NN, and are produced so as to meet the hyperbola in Q, R, S, T, and the areas ABQK, KQRL, LRSM, MSTN, and will be equal, and therefore analogous to the equal times and equal gravitating forces. But the area ABQK, by Coral, 3, Lem. 7 and 8, Book I, is to the area BKQ as KQ to 1/2 KQ, or AC to 1/2 AK, that is, as the force of gravity to the resistance in the middle of the first time. And by the like reasoning, the areas QKLR, RLMs, SM and are to the areas QKLR, RLMS, SM and as the gravitating forces to the resistances in the middle of the second, third, fourth time, and so on. Therefore since the equal areas BAKQ, QKLR, RLMs, SM and are analogous to the gravitating forces, the areas BKQ, QKLR, RLMS, SM and will be analogous to the resistances in the middle of each of the times, that is, by supposition, to the velocities, and so to the spaces described. Take the sums of the analogous quantities, and the areas BKQ, BLR, BMS, but, and, will be analogous to the whole spaces described, and also the areas ABQK, ABRL, ABSM, ABTN, and, to the times. Therefore the body, in descending, will in any time ABRL describe the space BLR, and in the time LRTN the space RL and QED. And the like demonstration holds in ascending motion. Coral, 1. Therefore the greatest velocity that the body can acquire by falling is to the velocity acquired in any given time as the given force of gravity which perpetually acts upon it to the resisting force which opposes it at the end of that time. Choral. 2. But the time being augmented in an arithmetical progression, the sum of that greatest velocity in the velocity in the ascent, and also their difference in the descent, decreases in a geometrical progression. Choral. 3. Also the differences of the spaces, which are described in equal differences of the times, decrease in the same geometrical progression. Choral. 4. The space described by the body is the difference of two spaces, whereof one is as the time taken from the beginning of the descent, and the other as the velocity, which spaces, also at the beginning of the descent are equal among themselves. Proposition 4. Problem 2. Supposing the force of gravity in any similar medium to be uniform, and to tend perpendicularly to the plane of the horizon. To define the motion of a projectile therein, which suffers resistance proportional to its velocity. Let the projectile go from any place d in the direction of any right line dp, and let its velocity at the beginning of the motion be expounded by the length dp. From the point P let fall the perpendicular PC on the horizontal line DC, and cut DC in A, so that dA may be to AC as the resistance of the medium arising from the motion upwards at the beginning to the force of gravity. Or, which comes to the same, so that the rectangle under dA and dP may be to that under AC and CP as the whole resistance at the beginning of the motion to the force of gravity. With the asymptotes DC, CP describe any hyperbola GTBS cutting the perpendiculars DG, AB and G and B, complete the parallelogram DGKC, and let its side GK cut AB and Q. Take a line N in the same ratio to QB as DC is in to CP. And from any point R of the right line DC erect RT perpendicular to it, meeting the hyperbola in T, and the right lines EH, GK, DP and I, T, and V, in that perpendicular take VR equal to, or which is the same thing, take RR equal to. And the projectile in the time drtg will arrive at the point R describing the curve line drAF, the locus of the point R, thence it will come to its greatest height A in the perpendicular AB, and afterwards ever approach to the asymptote PC. And its velocity in any point R will be as the tangent RL to the curve. QEI. For N is to QB as DC to CP or DR to RV, and therefore RV is equal to, and RR, that is, RV, VR, or, is equal to. Now let the time be expounded by the area RdGt and, by laws, Core 2, distinguish the motion of the body into two others, one of ascent, the other lateral. And since the resistance is as the motion, let that also be distinguished into two parts proportional and contrary to the parts of the motion, and therefore the length described by the lateral motion will be, by Prop. 2, Book 2, as the line dr, and the height, by Prop. 3, Book 2, as the area drAB, rdgt, that is, as the line rr. But in the very beginning of the motion the area rdgt is equal to the rectangle draq, and therefore that line rr, or, will then be to dr as ab, aq or qb to n, that is, as cp to dc. And therefore as the motion upwards to the motion lengthwise at the beginning. Since, therefore, rr is always as the height, and dr always as the length, and rr is to dr at the beginning as the height to the length, it follows, that rr is always to dr as the height to the length. And therefore that the body will move in the line drAF, which is the locus of the point R. QED. Core 1. Therefore RR is equal to, and therefore if RT be produced to X so that Rx may be equal to, that is, if the parallelogram ACPY be completed, and dy cutting CP in Z be drawn, and RT be produced till it meets dy in X. XR will be equal to, and therefore proportional to the time. Core 2. Whence if innumerable lines CR, or, which is the same, innumerable lines ZX, be taken in a geometrical progression, there will be as many lines XR in an arithmetical progression. And hence the curve drAF is easily delineated by the table of logarithms. Core 3. If a parabola be constructed to the vertex D, and the diameter dg produced downwards, and its lattice rectum is to 2 dp as the whole resistance at the beginning of the notion to the gravitating force. The velocity with which the body ought to go from the place D, in the direction of the right line dp, so as in an uniform resisting medium to describe the curve draf, will be the same as that with which it ought to go from the same place D in the direction of the same right line dp, so as to describe a parabola in a non-resisting medium. For the lattice rectum of this parabola, at the very beginning of the motion, is, and VR is. But a right line, which, if drawn, would touch the hyperbola GTS in G, is parallel to dk, and therefore TT is, and N is. And therefore VR is equal to, that is, because dr and dc, dv and dp are proportionals, to, and the lattice rectum comes out, that is, because qb and ck, dA, and AC are proportional, and therefore is to 2 dp as dp dA to cp AC. That is, as the resistance to the gravity. QED. Core 4. Hence if a body be projected from any place D with a given velocity, in the direction of a right line dp given by position, and the resistance of the medium, at the beginning of the motion, be given, the curve draf, which that body will describe, may be found. For the velocity being given, the lattice rectum of the parabola is given, as is well known. And taking 2 dp to that lattice rectum, as the force of gravity to the resisting force, dp is also given. Then cutting dc and a, so that cpac may be to dp dA in the same ratio of the gravity to the resistance, the point A will be given. And hence the curve draf is also given. Core 5. And, on the contrary, if the curve draf be given, there will be given both the velocity of the body and the resistance of the medium in each of the places R. For the ratio of cpac to dp dA being given, there is given both the resistance of the medium at the beginning of the motion, and the lattice rectum of the parabola, and thence the velocity at the beginning of the motion is given also. Then from the length of the tangent L there is given both the velocity proportional to it, and the resistance proportional to the velocity in any place R. Core 6. But since the length 2 dp is to the lattice rectum of the parabola as the gravity to the resistance in D, and, from the velocity augmented, the resistance is augmented in the same ratio, but the lattice rectum of the parabola is augmented in the duplicate of that ratio, it is plain that the length 2 dp is augmented in that simple ratio only, and is therefore always proportional to the velocity, nor will it be augmented or diminished by the change of the angle cdp, unless the velocity be also changed. Core 7. Hence appears the method of determining the curve draf nearly from the phenomena, and thence collecting the resistance and velocity with which the body is projected. Let two similar and equal bodies be projected with the same velocity, from the place D, in different angles cdp, cdp, and let the places f, f, where they fall upon the horizontal plane dc, be known. Then taking any length for dp or dp, suppose the resistance in D to be to the gravity in any ratio whatsoever, and let that ratio be expounded by any length sm. Then, by computation, from that assumed length dp, find the lengths dp, df. And from the ratio, found by calculation, subduct the same ratio as found by experiment, and let the difference be expounded by the perpendicular mn. Repeat the same a second and a third time, by assuming always a new ratio sm of the resistance to the gravity, and collecting a new difference mn. Draw the affirmative differences on one side of the right line sm, and the negative on the other side. And through the points n, 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 draw a regular curve nnn. Cutting the right line smm in x, and sx will be the true ratio of the resistance to the gravity, which was to be found. From this ratio the length df is to be collected by calculation. And a length, which is to the assumed length dp as the length df known by experiment to the length df just now found, will be the true length dp. This being known, you will have both the curve line draf which the body describes, and also the velocity and resistance of the body in each place. Scholium. But, yet, that the resistance of bodies is in the ratio of the velocity, is more a mathematical hypothesis than a physical one. In mediums void of all tenacity, the resistances made to bodies are in the duplicate ratio of the velocities. For by the action of a swifter body, a greater motion in proportion to a greater velocity is communicated to the same quantity of the medium in a less time. And in an equal time, by reason of a greater quantity of the disturbed medium, a motion is communicated in the duplicate ratio greater, and the resistance, by law 2 and 3, is as the motion communicated. Let us, therefore, see what motions arise from this law of resistance.